So take a look at a glass of water on your desk. I mean, it looks completely dead, right?
Oh, totally. Comfortingly boring.
Exactly. You set the glass down, the little ripples fade, and it just sits there.
Yeah,
But if you could zoom in far enough, you'd realize that water is actually this violent, chaotic war zone of perpetual motion.
it really is.
And today, we are going to completely shatter your illusion of stillness.
We are venturing into the hidden machinery of the universe today, basically peeling back the macroscopic world to see the gears turning underneath.
Right. And our source material for this mission is Chapter 1 of the legendary Feynman Lectures on Physics. It's titled Atoms in Motion.
A classic.
It is. We've got the text, we've got the incredible diagrams he uses, and our goal for this deep dive is to extract the core aha moments about how the world actually operates at the absolute smallest scales.
Yeah, we're going to decode the terminology, explain the mechanisms, and just, expose the fascinating microscopic world happening all around you right now.
But I guess before we can even get to the water, we need to lay the foundation.
We do. And the text does this in a really striking way by setting up a thought experiment. It's about a cataclysm.
Right. So the author asks you to imagine some total cataclysm destroys all of scientific knowledge.
Just everything gone.
Everything we've learned over millennia is gone. But you are allowed to pass on just one single sentence to the next generation of creatures to help them rebuild.
It's such a cool concept.
What statement contains the most information in the fewest words?
It's a brilliant framing device, I think, because it forces you to identify the absolute bedrock of all our understanding, like what is the ultimate shortcut to making sense of the physical world.
And the answer provided is the atomic hypothesis.
Right.
The one sentence you save is this, all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another.
That single sentence is doing an unbelievable amount of heavy lifting.
It really is.
It gives us the ingredients of the universe, the atoms.
Yeah.
And it establishes the fundamental rules of engagement.
Which are perpetual motion, attraction, and repulsion.
Exactly.
The scale of this, however, is what truly breaks my brain. The text uses an analogy to help you visualize it, and it's wild.
Oh, the Apple one.
Yes, if you took an ordinary apple and you magnified it until the apple was the size of the entire Earth.
Which is huge.
Right. The atoms inside that Earth-size apple would only be about the size of the original apple.
It's crazy. There are roughly 1 or 2 angstroms across. It's just a scale that defies human intuition entirely.
Wait, before we move on, let's actually define that for the listener. What exactly is an angstrom? Like, just how tiny are we talking?
Good catch. So an angstrom is a unit of measurement used specifically for the atomic scale.
Okay.
It is 1/10,000,000th of a meter. To put that in perspective, a single sheet of paper is millions of angstroms thick.
Millions. Wow. It is staggeringly small.
Yeah.
But I'm trying to picture this rule of universal motion, and I keep hitting a wall.
What do you mean?
Well, if everything is made of these impossibly tiny particles, and the rule is that they are constantly jiggling and bouncing and pushing away from each other when squeezed,
Yeah.
why doesn't the chair I'm sitting on just fly apart?
Uh,
Like, if it's all perpetual motion and repulsion, how does anything stay solid? It feels like it should just dissolve into a cloud of dust.
that gets right to the heart of the physics. The answer lies in the balance of those forces.
Okay.
Go back to the cataclysm sentence. It says, they repel when squeezed, but they attract when they are a little distance apart.
Oh, right. The attraction.
Exactly. The atoms in your solid chair have a mutual molecular attraction. They are essentially glued together by these attractive forces.
Yeah, that makes sense.
They are internally jittering and jiggling like crazy. I mean, that perpetual motion never stops, but that mutual attraction is strong enough to keep them bound together in a solid structure. The jiggling just isn't violent enough to break the glue.
Okay, so they're vibrating, but they're trapped. Let's actually visualize this with the water. The text takes us on this incredible, gradual zoom-in journey.
It's so vivid.
It really is. It asks you to imagine a tiny drop of water, just 1/4 of an inch across. First, we magnify it 2,000 times.
Right.
Now the drop is about 40 feet across, so like the size of a large room. The water still looks relatively smooth, but you might see these little football-shaped things swimming back and forth.
The paramecia.
Just to be clear, those are the tiny, single-celled organisms, right? Covered in little hairs called cilia.
That's them. The author throws in this great little biological detour just to give you a sense of scale.
Yeah.
You could totally get distracted by the biology here and look at their wiggling cilia, but to find the fundamental truth of the water, we have to push past the biology and go much, much deeper.
So we zoom in 1 billion times. A quarter-inch drop is now 15 miles across. And suddenly, the smoothness is completely gone.
It's gone.
It's teeming. It looks like a massive crowd at a stadium from high up. The text includes Figure 1-1 will show this, and it honestly looks like a chaotic sea of Mickey Mouse heads.
I love that description. That visual describes the water molecule perfectly.
Right.
You have the larger oxygen atom acting as the head, and the two smaller hydrogen atoms acting as the ears.
But I noticed the text isn't just being vague about this shape. It doesn't just say they look like ears.
Oh, it's very precise.
It gives the exact geometry. Those hydrogen atoms are exactly 105 degrees and 3 minutes apart.
Yeah.
The distance between the center of the hydrogen and the center of the oxygen is 0.957 angstroms. Why include such incredibly specific numbers for something so small?
Well, it's to prove a crucial point about the microscopic world. It isn't just a blurry, amorphous mess down there.
It's structured.
Highly structured. It is a place governed by strict, measurable, rigid mathematical architecture. Those atoms lock together in highly specific ways dictated by physical laws. And the other crucial thing to understand here is what their constant jiggling actually represents in our daily lives.
Okay, what is it?
The internal motion of those Mickey Mouse heads. That is what we experience as heat.
So heat is nothing more than atomic motion.
Purely motion. When we say something is hot, we're just saying its atoms are jiggling very fast.
Okay, wait, so if heat is just speed, if I put a flame under this 15-mile wide water drop, I'm not just warming it up.
No.
I'm actively making those molecules thrash around harder and harder. Does the glue eventually just fail?
It does. The jiggling gets more violent. The molecules start throwing their elbows, so to speak, taking up more volume.
Okay.
If you keep adding heat, eventually that internal kinetic energy overpowers the molecular attraction we talked about earlier.
The glue breaks.
Exactly. The attraction can't hold them and they just fly apart.
Which gives us steam.
Yep.
The text points to figures 1-2 and 1-3, showing steam or vapor, and the molecules are completely separated. They are just rogue agents bouncing off the walls of whatever container they are in.
And that bouncing is the physical mechanism behind gas pressure.
Oh, really?
Yeah. A gas exerting pressure on a wall is literally just billions of tiny high-speed projectiles hammering against it so fast that our coarse senses feel it as a steady average push.
This actually brings up what might be my absolute favorite analogy in the entire text.
The ping pong one.
Yes,
Yeah.
because it perfectly explains the underlying mechanism of why compressing a gas makes it hotter.
It's so elegant.
So imagine you're holding a ping pong paddle and someone serves a ball at you. If you just hold the paddle totally still, the ball bounces off at a certain speed.
Right.
But if you swing the paddle forward to hit the ball, just like a piston pushing down and compressing a gas, the ball bounces off much, much faster.
It's a brilliant way to conceptualize the transfer of momentum. The atoms in a gas are the ping pong balls.
Okay.
When you compress the gas slowly, you are pushing a physical wall toward them. When an atom hits that moving wall, it picks up speed from the collision.
Ah, I see.
And since we just established that speed, or atomic motion, is the exact same thing as heat.
Compressing the gas literally makes the atoms move faster, which means the gas inherently gets hotter.
Exactly. It's not magic. It's just tiny physical collisions.
That is so cool. So if we know what happens when we increase the speed, what happens when we slow the jiggling down?
Well, then the forces of attraction start to win the battle.
The glue takes over.
Right. As the motion decreases, the molecules can't push past each other anymore. Figure 1-4 shows what happens next. They lock into a rigid pattern. We get ice.
But it's not just a random messy clump, right?
Not at all. It's a beautiful hexagonal crystalline array.
And understanding that specific array solves a really practical mystery.
Yeah.
Because almost every simple substance in the universe shrinks when it gets cold.
Sure.
The atoms have latent energy to push away from each other, so they pack tighter. So why does water break the rule, expand, and burst our pipes in the winter?
Because that specific hexagonal crystalline pattern of ice has structural holes in it. Yeah. It's rigid, but it's an open structure. The molecules are actually forced into a shape that demands more space than when they were just tumbling over each other as a chaotic liquid.
Oh, wow.
So when ice melts, that rigid bridge-like structure collapses. The molecules fall into those empty holes, and the liquid water actually shrinks and becomes denser than the solid ice.
That makes perfect sense, although the text does mention one incredible exception to all these freezing rules.
Helium.
Helium. You can cool helium down to absolute zero, the theoretical limit where atomic motion is at its absolute minimum, and it still won't freeze.
It's so bizarre.
It is. The minimal amount of jiggling that remains even at absolute zero is enough to keep helium a liquid. You literally have to apply massive pressure to artificially squash the atoms together to force it to become a solid.
Helium is a fantastic outlier, but it proves the core negotiation happening in all matter. The state of a substance is entirely a tug-of-war between the forces of attraction pulling inward and the energy of motion pushing outward.
Okay, so we've looked at extreme heat and extreme cold. Let's go back to our glass of water sitting on the table in a normal room.
Oh.
The illusion of stillness.
Yes. Figure 1 to 5 illustrates this boundary beautifully.
Because to our eyes, it looks completely dead.
Exactly. But if we zoom in to the exact surface where the liquid water meets the air, it is wild, dynamic chaos.
What's actually happening there?
You've got the liquid water molecules constantly jiggling below the surface. Occasionally, randomly, one molecule gets bumped by its neighbors just right, with just enough extra energy that it breaks the attraction of the liquid and gets launched up into the air.
So that's evaporation.
Yep.
But the air above the glass isn't empty. You also have water vapor molecules already floating in the air, zooming around like the ping pong balls, and occasionally they randomly crash back down into the liquid water and get stuck again.
It's a dynamic equilibrium. Molecules are constantly leaving and molecules are constantly returning. If the glass of water looks perfectly still to you, it is only because the exact same number of molecules are leaving as are coming back. The rates are perfectly matched.
So nothing happens, it's just a statistical tie.
Basically, yeah.
Now, how do we tip the scales? The text asks this incredibly relatable question. Is this why blowing on hot soup cools it down?
I love that part.
And the answer is yes, but the mechanics of why are just amazing.
Right. If we analyze the physics of cooling by evaporation, we have to think about which molecules manage to escape the soup. It's not a random sample.
No, it's not.
No. The ones that break free are the ones that got bumped the hardest, the ones with the most energy. The high-energy molecules are the ones that evaporate.
Oh.
When they escape into the air, the average energy, the heat of the liquid that is left behind automatically drops. The soup cools down simply because its most energetic members just left the building.
It sounds like a crowded party where the most energetic dancers are sweating and leaving through the front door. And blowing on the soup is like a bouncer stopping them from coming back inside.
I love that analogy. If you just leave the bowl of soup sitting there, some of those escaped high-energy vapor molecules will accidentally crash back into the liquid and return their heat to the soup, slowing down the cooling.
Right.
When you blow on the soup, you are the bouncer. You are sweeping away those escaped high-energy vapor molecules before they have a chance to fall back in. You are literally hacking the dynamic equilibrium to ensure the liquid only loses hot molecules.
That is so practical. And we see this exact same dynamic equilibrium concept when we dissolve something solid, like salt in water.
Yep.
Figures 1-6 and 1-7 show this perfectly. If you drop a salt crystal in water, it's not just passively melting. Salt is made of sodium and chlorine ions locked together in a rigid crystal structure by electrical attraction.
Yep.
Let's define ion for a second. How is that different from a regular atom?
So an ion is simply an atom that has a net electrical charge because it has either gained or lost an electron. In salt, the sodium ion is positive and the chlorine ion is negative. They stick together like magnets.
Okay, so when you drop that crystal in water, the water molecules essentially attack it. The negative oxygen ends of the Mickey Mouse water molecules pull on the positive sodium ions, and the positive hydrogen ears pull on the negative chlorine ions.
It's a microscopic electrical tug-of-war. The ions are jiggling loose from the crystal and floating away into the water.
Just getting ripped apart.
Yeah, but again, just like evaporation, it's a two-way street. While some ions are getting ripped off the crystal, other ions that are already floating free in the water are accidentally crashing back into the crystal and reattaching themselves.
It's this continuous, invisible battle of dissolving and recrystallizing happening at the exact same time.
Exactly.
And whether the salt crystal visually shrinks or grows entirely depends on whether the rate of ions leaving outpaces the rate of ions returning.
It only looks like a smooth one-way event to us.
So far, we've had water molecules turning to steam or ice, and salt crystals breaking apart into free-floating ions. But the actual pieces haven't changed their fundamental identities.
Right, they're still what they are.
An oxygen atom in the water is still stuck to its two specific hydrogens. What happens when the atoms decide to completely swap partners?
Now we are crossing the border from physical processes into chemistry. We're talking about chemical reactions.
Oh, man.
Figure 1 to 8 represents this by showing carbon burning in oxygen. The text explains that two oxygen atoms stick together very strongly to form an oxygen gas molecule. But carbon attracts oxygen much more strongly than oxygen attracts itself.
And the phrasing the author uses here is wonderfully dramatic.
It is.
It states that when an oxygen molecule gets close enough to a carbon atom, the carbon rips the oxygen atoms apart and they snap together with, quote, a tremendous vengeance and commotion.
That massive sudden release of kinetic energy when they snap into their new, more tightly bound configuration, that commotion is exactly what we perceive in the macro world as heat and flames. It's just a violent reshuffling of partnerships to form carbon monoxide or carbon dioxide.
It's incredible to think of a fire not as a glowing thing, but as an event. A trillion microscopic violent collisions and partner swaps happening all at once.
It's pure chaos.
But atoms can do much more than just violently snap together in tiny groups. They can form sprawling complexities. Figure 1 to 9 poses a simple question. When you walk past a flower and smell it, what is physically happening?
Well, a molecule has literally worked its way into your nose.
Yeah.
The text strips away any romance from it, noting that the scent molecule has no desire to be in your nose.
It's just blundering around.
Yeah, it's just one helpless part of a jostling crowd of air molecules getting bounced around in a random path, and it just accidentally happens to drift up your nostril.
And the molecule causing the smell of violets is a masterpiece of atomic architecture. The text shows us a specific one in figure 110 and literally calls it a monster molecule.
It really is a monster.
It's called alpha iron. Its full chemical name is, bear with me here, 4-2-2-3-6 tetramethyl 5-cyclohexanol-3-butan-2-1.
It just rolls right off the tongue.
Doesn't it? But the diagram of it is insane. It's this massive puckered ring of carbon atoms with chains of other carbons, hydrogens, and an oxygen atom sticking off it in very specific three-dimensional directions.
It's super complex.
But if you're listening to this and remembering your high school chemistry textbook, you might be wondering, are chemists just guessing?
A lot of people wonder that.
How on earth do they know the exact 3D shape, the exact angles of a molecule they can't even see with a microscope?
The text actually addresses this skepticism.
Yeah.
Before we had modern physical measuring tools, organic chemistry was the most complex blind detective work in human history.
Because they couldn't see anything.
Right. They couldn't see the molecules, so they mixed bottles of stuff together.
Mm-hmm.
If you mix unknown substance A with a known testing substance and the liquid turns red, the chemist deduces that based on the laws of attraction, there must be one hydrogen and two carbons attached at a specific spot on the ring.
Oh.
If it turned blue, it meant a completely different structure.
Hmm?
They mapped out these monster molecules piece by precise piece just by observing how different chemicals reacted.
And decades later, when physicists finally developed the tools to actually measure and locate these atoms physically, the chemists were right.
They nailed it.
Their blind detective work was staggeringly accurate. And it wasn't just chemistry proving the behavior of these unseen atoms. The text points to a physical phenomenon called Brownian motion as ultimate proof.
Yes. If you put a tiny but visible particle in water, say a speck of pollen, and look at it under an optical microscope, it doesn't sit still.
It moves.
It continuously jiggles around in a random, jagged, erratic path.
And for a long time, people didn't know why. But the atomic hypothesis explains it perfectly using the push-ball game analogy.
It's a great visual.
Think of the pollen speck as a giant push ball on a field. Now imagine a massive crowd of unseen people are pushing the ball from all sides. The ball is going to wobble and jerk around based on which side happens to get pushed a little harder by the crowd at any given millisecond.
Exactly. The pollen speck is the giant ball, and the unseen crowd is the water molecules, constantly bombarding it.
Right.
Because the bombardment is random, sometimes slightly more molecules hit the left side than the right, and the speck jerks right. It is direct physical evidence of the invisible, jiggling atomic world.
So if atoms can arrange themselves into simple water drops, violent fires, and the insanely complex monster molecule that makes the odor of a violet, what is the upper limit? Like, how far does this complexity go?
Well, this brings us to the ultimate extrapolation. The text states the most important hypothesis driving modern biology. It says, everything that animals do, atoms do.
Wait, everything. Every movement, every instinct?
Yes. There is absolutely nothing that living things do that cannot be understood from the perspective of atoms acting according to the strict, unbreakable laws of physics.
That's intense.
It is. For centuries, people believed in some magical, vital force or life stuff that animated living creatures. The atomic hypothesis completely dismantles that.
The author specifically points to things like muscle contraction and nerve impulses to prove this. When you flex your arm, it's not some abstract biological magic.
No, it's mechanics.
Right. At the microscopic level, it's complex protein molecules, actin and myosin, sliding past each other, triggered by calcium ions snapping into place.
Yeah.
It's the exact same fundamental mechanism as carbon snapping into oxygen to create fire, just orchestrated on a vastly more complex, highly organized scale.
And nerve impulses are the same. A thought in your brain, or a signal to move your hand, is just sodium and potassium ions rushing back and forth across the cell membrane.
Like the salt crystal.
Exactly. It is driven by the exact same electrical tug-of-war we saw when the salt crystal dissolved in the glass of water. Biology is essentially just applied chemistry, and chemistry is just applied physics.
So when I reach out to pick up a glass of water, it's just a cascade of atomic dominoes falling according to the exact same rules of attraction and repulsion that govern a piece of ice melting.
Pretty much.
We are made of the exact same atoms, obeying the exact same rules as the rest of the universe.
It's a profound realization that connects you directly to the fundamental fabric of reality.
It really is. Let's unpack everything we've covered today, because we have gone all the way from the simplest droplet of water to the staggering complexity of life itself.
We covered a lot of ground.
We did. We learned that heat is nothing more than jiggling atoms. We learned that stillness is a total illusion masking a chaotic battlefield of dynamic equilibrium.
Yeah.
We learned that chemical reactions are just atoms violently swapping partners. And finally, that biological life isn't magic, it's just physics scaled up to unimaginable complexity.
It demands that you see the hidden action in everything around you.
I want to leave you with one final thought, building off the very end of the text. The author asks us to imagine looking in a mirror.
Okay.
When you see your reflection, you are looking at a staggering, unimaginably complex, non-repeating pile of atoms. A very special pile of atoms that is currently thinking about atoms.
It's a trip.
It is. So, here's a thought to mull over today. If every thought you have, every emotion you feel, and every single action you take is ultimately just the result of atoms blindly obeying the strict, rigid laws of physics, what does that mean for your sense of self?
That's a huge question.
What does it mean for your free will? Are you making choices, or are you just a billion chemical reactions playing themselves out in a deeply complex chain? The next time you look at that supposedly still glass of water on your desk, remember that the exact same chaotic, invisible machinery is churning inside of you.
I want you to imagine that you are standing on a beach. You know, you look out at the sea.
Right, just taking it all in.
Exactly. You watch the water breaking into this white foam. You feel the wind coming off the waves.
You hear the sloshing of the tide.
Yeah, and you see the clouds, the blue sky, the blinding sunlight. You feel the grit of the sand under your feet, the hard edges of the rocks.
It's an incredibly complicated, sensory-rich scene.
It really is. But, you know, curiosity kind of demands that we ask a rather profound question here. Are all these wildly different things like the rock, the wind, the sound, the light, are they actually just a few basic elements playing out an infinite number of combinations?
I mean, that is the ultimate question of physics, right?
Yeah.
Is the sand actually any different from the rock, or is it just tiny rocks? And if we understood the microscopic structure of a pebble, would we fundamentally understand the moon?
Which is exactly what we're getting into today. We are immersing ourselves in excerpts from Chapter 2 of the legendary Feynman Lectures on Physics.
Such a fantastic source.
It is. And the mission for this deep dive isn't just to memorize physics trivia or equations. We are going to unpack the fundamental rules of nature together.
Right, to completely upgrade how you view the fabric of reality.
But, you know, to figure out what the universe is made of, we first have to agree on what understanding something actually means.
That's a really important distinction to make.
Yeah, and the source material offers this brilliant analogy for this. It suggests that the world is like a great, impossibly complex game of chess being played by the gods.
I love that analogy.
Right, and we, humanity, we are just observers who don't know the rules. So understanding physics just means figuring out how the pieces move.
Which is a pretty humbling way to look at human intellect, honestly. We are just, allowed to watch the board.
I do want to push back on that analogy slightly, though.
Oh, How so?
Well, if I watch a grandmaster play, I might eventually figure out that a knight moves 2 squares forward and 1 square over. But knowing that rule doesn't mean I understand why the grandmaster just sacrificed their queen to secure the center of the board. I mean, knowing the rules of the game isn't the same as understanding the strategy.
That's a great point. And the source material actually wrestles with that exact limitation.
Really?
Yeah, even if we somehow discovered every single fundamental rule of nature, we still might not be able to understand why a specific complex event happens.
Because the game is just too big.
Exactly. The game is simply too vast, and our minds are too limited to track every single variable. We can't always follow the plays to predict exactly what's going to happen next.
Right.
So science has to accept a more modest goal, which is just finding the rules. If we can reliably deduce the rules, we consider that we understand the world.
But if we're just watching this impossibly complex game, and we can't follow the grandmaster's broader strategy, how do we even check if the microscopic rules we are guessing are actually correct?
Well, physicists have roughly 3 ways to test their guesses when the board gets too chaotic.
Okay, what's the first one?
First, we look for simple situations. We find a quiet corner of the chessboard where there are only 2 or 3 pieces interacting.
So we can observe them in isolation.
Exactly, and then we predict exactly what will happen. In the laboratory, that is basically the essence of a controlled experiment.
You strip away the noise.
Right. And then second, we rely on derived rules.
Meaning what exactly?
Say we figure out the rule that a bishop only moves diagonally. From that, we deduce a broader implication. This specific bishop, which started on a red square, will always remain on a red square.
Oh, I see.
So we don't have to monitor every single move it makes, we just occasionally glance over and check its color. If it's still on red, our underlying rule is holding up.
I love that because it sets up the exact moment where discoveries happen.
How do you mean?
Well, let's say I glance over and that same bishop is suddenly sitting on a black square. Instead of assuming the universe is broken, I realize I just encountered a new rule.
Yes, exactly.
Like, the old rule worked perfectly for a long time, but its failure points to something deeper. Maybe the original bishop was captured, a pawn made it to the other side of the board and, got promoted to a new bishop on a black square.
Discovering those broken rules is the lifeblood of physics. The most profound phenomena are always found in the places where our old rules suddenly fail.
Right.
Which brings us to the third way we check our understanding, rough approximation.
Rough approximation.
Yeah, the text mentions watching the legendary chess player Alexander Alekhine.
Okay.
We might not possess the intricate genius to understand his specific combination of moves, but we can roughly observe, he is gathering pieces around his king to protect it.
We can see the big picture.
Exactly. We can understand nature in broad strokes, even if we can't track every single atom.
Which feeds directly into what is arguably the biggest goal in physics.
Right.
Amalgamation.
Amalgamation, yes.
Because the history of science is essentially the history of taking things that look completely alien to each other and realizing they're, different expressions of the exact same rule.
Like heat and mechanics.
Yes. For centuries, we thought heat was its own distinct phenomenon, like a sort of invisible fluid.
Right.
But then we amalgamated it with mechanics. We realized that heat is literally just the mechanical motion of atoms.
The faster they jiggle, the hotter the object feels.
Exactly. Heat is motion.
And the amalgamation of electricity, magnetism, and light is an even more striking example of that.
Oh, totally.
I mean, 3 totally different sensory experiences, a spark, a compass needle moving, and the light from the sun, were eventually revealed to be just different behaviors of a single underlying entity.
The electromagnetic field.
Exactly.
So let's apply that classical kind of pre-1920s picture to demystify our original beach scene.
Let's do it.
In this classical view, the universe is a 3-dimensional stage of space. The medium of change is the ticking clock called time, and the actors are moving particles.
It's very elegant.
Right. And with that incredibly simple model, the multitude of attributes on the beach just kind of vanishes into logic.
Yeah, the wind you feel on your face isn't a unique substance. It's just a swarm of atoms drifting in one general direction.
And the pressure of the air is just millions of invisible particles constantly ricocheting off your skin.
Even the sound of the ocean crashing isn't an independent thing.
No.
No, it is merely a wave of excess particle density, like a localized traffic jam of atoms propagating through the air toward your eardrum.
That model explains almost our entire everyday experience.
Yeah.
But It does leave a massive glaring mystery.
The binding problem.
Exactly. If all matter is just a myriad of moving particles, what binds them together? Like if I pick up a rock on that beach, what is the machinery pulling the carbon and oxygen atoms together so tightly?
Well, it cannot be gravity.
Right, gravity's a smooth, long-range attraction. But on an atomic scale, it is laughably weak.
Extremely weak.
It could never hold a solid object together against the sheer kinetic energy of moving atoms.
So what is it?
The hidden architecture holding your rock together is the electric force.
Ah, the fundamental property of charge.
Yes. Unlike gravity, where mass simply attracts mass, the electric force operates on a binary positive and negative charges.
Likes repel and unlikes attract.
Exactly. And I think most people hear electric force and think of like an outlet in their wall.
Right. They completely underestimate its raw, terrifying power.
Yes. The source material provides a thought experiment that honestly permanently changed how I view physical objects.
The sand grains.
The sand grains. So I want you to imagine you have two tiny grains of sand, just 1 millimeter across.
Barely visible.
Right. You hold them 30 meters apart. Now assume they weren't electrically balanced.
Meaning no cancellation from opposing charges?
Exactly. Imagine everything in them attracted everything else, with no cancellation. The force pulling those two tiny grains of sand together wouldn't be a microscopic tug.
No.
It would be 3 million tons.
3 million tons of force between two specks of sand.
Isn't that insane?
It is staggering. And the only reason we don't notice this massive strength is because the universe is meticulously balanced. Every positive charge in the matter around us is perfectly matched by a negative one.
So from a distance, the massive attractions and massive repulsions cancel each other out perfectly.
Right. You only feel the force when things get incredibly close, like on the atomic scale, where the local structures can sort of see inside each other and bind together.
But wait, how does one charge actually know another charge is 30 meters away?
Action at a distance. The classical physicists wrestled with this concept.
Yeah, the text uses a great analogy of corks floating in a pool of water.
It does. If you want to move a cork that's floating right next to you, you can just push the water directly into it. Local interaction.
Right.
But if the second cork is all the way across the pool, you can't just magically make a move. You have to jiggle your cork, creating a disturbance.
And that disturbance propagates. The jiggling cork pushes the water next to it, creating waves that travel outward across the pool.
Yeah.
Eventually, those waves reach the distant cork and force it to move. There is a measurable delay.
That delayed oscillatory influence traveling through the medium is the perfect visualization of the electromagnetic field.
You know, instead of a pool of water, I like to picture the universe as an incredibly taut, invisible trampoline.
I like that.
If you press down on one side, it takes a fraction of a second for the ripple to travel across the fabric and affect an object on the other side.
Right.
When you shake an electrical charge back and forth on this invisible trampoline, you create waves in the electromagnetic field. And the only difference between the phenomena we experience is the frequency of the shaking.
Which is wild. If you oscillate a charge at 1 million cycles per second, you create radio waves. You can broadcast music across a city.
And if you shake it faster, you generate radar.
Shake it ridiculously fast, between 500 trillion and 1,000 trillion times a second, and you don't even need an antenna to detect the ripple.
Your biological eye picks it up.
Exactly. It manifests as visible light, red, blue, violet.
So a radio wave and a beam of sunlight are literally the exact same physical mechanism, just happening at different speeds.
It is the ultimate triumph of amalgamation.
Keep shaking it faster, and you get X-rays, then gamma rays from nuclear reactions.
The elegance of that classical field theory was intoxicating. I mean, physicists thought they had the rule book essentially mapped out. But as we entered the 1920s and began looking closer, zooming in on the atoms themselves, the universe threw a massive wrench into our beautifully constructed gears.
The classical picture actually creates a terminal paradox, doesn't it?
It does. Newton's mechanical rules of inertia and forces simply failed to predict reality on a small scale.
Because, think about it, we just established that opposites attract. And we know an atom consists of a heavy, positively charged nucleus surrounded by super light, negatively charged electrons.
Right.
Under classical rules, the electric force should cause the negative electrons to instantly crash directly into the positive nucleus.
Solid matter should utterly collapse. Atoms shouldn't be mostly empty space.
But they are. So how did we resolve that paradox?
The resolution required completely abandoning classical physics and embracing quantum mechanics.
A huge paradigm shift.
Massive. And the cornerstone of this new reality is the uncertainty principle.
Okay, unpack that for us.
It dictates that you fundamentally cannot know both the precise location of a particle and its exact momentum, meaning its speed and mass at the same time.
So there's a trade-off.
Exactly. The relationship is mathematically bound. The more tightly you constrain a particle's position, the more wildly uncertain its momentum must become.
Let's apply that directly to the collapsing atom. The source notes that an atom is about 10 to the minus 8 centimeters across. But the nucleus is a microscopic speck within that, measuring only 10 to the minus 13 centimeters.
Right, so if we magnified an atom to the size of a massive cathedral, the nucleus would be a tiny grain of dust floating in the center.
Imagine if the electron actually did surrender to the electric force and fall all the way into that dust grain.
If it fell into the nucleus, its position would be pinned down incredibly precisely. We would know exactly where it is.
But the rules of quantum mechanics forbid that without a cost.
Right. Because its position is suddenly so exact, its momentum must become massive and highly uncertain.
It would possess an absurd amount of kinetic energy purely from the uncertainty.
And that kinetic energy would vastly overpower the electric attraction. The electron would literally explode outward, breaking away from the nucleus entirely.
So nature negotiates a compromise.
Yes. The electron doesn't fall into the nucleus. It stays further out, occupying the vast, quote-unquote, empty volume of the atom.
By taking up more space, its position remains uncertain enough that its momentum stays low enough to maintain the electrical bond.
Exactly. Which means the electron can never sit still.
It has to constantly jiggle and smear itself across that orbital space.
If it stopped, we would know its location, violating the rule.
The only reason the chair you were sitting on, or the sand on the beach, possesses solid volume is because the electrons inside those atoms are aggressively wiggling to satisfy the uncertainty principle.
They refuse to be pinned down.
It's just so mind-bending.
It is. And this quantum compromise completely rewrote our philosophical understanding of nature. It marked the death of exact predictability.
The death of predictability.
Yeah. In classical mechanics, if you know the exact starting conditions of a system, you can predict its future with absolute certainty.
Right.
Quantum mechanics proved that nature operates on probabilities. If you observe an atom that is primed to emit a photon of light, it is fundamentally impossible to predict exactly when it will happen. We can only calculate the odds.
I find myself wrestling with the philosophical implications of that.
How so?
Well, the scientific method is built entirely on reproducibility, right?
Yeah, sure.
If I conduct an experiment in Stockholm, and then I perform the exact same experiment under the exact same conditions in Quito, Ecuador, I'm supposed to get the exact same result.
Right, that's the classical assumption.
But if nature is fundamentally unpredictable at the lowest level, doesn't the entire foundation of science collapse?
You know, you are echoing a profound yet very common misunderstanding about the philosophy of science. The source text actually tackles this head-on. The idea that identical conditions must unconditionally produce identical results everywhere is simply false. It is an arbitrary philosophical precondition we try to impose on nature.
But how do we do science without it, though?
By returning to the only absolute fundamental philosophy of science, the sole test of the validity of any idea is experiment. Period.
The experiment is king.
Exactly. Think about a pendulum suspended on a universal joint.
Oh.
If you pull it back and let it swing in Stockholm, you will notice the plane of its swing slowly rotates over time.
Right, due to the Earth's rotation at that specific northern latitude.
Exactly. But if I take that same pendulum down to the equator in Quito, the plane of the swing won't rotate at all. The local environment always intrudes. Science does not dictate that the pendulum must behave the same way in both cities. Science simply says, we conduct the experiment, we meticulously observe what actually happens, and then we formulate our rules based on that empirical reality.
We don't get to tell the universe how to behave.
Right. We do not get to dictate to the universe how it should behave ahead of time. If experiments show that atoms emit photons statistically and unpredictably, our philosophy must extend to absorb that truth.
We just have to accept the math.
Yes.
And by accepting it, physicists developed quantum electrodynamics, or QED.
A monumental achievement.
It is the ultimate amalgamation of particles and fields, explaining everything outside the nucleus of the atom.
All of chemistry.
Yeah, the collision of billiard balls, the color of neon signs, how oxygen and carbon interact in your bloodstream. All of it is governed by QED.
QED mapped the suburbs of the atom flawlessly.
The suburbs. I like that.
But when physicists finally turned their attention downtown to the incredibly dense 10 to the minus 13 centimeter nucleus, the rules broke down all over again.
Because it's an absolute nightmare in there.
Total
We
chaos.
just established that positive charges fiercely repel each other. Yet, inside the nucleus, you have multiple positive protons packed shoulder to shoulder in an impossibly small space.
Right, the electric force trying to detonate that nucleus must be astronomical.
So the fact that the nucleus doesn't instantly blow itself apart proves there must be an incredibly powerful, undiscovered force holding it together.
With a strong nuclear force.
Exactly.
Physicists reason that just as the electromagnetic force is carried by the photon, this new nuclear force must have a carrier particle too.
Right. And a theorist named Hideki Yukawa hypothesized this particle.
Yes, by looking at the extremely short range of the nuclear force, Yukawa actually calculated how massive this undiscovered particle should be. He predicted a specific mass.
Which leads to one of my favorite moments in the history of physics.
It's so good.
Experimentalists started looking for Yukawa's particle by studying cosmic rays hitting the atmosphere.
Okay.
And amazingly, they found a particle with exactly the mass Yukawa predicted.
Success.
Except it was the wrong particle.
It was a total cosmic prank.
Literally. They discovered the muon, it had the correct mass, but it didn't interact strongly with nuclei at all.
It just acted like a much heavier, entirely unnecessary version of the electron. It solved absolutely nothing regarding the nuclear force.
I love that. Physicists were basically like, who ordered that?
Exactly.
They eventually did find the particle Yukawa wanted, the pion.
Right.
But the mathematical calculations required to prove how the pion held the nucleus together were so insanely complex that, for decades, theorists couldn't actually solve the equations to check if the theory matched reality.
And while the theorists were drowning in impossible math, the experimentalists just kept building bigger particle accelerators.
Smashing protons together at higher and higher energies.
It's like trying to figure out how a pristine Swiss watch works by hitting it with a sledgehammer and frantically cataloging the gears as they fly across the room.
That is the perfect analogy. Only instead of finding three basic gears, electrons, protons, and neutrons, the sledgehammer revealed a chaotic zoo.
A literal zoo. The text famously refers to this era as the horrible condition of modern physics.
Because suddenly, physicists were drowning in roughly 30 entirely new, distinct particles.
Baryons, mesons, leptons.
Yeah, they discovered particles with names like lambda, sigma, and chi. Some decayed in a fraction of a microsecond. Some were incredibly heavy.
The beautiful, elegant amalgamation we achieved with QED shattered into a messy catalog of unconnected trivia.
And the desperation to find order is just palpable.
Oh, absolutely.
Physicists are constantly trying to construct a new periodic table for these subatomic particles, categorizing them by charge and mass.
And they encountered decay rates that made so little logical sense that they literally had to invent a new conserved mathematical property just to balance the equation.
Right, and they named this property strangeness. When the leading minds of a generation start categorizing the fundamental fabric of reality by its strangeness, you know the rule book has been thrown out the window.
It really has. There is, however, a faint glimmer of order amidst the chaos of the particle zoo.
Just a glimmer.
A glimmer. Despite discovering dozens of bizarre particles, experiments suggest they all seem to participate in only 4 fundamental interactions.
The 4 forces that govern everything.
Exactly. First, gravity, which affects all mass and energy but is almost impossibly weak on the microscopic scale.
Right, the smooth, long-range one.
Second, the weak interaction. A bizarre, slow process responsible for things like radioactive beta decay, where a neutron spontaneously turns into a proton.
Okay, that's 2.
Third, electromagnetism, our well-understood QED, which handles everything with a charge.
The trampoline.
Yes. And finally, the strong interaction, the immensely powerful force holding the nucleus together whose underlying laws we still fundamentally struggle to map.
Think about the journey we've taken today.
It's a lot.
We started by looking at a simple beach. We realized the wind, the sound, and the heat are just the mechanical wiggling of atoms.
We uncovered the terrifying hidden strength of the electric fields holding that sand together. Forces that would crush a city if they weren't perfectly balanced.
We ventured into the quantum realm, discovering that matter only possesses solid volume because electrons aggressively vibrate to satisfy the uncertainty principle.
And we stared into the chaotic, untamed frontier inside the nucleus. a realm of strange, fleeting particles that stubbornly resist our attempts at amalgamation.
The core takeaway here is a permanent shift in perspective. When you look at the world around you, do not settle for seeing static, solid objects.
Look deeper. Visualize the invisible, jiggling fields of potentiality. See the beautiful, perfectly understood rules of chemistry operating in your own bloodstream, constantly at odds with the wild, unexplored frontier raging inside the nucleus of every single atom you are made of.
I want to leave you with a final provocative thought pulled directly from the source material.
Oh, this is a good one.
Humanity has spent centuries trying to assemble this jigsaw puzzle of nature. We keep amalgamating pieces, discovering new ones that don't fit, and rearranging the board. But here's the ultimate humbling truth. We don't actually know if there's a finite number of pieces.
We don't even know if the puzzle has a border.
The next time you stand on a beach and look out at the staggering complexity of the water, the wind, and the sand, remember that the ultimate thrill of learning isn't possessing all the answers. It is realizing just how deeply mysterious the game still is.
Right now, as you're listening to these exact words, the physical arrangement of atoms inside your brain is, well, it's fundamentally altering.
It really is.
I mean, the biological machinery inside your neurons is physically moving ions around, right? It's changing chemical states just to store this very sentence in your memory. So mathematically speaking, you are literally a different physical universe than you were a minute ago.
It's a pretty staggering reality to confront, honestly. We spend, so much of our time just walking around experiencing the world at this macro level.
Yeah, exactly.
And we just assume that our thoughts or our movements are somehow, separate from the raw mechanical laws of nature.
But today, we are stripping away that macro-level illusion. Welcome to the deep dive. Today, we're exploring Chapter 3 of the legendary Feynman Lectures on Physics. It's titled The Relation of Physics to Other Sciences.
Which is such a great chapter.
Oh, it really is. And the mission of this deep dive is to explore this profound premise. Physics isn't just one specialized subject sitting on a shelf next to biology or chemistry and astronomy. Physics is the shelf itself.
Right. It's the foundational rulebook.
Exactly. Whether we're talking about a star burning in deep space or a frog jumping off the lily pad or even human psychology, it ultimately all comes down to what the text calls the jiggling and wiggling of atoms.
I love that phrase, the jiggling and wiggling of atoms. It perfectly captures what we used to call natural philosophy.
Oh, right. Before everything got so siloed.
Yeah, before we fragmented science into these highly specialized university departments, the original goal was simply to understand nature. If you zoom in far enough on literally any process in the cosmos, you eventually hit atoms following fundamental physical laws.
But, okay, let's unpack this. If everything is just atoms following the rules of physics, how do we end up with all these other sciences? Like, let's start with chemistry. If chemistry is just the study of how atoms bind together and share electrons, isn't theoretical chemistry isn't it just quantum mechanics?
At its absolute deepest level, yes, completely.
Okay.
The rules governing how, say, a carbon atom interacts with an oxygen atom, those are purely quantum mechanical. But there is a massive catch here, and the text uses this really great chess analogy to explain it.
Right, the grandmaster thing.
Exactly. Knowing the rules of chess, like, how the knight moves, how the pawn captures, that doesn't mean you can just sit down and play the game like a grandmaster.
Yeah, the complexity emerges from the interactions. But I've always struggled with that limitation. Like, if we actually have the rules of quantum mechanics,
Which we do.
right, and we know exactly how atoms behave, why can't we just perfectly calculate every single chemical reaction? If it's just physical matter, why can't a supercomputer just, plot them out like billiard balls on a table?
Well, it comes down to sheer, incomprehensible scale. In a standard chemical reaction, just a tiny beaker of liquid, you aren't tracking 2 billiard balls.
Right.
You are tracking trillions upon trillions of atoms, and they're all jiggling around, colliding randomly at incredible speeds. The math doesn't break down because the fundamental rules change.
It breaks down because it's just too much data.
Precisely.
Oh.
Calculating the individual trajectories of a trillion interacting particles, it exceeds the computational capacity of the human mind, and frankly, any computer we can possibly build.
So we're kind of forced to cheat, in a way. Since we can't track the individual atoms, we have to invent a way to track the crowd.
Yeah, and that cheat is an entire branch of science called statistical mechanics, or thermodynamics.
Okay, right.
So instead of asking what one specific atom is doing, statistical mechanics asks about the average behavior of this massive swarm. Think of it like a like a traffic helicopter observing a highway.
Oh, that's a good way to picture it.
The reporter up in the helicopter, they can't tell you exactly when one specific Honda Civic is going to tap its brakes.
No, of course not.
But they can perfectly predict that traffic is going to back up at the tunnel at 5:00 p.m. So physical chemistry studies that macro-level flow, like how fast molecules hit each other, which pieces fly off first, while quantum mechanics supplies the underlying rules of the road.
Okay, so if chemistry relies on observing the average behavior of massive crowds of atoms, then biology must be like the ultimate, most complex application of those averages.
Oh, absolutely.
Because the jump from inorganic rock to a living, breathing cell, that feels like crossing this unbridgeable canyon. But the text insists it's really just a matter of machinery.
And historically, we couldn't see that machinery.
Hmm.
Early biology was purely descriptive. Scientists would, catalog the shape of a leaf, or they'd sit there and count the little hairs on a flea.
Right, just drawing what they saw.
Exactly. They didn't have the tools to look inside.
Yeah.
But as our physical instruments improved, biology transitioned from observation to mechanism. We began to see that living things are just packed with highly specific atomic-level machines.
Yeah, and the section on the nervous system completely changes how you think about feeling pain. Like, say you step on a sharp stone, right, and your brain registers it.
Yeah. The text describes the nerve not as a regular wire, but as an incredibly fine tube. And the cell is physically pumping ions across the tube wall, creating this electrical charge difference between the inside and the outside. It's building up potential. It's very much like a localized battery or a capacitor. So when you step on that stone, the physical pressure causes the membrane at the bottom of your foot to become permeable.
And the ions rush back in.
Exactly. They rush in, discharging that specific section of the nerve.
And that discharge triggers the next microscopic section of the nerve to open up, and then the next, and the next. So an impulse isn't just one single thing traveling up your leg.
No, it's not.
It's a falling sequence of dominoes running all the way up to your brain.
With the vital caveat that, a fallen row of dominoes is useless until something sets them back up again.
Oh, true. You need to be able to feel the next step.
Right. So the nerve cell immediately expends energy to physically pump those ions back out against the gradient, resetting the charge for the next impulse. It is a purely physical, electrical, and chemical mechanism.
Which brings us to one of the most intimidating diagrams in all of biology, which the text actually highlights. Figure 3.1, the Krebs cycle.
Oh, the dreaded Krebs cycle, every biology student's nightmare.
Exactly. It maps out the chemical reactions happening inside our cells. You look at this crazy circle of complex chemical formulas transforming step by step. A carbon atom drops off here, a hydrogen atom attaches there. But if atoms are just like blindly jiggling around, what actually drives these specific transformations?
That is the central hurdle of biochemistry right there. These transformations don't just happen because two molecules bump into each other in the dark. They are separated by something physicists call activation energy.
Right, the energy hill.
Yes.
Like if I want to turn molecule A into molecule B, it's like trying to push a heavy boulder up a steep hill.
Yeah.
Even if rolling it down the other side releases a lot of energy, the boulder usually just rolls partway up and falls right back down.
Because it doesn't have the initial momentum to crest the peak.
Exactly.
And in a chemistry lab, you get the boulder over the hill by adding massive amounts of heat. You literally boil the solution, which makes the atoms jiggle violently enough to crash together and force the reaction to happen.
But inside a living cell, you can't boil the fluid.
No, the organism would instantly die.
So how does biological life cheat the system? Like how do we crest that hill without heat?
Life uses enzymes. An enzyme is a massive protein structure that acts as a physical workaround.
Okay, so it's not adding energy. It's more like, is it like digging a secret tunnel through the mountain?
That is a perfect way to visualize it.
So you don't have to push the boulder over the top anymore.
Exactly. The enzyme is this giant, highly customized mechanical pocket. It grabs molecule A, holds it at the exact perfect physical angle, and applies localized stress to the chemical bonds.
Wow.
So that molecule B can just snap into place without needing any of that extreme heat. And what's truly fascinating is how mechanical the design of that enzyme actually is. Proteins are basically just long chains of 20 different amino acids.
Right.
So if the biological instructions insert an amino acid called proline, it literally forces a physical kink in the chain.
Like bending a wire.
Yes.
Yeah.
And if it inserts an amino acid with a sulfur atom, that sulfur actively seeks out another sulfur further down the line, binding them together to form a physical loop.
So the specific sequence of amino acids forces this long chain to fold up into a very specific, like, three-dimensional origami shape.
Exactly.
And that shape creates the exact tunnel needed for one specific chemical reaction. The text points out that we've actually mapped the exact spatial location of thousands of atoms in certain proteins. Like, we have the full blueprint.
We do, but we still lack a fundamental understanding of the engineering behind it.
What do you mean?
Well, we know where every single atom is in a protein like hemoglobin, but we often cannot look at that 3D structure and explain why that specific shape is so perfectly efficient at capturing and releasing oxygen.
Oh, I see. We know the what, but not the why.
Right. It's still an incredibly active area of physical chemistry.
But we do know the output, though. Looking back at that Krebs cycle diagram, there's this tiny transformation at the bottom. GDP turns into GTP.
Ah, yes.
Guanosine diphosphate gains one more phosphate group. The text calls this the battery of life, but how does adding one little molecular group store energy?
It all goes back to electromagnetic forces. Phosphate groups are highly negatively charged. And in physics, we know that, charges repel.
Right, opposites attract, likes repel.
So forcing a third negatively charged phosphate group onto that molecule is like trying to push the identical poles of two strong magnets together.
Oh man, that's hard.
It requires a lot of mechanical work to force them into place and then lock them with a chemical bond.
So all the energy from the food we eat is basically being used to compress that microscopic spring.
Exactly. That GTP molecule now holds massive potential energy. So later, when a muscle fiber in your arm needs to contract, an enzyme snaps that third phosphate off.
And it springs open.
Yes. The highly repulsive negative charges violently push apart, and that releases the energy that physically drives the muscle contraction.
That is incredible.
Then the GTP becomes the depleted GDP, and the whole cycle just starts over again.
And the way early scientists mapped this whole cycle is just genius. They used physics to tag the atoms. They took carbon dioxide, but instead of standard carbon-12 atoms, they used heavy carbon-13 isotopes.
Which is brilliant.
It's like putting a microscopic tracking collar on a single atom and watching exactly where it travels through that massive clock face of the Krebs cycle.
It really is. But, this complex factory of enzymes and batteries, it begs a really massive question.
What's that?
Well, if an enzyme's function relies entirely on its specific 3D shape,
Right.
and that shape relies on the exact sequence of amino acids, how does the cell know the sequence? How does a living thing actually store the instructions to build a proline kink or a sulfur loop?
Ah, right. That brings us to figure 3.2, the schematic of DNA. And I want to skip the whole high school biology visual of the twisted ladder because the text goes straight for the underlying physics of it.
Let's do it.
The rails of DNA are just sugar and phosphate, but the rungs connecting them are 4 specific chemical bases. Let's just use the text's simplified letters, A, B, C, and D.
The crucial physical reality here is the thermodynamics of how those specific bases interact. Base A has a shape and a hydrogen bonding profile that makes it thermodynamically favorable to lock onto base B.
Meaning it physically cannot bind with C or D.
Right. The atoms literally repel each other. A only goes with B, C only goes with D.
So when a cell divides, it isn't making some, conscious, complex biological decision.
Not at all.
The DNA chain just physically splits down the middle, leaving half a rung exposed. If that exposed half is an A, the laws of physical chemistry dictate that only a free-floating B base from the cellular soup can lock into it.
It is essentially a self-replicating zipper dictated entirely by physical forces.
That's wild.
And that DNA sequence is then copied onto a messenger molecule called RNA, which carries the instruction code out to the ribosomes, the cell's actual manufacturing plants.
But the text highlights a massive unresolved mystery here. We know the RNA sequence goes into the ribosome and an amino acid chain comes out. But how does a sequence of A's, B's, C's, and D's physically translate into the instruction, put proline here?
Yeah, that's the translation mechanism. At the time of Feynman's lecture, it was a massive black box. Today we understand the role of transfer RNA and codons a bit better, but the profound mystery he highlights still remains.
Which is what, exactly?
How did physical atoms, blindly following the laws of thermodynamics, accidentally arrange themselves into a codified language that builds complex machinery? The driving assumption of all biology is that we will eventually trace this translation back to the blind jiggling of atoms. But the sheer complexity of it is just staggering.
It really is. And life is incredibly efficient at recycling these carbon, oxygen, and nitrogen atoms to build all this machinery. But it makes me wonder, if life is just constantly reorganizing a set number of atoms on Earth, Where did the very first batch of these atoms even come from?
That's a great question.
Like before biology existed, before the Earth existed, how did the universe forge the carbon that makes up our DNA?
To answer that, we have to pull all the way back from the microscopic machinery of cells and look at astronomy.
Okay, a big pivot.
Huge pivot. Historically, astronomy gave physics its start. Observing the mathematically perfect orbits of the planets is what led to the theory of gravity. But the most significant revelation in the history of astronomy was discovering the physical composition of the stars.
And we didn't do that by sending a probe. We
Yeah.
couldn't. We did it using spectroscopy, which is just such an elegant application of physics.
Oh, it's beautiful.
Atoms emit and absorb light at very specific rigid frequencies based on their electron configurations, right? So if you capture the light from a star burning millions of light years away, and you break that light apart with a prism, you see these distinct black lines where specific frequencies are simply missing.
And those lines are a literal chemical fingerprint. By matching those missing frequencies to gases that we can test in laboratories here on Earth, we can prove that the stars are made of the exact same hydrogen, helium, and carbon that we have right here.
Wait, didn't they actually find helium on the sun before they found it on Earth?
Yes, helium was discovered in the spectral lines of the sun before anyone ever isolated it on our own planet.
That is amazing. There is a moment in the text that carries so much philosophical weight about this. Feynman tells this anecdote of the astrophysicist who first realized that stars are powered by nuclear fusion.
Oh, I know this story. It's a bit sad, actually.
Yeah, he's out on a date, looking up at the night sky. His girlfriend says, "Look at how pretty the stars shine." And he says, "Yes, and right now I'm the only man in the world who knows why they shine."
It's a beautifully melancholy story. She just laughs at him, not understanding the magnitude of what he's just shared.
Right.
Physics often provides this lonely, reductionist view of the universe. To know the brutal nuclear mechanics underneath a beautiful night sky, it's a heavy burden, but it also reveals a much deeper truth about our existence. Because those stars aren't just burning, they are forging.
Forging elements.
Yes, the extreme heat and pressure crush simple hydrogen atoms together to create helium, and then carbon, and then oxygen.
But wait, I have to stop you there because the text sets up a paradox that really makes no sense to me.
Okay, what is it?
We can use statistical mechanics to perfectly calculate the nuclear fusion happening inside a star millions of light years away. We know its internal temperature, its pressure, its lifespan. But the text bluntly states we cannot accurately predict earthquakes, volcanoes, or even long-term weather on Earth.
It's true.
How is it possible that we understand a massive alien sun better than the ground directly beneath our feet?
It completely defies intuition, I know. But it comes down to the state of matter. A star is a plasma. It's essentially a massive ball of incredibly hot gas. And in physics, gases are relatively simple.
Simple. Really?
Compared to solids, the atoms are moving so fast and are so spread out that you can use statistical mechanics to calculate their average behavior with stunning accuracy.
But the Earth is not a gas.
Exactly. The Earth is a chaotic nightmare of variables. It has a solid crust of varying densities layered over a mantle of circulating, semi-solid rock, topped with oceans of liquid water and an atmosphere of swirling gas.
That is a lot of variables.
The mathematical complexity required to model the circulating temperature currents of magma and then calculate the exact moment a specific tectonic plate will succumb to stress and snap. It involves chaotic, nonlinear dynamics that current mathematics simply cannot resolve.
So we know the mechanics of the stellar furnace better than the rock we stand on, but the twist is that we have physical proof we are connected to that furnace.
We do, through those isotope ratios we talked about earlier. Chemical reactions in biology don't care if an atom is carbon-12 or the heavier carbon-13.
They process them exactly the same way.
Right. The specific ratio of those isotopes in our bodies was permanently locked in by the nuclear reactions that forged them. When a star dies in a supernova, it violently scatters those heavy elements across the cosmos.
And those atoms eventually coalesce into planets.
And eventually into DNA. The carbon in your cells is literally star stuff.
Which brings us to the ultimate observer in all of this. We've traced the atoms from the stars to the Earth into the biological machinery of our cells. But what about the mind that is actually observing all of this? How does physics grapple with psychology?
The source material is very cautious here. It draws a rigid boundary around what actually constitutes a physical science. It points to psychoanalysis and compares it to witch doctoring.
Ouch, that's harsh.
It is, but not to say it can't accidentally help someone. It's because it lacks rigorous, measurable, experimental checking. so it operates outside the physical framework.
But physics must account for the brain, right? Like, if every thought we have and every memory we form is just the result of atoms jiggling, then learning a new fact must require a physical change.
It has to.
If I memorize a phone number, the atoms in my brain must physically rearrange to store that data.
They absolutely must. Neural pathways must strengthen, synapses must physically alter their chemical thresholds, but we don't know exactly where or how. The text humbles us by pointing out that we don't even fully understand the physical atomic mechanics of how a dog's brain works, let alone the complexities of human consciousness.
The text also touches on history, which is interesting. We know biology has a history evolution. Earth has a history geology. But do the fundamental laws of physics have a history? Like, did the rules of the universe ever evolve?
That is a profound question. Currently, physics operates on the assumption that its laws are immutable. The strong nuclear force today is exactly the same as it was a billion years ago.
But what if it's not?
Well, if we ever discovered that the fundamental constants of the universe are slowly drifting over time, physics will suddenly find itself needing a history department. But right now, we only study how the matter behaves under fixed rules.
And even with fixed rules, we still hit a wall with everyday reality. We can calculate the quantum mechanics of a hydrogen atom. We can trace heavy isotopes through a cellular battery. But the text admits we cannot mathematically solve the flow of wet water through a pipe.
Ah, the problem of turbulent flow. It is one of the greatest unsolved mysteries in classical physics.
Really? Just water in a pipe?
Yeah. If you push a thick fluid like honey slowly through a pipe, the flow is laminar. It's smooth and predictable. The equations work perfectly. But if you push water through a pipe at high speeds, it breaks into chaotic eddies and swirls. It becomes turbulent.
And the math just stops working.
We know the fundamental equations of fluid dynamics, but applying them to the chaotic reality of wet water is mathematically overwhelming.
It's like the ultimate reality check. We know the rules of the chess game perfectly, but the board is so incredibly chaotic that we still can't calculate the outcome of the plumbing in our own houses.
It really forces a necessary humility upon the scientific method.
Which makes the conclusion of this chapter so brilliant, I think. The text synthesizes all of this massive complexity into a single poetic metaphor. A glass of wine.
It's a beautiful way to end the chapter.
When you look at a glass of wine, you aren't just looking at a drink. If your perspective is deep enough, you see the entire universe.
You see the physics in the surface tension and the twisting liquid evaporating into the air. You see the geology and the mineral composition of the rocks that nourished the roots of the vine.
You see the biology in the fermentation, the microscopic cellular machinery, those enzymes we talked about folding into specific shapes to metabolize sugar into alcohol.
And you see the astronomy. The star-cooked atoms of carbon, oxygen, and hydrogen forged in a nuclear furnace millions of years ago, sitting right there in the glass. We invented categories like biology and geology because our minds are too limited to study it all at once.
Right.
But nature doesn't know those boundaries. It is one continuous, interconnected dance of atoms.
And as we wrap up today, I hope you can walk away and look at the mundane things around you, your coffee cup, the tree outside your window, the water flowing from your faucet, and see that invisible dance. See the physics underneath it all.
And remember the reality we started with. Because you spent the last 15 minutes absorbing these concepts, engaging your memory, the literal arrangement of atoms inside your head is fundamentally, permanently different now than when you hit play.
That is still so crazy to think about.
We can't map exactly where the new connections formed, but mathematically and physically, you have evolved into a different universe of matter.
Drink that in. Keep jiggling those atoms and we'll catch you on the next deep dive.
You know that glowing blue energy bar in a video game?
Oh, yeah. Always flashing when you're about to lose.
Exactly. Or like maybe you picture this pulsing, glowing orb inside a battery, just kind of waiting to be squeezed out to power your phone or your car.
Yeah.
We are so used to thinking of energy as this physical stuff.
We really are. And, you know, the language we use constantly reinforces that illusion. Like, we complain that we're out of energy, or we read these news headlines about a power plant generating energy.
Right.
As if they're, I don't know, churning out a physical product on some industrial assembly line.
But what if I told you that is completely fundamentally wrong? Today on the Deep Dive, we are going to figure out what energy actually is. We're unpacking Chapter 4 of the legendary Feynman Lectures on Physics.
Which is just a total masterclass in the conservation of energy.
It really is. And our mission today is to take these incredibly complex ideas, the mechanics of lifting, the hidden heat inside materials, even the deep quantum symmetries of the universe, and translate them into something you can clearly visualize.
Yeah, we are going to look closely at the visual proofs Feynman uses to break all these concepts down. They're brilliant, honestly, in their simplicity. And the best part is, you really don't need a physics degree to grasp them.
Not at all. By the end of this conversation, you're going to see the everyday world from, like, a pendulum swinging on a grandfather clock to the warm cup of coffee in your hands in a radically new, completely interconnected way.
Definitely.
But to get there, we first have to unlearn our assumptions, right? We have to let go of that glowing orb idea of energy.
Right.
And Feynman does this using this famous analogy involving a messy child. He calls him Dennis the Menace.
It's the perfect place to start. So imagine a mother leaves her child, Dennis, in a room with exactly 28 indestructible identical toy blocks.
Okay. 28 blocks.
Right. And at the end of the day, she gathers them up and counts them. 28 blocks. This happens every single day. The number never changes. This is essentially her localized law of conservation of blocks.
Okay, let's unpack this. In a perfect world, she just counts 28 little wooden squares. But then, the real world gets messy.
Oh, yeah.
One day, she only counts 27 blocks on the floor. She panics, but then she looks under the rug, and boom, there's the missing block.
Exactly. And the next day, there are only 26. But she notices the window is open, goes outside, and finds 2 in the bushes.
So she's acting like a physicist, maintaining the boundary of a system.
Precisely. She has to make sure nothing comes in or goes out, or, well, if it does, she accounts for it. Like, another day, she counts 30 blocks.
Hey, 30? Where'd the extras come from?
Well, she investigates and realizes a friend came over with a few of their own toys, so she just subtracts the extras.
But then Dennis gets sneaky. The mother comes in, counts 25 blocks on the floor, and sees Dennis's toy box is firmly locked.
Right, and he screams when she tries to open it.
Typical kid. So she cannot physically see the missing blocks anymore. She has to use a workaround. She basically has to use math.
Yeah, she knows from past experience that an empty toy box weighs exactly 16 ounces. And she knows each individual block weighs exactly 3 ounces.
Okay.
So she takes the total weight of the locked box, subtracts the 16 ounces for the box itself, and divides the remaining weight by 3.
And when she adds that calculated number to the 25 blocks she can physically see on the floor, the total is exactly 28.
Every single time.
But Feynman pushes this even further, right? Yeah. Later, the mother comes in, can't find some blocks, but she sees Dennis taking a bath. And the dirty bathtub water is completely opaque. She can't see the bottom.
She can't see a thing. But she knows her physics, she knows the original water level, and she knows that dropping a single toy block into the tub raises the water level by exactly 1/4 of an inch.
So now, instead of weighing a box, she's measuring water.
Exactly.
Right.
She takes the new height of the water, subtracts the original height, divides by 1/4 inch, and adds that to her formula.
And again, when she calculates the blocks on the floor, plus the formula for the toy box weight, plus the formula for the water height, the answer is 28.
Always 28. And this is where Feynman drops the massive twist. It's the ultimate takeaway for real physics. In our universe, when we study energy, there are no blocks.
I mean, it's almost unsettling to think about. We've built our entire modern civilization on a formula for something we can't even picture.
Yeah, it's totally abstract.
Is energy kind of like the net worth of a digital bank account?
Oh, that's a good way to look at it.
Like your wealth might shift around constantly. You might have some in checking, some tied up in a house, maybe some locked in an index fund. It takes totally different forms.
Yeah.
And you have to calculate the value of those forms using completely different complex formulas.
That is a highly accurate analogy. There is no physical pile of gold coins sitting in a vault anywhere. Your net worth is just a number on a ledger. And what's fascinating here is that modern physics still has absolutely no knowledge of what energy actually is.
We just don't know.
We really don't. We don't have a picture of it coming in little glowing blobs. All we have are these wildly different formulas for calculating a numerical quantity. And when we add all the results of those formulas up, nature proves to be a flawless accountant. The ledger always balances perfectly.
That is deeply weird. We can calculate it flawlessly, but we don't know what it is. So if energy is just an abstract number on nature's ledger, how did early scientists even figure out how to calculate it in the physical world?
Well, they started with gravity, and they relied on pure, rigorous logic regarding something they called reversible machines. The foundational assumption they worked from, like the absolute unbreakable band, is that there is no such thing as perpetual motion.
And historically, I mean, people have spent centuries trying to cheat that ban, haven't they?
Oh,
Building
absolutely.
crazy water wheels and magnetic wheels, trying to get a machine to run forever and generate free power out of nowhere.
Countless inventors have tried, and every single one has failed. If you lift and lower weights in a machine, and when the machine comes back to its exact starting position, you somehow have an extra weight lifted up in the air, you've broken physics.
You've created energy out of nothing.
Exactly. It is strictly impossible.
Now, in reality, all real machines lose some momentum to friction, right? Like squeaky hinges rubbing gears.
Sure.
But Feynman asks us to imagine an ideal, perfectly reversible machine. Picture a simple pulley system that balances 3 pounds of weight on one side against 1 pound of weight on the other.
Right.
If it's perfectly reversible, lowering the 1 pound weight lifts the 3 pound weight. And because there's zero friction, you can run it perfectly backwards to reverse the exact process.
Feynman uses this setup to walk through an airtight logical proof. Let's say this reversible machine lowers the 1 pound weight by a distance of 1 foot in order to lift the 3 pound weight. That 3 pound weight must rise exactly 1/3 of a foot.
Okay, let me make sure I follow the logic here. Why must it be exactly 1/3? What if an inventor builds a really clever pulley that lifts the 3 pound weight half a foot instead?
If the inventor could do that, they would destroy the universe.
Literally break reality.
Think about it. If you lower a 1 pound weight by 1 foot and your machine lifts a 3 pound weight by half a foot, you could then take that newly elevated 3 pound weight and use it to run the machine backward.
Oh, I see where this is going.
Lowering the 3 pounds by just 1/3 of a foot would return the 1 pound weight to its original starting height.
Oh, wow. You'd still have the 3 pound weight sitting higher than where it started. Everything is back to normal, but you've magically gained extra lifting height for free.
Which means you'd have perpetual motion.
So logic dictates it can only ever lift it exactly 1/3 of a foot. The math is trapped by the impossibility of free energy.
Exactly. This creates a universal rule. If someone invents a vastly more complicated machine, say a massive puzzle box of gears, levers, and slanted shelves holding multiple metal balls, it doesn't matter how tangled the interior mechanism is.
Right.
By just tracking the start and end states, Feynman shows that if a machine lowers 1 pound by 1 foot, it can only ever lift 3 pounds by 1/3 of a foot. 3 times 1/3 always equals 1 times 1.
Here's where it gets really interesting, which brings us to the famous proof by Stevinus. I love this one. It's so elegant. It was actually engraved on his tombstone.
It's a classic.
He wanted to figure out how forces balance on an inclined plane. So picture a smooth, slanted ramp. It's a right triangle resting on a table. The vertical drop off the back is 3 feet, the horizontal base is 4 feet, and the slanted slope is 5 feet. A classic 3-4-5 triangle.
Right. Now, Stevinus asks a tricky question. If you have a 1 pound weight hanging straight down off that steep 3-foot back edge, how much weight do you need resting on the slanted 5-foot slope to perfectly balance it so nothing slides?
And instead of using messy math or force vectors, Stevinus just imagines a continuous loop of chain draped all the way around the entire triangle, a loop of heavy, equally spaced metal balls.
Exactly. Part of the chain is resting on the slant, part is hanging straight down the back, and the rest is just drooping underneath the table, connecting the two ends.
Wait, if the chain is drooping under the table, how does that help us? Doesn't that just add more messy weight to the problem?
Well, that drooping part is actually the genius of the whole proof. If you look at the chain hanging completely below the triangle, it forms a perfectly symmetrical U shape. Gravity is pulling on the left side of that U shape just as hard as it's pulling on the right side.
So the two sides of the droop completely cancel each other out.
Precisely. They are in a perfect tug-of-war stalemate.
So we could just mentally cut them off and ignore the U shape entirely.
You got it. You are left only with the balls on the 5-foot slant pulling against the balls on the 3-foot drop. And since the slant is 5 feet long and the drop is 3 feet long, there are 5 balls on the slant pulling against 3 balls on the drop.
Meaning the weight on the slope must be exactly 3/5 of a pound to balance a 1 pound weight hanging off the back. I mean, he proved a fundamental law of mechanics using just a shape and pure logic.
And this exact same conservation ledger applies to everything, even a heavy-duty screw jack you might use in a garage.
Like to lift a car.
Yeah. Feynman describes a jack lifting a 2,000-pound ton. The handle you crank is 20 inches long, and the internal screw has 10 threads per inch. So to lift the car exactly 1 inch, you have to turn that handle around in 10 full circles.
Okay, my brain is stalling a bit here. If I turn a 20-inch handle in 10 big circles, the end of that handle is traveling a massive distance.
It is.
The circumference of a 20-inch radius circle times 10, that's about 1,260 inches of total movement, just to lift the car 1 single inch.
That's the ledger at work. You are trading a massive distance for a massive force. We know from our previous rule that the force moving down times the distance it moves must equal the weight moving up times the distance it moves.
So we just balance the books. The weight lifted is 2,000 pounds times the 1 inch it lifted, that's 2,000.
Right.
So the unknown force I'm pushing on the handle, multiplied by the 1,260 inches I moved it, also has to equal 2,000. If we just divide 2,000 by 1,260, I only need about 1.6 pounds of physical force on the handle to lift a 2,000-pound car.
You've just calculated the mechanical advantage. And physicists take this even further with a clever mental trick called virtual work.
Virtual work?
Yeah, imagine a messy lever. A rod supported at one end, but with multiple random weights hung at totally different spots along it. You can't just use a simple ratio there.
So how do you find the hidden forces keeping it perfectly balanced?
You pretend to break the balance. You just imagine nudging the rod, making it pivot a microscopic fraction of an inch. A virtual movement.
Okay.
Because if the system is truly balanced, then even for a microscopic imaginary millimeter of movement, nature's ledger must hold true.
The sum of all those scattered weights multiplied by the tiny vertical distances they theoretically moved going down must perfectly equal the sum of the weights times the tiny distances they moved going up.
Exactly.
By pretending it moves, the hidden forces suddenly reveal themselves in the math. It's all just one singular rule: weight times height relative to the Earth.
And that specific relationship is what physicists call gravitational potential energy. It's energy that exists purely because of an object's location in space. It has the potential to do work.
But hold on, if I carry a bowling ball to the top of a steep hill, I understand it has all this gravitational potential energy, it's stored up.
Right.
But then I let it go. It rolls down the hill, it loses height.
Yeah.
The number on the ledger for gravitational potential energy goes down to 0. So where does the net worth go?
It transfers into another account. Feynman illustrates this with a simple pendulum. When you pull the heavy pendulum bob to the side and hold it still, it's at its highest point. All its energy is gravitational potential energy.
Because it's lifted up.
Exactly. But the moment you let go, it swings down. At the exact dead center bottom of the swing, its height is at its absolute lowest. The potential energy is entirely gone.
But the bob doesn't just stop at the bottom. It's moving incredibly fast.
Because the potential energy has been converted entirely into the energy of motion, which is called kinetic energy. And because it has all that kinetic energy, it has the ability to fight gravity and climb back up the other side of the swing, converting the kinetic back into potential. It trades back and forth constantly.
Just like shifting money from your savings to your checking and back again.
Exactly.
And we see this with springs too, right? If I stretch a heavy metal spring, I'm doing work. I'm storing what's called elastic energy. When I let go, it snaps back, and the elastic energy turns into kinetic energy.
That is correct. But here is where we hit a major real-wanted misunderstanding. In reality, the pendulum eventually stops swinging. The bouncing spring eventually stops bouncing.
Yeah, they don't go forever.
Right, and to the naked eye, the energy seems to have vanished. People often say the energy was lost to friction.
But the whole point of Dennis the Menace is that the mother always finds 28 blocks. Nature's ledger never loses a single cent, so where is it hiding?
It turns into heat energy. But Feynman points out something beautiful here. Heat isn't actually a new or separate form of energy.
It's not.
No. It is literally just kinetic energy, but happening on a microscopic scale. Inside that metal spring, or inside the rubbing gears of our machine, there are billions of atoms. When things bend or roll or grind together, those atoms get disturbed. They start to bump and jiggle.
Wait, so when I'm driving on a highway and I slam on the brakes, all that massive forward motion of a 2-ton vehicle isn't lost. It just turned into my brake pads throwing a microscopic, chaotic, atomic dance party.
That is exactly the reality of the situation. The organized forward motion of the car becomes internal, random, and confused motion inside the brake pads and the tires. The atoms are jiggling frantically.
That's wild.
We can't see that movement with our naked eyes anymore, but we can measure the intensity of the jiggling with a thermometer. We call that measurement temperature or heat.
That perfectly explains why large-scale, 100% reversible machines are practically impossible to build. Every time we move a large clump of stuff, we accidentally disturb the atoms, and some of that visible organized motion leaks into disorganized heat.
It's like dropping a handful of change and having it scatter across a busy street.
Oh, that's a great way to put it.
The money is still there, the total value hasn't changed, but it's incredibly difficult to gather it all back up to buy something useful. And this ledger accounts for every form of energy in the universe.
Right. There's radiant energy, which is light. There's chemical energy, which is really just the kinetic and electrical energy of the electrons and protons interacting inside atoms.
Yep.
There's nuclear energy hidden inside the core of the atom. And finally, mass energy. Einstein's famous E equals mc squared.
Where just the sheer physical existence of an object equals an astonishing amount of energy. Even standing perfectly still, all matter is essentially frozen energy. So energy constantly changes its costume, from gravity to motion to heat to mass.
Which brings us to the ultimate, grand-scale question. Why? Why is it perfectly conserved at all? What is the cosmic mother enforcing the law of 28 blocks?
To understand the why, we really have to look toward quantum mechanics. The conservation of energy is fundamentally tied to a profound symmetry of the universe. The fact that the rules of the universe do not depend on absolute time.
Okay, my brain just melted a little bit. What does it mean for the rules of the universe to not depend on time?
Think of it this way. The universe doesn't have an absolute aging cosmic clock that changes the physics as it ticks. If you set up a chemistry experiment and run it today, and then you set up the exact same experiment and run it a year from now, the chemicals will react in exactly the same way. The fundamental laws don't degrade or strengthen over time.
That makes sense.
And in the early 20th century, physicists proved mathematically that whenever a system has this perfect time symmetry, a natural consequence is that a specific mathematical quantity must be conserved. That quantity is what we call energy.
That is staggering. The fact that the rules don't age is the very reason the ledger balances.
Exactly.
And Feynman points out other conservation laws that work the exact same way, right? Like, momentum is perfectly conserved because the laws of physics don't care where you do the experiment. Space is completely symmetric.
And angular momentum is conserved because the universe doesn't care which direction you are facing when you do the experiment. Orientation is symmetric. These are the deep, subtle symmetries of reality. But nature also has simpler counting conservation laws, much closer to just counting Dennis's blocks.
Like the conservation of electrical charge. You can't create a new positive charge without simultaneously creating a negative one to balance it.
Right.
Or the conservation of baryons, which are heavy particles like protons and neutrons, and leptons, which are light particles like electrons and neutrinos. Whatever number of particles goes into a nuclear reaction, the exact same ledger must balance on the way out.
Which leads us to the final major misunderstanding we need to clear up today.
So what does this all mean for the energy crisis?
Hmm.
We constantly hear politicians, scientists, in the news stressing about an energy crisis and running out of power. But if energy is perfectly conserved and the universe never loses a single drop of it, what are we actually stressing out? The ledger is fine.
The stress comes from failing to differentiate between total energy and available energy. This steps into the realm of thermodynamics and the concept of entropy.
Okay, lay it on me.
Think back to the heat analogy. The ocean is full of trillions of gallons of water, and because it has a temperature above absolute zero, all those countless water molecules are constantly jiggling around. It is a massive ocean of heat energy.
But we can't power New York City by just plugging a wire into a warm ocean.
Because the jiggling is entirely random and chaotic. It's impossible to herd all those randomly wiggling atoms into a unified, organized motion that pushes a turbine without taking even more energy from somewhere else to do the herding.
Right.
The total energy is perfectly conserved, but the availability of that energy for human utility is constantly decreasing as organized energy degrades into random heat.
So nature doesn't care about saving useful energy for human machines. The sun just blasts unimaginable amounts of high-quality energy into the empty void of space in all directions. Only a microscopic fraction happens to hit the Earth.
Exactly. So the problem isn't that humanity is running out of energy. The problem is simply that we are remarkably bad at catching it and using it before it turns into chaotic heat.
Yeah.
But if we connect this to the bigger picture, the source material leaves us with a staggering conclusion about what happens if we get better at catching it.
The fusion concept.
Yes. If humanity can master thermonuclear reactions, specifically the fusion of hydrogen isotopes, the amount of available energy we could extract is almost unfathomable.
How much are we talking about?
Well, water is H2O. It is full of hydrogen. The energy locked inside the hydrogen of just 10 quarts of water, if processed efficiently every second, could generate the entire electrical power used in the United States.
Wait, really? 10 quarts? That's just 2.5 gallons.
Mm.
A couple of milk jugs of water per second could power the entire country.
With a small, steady stream of running water, you have enough raw fuel to supply all the energy used in the U.S. today, liberating a tiny fraction of that E equals mc squared mass energy. The energy is there. It's all around us. Physics just has to figure out how to practically unlock it.
What a profound place to land. Let's wrap this journey up. We've gone from Dennis the Menace, hiding his indestructible toy blocks under the rug, to the brilliant logic of reversible machines trading massive distances for heavy weights.
It's been quite a ride.
We've seen how the simple swinging pendulum turns gravity into motion, how slamming your car brakes turns forward motion into a microscopic atomic dance party, and how the deep, unaging time symmetries of the quantum universe ensure that the mathematical ledger of reality never misses a single cent.
We finally understand that energy isn't a thing. It isn't a glowing orb. It is the inescapable accounting system of reality itself.
The next time you climb a steep hill and feel your legs burning, or you watch a grandfather clock tick away the seconds, or you just warm your cold hands on a fresh cup of coffee, remember what's really happening beneath the surface. You are experiencing the universe balancing its ultimate unbreakable ledger. You can now see the hidden math behind the physical world.
And once you truly understand it, you can never unsee it. Every movement is an exchange.
But before we go, I want to leave you with a mind-bending question to chew on. Something that Feynman's text implies but leaves floating in the air.
Oh, like these.
We just learned that the conservation of energy relies entirely on the assumption that the fundamental laws of physics do not change over time. It's a perfect symmetry. But what happens if, billions of years from now, scientists discover that time itself is fundamentally aging or shifting?
Wow.
If the rules of the quantum game do slightly change as the universe gets infinitely older, does the universe's ultimate accounting book suddenly develop a slow leak?
That is exactly the kind of thought that will keep a physicist awake at night.
Keep questioning, keep looking past the surface of the everyday world, and we'll see you on the next deep dive. You usually walk through life assuming reality is built on this, rigid, predictable grid. Kind of like graph paper.
Right, yeah, nice and orderly.
Exactly. You have your clear X, marks the spot for exactly where things are, and a ticking clock for exactly when they happen. Clean, reliable, all that.
It feels reliable, sure.
But what if I told you that the closer you look, the more that graph paper actually warps? Like the lines blur, the ink smears, and you realize we're navigating a landscape of reality that is, honestly, incredibly murky.
It really is. It's the absolute definition of a moving target, to be honest.
Yeah. Today, we're tearing up that map of space and time. We're doing a deep dive into Chapter 5 of a foundational text on physics to explore how scientists actually measure the boundaries of reality.
Yeah.
We're getting into the unimaginably small, the incomprehensibly large, and why perfect measurement is literally impossible.
Which is something that challenges the very foundation of how you perceive your everyday life. I mean, we like our coordinates binary, right? You're either here or you're there.
Right.
But the universe just doesn't actually work that way.
Okay, let's unpack this. Because to really understand how weird physics gets, we have to start with motion. Just like Galileo did, 3.5 centuries ago?
Yeah, roughly 350 years ago.
Because before him, people just sort of philosophized about why things fall. But Galileo, he actually measured it. And if you imagine what he did, he sets up this inclined wooden track, rolls a ball down it, and he wants to know exactly how far it travels in equal intervals of time.
But he didn't have a stopwatch, They didn't exist.
Exactly. So he used his own pulse. I mean, he'd feel a beat, make a mark in the track, feel another beat, make another mark. And the result was this huge revolution. He figured out that distance is proportional to the square of the time. Distance equals time squared.
It's a beautiful, elegant mathematical relationship hidden right there in the physical world, just waiting to be quantified.
Yeah.
And by doing that, he shifted the entire human paradigm from just thinking about nature to actually quantitatively observing it.
But, thinking about Galileo standing there holding his wrist, it immediately raises a massive problem.
Oh, definitely.
Because to measure motion, to get that elegant formula, you need a really reliable way to measure time. But what actually is time? If you really stop and think about it, it's incredibly hard to define.
It's one of the great traps in physics, honestly. If you look it up, a dictionary essentially defines time as a period of time, which is completely circular and useless.
Totally circular.
We don't fundamentally know what time's essence is. So practically speaking, physicists just define it as how long we wait.
How long we wait.
Yeah. And because we can't define its underlying nature, we just measure it using repetition. We look for something that happens over and over again in a regular way.
Right. But since we are relying on repetition, how do we know those repetitions are actually equal? Like, how do I know the time between my heartbeats is exactly the same?
Well, you don't. Your heart rate fluctuates all the time.
Exactly. Or, on a larger scale, how do you know a day in winter is the exact same length as a day in summer?
It's a profound puzzle. You need a standard to compare against, but how do you test the standard itself? Think about how hard it is to standardize time. Imagine a guy standing by an hourglass.
Okay.
His whole job is to turn it over at the exact second the sand runs out, day and night.
I mean, that just sounds like the worst job
Oh,
ever.
absolutely the worst. But if you count the number of these hours from sunrise to the next sunrise, you'll actually find the number varies depending on the season.
Wait, really?
Yeah. Summer days give you a different count than winter days. So you might think the hourglass is broken, or maybe the sun is broken. But if you measure from noon to noon specifically, the exact moment the sun hits its absolute highest point in the sky, the number of hourglass turns is completely consistent.
So you found a regularity in the sand that matches a regularity in the sky.
Exactly.
And that desire for regularity
Yeah.
perfectly highlights this universal problem in physics.
Yeah.
There's this great old anecdote in the source text about a Swiss boy
Yeah.
who wanted all the town clocks to ring noon exactly when his pocket watch did.
Oh, I love that story.
Right. He runs around trying to convince everyone it was a great idea. And it sounds great right up until you ask the obvious question, like, wait, why do we use your clock?
Mm-hmm.
What makes your watch the absolute truth?
And what's fascinating here is that for centuries, our Swiss boy was the Earth itself. We used the Earth's rotation as the ultimate clock. Everyone just synchronized to it.
Because it seems perfectly regular.
It seems regular, but as our scientific instruments became more sensitive, we realized the Earth is actually a flawed clock. It wobbles.
Wow.
Yeah, tides drag on it, earthquakes shift its mass, some days are slightly longer, some are shorter, and overall its rotation is actually slowing down over the centuries.
So when your ultimate standard of measurement is flawed, you just have to throw it out and redefine the standard entirely. And I guess that led us to the atomic clock, right? We need a repetitive event that wasn't affected by friction or weather or wobbling planets.
Exactly. We moved from the macroscopic, messy reality of a spinning rock to the microscopic quantum precision of atoms. We found our new standard in the vibration of atoms, specifically the hydrogen atom.
And these hydrogen vibrations keep time to an accuracy of 1 part in 10 to the 9th power, which is just, I mean, mind-blowing precision.
It really is.
By finding this tiny, ultra-reliable repetition, we didn't just build a better watch. We fundamentally redefined what a second is, based on the universe's most stable metronome.
But of course, once you have that incredibly precise standard, you face a new problem. How do you slice it up? How do you measure tiny fractions of a second?
Right, because, I mean, our grandfathers used mechanical pendulums. A standard grandfather clock ticks, what, 3,600 times an hour to give us seconds? But you could only make a heavy piece of brass swing so fast before air resistance and mechanics just completely cap you out.
Yeah, you hit a hard physical limit. So the leap was moving from mechanical pendulums to electrical ones, which we call oscillators. Think about the smartphone in your pocket right now. It doesn't have a tiny grandfather clock inside it. It relies on a quartz crystal vibrating electrically millions of times a second in a circuit, because electrons can swing vastly faster than brass.
And to visualize this, physicists use an oscilloscope. It's essentially a microscope for short times.
That's a great way to put it.
It plots a graph of an electrical current against time on a screen. So you can plug a slow oscillator into it, map its wave, and then plug a much faster oscillator in and visually count how many of the fast, tiny waves fit inside the slow, big wave.
Exactly. You calibrate them against each other, building this ladder of precision, step by step. Use the second to calibrate the millisecond to calibrate the microsecond, all the way down into the nanosecond.
But wait, I have to push back here. In the text, when discussing advanced particle physics, they talk about measuring times as short as 10 to the negative 24th seconds.
Yeah, they do.
That's the lifespan of these strange, incredibly unstable subatomic resonances. We definitely don't have electronic oscillators that swing that fast. A quartz crystal or an oscilloscope screen cannot resolve a trillionth of a second. So how on earth are we measuring that?
This is where we have to abandon the clock entirely. When time is too short to count with any kind of ticking mechanism, physicists use a brilliant conceptual flip. We actually measure time using distance.
Wait, if we know the speed of light, are we reverse engineering the time? We're using distance to figure out the stopwatch.
Exactly. Think about driving a car on the highway. If you lock your cruise control at exactly 60 miles per hour and your odometer shows you've traveled exactly 60 miles, you don't need to look at your watch to know you've been driving for 1 hour. You just infer the time from the distance and the speed.
Oh, wow. Okay, that makes perfect sense.
Right. In particle accelerators, we create subatomic particles like the pi-zero meson. It's this fleeting spark of a particle that moves at nearly the speed of light, which is a constant we know perfectly.
Right, the speed limit of the universe.
Yeah. And when it flies through a photographic emulsion, it leaves a microscopic track before it disintegrates. We can physically measure that track with a microscope. Say it's 10 to the negative 7 meters long.
Oh.
Because we know exactly how fast it was going and we can measure the physical distance of its track, we calculate exactly how long it lived. In this case, about 10 to the negative 16 seconds.
So we literally use a ruler to measure a stopwatch. We measure the trail it left behind to understand the time it experienced.
Yeah. It requires us to stretch our very definition of what measuring time even means.
Okay, so we've sliced time into these incomprehensibly short slivers. But what happens when we look in the opposite direction?
To deep time.
Yeah. We've seen that to measure the infinitely small, we had to abandon the clock for the ruler. But what about unfathomably long times? Because counting tree rings or layers of river mud only gets us back a few thousand years. How do we measure billions of years?
For that, we need a clock that ticks incredibly slowly. And we found it in radioactivity. Radioactivity isn't a periodic repetition like a swinging pendulum or a vibrating atom. It's a statistical regularity.
Let's explain how that works, because the key concept here is the half-life, right? A radioactive material decreases by the exact same fraction over equal time periods.
Right. Think of it like flicking a trillion coins. You don't know what any individual coin will do. It's impossible to predict.
Right, it's just random.
But statistically, you know exactly half will land on heads and be removed. If it takes a certain number of days for half the material to decay, it will take that exact same number of days for the remaining half to drop to a quarter, and then another identical interval to drop to an eighth.
It's an exponential decay.
Exactly. And it is relentlessly consistent. It doesn't matter if the material is boiling hot, freezing cold under immense pressure, or floating in the vacuum of space. The nucleus just obeys this unbreakable statistical law.
Here's where it gets really interesting. We can use this statistical decay to actually date the past.
Yeah, we can.
Take carbon-14. It has a half-life of roughly 5,000 years. Because we know the natural baseline of carbon-14 in the atmosphere, if we dig up an ancient bone or a piece of wood, we can measure how much carbon-14 is left in it.
And by calculating how many times that amount has halved, we can accurately date organic objects back tens of thousands of years.
It brings human history into sharp focus.
And if we connect this to the bigger picture, we can scale this method up using isotopes with much, much longer half-lives. Uranium, for example, has a half-life of over 4 billion years.
4 billion, that's insane.
And the crucial part is that when uranium decays, it doesn't just disappear, it eventually turns into lead.
So it leaves a receipt.
A permanent geological receipt. If you find a very old rock, you can measure the ratio of uranium to lead locked inside its crystals. Because you know the decay rate, that ratio tells you exactly how long that rock has been solidifying.
That's amazing.
By using this method on the oldest Earth rocks and on meteorites that crash down from space, we've definitively dated the Earth to about 4.5 billion years old. And by extending these principles of cosmic evolution, we estimate our universe itself started roughly 10 to 12 billion years ago.
It's just staggering. From Galileo timing a rolling ball with his pulse to mapping the birth of the universe. But just as we had to invent new clocks for deep time, we had to invent entirely new rulers for deep space.
We really did.
I mean, you obviously can't use a literal meter stick to measure the distance to the moon.
No, definitely not. And just like with time, when we hit the limits of direct physical measurement, we have to change our strategy. For space, the first big conceptual leap is triangulation.
Which is basic, beautiful geometry. Imagine how we measured the height of the first Sputnik satellite back in the 50s. You have two observers standing at different known locations on Earth, both looking up at the satellite at the exact same moment. Because you know the exact distance between the two observers, and you can measure the angle from each observer's telescope up to the satellite, you've essentially drawn a massive, invisible triangle in the sky. If you know the base and the two angles, trigonometry gives you the height.
Which is how they calculated Sputnik was about 500,000 meters up. And that works perfectly for satellites and even for the moon. But it hits a wall when you try to measure the sun.
Right, because the sun is this giant blinding ball of gas. You can't focus your telescope on one precise, sharp point on the sun to get those crisp angles needed for a triangle. So if we can't triangulate the sun, how did astronomers ever figure out the true scale of our solar system?
Oh, they had a brilliant relative map. Astronomers knew the proportions perfectly. They knew Jupiter was a specific multiple of Earth's distance from the sun, Venus was a specific fraction, and so on.
Okay.
But they didn't have the absolute scale in miles or kilometers. They needed one hard, absolute measurement to anchor the whole system.
It's like having a map of a city with all the streets perfectly drawn, but no legend in the corner saying 1 inch equals 1 mile. You know the layout, but you don't know if the city is a mile wide or 100 miles wide.
Precisely. And the way they finally got that legend was using radar. We bounced radar waves off Venus.
Okay, radar.
Because radar is a form of light, and we know the exact speed of light, we simply timed how long it took the signal to travel to Venus, bounce off its surface, and return to Earth.
Wait a minute. We use the speed of light and time to infer distance.
We did!
That is the exact reverse of the particle physics trick. With the Missing particle, we use distance to figure out the time. Here, out in space, we use time to figure out the distance.
It's the beautiful symmetry of physics. You use whatever constant you have to solve for the variable you need.
Okay, but what about reaching the stars? The universe is vastly bigger than our solar system. We certainly can't bounce a radar signal off a star light years away.
No way. The signal would take years to get there and back, and it would be impossibly weak. So we have to go back to triangulation, but we need a much bigger baseline than just 2 telescopes sitting on Earth. We actually use the Earth's entire orbit around the sun.
Oh, this is the thumb trick.
Yeah.
If you hold your thumb out at arm's length and close your left eye, your thumb covers a certain spot on the wall. Then, if you swath and close your right eye, your thumb appears to jump horizontally against the background. Your eyes are the 2 observation points.
That's parallax. We do exactly that, but on a cosmic scale. We look at a relatively nearby star in the summer, record its position against the distant background galaxies. Then we wait 6 months until it's winter, and the Earth has traveled to the complete opposite side of the sun.
And we look again.
Right. We look at the star again. The diameter of the Earth's entire orbit, hundreds of millions of miles, is our new massive baseline. We measure how much the star jumped, and we calculate the distance.
But even that has limits. Right. Eventually, stars are so incredibly far away that the jump is too microscopically small to measure. So physicists had to invent yet another ruler, the color-brightness relationship.
Which is just a masterclass in reading the universe's signals.
Yeah.
Why does a star's color tell us its intrinsic brightness? Think about heating a piece of iron in a forge.
Okay.
First, it glows dull red, then bright yellow, then a searing blue-white. The color is a direct signature of its temperature and its energy output.
Right.
Stars work the exact same way. By looking at the exact color spectrum of a star, astronomers know exactly how much light it is inherently pumping out at its surface.
It's true wattage, basically.
Yes.
And once you know it's true wattage, you just compare that to how dim it appears in our night sky. Since light dims at a very predictable rate the further it travels, comparing the true brightness to the apparent brightness gives you the distance.
And this specific tool is what unlocks the most mind-boggling scales of the cosmos.
And what a scale it is. Using these methods, we mapped globular clusters, these massive, dense spheres of millions of ancient stars, which told us the center of our galaxy is 10 to the 20th meters away.
Huge distances.
Yeah. Then we looked at spiral galaxies beyond our own, using their apparent size to deduce they are 3 times 10 to the 23rd meters away. And finally, giant instruments like the Palomar telescope reveal deep-field galaxies a staggering 10 to the 26th meters away, literally halfway to the absolute limit of the observable universe.
And remember, every single one of those unimaginably large numbers is built on a fragile-looking ladder of inferences. The radar bounds calibrated the orbit calibrated the nearby stars using parallax, the nearby stars calibrated the color brightness scale, which finally allowed us to measure the galaxies.
It's a towering house house of cards made of pure math and observation, and somehow it holds up perfectly.
It really is a marvel.
All right, let's slam it into reverse. We've hit the limit of the macro universe, measuring distances in the billions of light years.
Yeah.
Let's shrink all the way down to the micro universe.
Okay, let's do it.
Subdividing a normal meter stick into millimeters or microns is easy with a good magnifying glass or a standard microscope. But then you hit a hard physical wall, which is the wavelength of visible light itself.
This is a really unintuitive concept for a lot of people. You literally cannot see anything that is smaller than the waves of light you are using to illuminate it.
Right.
Visible light waves are just too clumsy, too large a tool to probe the architecture of atoms. It's like trying to feel the delicate microscopic texture of a vinyl record groove while wearing a thick, padded winter glove. The probe is just bigger than the detail.
So we have to bypass visible light entirely. To see virus molecules, which are around 10 to the negative 8th meters, we use an electron microscope firing beams of electrons instead of light.
Right, much smaller waves.
And for individual atoms, which are even smaller at 10 to the negative 10th meters, we bounce X-rays off crystal lattices because X-rays have a much tighter, shorter wavelength.
Exactly. X-rays can slip into the tiny gaps and resolve those smaller details.
But then we hit another massive conceptual hurdle, the nucleus of an atom. The nucleus is 10 to the negative 15th meters. So what does this all mean? How do you measure something so impossibly small that you can't even bounce X-rays off of it?
This requires one of the most ingenious, indirect experiments in the history of physics. We measure what's called the cross-section. We don't try to take a picture of the nucleus. We try to hit it.
Imagine firing a machine gun randomly into a pitch-dark forest.
Okay, great analogy.
You can't see the individual trees at all.
Yeah.
But you have a detector on the other side of the forest counting how many bullets actually make it through.
Exactly. If you fire 1,000,000 bullets and 10% of them never make it out the other side, you know statistically that the solid trunks of the trees must cover exactly 10% of the total cross-sectional area of that forest.
So physicists do this with matter. They shoot a known number of high-energy particles through a thin block of carbon. You count the particles that go in, count the ones that come out, and the fraction that gets stopped, the bullets that hit the trees, gives you the total area of all the carbon nuclei combined.
Yeah.
From that area, you calculate the radius of a single nucleus. And that incredible shadow measuring trick gives us a brand new unit of measurement for the quantum world. The Fermi, 10 to the negative 15th meters.
We measure the shadow to understand the physical dimensions of the object itself. It's brilliant.
So we've gone from the edges of the universe at 10 to the 26 meters down to the center of an atom at the Fermi scale. But at the very bottom of this rabbit hole, physics drops an absolute philosophical bomb.
It really does.
We spent this whole time talking about how clever human beings are at inventing new rulers and clocks to measure things perfectly. But the foundational laws of quantum mechanics tell us that perfectly precise measurements are literally not allowed by nature.
And this raises an important question. What actually happens when we try to push our measurements to absolute zero error? What happens when we try to know exactly where a particle is and exactly how fast it's moving?
The universe flat out says no. This is Heisenberg's uncertainty principle. It's governed by a tiny number called the reduced Planck constant, often represented by the symbol h bar.
Right.
It means there is a minimum, unavoidable amount of error built into the very fabric of reality. The math shows us a seesaw. The more precisely we measure an object's momentum, its mass times its velocity, the less we can possibly know about its exact physical position.
Push one side of that seesaw down to zero uncertainty, so you know exactly how fast an electron is moving, and the other side shoots up to infinite uncertainty. Its position completely smears out.
Wow.
It's not that our microscopes are bad or our rulers are flawed. It's that the particle itself fundamentally does not possess a definite position and a definite momentum at the same time.
And it applies to time, too. The uncertainty principle has a formula for time and energy. The more precisely we pin down exactly when a subatomic event happened, the less we can possibly know about the energy involved in that event.
Reality, at its base level, is fundamentally fuzzy.
Yeah.
It resists being pinned down to a grid. It is wave-like and probabilistic.
It's just incredible. Think about the journey we've just taken. We started with Galileo standing on a hill using his own heartbeat to time a wooden ball.
Yeah.
Then we used the speed of light to measure a 10 to the negative 24th second subatomic resonance. We scaled up from a simple meter stick, bouncing radar off Venus, mapping parallax shifts, all the way out to 10 to the 26 meters at the edge of the cosmos.
Just mind-blowing scales.
And then we plummeted down into the pitch-black core of the atom, measuring tree shadows at 10 to the negative 15th meters.
And you interact with this legacy every single day. Every time you look at a digital clock, sync to atomic time, or check your location on a smartphone GPS, you are relying on these layered inventions of human ingenuity.
Right, it's all connected.
You're relying on atomic vibrations, the constant speed of light, and the geometry of triangulation. These aren't just abstract textbook concepts. They are the literal tricks of light, speed, and radiation we use to pin down our reality so you can navigate your morning commute.
But knowing everything we've just uncovered, it leaves us with an incredible paradox to chew on. If the very laws of nature dictate that knowing exactly when something happens fundamentally blurs our understanding of what happened, then time and distance aren't just a passive, rigid grid we live in.
No, they're not.
They aren't that clean graph paper we imagined at the beginning. They are interactive, blurry boundaries. It leaves you wondering, when we push our instruments to the absolute limit, are we actually measuring the structure of the universe, or are we just measuring the limits of our own ability to interact with it? Keep questioning the space and time around you. Thanks for joining the deep dive. Grab a quarter, or a dime, a penny, whatever's in your pocket right now.
Yeah, and just flick it into the air.
Right. And as it tumbles over and over, you're looking at what feels like a completely trivial game of chance. Just a 50-50 shot.
Exactly. But what if I told you that simple tumbling coin is, well, it's the exact same mechanism you need to understand the fundamental atomic structure of your own body?
It sounds kind of absurd, right? Connecting a spinning piece of metal to the literal foundations of the universe.
It does, but the mathematical logic governing that coin flip is the exact same logic governing the building blocks of reality.
And that is exactly our focus today for this deep dive.
Yeah.
We have a truly legendary stack of source material in front of us. We're looking at a chapter from Richard Feynman's famous lectures on physics.
Specifically, Volume I, Chapter 6, which is all about probability.
Right, but we don't just have the text. We also have 11 accompanying graphs and diagrams to mentally unpack for you.
And honestly, Feynman is arguably the greatest guide we could ask for here. He had this rare, almost frustratingly brilliant gift for taking incredibly dense, abstract mathematical realities and forcing them to make intuitive sense.
Which is our mission today.
Yeah.
We're going to embark on a full, detailed exploration of probability. No skipping over the hard parts, no taking shortcuts.
None at all.
We're going to explain the core ideas, visualize these complex figures, define the tricky terminology in plain spoken English, and, clear up some major common misunderstandings about how the universe actually operates.
It's going to be a trip.
It is. Okay, let's unpack this. Before we even look at a single equation, how do we actually define what probability is?
Well, to define probability, we have to start by admitting something that's deeply uncomfortable for most people, and especially for scientists. We have to admit what we do not know.
Okay, so it's about ignorance.
Yes. Probability isn't some magical physical force pushing a coin one way or another. It is fundamentally just a mathematical system for making better guesses when we have incomplete information.
Wait, hold on. So if I knew the exact force of my thumb hitting that coin, the precise air currents in the room, the micro-frictions on the coin's surface, I wouldn't need probability at all.
Right.
It's not a mystery, I just lack the data.
You've hit the nail on the head. Feynman gives us a mathematical definition to ground this idea. He says the probability of a specific outcome is just our best estimate of the number of times that outcome will happen, divided by the total number of times we imagine trying it.
I have to push back strongly on that. Our best estimate. That sounds entirely subjective.
It does sound that way.
It makes it sound like probability isn't a hard science at all, but just this, dressed up feeling based on our own personal ignorance.
But it is based on our ignorance. Let me give you a really simple scenario. Suppose I flip a coin, catch it, and immediately cover it with my hand against the table. What are the odds it's heads?
50-50.
Right. Now suppose I peek under my hand, I see it's heads, I ask you again, what are the odds?
Well, for me, it's still 50-50.
Exactly. But for me, the probability is now 100%. The physical coin didn't change at all. The universe didn't shift. The only thing that changed was my knowledge.
Wow. Okay.
The probability inherently depends on the ignorance of the observer.
That is a wild way to look at it. But Feynman actually gives a brilliant physical example of this in the text, regarding how physicists measure the cross-section of an atomic nucleus.
Right, the dartboard analogy.
Yeah, because a nucleus is way too small to see, physicists can't just aim at it. They have to shoot particles blind into a thin slab of material. It's exactly like throwing darts blindfolded at a huge wall covered in tiny targets.
Which is pure guesswork.
Exactly. Because you are totally blind, because of your ignorance, the chance of hitting a target is strictly a ratio. It's the total area of all those tiny targets divided by the total area of the whole wall. If you took off the blindfold and could suddenly aim, the probability wouldn't be a ratio anymore.
Right. What's fascinating here is how this subjective guessing holds up when we run actual experiments. Because abstract guessing is one thing, but physical reality has a funny way of complicating the math.
Absolutely. So let's look at the first couple of figures in our notes. Figure 6.1 and Table 6.1. Feynman details an actual real-world game where you toss a coin 30 times.
Okay.
Now, based on the math we just discussed, the most likely expected score is a perfectly even split, right? 15 heads, 15 tails.
Naturally, since the ratio is 1-to-1.
But look at the actual experimental results. In the first 3 games of 30 tosses, the results were 11 heads, then 11 heads again, and then 16 heads.
Not a single 15.
Exactly. Out of 3 full games, nobody hit the quote-unquote most likely number of 15 even once. And in the larger data set of 3,000 total tosses, they still didn't get exactly half.
And this highlights a massive, pervasive misunderstanding about probability. When physicists or mathematicians say an outcome is the most likely, they do not mean it will happen. They just mean it will happen slightly more often than the alternative, like more often than 14 or 16. The deviations from that perfect mathematical center, those are called fluctuations. And fluctuations are the rule, not the exception.
Okay, but what if I'm not flipping a coin thousands of times? Say I only flip it 3 times.
Yeah.
How do I figure out the exact mathematical chance of getting, say, exactly 2 heads? Do I just literally count up the different ways it could happen?
In essence, yes. And figures 6.3 and 6.4 visualize this beautifully as these branching paths. Imagine drawing a tree.
Okay, I'm picturing it.
You start at the trunk, toss the coin, and the path splits into 2 branches, heads or tails. You toss it a second time, and each of those 2 branches splits into 2 more.
So for 3 tosses, I have 8 total branch endings at the top of my tree.
Correct. Now, look at those 8 destinations. Only one path gets you 3 heads, 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 heads. But how many paths get you exactly 2 heads?
Let me think. You could throw heads, heads, tails? Or heads, tails, heads? Or
Yeah,
tails,
good.
heads, heads? So there are 3 unique paths to arrive at that exact same final score.
Exactly. And as you map this out for more and more tosses, the number of ways to reach these different scores starts to form a very specific geometric pattern.
Oh, Pascal's triangle.
Yes, the pattern is known as Pascal's triangle. The numbers inside this triangle are what mathematicians call binomial coefficients. It's really just a shorthand way to calculate exactly how many unique paths lead to a specific score.
Right.
Which leads us directly to the Bernoulli equation, sometimes called the binomial probability formula.
Okay, I am looking at this equation in the text right now, and it is honestly a terrifying jumble of algebraic letters. I'm seeing P, K, N, little p, little q. Can we translate the actual mechanism of this equation? Like, why does it work?
Sure, let's strip away the algebra. Think of it conceptually. You want to know the exact chance of getting a specific final score. First, you take your chance of winning a single toss and you multiply it by itself for every win. Then, you take your chance of losing and multiply that by itself for every loss.
Wait, why are we multiplying them, though?
Because the events are independent. If you have a 50% chance of winning the first toss and a 50% chance of winning the second, the chance of winning both is half of a half.
25%.
Right. You multiply them to find the shrinking likelihood of that specific sequence, but finally, you multiply that entire result by the number of possible paths, those branches on our tree, that could have actually gotten you to that final score.
Okay, it really is. It looks like a jagged city skyline superimposed over a perfectly smooth hill. 15 happened a lot, sure, but 16 and 17 actually happened even more than 13. Reality is just bumpy and chaotic.
It is, but there is an underlying structure to that chaos, which brings us to a crucial pivot in this deep dive. Flipping coins on a table is one-dimensional. What happens if we apply this exact same mathematical logic to something moving through three-dimensional space?
Oh, this is figure 6 and 5, the random walk. I love this concept.
Me too.
I want you to imagine you are standing in the middle of a massive, perfectly structured city grid. New York, Chicago, somewhere like that. You stand at an intersection, pull out a quarter, and flip it. If it's heads, you walk exactly 1 block north. If it's tails, you walk exactly 1 block south. You do this at every single intersection.
Okay, so a totally random journey.
Right. Where do you end up after taking n steps?
Well, your initial intuition might be to say, well, I have an equal chance of going forward or backward. They cancel out. So my expected progress is just 0. And strictly speaking, your average expected distance from the origin point is indeed 0.
But hold on. If I take 10,000 steps flipping a coin, I am absolutely not standing on the exact same street corner I started on. I've wandered off somewhere.
You have. Think of it like walking a dog on a very long, highly elastic leash in an open park.
Okay.
The dog darts forward, backward, left, right. On average, the center of all the dog's movements is just you, holding the leash. But the area the dog explores expands the longer you stand there.
That's a great way to picture it.
In physics, because distance can be a negative or positive number depending on which way you walked, we measure this wandering progress by squaring the distance. That turns everything positive.
And the text gives us a stunningly elegant formula for this. Your mean square distance, your typical wandering boundary squared, is exactly equal to the total number of steps you took.
Let's make that practical. If you take 100 steps, your mean square distance is 100. To get back to a regular readable distance, we just take the square root.
Right.
The square root of 100 steps is 10. So after wandering randomly for 100 blocks, your typical expected distance from where you started is 10 blocks away. If you take 10,000 steps, you'll likely be 100 blocks away.
It's crazy that the pure chaos of a coin flip perfectly dictates the boundary of your wandering.
And if we connect this to the bigger picture, this exact math is how scientists and casinos spot a cheat.
Oh, that makes sense. Because if I suspect you're using a weighted coin, I can't call you a cheater just because you flipped 60 heads out of 100.
Yeah.
We just established that fluctuations are totally normal.
Exactly. But the random walk gives us a mathematical boundary for our suspicion. Figure 6.6 maps this out. The expected fraction of heads should be exactly half, 0.5. The deviation, the fuzziness we expect around that perfect half shrinks as you do more tosses. Specifically, it's bounded by a formula involving the square root of your total tosses. If you flip a coin thousands of times and the fraction of heads strays way outside that specific mathematically predicted boundary, well, the math tells you someone is lying.
A literal formula for healthy skepticism. I love it. But let's push this even further. The random walk assumes you are taking perfect, uniform city blocks every single time. Real life isn't a grid. Think about the movement of the oxygen and nitrogen molecules in the air around you right now.
Right. This is the diffusion of gas. When we look at gas molecules bouncing around a room, we are still dealing with a random walk, but the step size is very unpredictably.
Because they're hitting each other.
Exactly. They bump into each other after a millimeter or maybe after a micrometer.
Yeah.
Because of this continuous variation, we lose an entire layer of certainty. You can no longer ask, what is the probability that a molecule ends up at this exact microscopic point in the room?
Wait, why not?
Because a geometric point is infinitely small. The chance of billions of random different-sized steps perfectly canceling out to land on a pinpoint of literally zero width is mathematically zero.
So how do we locate anything at all?
We have to shift from talking about exact probabilities to talking about probability density. Instead of looking for an exact point, we look for the density of chance within a certain area.
Okay, to visualize this, look at figures 6.7 and 6.8. Imagine a graph where the horizontal line is distance and the vertical line is probability density. We've lost those jagged vertical bars from the coin tosses.
Right, no more jagged edges.
We now have a completely smooth, continuous curve. If you want to know the chance of a molecule landing between point A and point B, you physically calculate the shaded area under the curve between those 2 points.
And that smooth curve takes a very famous shape. It's the normal, or Gaussian distribution. You probably know it as the classic bell curve. Figure 6.7 shows us something incredible about it. It shows what happens to that bell curve as time passes, and the molecules take more and more steps. As the steps increase from 10,000 to 40,000 to 160,000, the bell curve flattens out and gets much, much wider.
Because the gas is physically diffusing across the room, the molecule could be way further away.
Exactly. The width of the curve grows. But here is the critical rule. The total area under that curve, if you shade the whole thing in, must always equal 1.
Oh, because there is a 100% chance the molecule is somewhere in the room.
Spot on. So as the base gets wider, the peak has to get shorter to compensate.
Here's where it gets really interesting. It's not just where the molecules are located. It's how fast they are moving. Feynman brings in Maxwell's distribution of gas velocities in Figure 6.9.
And this completely fractures how we intuitively view physical reality. When you feel the wind on your face, you are feeling the pressure of billions of molecules impacting you. But scientifically, we cannot speak of the speed of the wind.
Like there is no single speedometer reading for those molecules.
Right. They're constantly colliding and changing speeds. We can only talk about the expected number of molecules within a certain range of speeds. Figure 629 graphs this, and it looks kind of like a lopsided hill.
Okay.
The area under a specific slice of that hill tells us how many molecules we expect to find going that particular speed. It's all probability.
Okay, let's take a breath and look at the path we've taken so far. We've gone from flipping single coins to predicting walks on a grid to managing giant swarms of gas molecules.
That's a big jump.
Yeah, and in all those cases, we used probability to handle our own ignorance. We just couldn't track all the tiny details. But what happens if we zoom all the way in? What if we isolate just one single particle, like an electron? Surely, if we only have one object to track, we can drop the probability and just measure it exactly right.
It is the most logical assumption in the world, but it's wrong. In quantum mechanics, nature actually forces us to use probability. It's no longer a matter of convenience or, missing data. It's a fundamental physical law. To describe a single particle, we have to use two probability density curves simultaneously. One curve maps out the probability of its location, and the other curve maps out the probability of its speed. We see this dual curve setup in Figure 610.
And this raises an important question. Why not just measure both perfectly? Why do we need curves at all for one tiny particle?
This is the climax of this entire deep dive. It's the Heisenberg uncertainty principle.
I have to admit, the math in the text for this looks pretty intimidating.
It does. Let's translate the logic of it instead of reading the syntax. The math dictates that the fuzziness of the particle's position multiplied by the fuzziness of its speed can never equal 0. Never. It must always be larger than a specific tiny fundamental number in nature, which involves Planck's constant and the mass of the object.
Meaning, if I build an incredible microscope and try to perfectly pin down the exact location of that electron, I am forcing the fuzziness of its position to become incredibly small.
Yes. And because the product of the two fuzziness values cannot drop below that fundamental limit, nature forces a compromise. If the location fuzziness gets tiny, the speed fuzziness must explode to compensate.
Oh, wow.
If you know exactly where the particle is, you mathematically have absolutely no idea how fast it's moving, and vice versa. If you measure its exact speed, its physical location basically smears out across space.
It's like imagine two sliders on an audio mixing board that are mechanically linked together. You push the precision of the location slider up, the precision of the speed slider is physically forced down. You can never have both at maximum.
It's a perfect analogy.
That is deeply frustrating. I mean, even Albert Einstein hated this concept. He looked at this quantum reality where you literally cannot know the exact state of the universe and famously declared, God does not throw dice. He just refused to accept that the universe at its core was built on inherent fuzziness.
He really did. He spent years trying to find a mathematical loophole, but the uncertainty principle holds. And it actually explains why that fundamental limit involves the mass of the object.
How so?
For a baseball, the mass is so large that the required fuzziness is completely undetectable to us. But for an electron, whose mass is infinitesimally small, the fuzziness is massive relative to its size. It completely changes how we visualize the building blocks of our world.
Right, because we all grew up with that standard textbook picture of an atom. A cluster of protons in the middle, and little electrons orbiting around it in perfect, neat little rings, kind of like a miniature solar system.
But the uncertainty principle destroys that solar system model, because the uncertainty in the position of an electron is actually as large as the atom itself.
Wait, really?
Yeah. If an electron had a perfect, trackable orbit, we would know exactly where it is and how fast it's going. Nature absolutely forbids that.
So if there are no neat little rings, how are we supposed to picture it?
Look at our final diagram, Figure 611. We have to picture a probability cloud. It looks like a fuzzy spherical smudge surrounding the nucleus. Some areas are dense and white, others are faint and gray. The density of the whiteness in that cloud doesn't represent a physical object smeared out like jam. It represents the exact mathematical chance of finding the electron at that precise spot if you were to look for it. The electron is somewhere in there, but until you interact with it, nature only permits you to know the odds.
We started this deep dive talking about a tumbling quarter, just trying to figure out how to guess heads or tails. And by rigorously following that exact same math, the calculus of probabilities, the branching paths, the expanding curves, we've ended up discovering that the very atoms making up the headphones you're wearing right now are built on a foundation of pure probability.
It's wild to think about.
The solid world you are touching is, at its core, literally a cloud of mathematical chances.
And it leads to a pretty profound philosophical realization, one that Feynman emphasizes right in the text. Modern physics has proven that absolute certainty is a physical impossibility. Much of our knowledge must always remain uncertain, not because we aren't smart enough, but because the universe simply demands it.
Which leaves us with a thought for you to carry into the rest of your day. We spend so much of our lives agonizing, right? Trying to gather enough data to make the perfect 100% certain decision. But what does it mean for you to navigate your life, to make choices, and to seek truth in a universe where the deepest laws of nature are written not in rigid certainties, but in the fluid language of probability? Maybe it's time we all get a little more comfortable with the flip of the coin. I want you to think about something for just a second. Think about the most fundamental, everyday force that you experience. You drop a pen, and it hits the floor.
Yeah, or you try to jump and you're just immediately pulled back down.
Right, exactly. We're talking about gravity. It is basically the invisible scaffolding holding your entire reality together.
Yeah.
But here is the secret that physicists really don't like to advertise. Under the hood, we don't actually know how it works.
No, we don't. I mean, we know what it does with terrifying precision, sure, but the actual physical machinery, completely invisible.
It's just a blank space. And filling in the edges of that blank space is exactly our mission today. We're doing a deep dive into Chapter 7 of the legendary Feynman lectures on physics. We've got the original diagrams, the thought experiments, the whole thing.
And, we aren't here to just recite formulas. This is really an intellectual detective story.
Yeah, we want to understand the actual mechanics of how humanity figured out the rules of the cosmos. From invisible angels all the way to bending space-time. And along the way, we're going to unlearn a lot of what we think we know about things like tides and orbits.
Because if you look at the progression of this idea, it changes everything. You can literally trace a direct line from humans looking up at the sky in total philosophical confusion to predicting the existence of invisible planets using, nothing but a pencil and paper.
So, okay, we have to start before the scientific revolution, right?
Right.
Back in the 16th century, people aren't really measuring things. They're debating.
Right. It was all pure philosophy.
Exactly. Trying to figure out how the heavens move based on vibes, basically.
Yeah.
And into this walks Tycho Brahe.
Brahe is such a massive turning point. He basically realized that sitting around arguing about the perfection of the heavens was useless without hard evidence.
You need the receipts.
Yeah, if we wanted to know how planets moved, we needed data. And keep in mind, he didn't even have a telescope. Brahe built these massive, meticulously calibrated brass instruments, quadrants and astrolabes.
Oh, wow. So just doing it all by eye?
Purely by eye. He spent decades mapping the exact positions of the planets night after night. He effectively forced astronomy to pivot from philosophy to rigorous, data-driven science.
Right, and then he passes away, and his assistant, the mathematician Johannes Kepler, is just left with this absolute mountain of data.
Specifically about Mars, yeah.
Yeah, and Kepler spends years crunching the numbers to find the pattern, and the text provides these brilliant diagrams to show what he found. Figure 1 illustrates Kepler's first law, which is that the planets don't move in perfect circles.
Which was a huge philosophical shock at the time.
Right, because circles are divine or whatever. But no, they move in ellipses. If you picture a flattened circle, the sun isn't exactly in the center, it's sitting off to the side at one of the focal points.
And then figure 2 shows his second law, the law of areas, which is just mathematically beautiful. It describes the variable speed of a planet.
Variable speed, so they don't move at a constant pace.
Nope. As a planet gets closer to the sun in its elliptical orbit, it accelerates. And as it swings further away, it decelerates. Kepler found that if you draw an imaginary line from the sun to the planet, that line sweeps across the exact same amount of area in a given amount of time, no matter where the planet is in its orbit.
Okay, I have to pause you there, because Kepler's describing the what flawlessly. But he still didn't have the why.
No, not at all.
And this leads to, honestly, one of my favorite absurd historical theories. At the time, they saw these planets moving forward through the sky, and because they didn't really understand momentum, they assumed something had to be constantly pushing them.
Yeah, the leading theory was that there were invisible angels behind the planets.
Right. Just constantly beating their wings to push them along their path.
Well, without a concept of inertia, that actually made intuitive sense to them. I mean, if you are pushing a cart and you stop pushing, the cart stops. So why wouldn't a planet stop?
That's fair. So what changed?
The missing piece comes from Galileo. Galileo discovers the principle of inertia. Basically that an object in motion will just keep coasting in a straight line forever unless a specific force acts upon it to change its direction.
Right, so we don't need planetary engines. We don't need angels beating their wings. The planets are just coasting.
Precisely. Through the vacuum of space, they would coast in a straight line for eternity. So when we apply Galileo's inertia to Kepler's ellipses, the logic totally shifts. The angels don't need to push the planet forward.
Oh, because it's already moving forward.
Exactly. If there is a force acting on the planet, it must be pulling sideways. It's constantly tugging it toward the sun, bending what would be a straight line into an elliptical loop.
Which sets the stage perfectly for Isaac Newton. Because if planets are constantly being yanked sideways toward the sun, what are the visible strings doing the pulling?
And this is where Newton drops just the ultimate intellectual bombshell. He realizes that the force making an apple fall to the dirt is the exact same invisible string holding the moon in the sky.
It's the same force. But I want to spend a second on the math here, because Newton doesn't just say they are the same and call it a day. He formulates the inverse square law of gravitation. What does that actually mean functionally?
So the inverse square law is a way of describing how the strength of gravity fades over a distance. Newton reasoned that the force of gravity is directly proportional to the mass of the objects. Bigger objects have a stronger pull.
Makes sense.
But it is inversely proportional to the square of the distance between them.
Okay, let me make sure I'm visualizing this correctly. It's kind of like spreading butter over toast. If you have a certain amount of gravity and you move twice as far away, that gravity isn't just half as strong.
Right.
It has to stretch over an area that is 2 squared or 4 times as large. So at twice the distance, gravity is only 1/4 as strong. At 3 times the distance, it's 1/9 as strong.
That's a perfect analogy. The force dilutes rapidly as it spreads outward through three-dimensional space. And using this exact geometry, Newton calculated that the moon falls away from a straight line path by roughly 1/20th of an inch every single second.
Which brings us to, honestly, the biggest conceptual hurdle in the text. You just said the moon falls.
Yep, it's falling.
The text explicitly says things in orbit are falling. I know you listening to this probably have the exact same immediate reaction I did. If the moon is falling, why the hell doesn't it hit the ground?
Because of its sideways velocity. Our sources actually use figures 3 and 4 to illustrate this with a cannonball.
Okay, walk me through the cannonball.
Imagine standing on a tall mountain and firing a cannon perfectly horizontally. Gravity begins pulling the cannonball down the instant it leaves the barrel, right? So it eventually hits the dirt.
Right.
But if you fire it with more force, it travels further horizontally before it hits the dirt.
Sure, but the Earth isn't flat. Because of the Earth's geometry, the ground is actually curving away at a rate of roughly 16 feet for every 5 miles of horizontal distance.
Exactly. So Newton realizes that if you can fire that cannonball fast enough, specifically about 5 miles per second, something magical happens. In the 1 second it takes gravity to pull the cannonball down 16 feet, the cannonball has traveled 5 miles horizontally.
And over that 5 miles, the spherical Earth has curved downward by exactly 16 feet.
So it falls 16 feet, but the ground drops 16 feet out from under it.
It's perpetually falling, but it's moving sideways so fast that the Earth just keeps curving out of its way. This just completely blew my mind. Because it means when astronauts are up on the space station, they aren't floating in some zero-gravity vacuum.
Not at all. Gravity up there is almost as strong as it is on the surface.
Right. They're plummeting toward the Earth, but the station is rocketing sideways at like 17,000 miles an hour, so they just keep missing the planet.
It completely reframes how you look at the night sky. And once Newton established this inverse square law for the moon, it became this master key that unlocked deeply confusing phenomena across the whole solar system.
Okay, well, if gravity reaches out and grabs the moon must be pulling back. So let's talk about how this affects the Earth, specifically the tides.
Oh, the tides.
Xiphias, figure 5 in the text completely upended my mental model of this. I always pictured the moon hovering over the ocean, pulling the water up toward it to create high tide.
Which is what everyone pictures.
Right. But the diagram clearly shows two tidal bulges on completely opposite sides of the Earth.
I'm struggling with this. How does the moon pulling from one side create a mountain of water on the far side of the planet?
This is a phenomenal point, and it's a super common misunderstanding. The key is that the moon doesn't actually orbit the static center of the Earth.
Wait, what?
Yeah, because the moon is so massive, the Earth and the moon actually orbit around a shared center of mass.
Yeah.
A Berry center. Hold on. You're telling me the Earth and the moon are basically like two ice skaters holding hands, spinning each other around.
Exactly like that.
And that centrifugal fling on the backside creates the second tide. But wait, if the Earth is getting whipped around a pivot point, why don't my coffee cups slide off the table?
Because it's a very slow, massive pivot, taking 28 days to complete one cycle. And that pivot point, that Berry center, is actually located about 1,000 miles beneath your feet, deep inside the Earth's mantle.
Okay, so the whole planet is doing this slow wobble.
Right. So as the Earth and moon swing around this point, there's a centrifugal effect on the Earth.
I see. So on the side of the Earth facing the moon's gravity is the dominant force, aggressively pulling the ocean water up.
Correct. But on the far side of the Earth, the moon is an extra 8,000 miles away. Its gravitational grip is much weaker over there.
Ah. And on that far side, the outward centrifugal fling from the Earth swinging around the Berry center overpowers the weakened pull of the moon.
Exactly. So the water on the far side bulges outward into space. As the Earth rotates on its axis once a day, land masses basically pass through both of those stationary bulges, giving us two high tides every 24 hours.
It's just staggering. You feed this one simple mathematical relationship into the machine, and suddenly the oceans make sense.
It really is.
But the law doesn't stop at our oceans. The Feynman text details how Newton's math essentially acted as a cosmic detective. It started exposing secrets we didn't even know we were looking for.
A prime example is the discovery involving the speed of light.
Wait, gravity helped find the speed of light?
Yeah. So in 1676, an astronomer named Roemer was closely observing the moons of Jupiter. He had calculated their orbit schedules using the law of gravitation, but the moons appeared to be drifting off schedule.
Weird.
Right? When Earth was on the side of its orbit closest to Jupiter, the moons seemed to run ahead of schedule. When Earth was further away, they ran behind.
But if the law of gravitation is absolute, a moon doesn't just speed up and slow down randomly.
Exactly. So Roemer realized the gravity math wasn't wrong. What was changing was the distance the light had to travel to reach his telescope.
Oh, wow.
It was the first definitive proof that light isn't instantaneous. It takes time to travel. The gravitational law was so rock solid that any deviation forced scientists to look for new physical realities.
And I think the ultimate flex of this math as a detective tool is the discovery of Neptune. The astronomers are tracking Uranus, and it's basically acting drunk.
It's wobbling.
Yeah, it is not following the perfect smooth ellipse that Kepler and Newton dictate it must follow.
And again, rather than assume the law of gravitation was flawed, two mathematicians, Adams and Leverrier, ran the calculations backward.
I love this part.
They asked, what if the law is perfectly intact, but there is an invisible, massive object out in the dark pulling on Uranus, perturbing its orbit?
And they didn't even use a telescope. They used algebra. They reverse engineered the wobble to calculate the exact mass and trajectory of a ghost planet.
Yeah, they literally mailed a letter to an observatory saying, point your telescope at this exact coordinate tonight, and boom, Neptune is sitting right there.
It perfectly validates the predictive power of a true physical law. You are extracting far more from the equation than you initially put in.
Absolutely.
But, all of this success is incredibly local. It's happening right here in our solar system neighborhood. A skeptic would say, sure, it works around our sun, but what about the deep universe?
Well, the text pushes us right into that question, and the visual evidence provided is conclusive. Figures 6 and 7 show double star systems, two massive, blazing suns light years away swinging around each other.
And when you map their orbits,
they trace the exact same perfect ellipses as the moon falling around the Earth.
It's the same invisible string. We see it in globular star clusters in Figure 8, binding tens of thousands of stars together. We see it dictating the spiral arms of entire galaxies in Figure 9.
Even in Figures 11 and 12, we see gravitation acting as the ultimate architect of the cosmos, pulling massive, disparate clouds of interstellar dust together, squeezing them tighter and tighter over millions of years until the pressure ignites nuclear fusion.
Birthing brand new stars. It operates at an unimaginable scale. But to me, the most impressive feat in the history of gravity isn't mapping a galaxy.
What is it?
It's measuring it down to the decimal point on a human scale. This brings us to Henry Cavendish and his torsion fiber experiment, which is illustrated in Figure 13.
Yep.
Okay, this is where I need you to walk me through the mechanics. The claim is that Cavendish essentially weighed the Earth using some lead balls in an 18th century room.
Yep, that's exactly what he did.
I understand he didn't literally put the planet on a giant scale, but how do you go from a twisting wire to knowing the mass of an entire planet?
It all comes down to isolating the variables in Newton's equation. Remember, gravity depends on the masses of the two objects and the distance between them, multiplied by a universal gravitational constant. We call it big G.
Right, but before Cavendish, nobody knew what that exact constant G was. They knew it was a ratio, but they didn't have the actual number.
Exactly. So Cavendish sets up a highly sensitive torsion balance. He suspends a rod with two small lead balls from a very fine fiber. Then he brings two massive lead balls near them, and he completely isolates the experiment from air currents and vibrations.
Okay.
Slowly, the gravitational attraction between the massive lead balls and the small lead balls causes the fiber to twist.
So he isn't waiting for planets to orbit. He is watching gravity happen sideways in a lab.
Yes, and by measuring that incredibly minuscule twist, he finally calculates the exact value of the gravitational constant, G.
Why?
Now, here's where the algebra unlocks the planet. Think about an apple falling to the Earth. We know exactly how fast it accelerates. We know the exact radius of the Earth, which is the distance from the apple to the Earth's center.
Okay, let me track the math. We know the force, we know the distance, and thanks to Cavendish, we now know the big G constant.
Which leaves only one missing variable in the entire equation.
The mass of the Earth.
Exactly. Because he found G, Cavendish could just run the algebra backward and solve for the Earth's mass. He weighed a planet of rock and iron using a twisting wire and some lead weights.
It's just brilliant experimental design.
Yeah.
It is humanity at its absolute smartest.
It really is.
We can weigh the Earth, we can predict hidden planets, we watch galaxies spin. But after centuries of victory laps, we have to confront what Feynman calls the most embarrassing question in physics.
Oh, right. The mechanism.
Yeah, we have to go back to the hook we started with. We have the math,
Yeah.
but we still have absolutely no mechanism for how gravity actually reaches across empty space.
It is deeply frustrating for physicists. I mean, there are no gears, no pulleys, no invisible fluid pushing the planets. It is purely an abstract mathematical law.
Right.
And it's not for a lack of trying to find the physical machinery. The text mentions a very clever, purely mechanical theory from 1750, the particle absorption theory.
Oh, right, and the logic here is totally fascinating. The idea was that the vacuum of space isn't actually empty. It's filled with a blizzard of invisible, fast-moving particles zooming in every possible direction.
underneath her.
Exactly. And when you have two massive objects like the Earth and the Sun, they essentially cast a shadow on each other. The Sun blocks some of the particles coming from its direction, so the Earth gets hit by fewer particles on its sunward side.
And bombarded by more particles on its outer side.
Right, which would theoretically result in a net inward push, driving the Earth toward the Sun.
It sounds like a perfectly viable physical mechanism.
It really does. But the Feynman text rips it apart. And here's where I want to introduce an analogy that really crystallizes why this fails. The text talks about running in the rain, but I think a better way to picture the particle field is to imagine trying to sprint through a waist-deep ball pit in a play area.
A high-density environment.
Exactly. If the Earth is moving through this dense field of invisible gravity particles, it isn't just getting pushed from the outside. Because it's moving forward in its orbit, it's plowing into the particles in front of it.
Oh, I see.
Just like your legs face immense drag pushing through a ball pit, the Earth would experience resistance on its leading edge. Over billions of years, that drag would bleed off the Earth's orbital momentum, and we would have spiraled into the Sun long ago.
Yeah, the mechanics simply don't allow for a stable orbit. So the particle theory is dead, and that leaves us with this glaring void. We have no mechanical explanation.
Nothing.
And to make it even more confounding, gravity is absurdly, almost inexplicably weak compared to the other fundamental forces.
The sources illustrate this beautifully with Figure 14. Let's look at the atomic scale for a second. If you take two electrons, they have an electrical charge, so they repel each other. But they also have mass, so they gravitationally attract each other.
Right. And when you compare those two forces, the numbers are just incomprehensible.
The ratio between the electrical repulsion and the gravitational attraction is 1 to 4.17 times 10 to the 42nd power.
Which is a 4 followed by 42 zeros.
Yeah, gravity is so astronomically weak that at the atomic level it essentially doesn't exist.
Which naturally led researchers to a radical hypothesis. If gravity is this uniquely weak, has it always been this way? Does the gravitational constant, our big G, actually degrade as the universe ages?
I love that they actually tested this, but the sources shut it down hard. Because if gravity was even 10% stronger a billion years ago, it means the sun's internal pressure would have been intensely higher.
Right.
The sun would have burned so hot and bright that the Earth's oceans would have boiled away entirely. Life could never have taken root. So gravity appears to be rigidly constant.
And it has another eerie property, which was rigorously verified by the Utfas and Dick experiments. They tested the relationship between mass, which is an object's inertia, its resistance to being accelerated, and weight, which is how aggressively gravity pulls on it.
And they found they are exactly proportional to an accuracy of 1 part in a billion.
Correct. This is why a massive, heavy piece of scientific equipment and a tiny piece of chalk will float side by side next to an astronaut in orbit. Gravity scales its pull perfectly to match the inertia of the object.
It's a flawless ratio. It feels almost too perfect to be an accident.
It really does.
Now, of course, we cannot finish a deep dive into gravity without talking about the one scientist who finally had to step in and correct Newton's math, Albert Einstein. Because Newton's equations had a massive philosophical flaw. He assumed gravity was an instantaneous connection.
Yeah, Newton believed that if the sun were to magically vanish, the Earth would instantly fly off in a straight line into deep space at that exact second.
But Einstein comes along and proves that nothing, absolutely nothing in the universe can travel faster than the speed of light.
Therefore, the gravitational signal holding the Earth in place cannot move faster than light. If the sun disappeared, the Earth wouldn't know about it for 8 minutes. We would continue orbiting in empty space until that final gravitational wave reached us.
That is so spooky.
Furthermore, Einstein's theory of relativity showed that energy itself has mass.
Which means gravity doesn't just pull on tangible things like rocks and moons. It actually bends the path of light itself as it passes by a massive object.
Exactly. The object is warping the literal fabric of space-time around it. We went from ancient philosophers arguing about perfect circles, to invisible angels, to Newton's falling moon, all the way to Einstein realizing that massive objects dictate the geometry of the universe.
We map the entire cosmos using an elegantly simple, universally applicable math equation. And yet, despite the genius of Brahe, Kepler, Newton, and Einstein, the actual gears and pulleys operating beneath the math remain completely invisible. We are tethered to the Earth by a force we fundamentally cannot hold in our hands.
It's true.
Which brings us right back to where we started. That dropping pen, that everyday force holding you down in your chair. The Feynman text points out that gravitation is the one fundamental force that hasn't been unified with quantum mechanics.
Yeah.
Why? Because at the microscopic scale, as we saw with those electrons, gravity is just too incredibly weak to study easily. But I want you to think about this as we wrap up. What if the physical machinery of gravity that we've been desperately trying to find for 400 years isn't hiding in the majestic sweeping dance of the galaxies?
What if it's somewhere else?
Exactly. What if it's buried deep down in the microscopic quantum foam, at the absolute jagged edge of reality, where our current laws of physics completely break down? The biggest, most universe-shaping force we know might just be the ultimate quantum mystery. Something to think about the next time you drop your pen. Imagine a car, right? Like, it's speeding down the highway, but it's completely frozen in a photograph.
Yeah, just a single frozen slice of time.
Exactly. And in that exact fraction of a millisecond, the car isn't actually moving. I mean, time has stopped. It's essentially a statue. So how can we look at that frozen instant and, mathematically prove the car is traveling exactly 60 miles an hour?
It sounds totally impossible, like a riddle.
Right. Measuring motion when the clock has stopped sounds like a Zen riddle, but answering it literally forced humanity to invent an entirely new branch of mathematics.
It really is one of those concepts that feels deeply intuitive until you actually try to pin it down. I mean, we experience motion fluidly, right, as a continuous stream,
Right.
but capturing it, defining it precisely at one exact microscopic moment that requires a total shift in how we perceive reality.
And that shift is exactly what we are unpacking today. Welcome to the deep dive. Our source material today is an absolute giant. We're looking at Chapter 8 of the iconic Feynman Lectures on Physics, which is simply titled Motion.
It's a classic for a reason.
It really is. And our mission here is to extract the brilliance of how physicists actually describe motion. We want to translate these abstract formulas into intuitive, aha moments for you, because by the end of this discussion, you're going to understand exactly why tracking a speeding car or a falling ball leads directly to the core mechanisms of calculus.
And, Richard Feynman was uniquely brilliant at exactly this. He had a way of taking these intimidating mathematical structures and really grounding them. Because calculus is, well, it's often taught as a dry set of rules to
Oh,
memorize.
absolutely, just rate memorization.
Right. But here, it's presented as this desperately needed language that we had to invent to solve practical, undeniable problems of motion.
So let's start with the most basic problem, which is just watching an object move. Before we can calculate motion, we have to agree on how to observe it in the first place. And Feynman points out that to study motion, physicists actually have to aggressively simplify reality.
They absolutely have to. Because think about trying to track that speeding car. If you want absolute pure reality, you'd have to track every single molecule of the rubber on the tires, the glass in the windshield, the driver's hands.
That's just way too much data.
Exactly. It's an insurmountable amount of data.
Yeah.
The problem becomes unsolvable. So physicists use a conceptual trick. They basically strip away all the complexity and treat the entire car as a single theoretical point.
Which honestly feels a little bit like cheating. I mean, a car is a massive, complex machine, but for the sake of the math, we just pretend it's a microscopic dot on a graph.
Well, as long as the distance the car travels is vastly larger than the car itself, it works beautifully. Like if you're driving 100 miles, the few feet between the front bumper and the back bumper, they don't really matter to the overall calculation.
Right.
It's an approximation, sure, but it's a vital one.
And Feynman actually illustrates this by mapping out a hypothetical road trip. He uses figure 8.1 and table 8.1. So time is ticking away on the horizontal axis of a graph, and distance is climbing on the vertical axis.
Mm-hmm.
And the data tells a whole story. At 1 minute, the car is 1,200 feet down the road. Then it accelerates. But between 4 and 5 minutes, the distance barely changes at all. The graph just plateaus.
Yeah, and a flat line on a distance time graph means time is passing, but distance isn't. So in the real world, that's, hitting a red light or maybe getting stuck behind a garbage truck.
Yeah, exactly. Then after that plateau, the car speeds up again, aggressively covering thousands of feet. But right at 9 minutes, at exactly 24,000 feet, the graph completely flatlines again. The car has stopped entirely. And Feynman playfully suggests the driver probably got pulled over by a cop.
Which perfectly illustrates how messy real-world motion actually is. That graph is completely erratic. It curves gently, then spikes up, then goes totally flat.
It's just human driving.
Right, it's unpredictable.
Yeah.
And he deliberately contrasts this messy human driving with the second scenario in figure 8.2, which is just a falling ball.
Yeah, the falling ball is an entirely different beast. You drop it, and the data over time isn't jagged at all. At 1 second, it's fallen 16 feet. At 2 seconds, it's at 64 feet. 3 seconds, 144 feet.
It doesn't stop for coffee or get a speeding ticket.
Right. It traces a perfectly smooth, beautiful parabolic curve on the graph.
Because the ball isn't making choices, it's governed by a fundamental mathematical law. The distance it falls is simply 16 times the time squared. Or, mathematically, s equals 16t squared.
And here's what I find so interesting about this whole setup. Feynman takes a moment to acknowledge this huge philosophical elephant in the room. We're treating complex cars as mere dots, and we're just blindly accepting a basic everyday definition of a minute or a second.
Yeah.
So aren't we basically ignoring the deepest mysteries of the universe, like what space and time actually are, just so we can do some math?
Well, that practical compromise is actually the secret engine of physics. People often assume scientists require absolute perfect definitions for everything before they even begin.
Sure, they want to be precise.
Right. But if you sit down and try to perfectly define the concept of time or the concept of space, you don't get physics, you get a philosophical trap.
He calls it the paralysis of thought. It's like two philosophers sitting in a room for a decade, fiercely debating the exact definition of the word no or something.
Exactly. If physicists waited to perfectly define the fundamental nature of reality before measuring a falling ball, we wouldn't have bridges or airplanes or space travel. They just agree on a rough, shared working understanding of time and space, and they get to work.
It's like ignoring exactly how a combustion engine works just so you can drive to the grocery store. I mean, you don't need to be a mechanical engineer to go buy milk.
That is a very grounded way to look at it. And abandoning that philosophical paralysis is what allows them to face the next massive hurdle. We have a graph mapping distance and time, but from those two simple things, we stumble right into the conceptual nightmare of trying to define speed.
It really is a nightmare. You'd think speed is the easiest thing in the world, But it absolutely baffled the ancient Greeks. The text brings up Zeno's paradox, which honestly still melts my brain a little bit.
Oh, Zeno's paradox is brilliant. Zeno of Elea proposed this scenario that seems almost impossible to refute. So imagine a foot race between the legendary warrior Achilles and a tortoise.
Okay.
Achilles is let's say 10 times faster than the tortoise. And to be fair, he gives the tortoise a 100-meter head start. Zeno argued that, logically, Achilles can never catch the tortoise.
Wait, so he's basically saying motion is an illusion. Because obviously a fast runner passes a slow animal in real life.
Not an illusion, but an infinite mathematical puzzle. Look at how Zeno broke the motion down. Achilles runs the 100 meters to reach the tortoise's starting line, but during that time, the tortoise has moved forward 10 meters.
Right.
So Achilles has to run that extra 10 meters, but by the time he covers that new distance, the tortoise has advanced 1 meter. Achilles runs the 1 meter, the tortoise has moved 10 centimeters.
Ah, so because you can divide the remaining distance infinitely, Achilles is trapped in this endless loop of playing catch-up.
That was the exact trap. Zeno's logic assumes that an infinite number of steps equates to an infinite amount of time. But this is a profound misunderstanding of how time works.
How so?
Well, just because a distance can be sliced into an infinite number of microscopic pieces doesn't mean it takes an infinite amount of time to cross them. A finite amount of time, say 10 seconds, can also be divided into infinite pieces. Achilles simply crosses those infinitely shrinking distances in infinitely shrinking amounts of time.
Oh, wow. The Greeks were really just tripping over the concept of the infinitesimally small.
Exactly.
And this inability to grasp tiny microscopic slices of reality directly connects to this great joke Feynman uses to explain instantaneous speed. It's the lady and the cop.
It's a classic for a reason.
So a cop pulls a lady over and says, "Ma'am, you are going 60 miles an hour." And she looks at him, totally bewildered, and replies, "Impossible, officer. I was only driving for 7 minutes. How could I go 60 miles an hour when I wasn't even in the car for an hour?"
And, her logic is flawless if you only understand speed as a literal translation of total distance divided by total time.
But if I'm the cop standing by the window, why can't I just point to the dashboard and say, "Look, lady, your speedometer said 60. Why do we need some deep philosophical definition of speed when we have a machine that literally points a needle at the number?
Because a speedometer is just a mechanical tool that measures a concept. It doesn't define the concept. Consider this: if the speedometer cable snaps and the needle drops to 0, is the car suddenly stationary?
Obviously not. You're still going to crash into the car in front of you.
Right. The car possesses a physical property called speed entirely independent of the instrument measuring it. I mean, the instrument was invented long after the concept existed. So, to answer the lady's argument, the cop, or rather the physicist, has to define what 60 miles per hour actually means when the car only exists in that state for a single second.
Or even a fraction of a second.
Exactly.
Which brings us back to our frozen photograph.
Yeah.
If she isn't driving for an hour, we could say, okay, in 1 second, you were traveling at a rate of 88 feet per second.
But even that isn't perfectly accurate, right? Because what if she slammed on the brakes during that specific second? Her speed wasn't perfectly constant.
Yes, to find her truest, most accurate speed at the exact instant she passed the radar gun, a second is far too broad a window. We have to look at a smaller slice of time. A tenth of a second, a thousandth, a millionth.
We basically have to zoom in.
And zooming in infinitely is what bridges us into the mathematical concept of the limit and the derivative. This was the infinitesimal solution that finally untangled Zeno's paradox. This is really calculus riding to the rescue. Okay, let's unpack this. Let's walk through exactly how this works intuitively, because this is where the math often loses people, but Feynman makes it so tangible. Let's use that falling ball again.
Perfect.
The distance it falls is s equals 16 squared. Let's say we want to find the exact instantaneous speed of the ball at precisely 5 seconds into its fall.
We can start intuitively.
Yeah.
At exactly 5 seconds, the formula tells us the ball has fallen exactly 400 feet.
But speed requires a change in distance over a change in time. So we have to look slightly into the future. Let's look at 5.1 seconds. At 5.1 seconds, the formula says it has fallen 416.16 feet.
Right, so in that tiny 1/10 of a second, the ball traveled 16.16 feet. Divide that distance by the 10th of a second, and you get an average speed of 161.6 feet per second.
But I see the problem there. That's still an average. Gravity's constantly pulling on that ball, accelerating it. So at the very beginning of that 10th of a second, at exactly 5,000 seconds, it must have been going slightly slower than a 161.6.
Exactly. A tenth of a second is still too clunky. We need a slice of time so small it barely even exists. So Feynman introduces a symbol for this vanishingly tiny extra sliver of time, the Greek letter epsilon. We add epsilon to our 5 seconds and run it through the formula.
Wait, hold on. If epsilon is just a time slice that we're shrinking down to absolute zero, aren't we eventually just dividing by zero to find the speed? Doesn't that break all the foundational rules of math? I mean, you can't divide by zero.
You've hit on the exact reason this took centuries to figure out. You cannot divide by zero. But Newton and Leibniz realized a brilliant workaround. You don't plug zero in right away. You let epsilon be a real tiny number just long enough to do the algebra.
Okay, walk me through that.
So our formula is 16 times the time squared. When we add our tiny extra time, it becomes 16 times the quantity of time plus epsilon squared. When you multiply that all out using algebra, you get an expression for the new distance.
Right.
To find the speed, you subtract the original distance, and then you divide by that tiny time, epsilon.
Because speed is the change in distance over the change in time.
Precisely. And here is the miracle of the algebra. Because you expanded the equation first, every single term left on top has an epsilon attached to it. So when you finally divide by the epsilon on the bottom, it cancels out cleanly. You aren't dividing by zero anymore.
Oh.
The algebra simplifies beautifully into a clean expression for the speed, which is 32t plus 16 epsilon.
Oh, wow. Okay, so the math essentially protects itself.
It really does.
Yeah.
And now we apply the magic of the mathematical limit. We have our clean formula for speed 32t plus 16 epsilon. We ask, what happens to this exact equation as epsilon gets smaller and smaller, approaching absolute zero?
Well, 16 multiplied by a number shrinking to zero just vanishes. The 16 epsilon part completely disappears from the equation.
Leaving you with what?
Just 32t. 32 times the time, so that's the exact speed. At 5 seconds, it's 32 times 5, which is 160 feet per second. Exactly 160, not 161.6.
Yes. By pushing the time interval to the absolute limit without technically dividing by zero, we pinpointed the exact speed at a frozen instant. That entire process is the derivative. In formal calculus terminology, it's written as ds over dt.
Okay, ds over dt.
Right, the ds signifies a differential, a microscopic change. It's the tiny change in distance d's over the microscopic change in time dt.
Visually, it plays out like this in my head. You have that sweeping upward curve on the graph for the falling ball. If you want to know the speed at one specific point, imagine taking a powerful microscope and zooming in on that exact spot on the curve. You zoom in closer and closer and closer until you are so incredibly tight on the line that it doesn't look curved anymore. At the microscopic level, it appears perfectly straight. And that straight line is your exact speed at that frozen moment.
That is a fantastic visualization. The steepness of that microscopic straight line is your derivative.
It's stunningly elegant. But, knowing her exact instantaneous speed at one fraction of a second doesn't completely help the cop. To really trap the speeding lady, the cop needs to prove how much total distance she covered. They need to run this microscopic math in reverse.
Exactly. If differentiation is the process of breaking a curve down into microscopic straight lines to find a rate of change, the reverse process must be adding up an infinite number of microscopic pieces to find a total amount.
Which takes us out of the realm of derivatives and into integrals. So how do we actually do that? If her speed is constantly changing, you can't just multiply one speed by an hour and call it a day.
No, you can't. You have to chop her entire erratic road trip into incredibly thin slices of time, milliseconds. Imagine building a bar chart of her speed. For every tiny millisecond, you draw a rectangular bar. The width of the bar is that tiny slice of time delta t. The height of the bar is her exact speed at that moment.
Oh, I see. Because speed multiplied by time equals distance. So the actual physical area of that microscopic rectangular bar represents the tiny distance she traveled in that specific millisecond.
You've got it. You calculate the area of that first microscopic bar. Then you calculate the area of the next milliseconds bar, and the next, and the next. You end up with thousands or millions of incredibly thin rectangles under the curve of her speed. To find the total distance traveled, you simply calculate the total area of all those rectangles added together.
This brings up one of the most famous and frankly intimidating symbols in all of mathematics, the integral sign. It looks like a tall, leaning hook on a blackboard.
It looks like an arcane rune, but its origin is wonderfully literal. Feynman points out that the integral symbol is literally just a distorted, elongated letter S.
S standing for sum.
Yes, it's derived from the Latin word summa, meaning sum. It isn't a complex equation in itself, it's just a set of instructions. It's telling the mathematician, hey, take all these infinitesimally small areas we just created and add them all up. It is the exact inverse operator of the derivative st.
Okay, so distance gives us speed through a derivative. Speed gives us total distance through an integral. But what if we take the derivative of speed itself? Because as the lady proves, speed changes.
If speed is the rate of change of distance, then the rate of change of speed is acceleration.
So this is what happens when she floors the gas pedal. She isn't just covering distance, she's adding miles per hour to her speed every single second. The unit becomes a bit of a tongue twister, feet per second.
Mathematically, acceleration is the second derivative of distance. You differentiate the distance formula once to get velocity, and then you take that new velocity formula and differentiate it again to find the acceleration. We write it as d squared s over dt squared.
So looking back at our falling ball, we started with the distance formula, s equals 16t squared. We did the algebra, took the first derivative, and found the instantaneous velocity was 32.2. If we take the derivative of 32.2, well, the 2 just drops away entirely. We are left with a flat constant, exactly 32.
32 feet per second squared? That is the constant acceleration due to Earth's gravity. It never changes. Every single second that ball is in free fall, its downward velocity increases by exactly 32 feet per second.
Let's ground this in a feeling everyone knows. If you're riding in a car, velocity is just the number pushing the needle on your speedometer.
Sure.
You look down, you know you're cruising at 60, you don't really feel it. But acceleration is the invisible hand that physically shoves you back deep into your seat when the driver suddenly floors it.
Human beings don't feel velocity. We only feel the change in velocity.
Right.
Like if you're on a commercial flight cruising perfectly smoothly at 500 miles an hour, you can pour a cup of hot coffee without a second thought. Velocity won't spill your coffee, but if the plane suddenly hits turbulence and accelerates downward, that coffee is immediately in your lap.
That is a very vivid way to put it.
Yeah.
So up to this point, our mathematical universe has been pretty constrained. We've been driving in a perfectly straight line or dropping a ball straight down. One-dimensional motion. But the real world operates in 3 dimensions. How does all this microscopic calculus survive when objects are moving forward, side to side, and up and down all at the exact same time?
It handles it surprisingly elegantly through a concept called compound motion. Instead of a single number line, picture a flat plane. A graph with a horizontal x-axis and a vertical y-axis.
So our object isn't just sliding along a ruler anymore, it's carving a path across a piece of paper.
Exactly. To map that path, physicists employ a brilliant divide-and-conquer strategy. They treat the horizontal motion and the vertical motion as 2 completely separate problems. They calculate the velocity purely in the x direction v sub x and the velocity purely in the y direction v sub y.
It's like tracking the horizontal shadow of the object on the floor and its vertical shadow on the wall entirely separately.
That's a great analogy. And to find the actual true speed of the object moving diagonally through the air, they rely on a staple of high school geometry, the Pythagorean theorem.
A squared plus b squared equals c squared.
Exactly. The total real-world velocity is simply the square root of the horizontal speed squared plus the vertical speed squared. The separate motions build a perfect right triangle.
I want to visualize this with, like, the ultimate physics class scenario. Imagine standing on the edge of a high cliff and throwing a rock straight out toward the horizon. It's moving forward over the water, but it's also immediately falling toward the waves.
This is the perfect theater for compound motion. Horizontally, assuming we ignore the friction of the air, the rock has a constant velocity. It just keeps coasting forward at whatever speed your arm provided. But vertically, it is experiencing constant acceleration. Gravity is hauling it downward, increasing its vertical drop speed by 32 feet per second every second.
So horizontally, it's on cruise control. Vertically, it's plummeting faster and faster. And when you blend those 2 simultaneous realities, the rock traces a parabola, that beautiful, sweeping, predictable arc.
The profound realization here is that the horizontal motion and the vertical motion are entirely blind to one another. The gravity viciously pulling the rock down doesn't sap a single ounce of its forward momentum.
Really?
No, and the forward momentum doesn't offer any resistance to gravity. They operate independently, yet when synthesized on a graph, they define the exact flight path of every thrown object in the universe.
From a kid tossing a baseball to a cannonball firing to a rocket entering orbit, it's just X and Y doing their own thing. together.
And the calculus we just explored scales perfectly to this. You take the derivative of the horizontal position to find forward speed, you take the derivative of the vertical position to find falling speed, sum them up, and you conquer motion. It really is a monumental triumph of human logic.
It truly is. Let's step back for a second and just survey the territory we just covered. We started by stripping a complex car down to a single point just to make observation possible. We waded into Zeno's ancient Greek paradox to realize that dividing distance infinitely doesn't mean infinite time. We helped a cop trap a hypothetical speeding lady by defining instantaneous speed. And in unraveling all of that, we exposed the engine of differential calculus, using derivatives to shrink time and find exact speed, and using integrals to add up microscopic areas of time to find total distance. We built an entire branch of mathematics just to understand what it actually means to move.
It really demonstrates how asking one seemingly simple question, exactly how fast is that object moving right now, can force an evolution in human thought. Newton and Leibniz engineered the intellectual tools to freeze a moment in time, extract its data, and seamlessly unfreeze it again.
Before we wrap up, I want to leave you with a final, slightly unnerving thought that Feynman actually hints at in the text. We just built this entire towering mathematical structure on one massive assumption that space and time are perfectly, infinitely smooth. The whole trick of the derivative requires epsilon, that microscopic slice of time, to be able to shrink infinitely close to zero forever.
Yes, the absolute assumption of an infinite continuum.
But modern quantum physics tells us that reality might not actually be a smooth continuum. When you look closely enough at an atom, you can't always track a continuous marker. There might be a fundamental hard limit to how small things can actually get. So what happens to our perfect, elegant calculus if we zoom in with our microscope and discover that space and time aren't infinitely smooth, but are actually pixelated, like a digital photograph?
Well, if the universe has a fundamental pixel, like a smallest possible unit of distance or time, then you simply cannot divide it any further. The concept of the infinitesimally small slice, which is the very bedrock of the derivative, suddenly slams into a brick wall.
Does our definition of speed shatter all over again in the quantum realm? Do we have to invent an entirely new, unimaginably complex kind of math to replace calculus down in the atomic basement? It is definitely something for you to ponder the next time you're stuck in stop-and-go traffic, staring blankly at your speedometer, trying to measure change at a frozen instant in time.
Imagine you drop a heavy lead bullet from your hand, right? And you fire a second bullet perfectly horizontally from a high-powered rifle at the exact same moment.
From the exact same height. Yeah.
Right, the exact same height. Which one hits the dirt first? I mean, logic and probably your gut says the dropped one.
Oh, absolutely. It feels like it has to be.
Because it's falling straight down while the fired bullet is tearing across the landscape at, supersonic speeds. But physics says they hit the ground at the exact same millisecond.
It totally breaks your brain the first time you hear it.
It really does. The horizontal speed of that fired bullet, it does not keep it in the air a single fraction of a second longer than the one you just let slip from your fingers. And today, for this deep dive, we are breaking down the hidden, invisible gears of the universe to understand why that happens.
And, well, more importantly, how that seemingly bizarre fact is basically the ultimate skeleton key to understanding everything.
The skeleton key. I love that. Because before Isaac Newton came along, right, the motion of the planets was just a complete mystery.
Oh, total magic. I mean, we had meticulous observations. Astronomers knew exactly where Jupiter or Mars would be in the night sky.
They had the charts.
Right? They had the charts, but humanity had absolutely no underlying mechanism to explain why they moved the way they did. It was giant, invisible, celestial clockwork.
And that is exactly our mission today. We are unpacking Chapter 9 of the legendary Feynman Lectures on Physics.
A classic.
Truly. We are moving past the memorized trivia of high school science class to look at the rigorous framework Richard Feynman builds to explain Newton's laws of dynamics.
And we're going to walk through this brilliant, surprisingly accessible method that proves how anyone, and I mean anyone, without a supercomputer or a PhD in advanced calculus, can predict the future of a moving object.
Whether it's a spring on a desk or, a planet hurtling through the dark vacuum of space.
Exactly. But to get there, we actually have to start with a concept of doing absolutely nothing.
Doing nothing. Okay, explain that.
Well, before we can predict how things change over time, we have to establish a baseline for what objects do when they are left completely alone, unbothered.
Right.
And for that, Feynman takes us back to Galileo and his principle of inertia. It's the idea that an object will just keep doing exactly what it's doing forever, unless some outside agency disturbs it.
So if it's sitting still, it stays still.
Oh, yep. And if it's moving, it keeps moving in a perfectly straight line at the exact same speed.
Which, I mean, sounds incredibly obvious to us now, sitting here in the 21st century. But what's fascinating is the sheer contrarian imagination that took on Galileo's part.
Oh, it's huge.
Because think about our everyday physical experience on Earth. Nothing keeps moving forever. If you slide a heavy book across a wooden table, it eventually grinds to a halt.
Right, because we live in a world heavily governed by friction and air resistance.
It's messy.
Extremely messy. So to look at a reality where literally everything eventually stops and correctly deduce that the natural, undisturbed state of the universe is actually endless, unyielding motion?
That requires a profound mental leap.
It really does. You have to intellectually strip away the tactile reality of the tabletop to see the pure, unadulterated rule hiding underneath.
So if the natural baseline is that things just keep moving in a straight line forever, that implies a powerful corollary. If we see something change its speed or curve its path, there has to be a cause.
There's a culprit, yes.
And that brings us to the core rule of everything, right? Newton's second law. Force changes momentum over time.
Exactly. Anytime an object is accelerating, whether it is speeding up, slowing down, or turning a corner, some force is actively being applied to it.
But Feynman doesn't just assume we know what we're talking about when we use words like mass or velocity, does he?
No, he rigorously redefines them for you, because you cannot calculate planetary motion if you carry around the sloppy definitions we use in ordinary language.
Right.
Like, he specifically isolates mass from weight.
Okay, let's unpack this. Because in everyday life, we treat mass and weight as the exact same thing. I step on a scale, that's my mass.
Right. But Feynman strips away gravity completely. He defines mass purely as inertia. It's the resistance to a change in direction in a vacuum.
It's a necessary mental reset. You can imagine an astronaut floating in deep space.
Right.
Completely weightless.
Perfect analogy, yeah.
If that astronaut attaches a massive solid steel block to a rope and tries to swing it around their head in a circle, they are going to feel a massive amount of physical resistance.
They have to pull incredibly hard on that rope to keep that block moving in a circle, instead of it just flying off in a straight line.
And that resistance, that inertia, that is mass. It has absolutely nothing to do with gravity.
Exactly. And Feynman does the same rigorous reset with speed and velocity.
Right, because people use those interchangeably all the time.
Constantly. But speed is a scalar. It's just a magnitude, 50 miles an hour. That's it. Velocity, though, is a vector.
Meaning it has a direction.
Yes. It contains both speed and precise direction. 50 miles an hour due north.
And we really have to care deeply about this distinction, don't we? Because Newton's law dictates that force changes velocity.
Right. A force can speed you up or slow you down, certainly. But a force can also keep your speed perfectly constant while just continuously altering your direction.
Like driving in a perfect circle.
Yes. If you're driving in a perfect circle at a steady 50 miles an hour, you feel a force pushing you against the door of the car.
Right, you get squished against the window.
Exactly. Your speed isn't changing, but your velocity is changing every single millisecond because your direction is changing.
Wait, hold on. I need to push back on this formula for a second. The equation states that force equals the change in mass times velocity over a specific period of time.
Correct.
This neatly assumes mass is just a static, unchanging number. But what if I'm looking at something like, I don't know, a SpaceX rocket launching into orbit?
Oh, okay.
It's burning through thousands of pounds of fuel every single second. It is actively shedding mass. Does Newton's neat little equation just break down?
That is a brilliant point, and it's a fundamental limitation you've hit on. Feynman explicitly points out that this basic formulation of Newton's law makes a massive underlying assumption.
Which is?
That mass must remain constant for these basic equations to work out so simply. If the mass is dynamically changing while the object moves, like your rocket, the mathematics become significantly more complex.
Because you're basically dealing with two moving targets.
Exactly. You have to account for the momentum of the expelled mass, the rocket exhaust as well. But for the vast majority of classical mechanics, and certainly for the celestial mechanics of massive stable objects like planets and stars,
they aren't exactly shedding thousands of pounds a second.
Right. We operate under the Newtonian approximation that the mass is constant.
Okay, good to know we aren't completely breaking the laws of physics today. So we've got our building blocks. Force changes velocity. But reality isn't a neat straight line on a two-dimensional piece of paper.
No, it is not.
Things move diagonally, they curve, they spiral through a three-dimensional void. Trying to mathematically describe a sweeping, complex diagonal curve in 3D space all at once, I mean, that feels impossible.
Oh, it is a mathematical nightmare if you try to tackle the entire motion simultaneously. So Feynman shows us how to cheat the system.
I love a good physics cheat code.
Right. We don't solve the complex curve. We slice reality into a rigid 3D grid. We break every single movement down into three separate, isolated directions.
The x-axis, the y-axis, and the z-axis.
Yep.
Left and right, up and down, forward and backward.
Exactly. And here's where it gets really interesting, and this connects right back to that opening thought experiment with the bullets.
Right.
Any diagonal displacement, any change in velocity whatsoever, can be viewed as just a combination of those three separate directions happening at the exact same time.
The wild, counterintuitive fact that Feynman highlights here is that motion in these three directions is completely 100% independent.
Yes. If the forces driving the motion aren't physically linked together, the resulting motions are entirely blind to one another.
So the horizontal momentum of that bullet fired from the rifle has absolutely zero impact on the vertical pull of gravity.
None. Gravity doesn't care how fast you're moving sideways. It pulls you down with the exact same acceleration as if you were standing perfectly still.
That independence is the absolute secret to solving complex motions in physics, isn't it?
It really is. We don't need to invent entirely new math to calculate a spiral or a parabolic arc. We just solve three incredibly simple, straight-line problems side by side at the exact same time.
Which is elegant in theory, but Feynman is a physicist who demands practical application.
He always brings it back to the real world.
Right. Knowing that we can break motion into components is great, but how do we actually calculate the future of an object? Like, how do we predict where something will be 10 seconds from now?
Well, he asks us to test this on a simple machine, a mass hanging vertically from a spring.
Okay, so we want to know exactly how this mass will bounce up and down over time. We know Newton's law says we have to pay attention to the forces.
And the force of a standard spring is beautifully simple. The further you pull the spring down away from its natural resting point, the harder it pulls back up.
And if you compress it by pushing it up, it pushes down.
Exactly. The force is perfectly proportional to the distance it has been stretched.
Which means the equation for its acceleration is simply negative x.
Right. Let's call the resting point 0. If you pull the mass down to a position of +1, the acceleration pulling it back in the opposite direction is -1.
The velocity is constantly changing at a rate entirely dictated by its current physical position.
Yes. So how do you actually chart the future of that bouncing weight without using complex calculus equations?
This is the part I love. Feynman introduces a technique called numerical integration. And I love this part of the lecture because it completely demystifies the math.
It really does.
You don't need to be a mathematical prodigy. You just need to be able to do basic arithmetic-like addition and multiplication and organize your work in a simple ledger, taking it one tiny step at a time.
You are essentially building a manual spreadsheet. You define a very small interval of time. Let's call it epsilon.
Epsilon.
And Feynman uses an epsilon of exactly 1/10 of a second. 0.100 seconds.
Okay, so we have our interval.
Right. Start at time 0. You look at the current position of the mass, which tells you the current force. That force gives you the current acceleration.
And then you just project forward. You use that acceleration to figure out what the velocity will be 1/10 of a second from now.
Exactly.
Then you use that new velocity to figure out where the mass will physically be positioned 1/10 of a second from now.
You're just looping it.
Right. You calculate step 1, which gives you the starting point for step 2. Step 2 gives you the starting point for step 3.
There's a mathematical trap hiding in this method, though.
Uh-oh. What's the trap?
Well, if you calculate where the mass will be in 0.1 seconds, based entirely on its velocity at this exact starting moment, your prediction will fundamentally fail.
Ah, because the velocity isn't static.
Exactly. The spring is constantly pulling.
Right. The speed of the mass is actively changing during that entire 1/10 of a second. It's like, well, think of it like predicting a road trip.
Okay, let's hear it.
If I'm merging onto a highway and accelerating hard, I can't calculate how far I'll travel in the next 10 seconds by using my starting speed of 30 miles per hour.
No, you'd be way off.
Right, because that starting speed only exists for a fraction of a second. It would completely underpredict my actual distance traveled, but I also can't use my final speed of 70 miles per hour because that would overpredict my distance. I wasn't going 70 the whole time.
That is a brilliant analogy. And to solve this without using calculus, Feynman introduces what he calls the half-step trick.
A half-step trick.
Right. Instead of looking at the velocity at the beginning of the time interval or the velocity at the very end of the time interval, you calculate the velocity exactly halfway between the 2 points in time.
Well, that makes so much sense. So you offset the time columns in your ledger. You measure position at time 0, time point 1, time point 2. But you measure velocity at time point 0.5, 1.5, 2.5.
Yes. By using the velocity at the halfway mark of your time step, the tiny errors of acceleration naturally cancel each other out.
The slow start is balanced by the fast finish.
Precisely. And when you apply this offset trick to the arithmetic for the bouncing spring, taking methodical 0.1-second steps, the results are astonishing.
What happens?
Well, plotting those calculated positions on a graph doesn't just create a rough approximation of a bounce. It creates a flawless, sweeping mathematical cosine wave.
Wow.
Pure harmonic motion, generated entirely from basic arithmetic.
It is literally like building a step-by-step crystal ball out of nothing but addition.
It really is.
We can point to a specific moment, say exactly 3.4 seconds in the future, and know precisely where that spring will be. We are constructing the future out of tiny blocks of the present.
But, predicting a spring on a laboratory desk is a fascinating exercise, sure.
Mm-hmm.
The real test of Newton's dynamics, however, isn't desk toys.
It is the cosmos.
Yes. If this step-by-step arithmetic works for a spring, could it possibly map the mechanics of a planet orbiting a star?
That's a huge leap.
It is. Feynman scales the concept up to the solar system, and the profound realization is that the underlying process is completely identical.
The only thing that changes is the specific formula for the force, right?
Exactly. Instead of a spring, where the force is proportional to distance, we're dealing with gravity. Newton's law of universal gravitation.
Right. The force is equal to the gravitational constant, multiplied by the mass of the sun, multiplied by the mass of the planet, all divided by the square of the distance between them. The famous inverse square law.
Yes, the inverse square law, meaning the further away the planet gets, the weaker the gravitational pull becomes, dropping off by the square of the distance.
But wait, we immediately encounter a geometric complication here.
Are you good?
Because the sun is sitting at the center of our grid, right? But the planet is out in space at some arbitrary coordinate.
Right.
So the gravitational force isn't neatly aligned with our x or y axis. It is pulling diagonally, straight towards the center of the sun.
And as we established earlier,
We aggressively avoid calculating diagonals.
we do. We
Yeah.
go back to our trusty X and Y grid.
Yeah.
We can resolve this diagonal force vector by drawing a simple triangle.
Okay, visual learner, stick with us here.
Right, imagine it. The diagonal line representing the total distance to the sun is the hypotenuse.
Got it.
The horizontal distance along the x-axis and the vertical distance along the y-axis form the sides of a right triangle.
Okay.
Because the force vector pointing towards the sun forms a perfectly similar triangle with those distance coordinates, we can break that total gravitational force into an x component and a y component just by using simple mathematical ratio.
Oh, that's brilliant. We separate the horizontal pull from the vertical pull.
Exactly. And once we have those isolated forces, we can build a new ledger. Feynman sets up a theoretical planet to prove the concept.
Let's hear the numbers.
He makes all the giant celestial constants equal to 1, just to keep the arithmetic clean. He starts the planet at a position sitting on the x-axis, at exactly 0.5 units away from the sun.
Okay, 0.5 units away.
And he gives it an initial vertical velocity, a guide velocity of 1.630.
Okay, wait, why does it need an initial velocity?
Because if we just drop the planet from a standstill, it would plunge in a straight line directly into the sun.
Oh, right, game over.
Right. But because it has an initial sideways momentum, it is going to attempt to fly straight past the sun while the sun's gravity continuously tries to pull it inward.
So we unleash the step-by-step arithmetic.
We do. We use the exact same 0.1/0 second intervals. We look at the coordinates, calculate the true distance using the Pythagorean theorem, calculate the inverse square of that distance to find the total gravitational force.
Break that force into x and y pieces using the triangle ratios.
Update our velocities using the halfway trick.
And plot the new position over and over and over.
It is incredibly tedious to do by hand, but the geometry of what happens is magnificent.
What does it look like?
The planet wants to move in a straight line. During that 0.1-second step, it essentially does. But gravity applies a tiny inward tug, changing the velocity just slightly for the next step.
So it takes another straight line step, just slightly angled inward.
Exactly. You're basically drawing a polygon with millions of tiny, straight, flat sides.
Okay.
And as that time interval, that epsilon, gets smaller and smaller, the corners of that polygon get shaved off.
Oh, wow.
The numbers reveal the raw orbital mechanics. When the planet is physically closer to the sun, the distance is small, so the gravitational force spikes immensely.
The acceleration skyrockets.
Yes, and the planet whips around the tight curve of the sun. As its momentum carries it further out into space, the distance increases, the force drops off rapidly, and the planet slows to a crawl on the white end of its path.
So, in just a handful of tedious calculations, plotting point by point, you literally chase a planet exactly halfway around its orbit.
Yes. You can visually see the plotted dots spaced far apart at the beginning when the planet is whipping around the sun, and clustered tightly together at the far end when it is moving sluggishly.
That is amazing.
It proves a profound truth about our universe. The shape of a planetary orbit, an ellipse, isn't some separate, arbitrary geometric rule handed down by the cosmos.
It's just cause and effect.
Exactly. An ellipse is simply the unavoidable geometric consequence of taking tiny linear steps of cause and effect under the influence of an inverse square force.
We aren't guessing at the shape. The shape emerges organically from the fundamental rule of motion.
Exactly.
But, okay, calculating one perfectly still sun and one single planet by hand using slide rules and reciprocal tables like the scientists of Feynman's era, I mean, it takes an afternoon, but it is entirely doable.
Sure.
But the actual solar system isn't just one sun and one planet. What happens when we have to account for reality?
Oh, reality.
Right. What happens when we add Jupiter and Saturn and Uranus? They aren't just orbiting the central sun. Their immense gravity is constantly pulling on each other at the exact same time.
Yeah, that is the infamous n-body problem. And it is where manual human calculation hits an absolute brick wall.
I can imagine.
To predict the true chaotic motion of a populated solar system, you have to sum up every single interactive force.
So if you want to calculate the next tiny 0.1 second step for Mercury,
You have to calculate the massive gravitational pull from the sun, plus the faint pull from Venus, plus the pull from Earth, plus the distant but massive pull of Jupiter, all using that exact same inverse square distance formula.
and you have to break every single one of those individual planetary pulls into isolated X, Y, and Z components.
You sum up all those horizontal forces, all those vertical forces, all those depth forces, and that
Yeah.
colossal pile of arithmetic gives you the total acceleration for Mercury for one single fraction of a second.
And then you have to start over and do the exact same thing for Venus.
And then for Earth. The combinatorial explosion of math is staggering. You don't have a simple ledger anymore. You have dozens of interacting columns, hundreds of calculations, just to inch the entire solar system forward by a single millimeter in time.
Which brings us to the ultimate paradigm shift. Feynman notes that while doing this by hand for the entire solar system would take a human being multiple lifetimes, the invention of modern computing machines changes the fundamental limits of what we can know.
It completely changes the game. Even the early computing machines he references were capable of doing an addition in a single microsecond.
Which allows for thousands of cycles of computation in a single second.
The leap from human minds to silicon processors is the climax of this entire physical theory. To accurately track Jupiter entirely around the sun, while simultaneously accounting for the constantly shifting gravitational pull of every other planet and moon in the solar system to an astonishing accuracy of 1 part in a billion.
How long does it take?
It takes roughly 400,000 complete cycles of calculation.
400,000 tiny linear steps of cause and effect.
And an early computing machine executes those 400,000 steps in just 130 seconds.
A little over 2 minutes.
Exactly. In 2 minutes of processing time, humanity goes from staring blankly at a spring bouncing on a wooden desk to flawlessly mapping the exact microscopic perturbations of an entire planetary system millions of miles wide.
That gives me chills. The machine doesn't use magic. It doesn't use intuition. It just uses Feynman's basic ledger of arithmetic, executed at blinding speed.
That's the beauty of it.
So by clearly defining the parameters of motion, stripping away gravity to understand mass and isolating direction to understand velocity, and by slicing messy, chaotic 3D reality into independent straight-line axes, we unlock the ultimate physical superpower.
We do.
We realize that the terrifying complexity of the universe is an illusion. All motion, from a falling leaf to a colliding galaxy, is just Newton's second law happening over and over again in incredibly tiny increments.
It is a radical shift in how we perceive reality. We often assume that massively complex systems must be governed by massively complex rules that are just beyond our comprehension. Right.
But the mechanics of the solar system prove that chaotic, breathtakingly complex patterns are actually governed by incredibly simple rules repeating infinitely. The complexity is just an emergent property of time and scale.
That is perfectly stated. And actually, that brings me to a final, somewhat unsettling thought I want to leave you, the listener, to mull over.
Uh-oh. Unsettling.
Just a bit. We've established that the key to predicting the future is just simple rules of physics applied over tiny time steps.
Right.
Cause and effect, repeated flawlessly.
Right.
If a computer can predict a planet's exact location 10 years from now to 1 part in a billion just by breaking time into tiny 0.1-second intervals of inertia and gravity, does that mean the entire physical universe is fundamentally deterministic?
Oh, wow.
Right. If we possessed a computing machine fast enough, with a memory bank large enough, and we chose a time interval small enough, could we theoretically map the exact movement of every single atom on Earth?
That is a heavy question. Could we mathematically calculate the outcome of a coin flip before it lands? Or predict the future of the weather weeks in advance? Or even model the trajectory of human history just as easily as we calculated the bounce of that mass on a spring? It begs the profound question, is the future of everything already written into the mathematics of the present, just waiting for a fast enough computer to calculate the next step?
If you punch the right sequence of buttons into a complex video game, you unlock a cheat code.
Right, yeah.
Like, you don't have to fight your way through some giant maze of 1,000 enemies. You just, walk right through the walls.
You bypass the grind entirely.
Exactly. You bypass the grind. And today, we're going to show you how physicists discovered that the actual physical universe has, well, a cheat code of its own.
It's really a phenomenal concept because normally you'd just assume that to understand how things move or, crash or explode in the real world, you have to play by the messy rules.
Yeah, the grueling math.
Right. You'd have to do the step-by-step math for every single tiny piece of the puzzle. But it turns out you can actually manipulate the underlying code of reality itself.
Welcome to the Deep Dive. Our mission today is to uncover that cosmic cheat code. We're pulling from a pretty legendary set of physics lectures, specifically looking at Chapter 10 on the conservation of momentum.
And it is a wild journey.
It really is. It starts with these incredibly simple ideas, takes us through frictionless tracks and mental car rides, and ultimately drops us into the absolute weirdness of quantum mechanics.
Yeah, and we're going to look at how this one principle allows us to solve incredibly complex problems without needing just, impossible amounts of computation.
So by the end of this deep dive, you're going to understand why a child bouncing a ball on a speeding airplane experiences the exact same physics as someone standing still on the ground.
Mm-hmm.
And we are finally going to figure out how rockets can possibly propel themselves in the dead vacuum of space. Because, there is absolutely no air to push against out there.
Right. But to really appreciate that solution, we first have to understand the nightmare that physicists were trying to avoid in the first place.
The impossible math problem.
Exactly. We have to look at the absolute limits of raw mathematical calculation.
Because, the basic math we learn in school is actually deceptively easy.
Oh.
Like, if you drop a rock off a cliff, you know the acceleration due to gravity is roughly 32 feet per second squared.
Sure.
So you can use a really simple equation to predict exactly where that rock will be 3 seconds from now.
But the moment you add even a tiny bit of complexity to that system, that clean math just shatters.
It breaks down fast.
Remarkably fast. Like, consider the famous three-body problem in astrophysics.
Oh, yeah.
If you have just two planets orbiting each other, the math is pristine. But the moment you add a third planet, well, all three are pulling on each other with gravity simultaneously.
Right, so the distances are constantly changing.
Which changes the gravitational pull.
Which changes the speed.
Which changes the distances again. It's an endless loop. Mathematical analysis simply cannot produce a simple formula to predict their motion. You have to calculate it point by point, millimeter by millimeter.
Just grinding through it.
Yeah. Now, scale that up from 3 planets to, say, a cloud of gas.
Right, and our source materials point out that in just 1 cubic millimeter of gas, so like a space barely the size of a pinhead,
Yeah.
there are about 10 to the 17th power molecules.
It's an unfathomable number.
That's 100 million billion particles.
Yeah.
And they're all flying around at supersonic speeds, crashing into each other, bouncing off the walls, and constantly changing direction.
So trying to track those individual collisions mathematically isn't just difficult. It is fundamentally impossible for any computer we could ever build.
You literally can't calculate every detail.
No. We need a general rule that governs the entire system from the top down, completely ignoring all that microscopic chaos underneath.
You know, it makes me think of trying to track a hurricane.
Oh, that's a good analogy.
Like if you try to map the trajectory of every single raindrop swirling in the wind, you'll completely lose your mind. It's mathematically impossible.
He'd never do it.
Right. So instead, meteorologists just track the overall storm. They treat the whole chaotic mess as one unified thing.
That is a perfect way to look at it. And the way physicists track their storm is by looking at a concept Isaac Newton gave us.
Action and reaction.
Right. Newton gave us the law of gravitation, but for the complex microscopic forces between atoms, he didn't have the exact equations. He did, however, discover one universal property of forces, which is his third law. Action equals reaction.
Meaning, if I push you, you push back on me with the exact same amount of force, but in the exact opposite direction.
Precisely. Now let's connect that idea to momentum.
Okay.
Momentum is just an object's mass multiplied by its velocity. Basically, how heavy is it and how fast is it going?
So a moving train has huge momentum.
And a buzzing mosquito has very little.
Right.
Now, because force is just the rate at which momentum changes, if the forces between two particles crashing into each other are always perfectly equal and opposite, then their changes in momentum are perfectly equal and opposite.
Wait, let me make sure I'm visualizing this correctly. So if particle A slams into particle B and particle A gains 10 units of momentum from that crash, does that mean particle B has to lose exactly 10 units of momentum?
That is exactly it. If you add up the total momentum of particle A and particle B before the crash, and then add them up after the crash, the total number is completely identical.
The momentum just shifted from one to the other.
Exactly. Now, apply that to your hurricane of 100 million billion gas molecules. Mass 1 times velocity 1, plus mass 2 times velocity 2, plus mass 3, all the way to infinity.
And the total sum of all that momentum equals a constant number.
It never changes, no matter how many trillions of internal collisions happen every millisecond.
Well, as long as no outside force interferes, right? Like, as long as the system is isolated, that total momentum is locked in.
Yes, that is the conservation of momentum. It is a cosmic ledger that perfectly balances itself. You don't need to know what every individual molecule is doing. You just look at the total ledger.
Man, that is incredibly elegant on paper. But proving it in the messy reality of a laboratory is a different beast entirely.
Oh, absolutely.
Because in the real world, we have friction. Galileo figured out a lot about motion, but he was constantly frustrated because whenever he tried to slide two objects together to measure their momentum, they would just grind to a halt.
The environment just steals the energy.
Right.
Friction ruins the mathematical picture. The energy bleeds away into the table, into the air, into sound. To actually test this universal ledger, modern physicists needed a way to erase friction entirely.
They had to isolate the objects completely.
Yeah.
And the physicists tackling this came up with a brilliant hack. In the source material, they show these diagrams, like figures 10.1 and 10.2, of a marvelous invention called the linear air trough.
It's such a clever device.
It really is. Imagine a giant air hockey table, but condensed down into a single long metal track. They pump high-pressure air through tiny holes drilled all along the surface.
Right.
And when you place a metal glider on this track, it literally hovers on a microscopic cushion of air.
It's beautiful in its simplicity. By floating on the air, the gliders experience practically zero friction. If you give one a tiny push, it will just slide down the track at a constant velocity until it hits the end.
It's as close to the pure vacuum of space as you can get in the classroom.
Exactly. So we finally have our pristine environment. Now, how do we actually test the ledger?
Right.
The classic experiment detailed in our dive goes like this. You take two gliders of equal mass, you place them touching each other right in the middle of the track.
Okay.
You put a small explosive cap in a little cylinder right between them, and you spark it.
So the explosion violently pushes them apart.
Right. Now, before the explosion, they were sitting still. The total momentum of the system was exactly zero.
And the ledger says the total momentum after the explosion must also be zero.
Exactly. So if one glider shoots off to the right with a certain momentum, the other glider must shoot off to the left with the exact same momentum to cancel it out.
And since we know their masses are equal, that means they have to fly apart at the exact same speed.
Yep. They hit the spring bumpers at the far ends of the track, bounce back, and meet perfectly dead center where they started.
Which is visually stunning. But I actually have to push back on a fundamental premise here.
Oh, what's that?
How do we actually know the masses are perfectly equal in the first place.
What do you mean?
I mean, we don't have some universal divine scale that just tells us the true mass of an object. Are we literally just defining what equal mass means by blowing things up and seeing if they fly away at the same speed? It sounds like a circular argument. We say momentum is conserved if the masses are equal, but we are deciding the masses are equal because they conserve momentum.
That is a wildly perceptive critique, and it's something that often trips up physics students. You're absolutely right. At first, it is a circular definition.
Really?
Yeah, we are forcing the definition of mass based on the outcome we want. But the brilliance of the scientific method is how it transforms that forced definition into a predictive, unbreakable physical law.
Could walk me through how we escape that circular logic.
Sure, so imagine you take a small block of copper and a huge, heavy chunk of aluminum. You put them on the air track and explode the cap between them.
Okay, so the heavy aluminum barely moves while the light copper goes flying.
Right, so you shave a little bit of the aluminum off and you try the explosion again.
And you just keep shaving off aluminum.
Testing and tweaking over and over until finally the explosion sends them flying apart at the exact same speed.
Okay, so at that exact moment, we just declare these two totally different objects now have equal mass. We essentially manufacture the equality.
We did, but here is the critical leap. Let's say you take that exact piece of copper and you find a completely different material, say a piece of gold.
Okay.
You do the shaving and tweaking on the gold until it perfectly balances the copper in an explosion.
Right.
Now you have a piece of aluminum that balances the copper, and you have a piece of gold that balances the copper. Pure logic does not guarantee that the gold and the aluminum will balance each other. They have never interacted. The universe doesn't have to obey our manufactured definitions.
Oh, I see where this is going. We test them against each other.
Exactly. You put the tailored gold and the tailored aluminum on the track, you spark the cap, and they fly apart at absolutely identical speeds. Nature agrees with our definition across the board.
Yeah.
The experiment proves the transitive property of mass. If two objects equal a third, they are fundamentally equal to each other. Suddenly, it's no longer a circular definition, it is a universal law.
That is deeply satisfying. We proved how equal masses behave when they violently blow apart.
Yes.
But physics is rarely just about things blowing apart. What happens when things crash together? Like if I have two objects slamming into each other on this track, I really don't want to calculate the messy transfer of forces during the crunch.
And the good news is, you don't have to. Physicists rely on a brilliant mental shortcut rooted in Galilean relativity.
Okay, let's clarify that term, because relativity usually makes people think of Einstein and warp speed and time travel.
Right, but this is much older and simpler. Galilean relativity is the core idea that the fundamental laws of physics look exactly the same whether you are standing completely still or moving in a straight line at a constant speed.
This is the airplane example from the intro.
Exactly.
If a child is standing in the aisle of a 747 cruising at 500 miles an hour and they bounce a tennis ball, it drops straight down and comes straight back up to their hand.
Yeah.
They don't have to throw it forward at 500 miles an hour just to catch it.
Right.
Inside that moving frame of reference, the physics are identical to standing in their living room.
Precisely. To the child, the plane is standing still and the Earth is rushing backward outside the window. Both perspectives are equally valid in physics.
Right.
And we can use that shift in perspective to solve complex collisions without heavy algebra. In the source material, they illustrate this beautifully across figures 10⁴ through 10⁷.
Let's run a scenario to make this concrete for everyone listening. Imagine two sticky lumps of putty on our air track. Lying perfectly still on the right side of the track is a 1-pound lump of putty. Sliding toward it from the left is another 1-pound lump, moving at 60 miles per hour.
Got it.
When they hit, they're going to stick together into one giant 2-pound lump. So the question is, how fast will that new giant lump be moving?
If you try to calculate the momentum transfer from the perspective of someone standing perfectly still next to the track, you have to juggle the moving mass, the stationary mass, and the combined mass after the impact.
Which is annoying.
Very. But Galilean relativity says we can just shift our camera angle, so to speak, to make the math trivial.
Okay, let's shift the camera. Imagine instead of standing by the track, you're watching this happen while driving past in a car.
Okay.
And you're driving parallel to the track at exactly 30 miles per hour in the same direction as the moving putty.
Perfect setup. Let's look at what the putty lumps are doing from your point of view inside that moving car. The first lump was going 60 miles per hour, but since you are driving alongside it at 30, it only looks like it's creeping ahead of you at 30 miles per hour.
Right. It's just overtaking me slowly.
And the lump that was standing still on the track, well, you're driving toward it at 30 miles per hour. So out your windshield, it looks like it's rushing toward you at 30 miles per hour.
Exactly. So by shifting my perspective to 30 miles per hour, the scenario has magically transformed. Instead of one fast object hitting a stationary one, I now see two identical lumps coming toward each other at the exact same speed, 30 miles per hour.
Oh, it's brilliant. The whole situation became perfectly symmetrical.
And because it is symmetrical and their masses are equal, when they crash and stick together, what has to happen?
Their momentums perfectly cancel out. From the perspective of your car, the new giant lump just stops dead. Its velocity is zero.
But wait, that's only inside the car. In the real world, the track isn't moving. If the combined lump is completely stationary relative to my car, and my car is driving at 30 miles per hour, that means the combined lump must be moving down the track at 30 miles per hour.
You've got it. We solved the collision by just changing our point of view. A 1-pound mass at 60 miles per hour hits a stationary 1-pound mass. The combined 2-pound mass moves at exactly half the speed, 30 miles per hour.
The ledger perfectly balances. Mass times velocity before equals mass times velocity after.
Yes. It's such a powerful mental tool.
It really is. It reminds me of walking on a moving walkway at an airport. Like your speed feels totally normal to you, but to someone standing at the gate, your velocities are combining.
That's a great everyday example of Galilean relativity.
Now, we specified that the objects stick together like putty. In physics, that's called an inelastic collision,
Yes,
right?
exactly.
Total momentum is conserved, but what happens to the energy? A lot of kinetic energy. The energy of motion seemed to just vanish when they slam together and clump up.
Well, it doesn't vanish. It transforms. During that split second of maximum compression when they crash, the kinetic energy is absorbed by the internal structure of the putty.
Like, where does it go?
It turns into heat and internal vibration. If you measured it with a highly sensitive thermometer, the putty actually gets warmer. The energy is lost to the internal gears and wheels of the object.
How does that compare to an elastic collision, like hitting two perfectly rigid billiard balls together?
Right. In a perfectly elastic collision, the objects don't absorb the energy as permanent heat. They act like highly efficient compressed springs.
Oh, interesting.
They crush inward for a microscopic moment, store the kinetic energy elastically, and then immediately explode back apart, fully recovering their motion.
Okay.
If a moving billiard ball perfectly strikes an identical stationary one, it transfers everything. The moving ball stops dead, and the stationary ball shoots off at the exact speed the first one had. They just swap velocities.
So the energy is fully conserved as motion.
Exactly.
Okay, so we've covered objects hitting each other, sticking and bouncing. Let's tackle the biggest mystery from the intro.
The rockets.
Yes. If everything is about action and reaction, if every push requires pushing back against something, how in the world does a rocket fly in the vacuum of space? A car tire pushes against asphalt, a boat propeller pushes against water, but in deep space, there is absolutely nothing.
It is the most common misunderstanding about spaceflight. People assume the rocket's exhaust flames are pushing against the air behind the ship,
Right.
but they aren't. A rocket works purely on the internal conservation of momentum. It doesn't need the outside universe at all.
So how does it work?
A rocket engine is essentially a continuous, controlled explosion. It's exactly like the spark cap we use between the two gliders on our air track.
Wait, so the rocket is just endlessly blowing itself in half?
Conceptually, yes. Imagine the rocket is a massive object, and the rocket fuel is a very tiny object. Before you fire the engines, the ship is just floating there. Total momentum is zero. To move forward, the rocket ejects that tiny mass of fuel out the back. But it doesn't just drop it. It ignites it, forcing it out the exhaust nozzle at a terrifying supersonic velocity.
Okay, so you have a tiny mass moving at a massive velocity backward. That's a huge chunk of momentum heading in the negative direction.
And because the universe demands the total momentum remain zero, the giant mass of the rocket itself must recoil in the positive direction to balance the ledger.
Ah, I see.
It's exactly like the kickback you feel when firing a shotgun. The gun doesn't kick your shoulder because the buckshot pushed on the air. It kicks back because the explosive force sent mass forward, and the gun has to go backward to conserve momentum.
So the rocket is literally just recoiling its way across the solar system. By continuously throwing tiny bits of mass backward as hard as it possibly can, the heavy ship gains a steady creep of speed forward.
That's it, exactly.
That is brilliant.
Yeah.
But of course, the universe never lets us get too comfortable with these classical rules. What happens when we take this beautiful, simple ledger and push it to the absolute extreme limits of reality?
Oh, this is where we subject Newton's cheat code to the ultimate stress test. In the 20th century, Albert Einstein completely upended our understanding of physics with his theory of relativity.
Okay.
We just spent all this time establishing that mass is a reliable constant. Einstein proved it isn't. As an object moves faster, approaching the speed of light, its mass actually increases. It literally gets heavier the faster it goes.
Wait, if the mass is ballooning as the object accelerates, how can momentum possibly be conserved? The math must fall apart completely.
You would think so, but here is the genius of the universe. Einstein found that even as the definitions of mass and time are actively warping at light speed, the conservation of momentum still flawlessly holds true.
Really?
Yes, the ledger adapts to relativity and continues to perfectly balance itself.
That actually brings up a crazy thought. If the ledger is that strict, can momentum ever get lost in transit? Like, can we lose some in the couch cushions of the universe?
What do you mean by lost in transit?
Let's say we have two powerful magnets separated by a few feet. I suddenly rip one magnet to the left. The magnetic force should pull the second magnet along with it. But we know there's a speed limit to the universe.
Yes, the speed of light. Nothing happens instantly across a distance.
Right. So the change in the magnetic field takes a tiny fraction of a second to cross the gap and reach the second magnet. For that microscopic sliver of time, the first magnet has moved, it has gained momentum, but the second magnet hasn't reacted yet.
Oh.
The ledger is totally unbalanced. Where is the momentum during that delay?
It is a stunning paradox. And the answer is that the universe stores the missing momentum in the empty space between them. It is hidden in the electromagnetic field itself.
Wait, how does empty space hold momentum? Space doesn't have mass.
It doesn't have mass, but the field has physical reality. Electromagnetic waves, like light or radio waves, are ripples in that field, and they physically carry momentum.
So light carries momentum.
Absolutely. When a flashlight shines on a wall, the particles of light photons have zero mass. But they absolutely have momentum. They are bombarding that wall, exerting a microscopic physical push. With delicate enough instruments, you can actually measure the physical pressure of a beam of light.
That is wild.
So during that delay between the magnets, the momentum was literally traveling through the space in the form of a field pulse. Space held the bag.
That is deeply unsettling, but awesome. Empty space isn't empty.
Not at all.
Okay, what about the absolute opposite extreme? Let's zoom down to the smallest scales possible. Quantum mechanics. The realm where solid particles stop acting like physical marbles and start acting like smeared out waves of probability.
Oh, quantum mechanics is the graveyard of classical physics. Down there, Newton's core foundation force equals mass times acceleration is proven absolutely false. It completely dies.
Why does it die?
Because of Heisenberg's uncertainty principle. In the quantum realm, it is fundamentally impossible to know exactly where a particle is and exactly how fast it's moving at the same time.
Right, they're fuzzy.
Exactly. If you can't precisely define its velocity, how can you possibly calculate momentum as mass times velocity? You can't. The classical equation is completely useless.
But if the equation is useless, how does momentum survive?
Because we shift how we look at reality. Since particles like electrons act as waves, physicists redefine momentum based on the wave itself. Instead of mass and speed, momentum in the quantum world is determined by the wavelength.
The physical distance between the crests of the wave.
Yes. The shorter the wavelength, the higher the momentum, measured in waves per centimeter.
So even though Newton's specific math gets thrown out the window and particles act like ghostly vibrations, the fundamental concept still works.
It works perfectly. When a quantum wave interacts with another quantum wave, the total sum of their wave numbers before the interaction perfectly matches the sum after. The conservation of momentum survives intact. It is one of the only classical rules that makes it out of the quantum fire completely unburned.
Let's bring this all together. We started this deep dive because we couldn't possibly calculate the chaotic collisions of 100 million billion gas molecules in a space the size of a pinhead.
Right.
We needed a shortcut. And we followed that shortcut, that cheat code of the cosmic ledger, from explosive, frictionless air tracks through mental car rides that bend our perspective, all the way to rockets recoiling through the dead vacuum of space.
And we proved that whether you are warping mass near the speed of light, hiding energy in invisible fields, or replacing physical matter with quantum waves, the universe always balances the books. The conservation of momentum is the unbreakable rule.
So the next time you watch a chaotic event in everyday life, maybe it's a messy car crash, or the chaotic break of the balls in a game of pool, or honestly, just turning on a flashlight, remember that you are witnessing that invisible ledger balancing itself in real time down to the tiniest subatomic decimal point.
It gives you a profound appreciation for the massive hidden order running silently beneath all the chaos of everyday life.
It really does. Which leaves you with one final thing to ponder as you go about your day. We just learned that light itself and the invisible electromagnetic fields around us can carry tangible physical momentum without having any mass.
Mm-hmm.
So consider the Wi-Fi signals, the radio broadcasts, the thermal radiation, and the light bulbs around you.
Mm-hmm.
Just how much hidden physical momentum is actively passing through the empty air in the room you are sitting in right now, just waiting to crash into something.
Mm-hmm.
You might know the cheat code, but the game is infinitely deeper than it looks.
If you slide like a perfectly tuned, insanely complicated Rube Goldberg machine 10 feet across your living room, you expect it to still work.
Oh, absolutely.
You know, you've got dominoes perfectly spaced, marbles rolling down little ramps, a tiny catapult that launches a ping pong ball into a bucket. It runs flawlessly.
Right. It's a perfect system.
Yeah, so you carefully slide the whole table over, you set off the first domino. It's common sense that it's going to work exactly the same way. I mean, the universe doesn't care where you're standing.
Exactly. But when physicists actually sat down to mathematically prove that the rules of reality don't break when you move or, when you tilt your head, they realized our standard math was entirely broken.
Welcome to the deep dive. We've got a fascinating stack of notes to unpack with you today, all centered around Chapter 11 of the legendary Feynman Lectures on Physics.
And for anyone listening who loves those massive, mind-expanding conceptual shifts, but maybe dreads getting bogged down in pages of dense, jargon-filled equations, this specific material is a goldmine.
It really is.
The entire chapter is dedicated to a concept called vectors, which I know might bring back some traumatic memories of high school geometry.
Oh, definitely. The word vectors just sounds like a dry, tedious math lesson involving graph paper and protractors. But diving into these notes, you quickly realize this isn't just about math at all.
No, not at all.
It is a profound exploration of a deeply philosophical and physical concept, which is the fundamental symmetry of the universe.
Right. And before we can even touch the concept of a vector or why they were invented, we have to establish what physicists actually mean when they use the word symmetry.
Okay, lay it on us.
So Hermann Weyl, the great mathematician, provided a beautiful, highly workable definition that Feynman relies on here. Symmetry basically means you can subject something to a certain operation, and it appears exactly the same afterward.
Let's visualize that for a second. Imagine you have a perfectly smooth, unpainted, perfectly round vase sitting on a table.
Okay, I'm picturing it. If you close your eyes and I spin that vase 180 degrees on its vertical axis, and then you open your eyes well, you wouldn't be able to tell I did anything. It looks utterly identical.
Exactly. That operation, the rotation, reveals the vase's symmetry. And Feynman takes that intuitive geometric idea and scales it up to the very laws of physics themselves.
Right.
Let's go back to your Rube Goldberg machine. If we build that machine with all its bouncing balls and interacting forces, and then we build an exact duplicate right next to it, what we would formally call a lateral displacement or a translation in space, will they act exactly the same? We assume yes.
Assuming, of course, that we didn't accidentally build the second machine inside a wall.
Which sounds like a silly joke, but it's actually the most crucial caveat in all of physics.
Yeah.
When we say the phenomena will be the same, we mean we have to duplicate or move all the relevant influences. If your second machine is hitting a wall, or if it's placed over a powerful electromagnet you didn't know was buried under the floorboards, it obviously won't act the same. Right, so if the laws of physics ever seem broken in an experiment, it usually just means we missed an outside force.
Precisely.
We can unpack this with a specific thought experiment from the text. Feynman introduces us to two observers to help us visualize this translation in space. We'll call them Joe and Mo.
Classic Joe and Mark.
Right. So Joe sets up his coordinate system, his imaginary three-dimensional grid of X, Y, and Z axes, with himself sitting right at the origin, the absolute 0 point.
Okay.
Mo sets up an identical parallel coordinate system, but he is standing some distance away. He's offset along the x-axis by, say, 10 feet.
So they're looking at the exact same physical event, maybe a particle accelerating through the room, but they are measuring it from different starting points.
Exactly.
If Joe says the particle is at position X, Mo says it's at position X minus his 10-foot offset.
But the profound part is what happens when they measure the forces acting on that particle. They measure the exact same thing.
Yes, they do.
And we can think about this physically without getting lost in the calculus. Mo is standing 10 feet away from Joe. That 10-foot gap isn't growing or shrinking. It is static.
That static nature is everything. Joe writes down Newton's second law, right? Force equals mass times acceleration. Now, Mo wants to write down his version.
Right.
Acceleration is all about the change in motion. It's the rate of change of the velocity. Because Mo's 10-foot offset is constant, it has no rate of change. It completely vanishes from the math when you calculate the acceleration.
So the math proves what our gut tells us, which is that a static 10-foot offset doesn't create phantom forces.
Exactly.
Mo's acceleration is completely identical to Joe's acceleration. And since they agree on the mass of the particle and they agree on the forces pushing it, Mo's equation looks absolutely identical to Joe's.
Which gives us a remarkably democratic view of the universe. Every single point in space is as good as any other point for writing the laws of physics. We just proved that the universe has no definitive center.
Wow, yeah. There is no master origin point that governs reality.
Exactly.
It's like moving your entire desktop computer from the left side of your bedroom to the right side. As long as you plug it into the wall, as long as you include the essential power source, the relevant influences your software runs exactly the same.
The computer code doesn't care where the desk is.
Right. The laws of physics are symmetrical for translational displacements.
Moving things side to side is the easy part, though. Feynman doesn't let us stop there. What happens if we change the direction of our axis?
You mean like, does that Rube Goldberg machine still work the same if we build it on a tilt? If we prop one side of the table up by 30 degrees?
Yeah, exactly.
And then my instinct says no, the marbles are going to roll backward.
And Feynman throws a brilliant historical counterexample at us to test this exact intuition. He uses a grandfather clock.
Oh, this part of the text is fantastic. If you take a grandfather clock, which works perfectly standing upright, and you tilt it sideways, well, the pendulum just falls against the wooden case and it stops ticking.
Right. The machine completely fails.
So the immediate question is, did we just break physics? Are the laws of the universe not symmetric when things rotate?
It certainly looks that way at first glance, right?
Yeah.
The operation of tilting it changed the outcome. But we have to remember our caveat about building the machine inside a wall.
Ah.
We forgot an absolutely essential, unseen outside influence in our system. What is actually making that pendulum swing in the first place?
Gravity. The mass of the Earth pulling down on it.
Exactly. The brass machinery of the clock is only a tiny fraction of the total system. The entire Earth is pulling on that pendulum. To truly test rotational symmetry, we can't just tilt the wooden box.
We would have to tilt the entire Earth along with it.
Right, which is a bit outside the scope of a standard laboratory experiment.
Just slightly, yeah.
But Feynman gives us the perfect mental workaround to strip the Earth out of the equation. Take that pendulum clock into deep space, onto a satellite orbiting the planet, where there's no effective gravity pulling it in one specific direction.
Oh, right. It won't tick when it's upright, and it won't tick when it's tilted. The behavior is exactly the same.
Exactly. Or take it to Mars. It will tick at a different rate because Mars has less mass, but again, tilting it relative to Mars's surface will stop it in the exact same way.
So the asymmetry isn't in the fundamental laws of physics. The asymmetry is in the local environment we forgot to include.
Spot on.
Yeah.
If we account for everything, the law should be rotationally symmetric. So let's bring our observers, Joe and Mo, back into the picture to prove it mathematically.
Okay, so this time, they are standing in the exact same spot. They share the same origin point. But Mo has rotated his coordinate axis by some angle. Let's call it angle theta. Essentially, he's looking at the world with his head tilted to the side.
And this is where the standard math we use completely falls apart into a nightmare of bookkeeping.
A total mess.
Right, to translate Joe's measurements into Mo's measurements now, you can't just subtract a simple 10-foot constant anymore. You are forced to use complex trigonometry. Because Mo's grid is tilted, his new x-coordinate is a messy mixture of Joe's x and Joe's y.
Ugh.
You have to multiply Joe's measurements by the cosine and the sine of that tilt angle, theta.
And when Mo tries to write down Newton's laws now, he has to calculate the acceleration by taking the derivatives of those massive jumbled sine and cosine equations.
It is an incredibly tedious, painful mathematical burden. You have all these terms expanding across the chalkboard. Now, eventually, it does work out.
Right, the left side of the equation and the right side ultimately match up.
Yes, proving that force still equals mass times acceleration regardless of the tilt. But the sheer exhaustion of proving it every single time you want to analyze a rotating system is unsustainable.
Because physicists despise doing tedious bookkeeping every single time they want to tilt an experiment.
They really do.
They realize they either had to do exhausting trigonometry every time Mo tilted his head, or they had to invent an entirely new mathematical language, a language where the physical symmetry of the universe was built in automatically.
And that language is vectors.
The grand solution.
Yeah.
But we need to clearly define our terms here, because the terminology is the key to understanding the magic.
Absolutely.
First, the text talks about ordinary, undirected quantities, things that just have an amount. These are called scalars.
Think of scalars as just a magnitude. The textbook gives a wonderfully folksy example to ground this, which is the number of potatoes in a sack.
I love that one. If I have a sack of 50 potatoes, it doesn't matter if I point the sack north-south or turn it completely upside down. It's still exactly 50 potatoes.
Right. The tilt doesn't change the reality of the amount.
Temperature is another great one. It's 70 degrees in this room. The temperature isn't pointing towards the ceiling.
Exactly. Then you have directed quantities. These are the physical properties where which way they point is just as critical as how much there is. Velocity is the classic example. You need to know a body is moving at 60 miles per hour, but you also absolutely need to know if it's heading north toward the city or south toward the cliff.
Momentum, force, and physical displacement, which the text beautifully calls a step in space. These are all directed quantities. These are vectors.
Yes.
Now, hold on. Let me push back here for a second and play devil's advocate. I want to make sure the listener is completely clear on the strictness of this definition.
Sure, go ahead.
The text says a vector can be represented by three numbers, an x, a y, and a z component. So if I just grab any three random numbers about myself, say my shoe size, my height, and my weight, does that collection of three numbers count as a vector?
Oh, no, not at all. Feynman is remarkably strict about this trap. Not just any three numbers make a vector.
Right.
To be a true vector in physics, those three numbers must be tied to a coordinate system in a very specific, almost magical geometric way.
Wait, I think I see it. If Mo tilts his head 30 degrees, my shoe size doesn't mathematically mix with my weight. They don't rely on trigonometry to maintain a physical reality. They don't transform at all.
You've got it. A vector isn't just a list of numbers, it's a geometric relationship. If you physically rotate the coordinate system, the three components of a true vector have to revolve and mix into each other by the exact same mathematical rules as a physical step in space does.
Wow, okay.
Your height and weight don't transform together in sync with the geometry of space. A true vector's components do.
And because of that perfect geometric syncing, we can introduce the magic symbol. The little arrow physicists draw over a letter, like a V for velocity, with a tiny arrow pointing right over the top of it.
Yes, that little arrow.
That arrow is essentially a declaration of independence from Joe and Mo. It says, this represents the actual physical motion, independent of whatever arbitrary grid we use to measure it.
The universe doesn't care about our arbitrary XYZ grid. The vector symbol captures the objective reality of the physical push, or the physical motion, without us having to constantly write out the separate x, y, and z equations with all those terrible sines and cosines.
So clean.
One simple vector equation, like force vector equals mass times acceleration vector, is actually three incredibly complex equations disguised as one elegant truth.
So vectors give us a foolproof, elegant way to track things moving through space. But that raises a new problem. How do we actually use this language to describe changing reality? We have to be able to do algebra with these arrows.
Vector algebra is incredibly visual, which makes it very intuitive once you grasp the rules. If you want to add two vectors together, say you take one step in space and then another step in a different direction, you just visually place the tail of the second vector onto the head of the first one.
Like drawing a path on a pirate's treasure map. You draw the first arrow going north, then you start the next arrow right where the first one ended, maybe pointing east. The total addition, the final result of those two movements is just a brand new arrow pointing from your very first starting dot straight to your final destination dot.
And this visual math immediately gives us a handle on velocity. If you track an object's position vector, an arrow from the origin to the object at one moment, and then you check it again a tiny fraction of a second later, the object has moved.
Right.
The difference between those two position vectors, that little step it took, divided by the time it took, is the velocity. So naturally, velocity is a vector.
And if you track how the velocity vector changes over time, you get the acceleration vector. But here is where it gets
Oh,
dangerous.
yeah, it does.
Feynman highlights a massive conceptual trap in the sources that trips up almost everyone when they first visualize this. It's regarding acceleration on a curved path.
This is a classic stumbling block. Our intuition completely betrays us here.
Imagine you are watching a car move along a curved path, like a winding mountain road. At instant 1, it has a velocity, we'll call it velocity 1, and it's an arrow pointing straight ahead, perfectly tangent to the curve at that spot.
Okay, got it.
A tiny moment later, it's further down the road and the road has turned. So now it has velocity 2, an arrow pointing in a slightly different direction because of the turn. We know acceleration is the change in velocity.
So mathematically, we need to subtract velocity 1 from velocity 2 to find that change.
As a visual learner, my immediate instinct is to look at the winding road, see the tip of the velocity 1 arrow pointing out into space, see the tip of the velocity 2 arrow further down the road, and just draw a straight line between their tips right there over the pavement. That line must be the change in velocity, right?
And Feynman practically jumps out of the page to warn against this. You cannot do that. It is completely meaningless to subtract vectors when they're sitting at different physical locations in space like that.
It's a massive trap.
The absolute golden rule of vector subtraction is that you can only find the meaningful difference between two vectors when their tails are in the exact same place.
Right, so you have to mentally pluck the velocity 1 arrow and the velocity 2 arrow off of that winding mountain road. You pull them into a brand new empty space, and you stick their tails together at a single shared origin point.
Exactly. And when you do that, you see them fanning out from the same starting dot, like hands on a clock. Now, if you draw an arrow from the head of velocity 1 to the head of velocity 2, you have found the true change in velocity. You have found the actual acceleration vector of the car.
What's fascinating is that when you look at that true acceleration vector on a curve, it naturally breaks down into two distinct physical parts, two components that we feel in our bodies every day.
Right. One component of that acceleration is parallel to the path the car is taking. That part is simply the change in speed.
Okay.
It's what pushes you back in your seat when you press the gas pedal, or throws you forward against the seatbelt when you brake. The math for that is just the change in speed over time.
But the other component is completely perpendicular to the path. It is pointing at a perfect right angle to the way the car is moving, pointing inward toward the center of the curve.
And that component represents the change in direction. This is profound. Even if your speedometer reads a constant, steady 60 miles per hour, if you are turning a corner, your velocity vector is changing direction.
I see.
Therefore, you are accelerating.
Yeah.
And the map for this perpendicular acceleration is the velocity squared divided by the radius of the curve.
Which completely explains the physical sensation of taking a tight curve at high speed. It throws you against the side of the car door so violently because you need a massive amount of perpendicular acceleration to change your direction that quickly.
Exactly.
The tighter the curve, the smaller the radius, the bigger that inward acceleration has to be.
It perfectly described the physical reality we experience in the passenger seat,
Yeah.
all decoded through the simple geometry of arrows.
So vectors give us a flawless way to track things moving and turning through space. But that raises our final and perhaps most interesting problem. Some fundamental things in the universe don't have a direction. How do our directional arrows account for the directionless reality of the universe?
This is one of the most powerful concepts in the entire chapter. It starts with a simple, unifying observation about distance. We talked about how Joe and Mo might completely disagree on the X, Y, and Z coordinates of a specific point because Mo's head is tilted. Their individual numbers are a mess.
Right, Mo is dealing with his trigonometry nightmare.
But if they both use their messy numbers to calculate the actual physical length of that step in space, the straight line distance from the origin to that point, they will always arrive at the exact same final number.
Wow, okay.
The math is just the three-dimensional version of the Pythagorean theorem, which is x squared plus y squared plus z squared. That total physical length is invariant. It is an objective truth that does not change no matter how you rotate the axes.
So we took a vector, a step in space, which inherently has a direction, and by multiplying its components by themselves and adding them up, we produced a scalar, a pure number with no direction that every observer in the universe agrees on.
And this specific mathematical operation has a name. It's called the scalar product, or more commonly, the dot product. It takes two vectors, interacts them, and produces a single invariant directionless number.
The math can sound abstract, but we can visualize the dot product geometrically. It is essentially asking a simple question: how much of vector A is aligned with vector B?
That's the perfect way to conceptualize it.
If you have vector A pointing straight out and vector B is pointing off at an angle, you are finding out how much of B is casting a shadow perfectly along A. You multiply the length of A by the length of B by the cosine of the angle between them.
Which means if they're pointing in the exact same direction, the angle between them is 0. The cosine of 0 is 1, so it's just their full lengths multiplied together. They are in maximum alignment.
But if they're perfectly perpendicular at a 90-degree angle to each other, how much do they align? The shadow disappears.
Right.
The cosine of 90 is 0, so their dot product is 0. They share absolutely no direction.
Now, why do we care about shadows and cosines? Because this mathematical trick is how we define the deepest and most fundamental concepts in all of physics. Think about energy.
Okay.
Energy does not have a direction. You don't have 10 joules of energy pointing north. It's just an amount.
But kinetic energy, the energy of motion, depends on velocity.
Yeah.
And we just established that velocity definitely has a direction.
And how do we resolve that paradox? The dot product. Kinetic energy is simply 1/2 the mass times the dot product of the velocity vector with itself.
That is brilliant.
The dot product perfectly strips away the direction, it removes the spatial orientation, and leaves us with pure invariant objective energy.
Another great example from the text is work. In physics, work is defined as the force you apply to an object, multiplied by the distance you move it. Both force and displacement are vectors. They point somewhere. But work is a scalar. It's just a raw amount of energy transferred.
Work is simply the dot product of the force vector and the displacement vector. You only get work done for the part of the force that actually aligns with the direction the object moved.
Right.
If you carry a heavy box across the room, your force is pushing up against gravity, but your displacement is horizontal. They're perpendicular. The dot product is 0. In physics terms, you did no work on the box.
You build the directionless objective reality out of the directed pieces. It's an incredibly beautiful piece of mathematical machinery.
It really is.
We started this deep dive trying to figure out if moving a Rube Goldberg machine or tilting a grandfather clock breaks the laws of physics, and that simple, almost childlike question forced us to realize that we needed an entirely new language.
We needed vectors to guarantee that our equations stay true no matter our perspective.
I hope this is the ultimate takeaway for you listening. Vectors aren't just tedious arrows drawn on a chalkboard to make high school physics harder. They are the mathematical proof that the universe operates on objective, symmetric rules.
Absolutely.
They ensure that whether Joe is standing up straight or Mo is standing on his head 10 feet away, they both live in the exact same universe governed by the exact same laws.
It is deeply reassuring that reality holds together so perfectly.
It is, but I want to leave you with something to chew on, something to explore on your own that pushes past even Feynman's brilliant explanations here.
Oh, I like where this is going.
We just spent this whole time proving that vectors perfectly describe the symmetric space we live in. But what happens if tomorrow we discover some bizarre new quantum phenomenon or some strange cosmic force at the edge of a black hole that fundamentally doesn't transform symmetrically?
That is the kind of thought that keeps theoretical physicists awake at night.
What if the universe has a hidden tilt, after all, a fundamental asymmetry that our current math just can't see? Would we have to throw out vectors entirely and invent a completely new kind of mathematics just to explain reality all over again?
It definitely makes you wonder if our perfectly tuned Rube Goldberg machine is truly as independent as we like to believe it is.
Until next time, keep questioning your perspective.
You know, when you think about physics, there's this expectation of pristine perfection. Like, we just picture pure mathematics.
Oh, totally. It's really comforting to think that way. We naturally gravitate toward, exact laws and perfect spheres and frictionless vacuums.
Right. You write down this elegant equation on a clean chalkboard, and you just expect the universe to obediently follow those rules.
Well, exactly, because neatly categorizing the universe like that, well, it makes us feel like we actually have a handle on it.
But the second you step off that theoretical chalkboard and into the actual physical world, that pristine math just crashes into reality.
It really does. Suddenly you're dealing with dirt and heat and, atoms vibrating unpredictably.
Which is exactly what we're getting into today. Welcome to this custom deep dive. Our mission today is to explore a genuinely fascinating document, Chapter 12, from Richard Feynman's iconic lectures on physics.
And the goal here isn't to just memorize textbook equations. We're going to completely change how you see the everyday physical world around you.
Yeah, I mean, we're talking about the simple act of sliding a glass across a table or just sitting in your chair feeling the pull of gravity. Okay, so let's unpack this.
Let's do it. By the end of this deep dive, the way you perceive those everyday actions will be completely turned upside down.
Because the central premise here is that physics isn't this flawless, pristine system of exact definitions. It's actually a beautiful, kind of messy series of approximations.
Right. Like,
Yeah.
you're going to understand why two perfectly clean pieces of copper will actually fuse together instead of sliding past each other.
Which blew my mind when I read it.
Oh, it's wild. And you'll see why the feeling of being pushed back in your seat when a car accelerates may be exactly the same thing as the gravity holding you down right now.
Yeah, and maybe most surprisingly, why our basic common sense usually gets the concept of friction just entirely wrong. But before we can even understand specific forces, we have to establish what a force actually is.
And maybe more importantly, what it isn't. Because that distinction is where so many people get tripped up.
Exactly. It's so easy to invent definitions that sound deeply scientific, but actually tell us absolutely nothing about how the universe operates.
The text sets up this brilliant thought experiment to illustrate that exact trap.
Right. The Gorse.
Yes, the Gorse. Imagine we decide to invent a brand new scientific concept, and we call it a Gorse.
Okay.
And we declare that a Gorse is defined as the rate of change of position.
So if you see a bicycle moving down the street, you point it and say, it's being acted on by a Gorse.
Exactly. And if it stands still, there is no Gorse. It sounds authoritative, right? Like a real law of physics. But it's utterly useless.
Because it's a completely circular definition. It predicts nothing.
Right. If two moving objects are about to collide, knowing they have a Gorse tells you absolutely nothing about what's going to happen after the impact.
Which honestly made me look at Isaac Newton's famous second law of motion completely differently. I mean, we all learn F equals ma, right?
Yeah.
Force equals mass times acceleration.
Everyone remembers that from high school.
Yeah, but on the surface, you could argue Newton is doing the exact same thing as the Gorse. He's just defining a force as whatever makes a mass accelerate.
It definitely looks that way at first glance, but the genius of Newton is that F equals ma is not a simple definition. The source material actually describes it as a program.
A program. I want to make sure I'm grasping that. Like, it's a program because it demands a physical cost.
Yes. Think of it like a hunting license.
A hunting license. Okay. So it says if you see an object accelerating, you can't just chalk it up to some mathematical variable. You have to go out and find the physical body nearby causing it.
That is the perfect way to phrase it. Newton is stating that forces have an independent material origin. If there's acceleration, there must be a physical source interacting with the object.
Like another planet, or a magnet, or a stretched spring.
Exactly. He left the specific properties of all those different forces blank for future scientists to figure out, but he established the absolute rule that forces require a physical interaction.
You know, it makes me think of geometry versus physics. Like, if I ask you to draw a perfect circle on a chalkboard, the mathematical formula for that circle is flawless.
Yeah.
But if we go outside and I ask you to draw that exact same circle in the dirt with a stick, the geometry doesn't care about the pebbles or the uneven ground or the mud.
But physics has to care about the dirt.
Right. The pristine math has to constantly negotiate with messy material reality.
And that tension is exactly what the source gets at with the classic chair problem. Philosophers often demand that we define our terms perfectly. They'll point to a chair and say, let's precisely define the mass of this chair.
But a physicist looks at that chair and sees just an absolute nightmare of ambiguity.
Because where does the chair actually end?
Yeah, exactly. Atoms are constantly evaporating off the surface of the wood. Moisture from the air is, like, seeping into the fabric.
Microscopic dust is settling on it and binding with the paint. You can never assign a perfect, permanent mass to a single chair because purely isolated objects just do not exist in the real world.
Everything is a constantly shifting mixture of interactions. So physics handles this by relying on idealizations. We basically draw a mental box around the chair and say, for this experiment, we'll pretend the atoms here are constant.
Right. We knowingly use an approximation so we can make sense of the mess.
And since real-world objects are these messy idealizations, the forces between them are incredibly messy too, which takes us straight into the macroscopic chaos of friction.
Oh, friction is fascinating.
The source material has this great comparison between dragging an object through the air versus dragging it through honey. It just shows how empirical and weird these everyday laws are.
Right, like if you fly an airplane through the sky, the air resistant, the drag increases roughly proportional to the square of the airplane's speed.
But if you slowly drag a metal ball through a vat of honey,
Mm.
the drag is just linearly proportional to the speed.
And the deeper you analyze that airplane moving through the air, the more the simple math falls apart. The coefficient changes based on the wing shape, the turbulence behind the tail, the temperature.
It's just endless variables.
Mm.
Investigating an empirical law closely always reveals that the simple rule is just a rough summary of like a trillion complicated events.
Absolutely. And dry sliding friction is just as wild. Let's visualize that classic physics experiment. You place a heavy wooden block on a flat board and slowly tilt the board up like a ramp.
Until the block finally slips and slides down.
Exactly. We use a specific formula for this. Friction equals the coefficient of friction, which we call mu, multiplied by the normal force.
And the normal force is just how hard gravity is pressing the block down into the board.
Right. When you tilt that board to the exact angle where the block breaks loose, gravity is actually doing two separate things. It's pulling the block down the ramp, fighting the friction, but it's also pulling the block straight down into the surface of the ramp, which creates that normal force.
And the math reveals something amazing here. Because the weight of the block is driving both the downward slide and the inward press, the mass completely cancels out of the equation.
It really does. The coefficient of friction ends up just equaling the tangent of the tilt angle.
Which means, to translate that for everyone, the weight of the block doesn't matter at all. If you have a 1-pound block of wood and a 100-pound block of the exact same wood, they both start sliding at the exact same angle of tilt.
It's so counterintuitive. But we really need to clear up a massive historical misunderstanding about what is physically happening when that block slides.
Oh, the microscopic mountains, though.
Yes.
Yeah.
For a very long time, people assumed friction was purely mechanical. They thought surfaces were covered in microscopic mountains and valleys, and friction was just the energy required to lift the object up and over those bumps.
I am completely guilty of this. I always pictured, like, microscopic jagged teeth dragging over each other.
It's a very intuitive image, but it completely violates the laws of physics.
Wait, why?
Well, if friction were simply lifting a block over tiny mountains, the block would go up the bump, but then it would slide right back down the other side. The energy would balance out. There'd be no net loss of power.
Oh, wow. I never thought of that.
Right. But we know friction consumes immense amounts of energy. It generates massive heat. Just think about rubbing your hands together vigorously on a cold day.
So if it's not microscopic mountains lifting over each other, what is actually happening? Are the surfaces just getting destroyed?
They are essentially tearing each other apart at the atomic level. When two surfaces touch, the atoms on the opposing sides actually cling to one another. They form temporary molecular bonds.
So they're literally sticking together.
Yes. And as you force the block to slide, you are violently snapping those bonds apart. That microscopic tearing causes the atoms to vibrate chaotically, and that chaotic vibration is what we feel as heat.
Which leads to one of the most unbelievable examples in the material, the pure copper experiment. Engineers have these reference tables that list the friction coefficient for copper sliding on copper.
Yes, but the text argues those tables are actually describing something else entirely. When you slide a copper pipe across a copper sheet, you aren't really sliding metal on metal. You are sliding a microscopic layer of dirt and grease and oxidized tarnish over another layer of dirt.
Exactly. And the profound nature of atomic bonds becomes super clear when you remove that dirt. The text explains this experiment where you take two pieces of absolutely pure copper.
You clean them perfectly.
Right. And you place them in a vacuum chamber, baking out every single atom of impurity or gas between them.
And when you finally touch them together, they don't slide at all. The friction coefficient just spikes off the charts. They instantly fuse together.
Because from the perspective of the copper atoms, there's no boundary anymore. Without the dirt to separate them, the atoms have no way to know they're supposed to be two different objects.
That is insane. They just violently bond into one solid, continuous block of copper.
We actually witness a milder version of this destruction in our own kitchens. Think about a glass tumbler sitting on a glass plate. If the plate is dry, the tumbler slides easily because it's gliding on an invisible layer of microscopic grease from our fingers or the air. But if you pour water onto the plate, the water lifts that grease away.
And you get true glass-to-glass contact.
Yes. The molecular bonds between the pure glass surfaces become so strong that if you force the tumbler to slide, the bonds won't cleanly let go. It physically tears microscopic chunks of glass out of the plate. It scratches it.
Wow. So to really wrap our heads around why that copper fuses and why that glass tears,
Hmm.
we have to zoom way in. We have to go from looking at the macroscopic block down to the individual molecules.
Right.
The source material maps out the force between two atoms based on the distance separating them, right? Figure 12.2.
Yeah, so imagine pushing two atoms toward each other. When they're relatively far apart, they experience a weak attraction, pulling toward one another.
And in nonpolar molecules, this attractive force drops off incredibly fast as they separate.
Yeah.
Like inversely is the seventh power of the distance.
Exactly. To put that in perspective, if you just slightly increase the gap between them, the attraction virtually disappears. It's a very specific, steep curve of attraction.
As you keep pushing those atoms closer and closer together, passing a certain point, the interaction violently flips. The curve shoots straight up into a massive repulsive force.
Which is incredibly lucky for us. That sudden, violent repulsion is the only reason our physical world has any structure at all.
Right, because if the atoms in my shoes get too close to the atoms in the floor, they violently push back. It's why we don't fall through the earth.
Exactly. And the most critical point in this interaction is the sweet spot right in the middle. There is an exact, specific distance where the inward pull of the attraction perfectly balances the outward push of the repulsion.
The atoms just lock into a stable resting position where the net force is zero.
Mhm.
And human engineering actually exploits this tiny sweet spot.
Oh, the Johansen blocks.
Yes. The text talks about these. There's these blocks of steel used by machinists, and they're polished so perfectly flat that if you slide them together and squeeze out the air, they hit that exact atomic resting distance.
It's amazing. They lock together tight enough to hold heavy weights, entirely without magnets. Just pure molecular attraction finding that perfect balance point.
But looking at this incredibly complex push-pull curve made me question something I learned in high school. We were all taught Hooke's law for springs.
Sure, F equals kx.
Right. The rule is that the force of a spring is perfectly linearly proportional to how far you stretch it. Pull it 1 inch, it pulls back with 1 pound of force. Pull it 2 inches, 2 pounds.
Right.
But if the actual molecular bonds in the metal are behaving based on this crazy steep curve, is Hooke's law just a lie?
It's not a lie, it's just an approximation. Let's look at that sweet spot again, that resting distance. If you stretch the metal atoms just a microscopic fraction of a hair away from that point, that tiny zoomed-in section of the complex curve actually looks relatively straight. Hooke's law only works if you stay entirely within that tiny, straight-looking section.
So if you pull a metal spring too far, you venture out of the straight line approximation and into the wild part of the curve.
Exactly. The atoms can't maintain the balance, the bond snaps, and your spring is permanently warped. It's just another idealization layered over a chaotic reality.
Okay, so if friction and spring forces are just massive macroscopic summaries of billions of complex molecular interactions, we have to ask, what is actually fundamental? When we strip away all the approximations, what forces are truly at the bottom of the physics toolbox?
Well, the text points to gravity and electromagnetism. These are fundamental because the underlying laws governing them are surprisingly simple. They operate on inverse square laws.
Right, so you double the distance between two charges or two planets, the force between them drops to 1/4 of its strength.
Exactly. It's elegant. But the text also notes that while the law is simple, the math becomes an absolute nightmare the second those objects start moving around.
Which is why physicists developed the concept of a field, right? Instead of trying to calculate exactly how charge A is directly pushing on charge B across a vast distance while both are moving.
We divide the problem. We say charge A creates an electric field in the space around it, and charge B simply reacts to the field at its specific location.
This blew my mind because I always assumed a field was just a mathematical accounting trick, like a shortcut for physicists so they didn't have to do the hard math.
A lot of people think that.
But the text makes a brilliant argument for why fields absolutely physically exist. And it comes down to the speed of light.
Yes, because interactions across space are not instantaneous. If I'm holding an electron here, and you're holding an electron a mile away, they're constantly repelling each other.
Right.
But if I violently shake my electron up and down, your electron doesn't feel that shape immediately. It takes a fraction of a second for the signal to cross that mile.
So during that delay, where is the energy of my shake? It has left my electron, but it hasn't reached yours yet. It has to exist somewhere.
The material offers a profound way to look at this. The field is the physical memory of the universe.
The memory of the universe, I love that.
The field remembers the history of your shake, holding on to that energy and propagating it outward like a ripple on a pond until it finally crashes into my electron.
And to visualize how these fields push things around, the text describes shooting a beam of electrons through a tube toward a glowing screen, kind of like an old television set.
Right. If you put a negatively charged metal plate under the beam, creating an electric field, the negative electrons are repelled. The beam bends up. Very simple.
But then you introduce a magnetic field, like a horseshoe magnet.
And magnetic fields behave completely differently. A magnetic field doesn't just push or pull an electron directly toward or away from the magnet. It exerts a force at a right angle to the electron's motion.
This concept is incredibly difficult to visualize. The electrons are flying forward, the magnetic field is pointing inward, but the force pushes the electrons sideways or up.
Think of it like a spinning baseball thrown through the air. The pitcher throws the ball straight forward. But because the ball is spinning, it interacts with the air pressure around it in a weird way, creating a sideways force.
So the ball curves horizontally.
Right. The magnetic force works somewhat similarly. It takes the forward velocity of the electron in the direction of the magnetic field and generates a push perpendicular to both of them. Turn the magnet 180 degrees, the spot jumps down.
And crucially, if the electron stops moving, the magnetic force completely disappears. It only acts on moving charges.
Exactly.
That is bizarre, but it actually gets even weirder because we've been assuming all these forces have a material origin, atoms or fields or magnets. But the deep dive goes into another category entirely.
Yeah.
Pseudo-forces.
Pseudo-forces are fascinating. What if a force is just an illusion of your perspective?
Right, like the accelerating jar of water. If you push a jar of water across a table so it speeds up, the water inside sloshes toward the back. The surface of the water tilts.
To us, standing in the room, it's obvious what's happening. The jar is accelerating forward, and the water is just trying to stay still due to inertia.
But imagine you were a tiny organism living inside that water. From your perspective, your entire world just tilted. You feel a mysterious, brand new horizontal force pushing you against the back wall.
That is a pseudo-force. It exists entirely because the observer is trying to make sense of the world while living inside an accelerating coordinate system. To make the physics equations balance from inside the jar, the math has to invent a mysterious new force to explain why everything is sliding backward.
And the text drops a massive clue about pseudo-forces. No matter what kind of object is inside that jar, a heavy rock or a light feather, the pseudo-force pushes them back in exact proportion to their mass. They accelerate backward at the exact same rate.
Which is the exact same unique characteristic shared by gravity.
Gravity accelerates all masses equally.
Yes, and this specific clue is what led Albert Einstein to one of the greatest leaps in human thought. He proposed the equivalence principle.
What if gravity isn't a traditional force at all?
Exactly. What if it is a pseudo-force? Einstein argued that standing on the surface of the Earth feeling gravity pull you down is mathematically identical to standing inside a windowless elevator in deep space that is being hauled upward, accelerating at 1g.
There is no experiment you can perform inside that box to prove whether you are feeling gravity or just acceleration.
None.
Now, I immediately hit a wall with this. Because if I am pressed to the floor right now, because the Earth's surface is accelerating upward into my shoes, what about the people in Madagascar on the exact opposite side of the planet?
Right, the Madagascar pushback.
Yeah. Is the Earth accelerating outward into their shoes too? The planet would have to be expanding in all directions constantly like a balloon. It makes no sense.
It's the ultimate logical pushback. If gravity is just the illusion of an accelerating floor, a spherical planet creates a massive contradiction. Einstein realized that to make the pseudo-force theory work, the geometry of the universe itself cannot be a simple flat grid.
He had to warp the coordinate system itself. It can't be Euclidean.
Right. The material uses a brilliant thought experiment to explain this without getting lost in high-level tensor calculus. Imagine a race of two-dimensional beings living on the surface of a giant 3D globe.
Okay, like flat figures on a sphere.
But they have no concept of up or down in the third dimension. They genuinely believe their universe is a perfectly flat, infinite sheet of paper.
Okay, they think they live on a flat plane.
So two of these 2D scientists stand on their equator, a few miles apart, and they both shoot a laser perfectly straight north. According to their flat world physics, parallel lines should remain parallel forever.
But because they actually live on a sphere, As the lasers travel north, the curvature of the globe forces the lines to converge. They get closer and closer together until they cross at the North Pole.
And the 2D scientists look at these converging lasers and think, wow, some mysterious force of attraction must be pulling those light beams together.
That is brilliant. They invent a force to explain the convergence.
Exactly. But there is no force. It is an illusion created by the hidden curvature of the space they are moving through. Einstein concluded that the mass of the Earth actually curves the four-dimensional space-time around it.
So when a thrown ball falls in a parabolic arc to the ground, it isn't being pulled by a magnetic-like attraction.
No, it is just following the straightest possible path through a violently curved geometry. The force of gravity is an illusion of the grid.
It is staggering.
Yeah.
We've gone from the violent, heat-generating atomic tearing of friction all the way to the geometric curvature of the cosmos. But we can't wrap up without visiting the absolute smallest scale known to physics.
We have to talk about the nucleus.
Because deep inside the atoms that make up that sliding block in this curved planet, there is a glaring contradiction. We established that fundamental forces like electromagnetism are powerful and follow simple rules, like charges repel. Well, the nucleus of every atom is packed tight with positively charged protons. By all the laws of electromagnetism we just discussed, those protons should violently push each other apart. The nucleus should detonate. What is holding it together?
It is an entirely different mechanism called the nuclear force, and it shatters the neat, elegant rules we found for gravity and electricity. It does not follow a gentle, inverse square law.
The source material states it dies off exponentially over a range that is almost impossibly small, like 10 to the minus 13 centimeters.
To put that into perspective, if you scaled an atom up to the size of a massive cathedral, the nucleus would be a tiny fly buzzing in the center. The nuclear force is immensely powerful, easily overpowering the electromagnetic repulsion.
But it only works within the surface area of that tiny fly. The moment a proton moves a fraction of a millimeter outside that boundary, the force drops to zero instantly.
And perhaps the most humbling takeaway from Chapter 12 is that despite everything we've mapped out from fields to curved space-time, the nuclear force remains deeply mysterious.
Even today.
Yes, there is no simple classical equation for it. It involves quantum mechanics, the exchange of exotic particles, and levels of complexity we are still struggling to model perfectly.
This has been a massive journey. I mean, we started by realizing that F equals ma isn't just a definition, it's a program that demands we look for physical interactions.
We saw how pure copper will literally fuse together in a vacuum without dirt to separate the atoms.
We discovered that the magnetic force pushes sideways like a curveball in the wind. We learned that fields aren't math tricks, but the physical memory of the universe holding energy in transit.
And we saw how the inescapable pull of gravity might just be a pseudo-force illusion caused by the curvature of space-time itself.
When you connect all of those profound shifts in perspective, it leaves us with one unavoidable question.
If the solid, everyday push of friction is just an illusion of billions of vibrating molecular bonds, and if the mighty pull of gravity is just an illusion of geometric curvature?
I am bracing myself.
What if the fundamental forces we think we understand today, electromagnetism and the nuclear mysteries, are just the next layer of approximations? What profound illusions are we living inside right now simply because we haven't discovered the proper coordinate system to look from?
I absolutely love that. It makes you realize that the pristine chalkboard physics is just a temporary story we tell ourselves to make sense of the beautiful dirt we live in. I really encourage you to think about that the next time you slide a glass of water across a table. Are you just sliding it? Or are you ripping the universe apart, one microscopic atomic bond at a time? Until next time, keep questioning the world around you.
Imagine a world where you could fly 1,000,000 miles into space, and the gravity of the planet you left behind just never gets any weaker.
Right? It completely defies common sense.
Yeah, or, imagine stepping inside this massive, hollow planet only to find that gravity simply ceases to exist entirely. Like, you're just left floating completely weightless no matter where you move inside it.
I mean, it sounds like science fiction. Right. Or maybe like a broken physics engine in a video game.
Exactly.
But it's actually the exact mathematical reality of how our universe handles energy and mass.
Ah.
It's a reality most of us never see because we rely entirely on our everyday intuition.
Right, because you throw a ball up, it comes down. You push a heavy box, you get tired. It feels really simple.
Yeah, our brains are hardwired for that surface level.
But when you actually look under the hood of reality, nature is secretly running like the most flawless, mathematically perfect accounting system imaginable. A system where not a single drop of energy is ever lost. It's just meticulously transferred from one ledger to another.
Perfectly balanced every single time.
Exactly. And today we are unpacking Chapter 13 of a really foundational physics text to look at that exact ledger. So, welcome. We are taking a deep dive into the laws of work and potential energy.
And we're going to be looking at a lot of specific diagrams from the text, too. Figures 13 to 1 through 13 to 6, which really help visualize these wild concepts.
Yeah, we have the original text, the mathematical proofs, all of it. And we're going to trace this from the simple act of just dropping a ball all the way to proving why perpetual motion machines are mathematically impossible.
Right, which is a huge deal.
And finally, we'll arrive at those mind-bending geometric shapes where gravity stops behaving the way you think it should. So, okay, let's unpack this.
Well, to really grasp the cosmos, I think we have to start with the most basic parlor trick of physics right here on Earth, which is simply an object falling.
Okay, so just dropping something.
Right. When something falls, it has two types of energy at play.
Mm-hmm.
First, there's kinetic energy, which is the energy of motion. Now, we don't need to get bogged down in the rigid formulas today. Thank goodness.
But essentially, this energy is tied to the object's mass and its speed. So, as it falls, it speeds up, meaning that kinetic energy goes up.
Makes sense.
But it also has potential energy, right, which is the energy of its height.
Yeah.
As it falls, its height decreases, so its potential energy goes down.
You know, I always picture this like a bank account.
Oh, I like that.
Yeah. So you have your checking account. That's your kinetic energy, right? The motion you are actively doing right now.
Yeah.
And you have your savings account, your potential energy, which is the stored up height.
Right, exactly.
So when the ball falls, it is basically just transferring funds directly from savings into checking.
That's a great analogy. And just like a perfect bank transfer, there are absolutely no transaction fees here.
No hidden physics taxes.
None at all. If you measure the exact rate of change of the kinetic energy over time, it perfectly mirrors the negative rate of change of the potential energy.
Oh, wow.
Yeah, if one account goes up by 50 units, the other goes down by exactly 50 units. The total net worth of the system remains absolutely constant. Okay, so we know what happens when you drop something straight down. But, looking at figure 13 to 1 in our sources, it shows an object moving on a frictionless curve instead.
Right. A slanted, curved path.
So what if the path isn't a straight line? Like if I slide down a crazy, twisting, winding, frictionless slide, does my final speed at the bottom still only depend on my starting height?
Actually, yes.
Wait, really? Are you telling me the physics ledger completely ignores all the horizontal twists and turns I took to get to the bottom?
It absolutely ignores them. It comes down to this concept called the tangential force.
Okay, what is that?
Well, it's the component of force that's actually pushing you in the exact direction you are moving. See, gravity is always pulling straight down toward the center of the Earth.
Right, straight down.
So when you are on a slanted or curving part of the slide, gravity isn't actually pushing you forward along that horizontal curve. It's really just pulling you down against the track.
Oh, I see.
Yeah, so the horizontal distance you cover doesn't contribute to the speed you gain from gravity at all. The rate at which you gain kinetic energy is strictly tied to the rate at which you are losing vertical height.
So the horizontal movement is basically a distraction. The universe only cares about the vertical drop when it comes to that gravity accounting book.
Precisely. But since we just established that only the force applied in the actual direction of motion matters, we really need a way to formalize that rule, especially for objects moving in full three-dimensional space.
Right, because the real world isn't just a 2D slide.
Exactly. And physicists use some very specific terminology here that differs from how we use the words in everyday life.
I'm assuming we're talking about power and work, because I know that those words get thrown around a lot in Chapter 13.
Yes. So in physics, power is the force acting on an object multiplied by the velocity of that object. But it's a specific kind of mathematical multiplication called a vector dot product.
A dot product. Okay, let's break that down for people who haven't taken a math class in a while.
Sure. It basically means you only multiply the portion of the force that perfectly aligns with the direction the object is already moving.
Okay, so if a force is pushing sideways relative to the way I'm already moving, it doesn't count towards the power.
Exactly. It has to be in the direction of motion. And work is what happens when you let that power act over a distance. So work is the integral or the accumulation of the force applied along the path of motion.
And we measure work in Newton meters, right? Which physicists usually call joules.
Nope, joules. And power is simply the rate of doing work. So joules per second, which we call watts.
Wait, watts? Like a light bulb?
Exactly like a light bulb.
You know, our text brings up a really tangible example of this with the electric company. Like, when you look at your utility bill and you pay for kilowatt hours, you are quite literally buying work.
Yeah, you really are.
Because 1 kilowatt hour means 1,000 watts applied for 3,600 seconds. So you are paying for 3.6 million joules of physics work.
It's a very direct, real-world application of the concept. But, the rigid definition of work, that strict requirement for the force to be in the direction of motion, it leads to some very counterintuitive situations.
Okay, let me test this then. Imagine you are helping a friend move.
Uh-oh. Always a bad idea.
Right. So you pick up this incredibly heavy box of books and you walk perfectly horizontally across a room.
Okay, I'm picturing it.
Your arms are shaking, you are sweating, you are definitely exerting a massive upward vertical force just to hold that box against gravity.
Definitely.
But your movement is horizontal. Because your upward force isn't in the direction of your horizontal motion, are you technically doing zero work on the box in the physics sense?
As frustrating as it sounds to your shaking arms. Yes.
You're kidding.
Nope. You're doing zero physics work on that box.
Yeah.
The force you're applying is vertical, but the motion is horizontal. They're at a perfect 90-degree angle to each other.
So no dot product.
Right. Therefore, the transfer of energy to the box is zero. Now, of course, your muscle fibers are doing biological work internally, burning calories to maintain tension. But on the box itself,
Nothing.
nothing. The box's kinetic and potential energy relative to gravity haven't changed at all.
That is such a quirky reality. The universe's accounting system doesn't care about your sweat. It only cares about the net change in the object's state along the direction of the force.
It's ruthlessly efficient.
Okay, so we know how this plays out on Earth, where gravity feels like this constant downward pull. But what happens when we zoom out?
Into space.
Yeah, if we move into space, gravity's force starts changing the further out we go. Our text shows this in figure 13-2, with a small mass falling toward a really large mass.
Right. Out in space, the force of gravity isn't a constant. We know from Newton's inverse square law that the force weakens drastically the further you get from a massive object like a planet or a star.
Because it's spreading out over a larger area.
Exactly. And because the force is constantly changing depending on your distance, our simple potential energy formula, that savings account based purely on height, it has to adapt.
How so?
Well, when you calculate the accumulated work over that changing distance, the potential energy formula becomes reliant on the inverse of the distance, basically 1 over r.
Okay, so the math for the savings account gets a little more complex, but the fundamental rule holds, right? Energy is still perfectly conserved.
Oh, absolutely.
Which, leads us to one of the most persistent myths in science. The perpetual motion machine.
Ah, yes. The impossible dream.
Right. For centuries, people have tried to invent machines that run forever without fuel, and gravity always seems like the ultimate free battery because it's this invisible force that never turns off.
It's incredibly tempting to look at a gravitational field and think you can extract endless energy from it.
So let's build a thought experiment based on the text. Figure 13-3 talks about this. Imagine we build a massive closed-loop track in space around a planet. And we want a track designed specifically to trick gravity into speeding us up forever. So picture a jagged staircase-like path.
A staircase in space. Got it.
Yeah, it has radial lines where you drop straight down toward the planet and then sweeping circular arcs that curve horizontally around the planet.
Okay, so moving in and out and then moving side to side.
Exactly. The idea is we drop a ship down a steep radial slope to gain speed, then we coast along an arc, pull it back out, and try to arrange the whole path so that when we get back to the exact starting point, the changing gravity gave us a net speed boost.
I see where this is going.
Right, because if we come back faster than we left, we can just go around again, getting faster and faster forever. Free energy.
Well, let's run that through the physics work accounting ledger we just established.
Okay, ruin my dreams. Let's hear it.
Sorry. So when the ship moves along those circular arcs, its motion is perfectly horizontal, right? It's perpendicular to the pull of gravity, which is pulling straight in toward the planet.
Oh, it's exactly like me carrying the heavy box of books across the room.
Exactly like that. Zero work. Gravity isn't adding or subtracting any energy on those sweeping arcs.
Okay, so the arcs do nothing. What about the radial lines? Dropping straight in or pulling straight out?
Well, when you drop in towards the planet, gravity does positive work. It speeds you up.
Okay, good.
But when you climb out away from the planet, you do negative work against gravity.
Mhm.
It slows you down. And here is the catch. If you start at point A and eventually return to point A to close the loop, the total distance you moved inward must perfectly equal the total distance you moved outward.
Because you have to get back to where you started.
Precisely.
So the positive work you gained falling in is perfectly canceled out by the negative work you paid climbing back out.
Yep. The total work done going around that entire closed loop is exactly zero. You arrive back with the exact same kinetic energy you left with. No free lunch.
But wait, here's where it gets really interesting. I can see how a jagged staircase track cancels itself out because the in and out parts are so clearly defined.
Sure.
But what if the track isn't jagged? Our text brings this up in figure 13-4. What if I build a perfectly smooth, beautiful elliptical orbit? No sharp angles, just a continuous changing curve. Doesn't a smooth curve change the math so it's not a simple one-to-one cancellation?
That is a brilliant pushback, and it's something physicists actually had to prove mathematically.
Because it feels like a loophole.
It does feel like a loophole.
Yeah.
But you can take any smooth, continuous curve in space and zoom in on it with calculus. If you magnify a tiny section of a smooth curve, you can approximate it as a series of microscopic sawtooth jiggles.
Sawtooth jiggles.
Yeah, billions of tiny little radial and circumferential steps, basically microscopic stairs.
Oh, wow. So you just break the smooth curve down into an infinite number of tiny staircases.
Yes, and we already proved that the work done on the circular part of any step is zero, and the inward and outward radial steps inevitably cancel each other out by the time you close the loop.
So it scales up perfectly.
Exactly. If the work is zero for the jagged path, and the smooth path is mathematically just an infinite number of tiny jagged paths, well, the work is zero for the smooth path, too.
The universe's accounting system is completely airtight.
It really is. Perpetual motion from a gravitational field is mathematically impossible.
Nature really doesn't leave loopholes. So, okay, we've talked about falling objects and two masses interacting in space. But gravity isn't the only force that acts this way, right?
Not at all. The text notes that this conservation rule applies broadly. Think of a mass on a spring.
Okay.
When you stretch a spring, the restoring force gets stronger the further you pull it. The potential energy is stored in the tension of the spring. And as the spring snaps back, that potential energy becomes kinetic energy, and vice versa.
Right, so in a perfectly frictionless environment, it would just bounce back and forth forever, perfectly conserving energy. Okay, so a spring is a two-part system. A planet and a sun is a two-part system. But our actual solar system isn't two parts. We have the sun, 8 planets, dozens of moons, asteroid belts. I mean, it's a massive multi-body problem.
It gets very complicated very fast.
So how does the universe balance the books when dozens of objects are all pulling on each other at the exact same time?
To find the total energy of a complex system like our solar system, which is equation 13.14 in the text, for anyone following along, physicists do it systematically.
Okay, walk me through it.
First, you sum up the kinetic energy of every individual moving particle. That part is straightforward.
Just add up all the moving pieces.
Right. But then, for the potential energy, you have to calculate the gravitational potential energy of every single unique pair of particles in this system.
Every single pair. So like Earth and Mars, Earth and Venus, Mars and Venus.
Every unique pair. You calculate the potential energy between them as if the rest of the universe didn't exist, and you just add it to the running total.
You know, it's kind of like building a massive, intricate Lego set.
How so?
Well, imagine bringing the planets into the solar system from infinity, one by one.
Okay, it's like this.
You bring the sun in. It's the first piece, so it takes zero work, or there's nothing pulling on it yet.
Right.
Then you bring in Jupiter. Jupiter interacts with the sun, so you calculate that connection. Then you bring in Earth. Earth interacts with Jupiter, and it interacts with the sun, so you calculate those two connections independently.
Yes.
You just keep adding up the work of all those individual pair connections as you build the entire system piece by piece.
That is a perfect visualization of the principle of superposition. Gravity obeys this principle, meaning we can break incredibly complex webs of interacting forces down into simple independent pairs and just sum them up.
But wait a second. Doing this Lego building math for a handful of planets is one thing, but planets aren't just tiny dots, are they?
No, they're not.
They are massive physical objects made of billions, trillions of atoms, tracking every single atomic Lego piece pair between, say, the Earth and the Moon. That would be mathematically impossible. It would take forever.
Oh, absolutely forever.
So how do physicists actually calculate the gravity of giant, continuous solid shapes without tracking every single atom?
Well, that is the exact problem early physicists faced. They needed a way to calculate the gravity of continuous mass distributions. And when they developed the calculus to do this, the math revealed behaviors that the author of our text literally calls miracles.
Oh, I love that. Let's get into the miracles.
Let's do it.
The first extreme scenario the text explores in Figure 13-5 is an infinite flat plane of matter. So just a solid sheet of rock that goes on forever in every direction. Imagine an endless flat Earth.
Right. Now, what is the gravitational pull of that infinite sheet if you were floating, say, a few miles above it?
I would assume it pulls you down.
It does. But the math reveals a shocking truth. The gravitational pull of an infinite flat sheet is completely independent of distance. It never weakens.
Wait. If I fly a million miles away from an infinite flat planet, gravity doesn't get weaker. That feels impossible. It violates everything we just said about the inverse square law. The further you get, the weaker the force should be.
It is incredibly counterintuitive until you visualize the geometry. So let's say you were hovering just 1 inch above this infinite sheet.
Okay.
The mass directly below you is pulling you down very strongly. But the mass a mile to your left or a mile to your right is pulling you at a very shallow horizontal angle.
Right.
Most of that sideways pull just cancels itself out. Left pulls left, right pulls right, leaving only the weak downward component from those faraway pieces.
Okay, I'm picturing that the stuff far away is pulling me sideways, not down.
Exactly. Now, fly a million miles away from the sheet. Yes, the gravity from the specific chunk of rock directly below you has gotten much, much weaker because of the distance.
Right.
But look at your field of view. Because you are so far away, the cone of matter that is now pulling at you at a favorable downward angle has gotten massively larger.
Oh, because I'm further away, I can sort of see a huge expanse of the sheet at a steeper angle?
Exactly. The individual pull of each piece of rock gets weaker by the square of the distance, but the sheer area of rock effectively pulling you down increases by the exact same square of the distance.
That is wild.
The weakness of the distance is perfectly countered by the volume of new mass coming into the effective angle. They perfectly cancel out. The force remains totally constant.
That is a stunning piece of geometry.
It really is. And incidentally, this mirrors exactly how electric fields work between two infinitely charged flat plates. The force is constant no matter where you are between them.
Okay, so that's the miracle of a flat sheet. But the Earth isn't a flat sheet, it's a sphere.
Which brings us to Figure 13-6 and the final geometric miracle. A thin spherical shell of mass, basically a hollow Earth.
Okay.
If you are floating anywhere outside that hollow shell, the math gets complicated quickly. The part of the shell closest to you pulls harder, the part on the far side pulls weaker. But when you integrate all the potential energies of all those pieces of the shell,
What happened?
the math perfectly collapses. It acts exactly as if all the mass of that entire shell were concentrated at a single, infinitely dense point dead center.
So treating planets as simple dots in our equations isn't just a convenient shortcut. It is the literal, exact mathematical reality of how spherical mass behaves to anything outside of it.
Yes, exactly. It's not a simplification, it's the truth. But the real magic happens when you move inside the hollow shell.
Okay, I step inside the hollow Earth. What happens?
Inside the hollow shell, the potential energy becomes perfectly constant everywhere.
Yeah.
It doesn't matter if you are dead center or floating 1 inch away from the inner wall.
Wait, constant everywhere?
Yes. And because the potential energy doesn't change from point A to point B, that means it takes zero work to move around. And if there is zero work being done to move you, the net force of gravity is exactly zero. You would float perfectly weightless anywhere inside that hollow shell.
I need to understand the mechanism there, because if I am floating just 1 inch away from the inner wall, shouldn't that massive wall right next to my face pull me toward it?
It does pull you toward it very strongly because you are so close. But turn around and look behind you.
Okay.
You have the vast expanse of the rest of the sphere on the opposite side. Because you are so close to one wall, the cone of shell pulling you from the far side is massive.
Oh, I see it.
Yeah. The huge amount of faraway mass pulling you in one direction perfectly exactly balances the tiny amount of up-close mass pulling you in the other direction.
Mm.
The cancellation is absolute.
It gives you chills when you really think about the precision of it all. I mean, we've gone from dropping a simple ball to understand how potential and kinetic energy trade off.
Right.
We formalized the rigorous definitions of work and power. We debunked the dream of orbital perpetual motion by zooming in on jagged microscopic paths. And we ended up realizing that an infinite sheet has constant gravity and a hollow sphere hides a perfectly zero gravity sanctuary inside.
And, that is the true value of unpacking a text like this deep dive today. You aren't just memorizing definitions, you are acquiring new mental models for how the universe operates. The next time you see a swinging pendulum, or look up at an orbiting satellite, or even just push a heavy box, you won't just see objects moving. You will see the invisible accounting system of energy conservation at play.
It makes the universe feel so deeply ordered, which actually brings me to a thought I couldn't shake while we were looking at these sources.
What's that?
Well, we just established that if you are inside a uniform, hollow shell of matter, the gravitational pulls from all directions perfectly cancel out to exactly zero. You are completely weightless. Well, what does that imply about the gravity of the universe as a whole?
Oh, that's an interesting leap.
If we assume the universe is infinite and uniformly filled with stars and galaxies in every direction, are we effectively floating inside the ultimate infinite hollow shell? Is the background gravity of the cosmos perfectly canceling itself out to zero around us right now?
Now that is a fascinating question to end on.
Something to chew on. Well, thank you for joining us on this deep dive. We hope you walk away seeing the physical world just a little bit differently today. We'll catch you on the next one.
I want you to imagine, just for a second, that you are holding a large, incredibly heavy box of books.
Oh, yeah, like the kind that makes your back ache just looking at it.
Exactly. You've got your arms wrapped underneath it, right?
Yeah.
And you're standing completely still in the middle of a room, but you're sweating. Your arms are physically shaking.
I'm completely exhausted.
Yeah, you're exhausted. But according to the fundamental laws of physics, you are doing absolutely zero work.
Right. It sounds like a trick question, or maybe just a really bad definition. But in the realm of physics, it is entirely accurate. Your body is burning through energy, but physically speaking, nothing is actually being accomplished.
Which is incredibly frustrating if you're the one holding the box.
Oh, absolutely.
But, that discrepancy between what our bodies feel and what the universe is actually measuring, that's the key to completely reconstructing how we think about, well, work and energy, and really the invisible rules that govern everything around us.
Yeah, the fundamental forces.
Right. So today in this deep dive, we are tearing down our basic assumptions. We're going to look at why your shaking arms are doing zero work, and how that exact same principle scales all the way up to calculating rocket trajectories.
And all the way down to the atomic structure of the air you're breathing right now.
Exactly. Our source material today is a classic, Chapter 14 from the legendary Feynman Lectures on Physics. It's this chapter on work and potential energy.
And we're going to do this without getting bogged down in messy chalkboard proofs, which is great. I mean, Richard Feynman himself famously pointed out that a lot of those elegant mathematical proofs you see in textbooks, they're essentially parlor tricks.
Wait, really? Tricks?
Yeah, they're concocted by physicists after the fact to look clean and tidy. But we aren't interested in the trick. We want to understand the underlying relationships, We want to unravel how the universe actually balances its energy checkbook.
I love that. Okay, so let's start with that heavy box. If holding it steady requires no work, how does physics actually define the concept of work? Because, clearly my everyday definition involves anything that makes me sweat.
Right, which makes sense biologically. But in physics, work is defined very strictly as force multiplied by distance.
Okay, force times distance. Sounds simple enough.
It does, but there is a massive caveat that always trips people up. It only counts the component of your force that is applied in the exact direction of the movement.
Oh, the exact direction. Give me an example of that in motion. Let's say I'm pushing a heavy lawnmower across the grass.
Perfect. Yes. So when you push a lawnmower, you are pressing down and forward on the handle, right, at an angle.
Right, leaning into it.
Exactly.
Yeah.
But the lawnmower only moves horizontally across the yard. According to physics, only the forward part of your push is doing actual work. That downward force you're applying, the part that's just mashing the wheels into the dirt, that doesn't move the lawnmower down into the earth.
Hopefully not, yeah.
Right. So the distance moved downward is zero. Therefore, that downward push does zero work. You're basically just wasting effort fighting the solid ground.
Ah, I see. So you have to be moving the object, and you only get credit for the push that actually contributes to that specific direction of movement.
You nailed it.
Which, I guess, brings us right back to the box of books. I'm pushing up against gravity to keep it from falling, but the box is stationary. Zero distance moved means zero physical work.
That is the core of it, yeah.
But I'm still sweating. My heart is beating faster. If I'm doing zero work on the box, where's all my internal energy actually going?
Well, you're confusing physical work with physiological effort. The reason you get tired is due to a sort of biological loophole, a design flaw in human anatomy compared to, say, a clam.
Wait, a clam? Like the seafood?
Yes, exactly, the shellfish. So humans and most animals that move quickly, we use striated muscle, skeletal muscle.
Right.
When you hold that heavy box, your muscle fibers don't just lock into a solid, rigid structure. They operate through rapid, continuous twitches.
Oh, so they're turning on and off.
Constantly.
Yeah.
Your nervous system is firing microscopic volleys of impulses, contracting and relaxing thousands of tiny fibers over and over again, incredibly fast, just to maintain that static position.
Wow. So when my arms start shaking, that's just the fibers getting exhausted and failing to fire smoothly.
Exactly. You're consuming massive amounts of internal chemical energy just to keep that twitching process going.
But the clam doesn't do that.
No, a clam uses what we call smooth muscle. When a clam closes its shell to protect itself, it doesn't use rapid twitches. The muscle physically latches, it sets into place.
Oh, wow.
Yeah, a clam can hold its shell shut against a predator trying to pry it open for hours without expending any significant extra energy.
It essentially turns into a padlock.
Exactly. A clam holding a weight is like a wooden table holding a weight. A table doesn't sweat, right? It just structurally supports the load.
Right, just exists. Which, I mean, raises an obvious question for me. If smooth muscle is so incredibly efficient at holding things, why didn't evolution give humans smooth muscle in our arms? I could hold my groceries all day, like a human bookshelf.
It comes down to speed. Evolution just couldn't figure out how to make a latching, smooth muscle operate fast enough for survival tasks. You know, running, jumping, throwing a spear.
Ah, so we need to be fast.
Right. Smooth muscle is fantastic for an enduring, static grip, but it takes incredibly long to engage and release. Striated muscle is an evolutionary trade-off. We sacrifice static efficiency for explosive speed.
Okay, so we're built to sprint, not to be living furniture. That makes a lot of sense.
Right.
So holding still does no work. But let's look at things that are actually moving. The physics of constrained motion. Say I'm riding in a cart on a roller coaster track.
Oh, constrained motion is fascinating because it introduces forces that look really important but actually do nothing.
Okay, break that down.
So, as your cart flies down a curved slope, gravity is pulling you toward the center of the Earth. But the metal track is pushing back up against the cart, stopping you from plummeting through the support beams.
Right. The track holds me up.
Yeah, that push from the metal is called a force of constraint.
But if we're calculating the work done on the cart, we just ignore the track entirely? Is that because of that directional rule we talked about with the lawnmower?
You got it perfectly. Assuming it's a frictionless track, it only ever pushes exactly perpendicular, so at right angles, to the motion of the cart.
Oh, I see.
It pushes away from the surface while the cart slides along the surface. Since the track's force is at a 90-degree angle to the displacement, it contributes absolutely nothing to the forward movement. It does absolute zero work.
So you only have to calculate the work done by gravity.
Exactly.
Which makes the math so much cleaner.
Right.
I mean, you don't have to factor in every loop and corkscrew of the track pushing against the wheels. You just look at gravity.
And gravity belongs to a very special, mathematically elegant category called conservative forces.
And we should clarify for everyone, there is no political leaning here, right? Conservative in physics means something entirely different.
Right. No politics here. It means it conserves energy perfectly, based on a principle called path independence.
Path independence. Okay.
Imagine you're standing at the base of a mountain, point A, and you want to reach the summit, point B. You could take a direct, incredibly steep path straight up the cliff face. Or you could take a winding, gentle path that circles the mountain 10 times before reaching the top.
So, if the force of gravity is conservative, the total amount of physical work gravity does against me is identical in both scenarios, regardless of the path.
That's the magic of it. Gravity doesn't care about the route. It only cares about where you started and where you ended.
So think of it like taking an elevator in a skyscraper.
Oh, yeah, good analogy.
If I start in the lobby and need to get to the 10th floor, I could ride straight up. Or I could accidentally press the button for the 20th floor, ride all the way up there, realize my mistake, ride down to the 5th floor, and then finally go back to the 10th.
Yeah.
The total energy toll gravity charges me at the end of that ridiculous trip is exactly the same as if I had just gone straight to the 10th floor.
A perfect analogy. Because the downward trip perfectly canceled out the extra upward trip. This property of path independence was a massive breakthrough for physicists.
Because it simplified everything.
Huge simplification. It meant they didn't have to calculate complicated winding force vectors every time an object moved. They could simply assign a baseline energy value to every single altitude. And we call this potential energy.
Potential energy.
Yeah.
So it's essentially an energy bank account based purely on your location.
A bank account with very strict accounting rules? Yes. In a system governed by conservative forces, your total energy, which is your kinetic energy, the energy of motion, plus your potential energy, the energy of position, always remains a constant number.
It never changes.
Right. As you fall, potential energy converts into kinetic. As you climb, kinetic converts back into potential. They just trade back and forth seamlessly.
Wow. Okay, let's scale this up. How does this universal bank account apply to something enormous, like trying to launch a rocket off the Earth?
Well, rocket science relies entirely on this principle. Think about a satellite in a stable, low Earth orbit.
Okay.
To stay up there without falling back into the atmosphere, it needs a specific amount of kinetic energy, which translates to moving at a speed of about 5 miles per second.
Right, so it's essentially falling toward Earth, but moving sideways so fast that it constantly misses the ground.
Exactly. But what if you don't want to orbit? What if your goal is to shoot a probe so far out into space that it completely escapes Earth's gravitational pull? You want to send it to infinity.
Because at an infinite distance, Earth's gravitational grip, and therefore the potential energy influence of Earth, just drops to zero. Yes. To climb completely out of that gravitational well and reach infinity with zero energy left over, you need to start with exactly twice the kinetic energy of a standard low orbit.
Okay, double the energy.
Now, here is where the math gets really interesting. Kinetic energy scales with the square of your velocity. So to double your energy, you don't double your speed, you multiply your speed by the square root of 2.
Oh, wait, the square root of 2 is roughly 1.4, right? So I just need to go 1.4 times faster than orbital speed.
Exactly. Which means if orbit requires 5 miles per second, escape velocity requires about 7 miles per second. Just by knowing that the universal bank account has to balance out to zero at infinity, you can calculate the exact speed required to leave the planet.
That's incredible.
Yeah, you don't need to map the gravitational pull at every single mile along the rocket's flight path. You just balance the initial and final states.
That is such a clean way to view the universe. But I know this doesn't just work on a planetary scale. It scales all the way down to the microscopic level, right? Let's look at something tiny, like 2 oxygen atoms floating around in this room.
The exact same rules of potential energy govern the invisible world. When 2 oxygen atoms are relatively far apart, they actually pull toward each other. They have an attractive force.
Okay.
But if they get too close, their electron clouds overlap and they repel each other violently.
So there has to be a compromise, like a specific distance where the push and the pull perfectly cancel each other out.
We visualize this on a graph as a deep valley or a potential energy well.
Oh, well.
Yeah. The oxygen atoms fall down the sides of this valley and settle right at the very bottom. That bottom point represents the minimum potential energy, and that specific distance is where they naturally lock together.
And when they're sitting peacefully at the bottom of that well, it's just a normal, stable oxygen molecule.
Assuming the room is cold, yes. But if you introduce heat into the room, you are adding kinetic energy to that system. The atoms start to jiggle, they vibrate.
Okay, so they're getting restless.
Right. And as they shake, they're essentially climbing slightly up the steep walls of that potential energy well and then sliding back down. If you crank the heat high enough, adding massive amounts of energy, they will violently shake themselves completely out of the well. The molecule breaks apart into single atoms.
Okay, this brings up a major shift in how physicists talk about the quantum world that I want to ask about. When you start dealing with atoms and subatomic particles, the concept of force, like a literal push or pull, seems to completely vanish from the vocabulary. Why do physicists abandon forces at that level?
Because forces become an absolute nightmare to calculate. A force is a vector. It has a magnitude and a very specific 3D direction.
Right, an arrow pointing somewhere.
Exactly.
Yeah.
And when you have particles exhibiting weird quantum behaviors, mapping precise directional arrows for every interaction completely breaks down. But energy Energy is a scalar. It's just an amount, a universal currency.
But it's just a number.
Yes. It is vastly more accurate to map out those potential energy valleys and hills than to try and draw invisible pushing and pulling arrows. Energy remains a reliable concept even when our classical everyday intuition about forces completely fails.
Speaking of our everyday intuition failing, I want to challenge one of the core rules we just talked about. You stated that gravity is a conservative force, meaning energy is never lost, just traded between kinetic and potential.
That is the rule.
Yes. Well, what about friction? If I take a heavy wooden block and slide it across a hardwood floor, it moves for a few feet and then it stops.
Right.
The kinetic energy of its motion is just gone. It didn't climb a hill, so it didn't gain potential energy. The energy just feels destroyed. That doesn't seem conservative at all.
Okay, this is one of the most profound realizations in modern physics. Feynman makes it very clear in the text. There are no non-conservative forces in nature.
Wait, none. Zero.
Zero. At a fundamental level, all forces are conservative.
But the sliding block, I watched it stop.
Yeah.
The kinetic energy disappeared.
It didn't disappear. It simply vanished from your macroscopic view. Our human eyes are incredibly crude instruments. When that wooden block slides and grinds to a halt, the kinetic energy of the forward motion didn't cease to exist. It transferred into the microscopic world.
Okay.
It shattered into the chaotic, random jiggling of the billions of individual atoms inside the block and the floorboards.
So the big organized movement of the block turned into tiny disorganized movements of the atoms.
Yes, and that internal chaotic kinetic energy is exactly what we measure as heat. Friction doesn't destroy energy, it scatters it.
Heat is just microscopic motion.
Primarily, yes. Consider this analogy. Imagine looking through a telescope at a globular star cluster millions of light years away.
Okay, I'm picturing it.
From that distance, 100,000 stars blur together to look like a single, solid snowball of light drifting slowly through the void.
Just a single glowing object.
Now imagine a massive gravitational event slows that glowing snowball down. From Earth, you might look at it and say, the snowball lost kinetic energy, energy was destroyed. But if you jumped into a spaceship and flew right up to the cluster, you would see that the snowball isn't a solid object at all, it's a swarm. And those individual stars are now zipping around each other frantically. The energy wasn't lost. The organized forward motion of the whole cluster was simply converted into the chaotic internal motion of its parts.
Oh, wow.
The sliding wooden block is doing the exact same thing. The total energy of the universe is a perfectly balanced constant. You just have to zoom in far enough to see where the accounting went.
The universe never loses a penny. It just breaks large bills into microscopic coins.
That's a great way to put it. Which brings us to the final hurdle. If energy is never lost, but it's scattered across trillions of atoms or stars, how do physicists possibly map all of this out? You can't draw a force arrow for every single atom in a floorboard.
No, that would be mathematically impossible.
So they switch from tracking individual force vectors to mapping fields and potentials.
Let's break those down. What is the distinction there?
So a field is a way to describe what's happening at every point in space. Think of a room full of swirling wind. The field tells you exactly which way the wind is blowing and how hard at every single millimeter in the room. It relies on vectors, those arrows with direction.
Mm-hmm.
But a potential simplifies everything. It is a scalar.
I mean, it drops the direction entirely. It's just a raw number.
Exactly. You assign a single number to every point in space representing the potential energy an object would have if you dropped it right there.
So instead of a room full of complicated wind arrows pointing in 3 dimensions, you just have a heat map of numbers.
It's an incredibly powerful simplification. And it reveals some deeply unintuitive properties about gravity. Let's look at the mystery of the hollow sphere.
Oh, this is a fantastic thought experiment from the chapter.
Imagine a massive, perfectly hollow sphere made of incredibly dense lead. If you are floating in space outside this sphere, the gravitational pull behaves normally. As you get closer to the shell, the pull gets stronger, acting almost as if all the mass of the sphere were crushed into a tiny dot at the very center.
Just like Earth pulling on a satellite.
But what happens if we cut a small door and you float inside the empty space of the hollow shell?
Well, let's think through the geometry. If I float perfectly in the center, I'm being pulled equally in all directions by the walls of the shell. So the net force is 0. I just float there.
Right.
But what if I drift off center, like closer to the left wall?
That's the trick. If you move closer to the left wall, the gravitational pull from that left wall gets much stronger because you are physically closer to it. You would expect to be yanked right into the metal.
But I'm not.
Yeah.
Because even though the left wall is closer and pulling harder, I now have a vastly larger amount of the sphere's surface area situated on my right side,
Yeah.
further away. And all that extra mass on the right side perfectly cancels out the stronger pull from the closer left side.
The geometry balances flawlessly, and because the forces cancel out everywhere inside, the potential energy map, that scalar heat map we talked about, is completely flat. The number is exactly the same no matter where you move inside the empty space.
And if the potential energy never changes from point A to point B,
Then the work required to move between those points is exactly zero. And if it requires zero work to move in any direction whatsoever, that means the gravitational force inside a hollow shell is completely unequivocally zero.
that is mind-blowing. You could build a massive lead shell, step inside, and experience total zero gravity, completely shielded from the mass of the shell itself. That's brilliant. But let's say I have this scalar map of flat plains and steep mountains. How do physicists translate that simple map of numbers back into an actual physical force?
They look for the steepness. They measure how rapidly the potential energy number changes as you move. Mathematically, this involves taking partial derivatives. You check how fast the number changes if you take one step north. Then you check the change if you take one step east. Then one step up.
So you isolate each direction one by one.
Right. And when you combine the rate of change in all three directions, you create a powerful mathematical operator called the gradient. Feynman calls it nabla. It looks like a backwards 6.
Okay, let's ground this. If the potential energy field is a topographical map of a mountain range, where the scalar numbers are just the altitude at any given point, the gradient is essentially a mathematical compass.
Ooh, yes.
It doesn't just tell you how high you are. It calculates exactly which direction the steepest part of the hill is and exactly how severe that drop is.
That is precisely how it works. And that steepness is the force. The steeper the hill on your potential map, the stronger the physical push or pull. Force is mathematically defined as the negative gradient of the potential. The compass points down the steepest path, and that tells you exactly where gravity is going to drag you.
So by mapping the altitudes, you get the forces for free.
Exactly. And this mathematical framework isn't just a trick for gravity. It translates perfectly to electrical fields. Imagine a parallel plate capacitor.
Two flat metal plates facing each other, one positively charged, one negatively charged.
Right. Between those plates, there is a constant, uniform electrical field pulling from the positive to the negative. It's like a perfectly steady wind. If you want to grab a positive particle and drive it against that wind, moving it from the negative plate toward the positive plate, you have to do work. You are pushing it up an electrical hill.
And climbing that electrical hill changes the potential energy of the particle.
Yes. In electronics, we just give that potential energy difference a special name, voltage.
Wait, really? So when I buy a 9-volt battery at the store?
A 9-volt battery is just a system that maintains a specific altitude difference or potential difference between its two terminals. The math used to calculate the energy required to force an electron across those 9 volts is fundamentally the exact same math used to calculate the energy required to lift a box of books against the gravity of the Earth.
That is wild.
It's the same universal framework.
It's all just topographical maps of energy,
Okay.
which completely changes how you view the physical world. I mean, we started with a biological illusion, the idea that sweating while holding a box meant you were doing work, when really it was just the inefficient, twitching nature of human muscle-wasting internal energy.
Right, compared to our friend the clam. And we learned that physics only counts movement, and forces pushing sideways against that movement, like a roller coaster, track do zero work.
We discovered the elegance of conservative forces like gravity, how the path doesn't matter, only the start and end points, which allows us to treat the universe like a giant energy bank account of kinetic and potential states.
Yeah, and we saw how that scales from calculating the escape velocity of a rocket to mapping the specific vibrational energy required to rip an oxygen molecule apart.
And we confronted the grand illusion of friction. The realization that energy is never truly destroyed, only shattered into the microscopic chaotic jiggling of atoms that we perceive as heat.
Finally, we saw how physicists tame all of this complexity by dropping messy force vectors and instead painting the universe with scalar fields, simple numbers representing potential energy.
Armed with the gradient, a mathematical compass that measures steepness, they can uncover the hidden rules of everything from the zero-gravity void inside a hollow sphere to the voltage inside a household battery. It is a universe defined not by random chaotic impacts, but by an intricately balanced, perfectly accounted-for exchange of energy.
It really is the ultimate conservation law. Nothing is ever lost. Everything is simply transformed.
Which leaves me with one final provocative thought for you to explore on your own. If every single fundamental force in the universe is perfectly conservative, and if energy is never truly lost, only hidden as scattered microscopic jiggling, imagine the engineering required to reverse that process. Think about driving your car and coming to a hard stop at a red light. The brake pads heat up incredibly fast. All the kinetic energy of your moving car didn't vanish. It shattered into the random thermal vibrations of the atoms in those brakes. But what if you could somehow command all those trillions of scattered, chaotic atoms to suddenly align? What if you could force them to move their kinetic energy in exactly the same direction all at once? Could you theoretically launch a car forward from a dead stop using nothing but the wasted heat of its own friction? The math says the energy is still right there. It hasn't gone anywhere. It's entirely a matter of who is doing the accounting. If you take a piping hot cup of coffee and place it right next to an identical cup of iced coffee, the hot coffee is actually physically heavier.
Yeah, it has more mass, which is just wild to think about.
Right. I mean, you couldn't measure the difference on your kitchen scale, obviously, but fundamentally, physically, the hot one weighs more. And the reason why reveals this completely hidden architecture to our universe that rewrites everything we think we know about speed, time, and reality.
It totally forces us to just abandon our basic everyday intuition. When we actually look at how the universe behaves at extreme speeds, those common sense rules we learn in middle school simply break down.
Which is exactly why our mission today for this deep dive is to thoroughly unpack Chapter 16 of the legendary Feynman Lectures on Physics, Volume 1. We're looking specifically at relativistic energy and momentum.
It's such a great chapter.
It really is. We have the source text, we have the original diagrams, and our goal is to get past those, vague surface-level catchphrases people throw around about Einstein. We want to really understand the actual mechanics of what happens when objects move incredibly fast.
So I think the best place to start is by clearing up a really common misunderstanding. Early on, Feynman takes a swing at what he calls the cocktail party philosophers.
Oh yeah, I love that phrase.
Right. These are the folks who confidently claim that relativity just means, everything is relative or everything just depends on your point of view.
Like it's some sort of subjective philosophy.
Exactly. They treat physics like it's just subjective, arguing that scientists were foolish for ever thinking they could measure absolute motion.
They compare it to that old parable of the blind men feeling different parts of an elephant, right? Concluding that knowing things look different from different angles is some profound philosophical breakthrough.
But Feynman draws a very hard line here. Physics is not about subjective perspectives, It makes precise, testable predictions. Our inability to detect our own absolute uniform motion isn't just a logical puzzle someone solved in an armchair.
It's an actual physical law.
Yes, it is a hard experimental result. It was proven by actually observing the universe, specifically after James Clerk Maxwell formalized electrodynamics.
Let me pause you there and see if I can clarify that distinction, because my own intuition immediately rebels against the idea that I can't tell if I'm moving.
That's a super normal reaction.
Because, if I sit in my office chair, close my eyes, and spin myself around, I absolutely know I'm moving. I feel it in my inner ear. I don't need to look at the room to know I'm spinning.
That is a brilliant distinction, actually, and it highlights the exact boundary of the rule. You are feeling rotation. If your office suddenly started spinning, you'd be thrown against the wall by centrifugal effects. We can measure rotation without looking outside at all. I mean, a Foucault pendulum swinging in a closed room will slowly shift its path over the course of a day, perfectly proving the Earth is rotating.
So rotation and acceleration are absolute. I can feel my car braking or taking a sharp turn.
Exactly. What relativity says is that you cannot detect uniform straight-line velocity. If you're in a perfectly smooth train moving at a perfectly constant speed in a straight line, there is literally no physical experiment you can do inside that closed train to tell if you're moving at 100 miles an hour or standing completely still.
Okay, that sets up a classic puzzle beautifully. If uniform motion is impossible to detect, then we run into the twin paradox.
Oh, the famous Peter and Paul.
Yeah. Say we have two twins, Peter and Paul.
Yeah.
Paul gets in a spaceship, blasts off, and travels at an incredibly high constant speed away from Earth. Peter stays home. Because Paul is moving so fast, time physically slows down for him relative to Earth. When he finally returns, Paul is younger than Peter.
The ultimate science fiction trope, but mathematically completely sound.
But wait, If uniform motion is completely relative, why couldn't Paul say, well, from my perspective inside my ship, I was standing still. Peter and the entire planet Earth flew away from me at high speed, and then Earth came back.
Right, why isn't it symmetrical?
Exactly. If neither can tell who was really moving during that straight-line journey, why is the situation asymmetrical? Why is Paul definitely the one who aged less?
Because you have to think about the physical reality of Paul's journey. It wasn't just a uniform straight line. To leave Earth, he had to fire enormous rockets. He felt himself pinned to his seat.
Ah, the acceleration.
Exactly. When he reached his destination, he had to fire thrusters to slow down, turn the ship around, and accelerate back. He felt the gravity-like forces of acceleration and deceleration. Peter, sitting on Earth, felt absolutely none of that extreme force.
So the one who feels the acceleration is the one who breaks the symmetry.
You nailed it.
Yeah.
And the one who feels that acceleration is the one whose clock ultimately runs slower when they meet back up. And this isn't just a thought experiment, by the way. It happens in the laboratory constantly.
Wait, really? With actual twins?
Well, no, not twins. With subatomic particles called muons, they naturally decay and disappear in a fraction of a microsecond.
Okay.
If you put those muons in a particle accelerator and force them to travel in a circle at near light speed, they are constantly accelerating because they are constantly turning.
Oh, like the feeling of taking a sharp turn in a car, but continuously.
Yes. And because they're experiencing that continuous extreme acceleration, those moving muons live measurably longer than stationary muons just sitting on a desk. Time literally stretches for them to compensate for their motion.
Wow. Okay, so if time is physically stretching and warping, then our basic understanding of speed has to fall apart. Because, speed is just distance divided by time.
Exactly.
If the denominator of that equation is a moving target, speed can't just be simple addition anymore.
It absolutely cannot. Newtonian math works perfectly fine for low speeds. Like if you're on a train moving 50 miles an hour and you throw a baseball forward at 50 miles an hour, someone standing on the ground sees that baseball moving at 100 miles an hour.
But what happens when we approach the cosmic speed limit? Say I'm in a spaceship traveling at half the speed of light, so 0.5 c, and I build a cannon that fires a probe forward at 0.5 c.
Right.
My brain wants to just stack those numbers. Half plus half equals 1. Does an observer on Earth see that probe traveling at exactly the speed of light?
Nope. The universe intervenes. Feynman walks us through the Lorentz transformation in the text, which shows that velocities don't just stack, they are governed by this mathematical penalty factor.
A penalty factor.
Yeah. When you add two extreme speeds, the universe divides your total by a specific equation. It's 1 plus the two speeds multiplied together, divided by the speed of light squared.
Like a sort of cosmic tax bracket.
That is a great way to put it. The faster the two speeds you're trying to add, the higher the tax. In your example, 0.5 c plus 0.5 c doesn't equal 1.0 c.
Because of that denominator.
Right. Because of that penalty factor, it actually equals 0.8 c. As Feynman puts it, in relativity, half and half does not make 1, it makes 4/5.
So the closer you try to get to the speed of light, the heavier that mathematical penalty becomes, forcing your total speed to stay just under the limit.
Exactly.
Okay, but I want to try and break that math. What if, instead of firing a physical probe, I stand at the front of that ship moving at 0.5 c and I turn on a flashlight?
Okay, let's look at the light.
The light is already moving at 1.0 c relative to me. Do my headlights hit the observer on Earth at 1.5 times the speed of light?
It's a great question, but if you run that scenario through the exact same cosmic tax bracket, this incredibly elegant thing happens. The math forces the result to condense perfectly back down to 1.0.
Are you serious?
Yeah. The observer on the ground sees the light moving at exactly c. You on the ship see the beam moving away from you at exactly c. Light just refuses to be added to. It is the absolute anchor of reality.
Man, that is wild. Okay, so forward and backward motion gets heavily penalized. But what happens if something is moving sideways inside that spaceship?
Yeah.
We have a diagram from the sources, figure 16-1, that deals with this.
Let's try to visualize this without the abstract diagram first. Imagine you're on a smoothly moving train and you're bouncing a basketball straight up and down.
Okay, I'm with you.
To you, the ball is just moving vertically. But to someone standing on the platform watching the train zip by, the ball isn't just going up and down. By the time the ball hits the floor has moved 10 feet down the track.
Oh, I see. So the person outside sees the basketball tracing this jagged diagonal zigzag path.
Exactly. Now, let's take that concept to the absolute extreme. Inside your spaceship, you have a clock. But this clock ticks by bouncing a beam of light up to a mirror on the ceiling and back down to the floor.
A light clock.
Right. And next to it, you have another clock that bounces a physical material particle up and down. It's moving incredibly fast, but slower than light. Let's say they're perfectly synchronized, so that for every 10 bounces of the light, the particle bounces exactly once.
So they hit the floor at the exact same moment.
Yes. Now, to the outside observer watching your ship fly by, both the light and the particle are tracing long, diagonal zigzag paths.
Just like the basketball.
Right. But we know the speed of light cannot change. So because the light is forced to travel a longer diagonal distance at the exact same speed, the outside observer sees the ticks of the light clock slowing down.
Oh, wow. But physical reality still has to agree, right? I mean, if the particle and the light beam hit the floor at the exact same instant inside the ship, they have to hit the floor at the exact same instant for the person outside. You can't have an event happen in one perspective and not another.
Exactly. And here is the unavoidable consequence of that. To make sure those events stay perfectly synchronized for the outside observer, the vertical speed of the physical particle must appear mathematically sluggish. Sluggish.
Yeah, its sideways motion gets slowed down by that exact same relativistic penalty factor.
It's like the ship's forward momentum is basically stealing the object's ability to move sideways quickly.
That's a really good way to think about it.
Which brings up a massive logical dilemma. If you keep pushing an object, dumping more and more energy into it to make it go faster, but the universe stubbornly refuses to let it break the speed of light,
Right.
where does that extra pushing energy actually go? I mean, it has to go somewhere.
And this is where the physics shifts from just being weird to being truly profound, because that energy doesn't dissipate, it transforms. The object physically gets heavier.
Okay, that sounds like actual magic. We need to ground this. I know Feynman uses collisions to prove this, specifically looking at the conservation of momentum.
Momentum is the absolute key here. Momentum is mass multiplied by velocity. And in any closed system, the total momentum before a crash has to perfectly equal the total momentum after a crash.
So, imagine two perfectly identical protons moving toward each other. They crash head-on and bounce away at the exact same speed they came in with. This is figure 16.2. It's perfectly symmetrical, like an X drawn on a piece of paper.
The math there seems easy. They just cancel each other out perfectly.
But now, imagine you're driving past that exact same collision in a car. This is figure 16.3. And your car happens to be moving horizontally at the exact same speed as one of those protons.
Okay, so if I'm moving right alongside proton A, it doesn't look like it's moving horizontally at all. To me, looking out the window, proton A just looks like it's drifting straight up, getting hit, and drifting straight down.
Meanwhile, proton B, coming from the opposite direction, looks like it's flying past your car at a terrifying compounded speed. It comes in at a sharp, shallow angle, clips proton A, and ricochets away violently.
Wow, so the visual symmetry is completely shattered.
Completely. But the laws of physics cannot be shattered. The momentum still has to perfectly balance to zero.
Okay, but how?
When we analyze the vertical motion, proton A looks like it's moving slowly up and down. Proton B is moving incredibly fast. If their masses were identical, the vertical momentum wouldn't balance. The fast one would overpower the slow one.
Right, because momentum is mass times velocity. If the velocities look completely mismatched from my car window, the only mathematical way the momentum can still cancel out to zero
Yes.
is if the mass itself changes.
Boom. The universe literally tweaks the mass dial to make sure the accounting books of momentum always balance. The formula demands it. A moving object's mass equals its rest mass divided by that same relativistic penalty factor.
So the faster it goes, the heavier it mathematically must become.
Yeah.
That blows my mind, but it also feels a bit like an abstract trick of the observer in the car.
Yeah.
What happens if the objects don't bounce? What do we look at an inelastic collision like figure 16.4?
That's the perfect test. Let's look at two clumps of clay moving toward each other head-on at high speed. Let's say their rest mass is exactly 1 kilogram each. They crash, they stick together, and they form a brand new, completely stationary clump of clay.
Okay, basic logic tells me 1 kilogram plus 1 kilogram equals a new stationary object weighing 2 kilograms.
But remember, before they crashed, they were moving incredibly fast. Because they were moving, their mass was enhanced. They were heavier than 1 kilogram each. Let's say their moving mass was 1.5 kilograms.
Oh, I see. So the total mass entering the crash was actually 3 kilograms.
Right. Feynman views this crash from a moving elevator to check the conservation of momentum, and the unavoidable result is this. To keep the momentum perfectly conserved across all viewing frames, the mass of the new stationary clump of clay must equal 3 kilograms.
Wait, I want to make sure the gravity of this is landing for you listening. If two objects crash and stop moving, the new object is physically heavier than the sum of the original parts.
Yes. The mass of the stationary object is greater than the rest masses of the pieces that made it. Astonishing as it seems, the kinetic energy, the sheer violence of their motion before the crash, got trapped inside the new object.
And that trapped energy literally manifests as extra weighable mass.
Exactly.
Trapped movement makes an object heavier, which means energy and mass aren't just related concepts. They are the exact same fundamental currency.
Energy has inertia. If you put energy into a system, even if the system as a whole isn't moving, it gets heavier. Which brings us right back to your coffee example from the intro.
Oh, right. The hot coffee has more mass than the iced coffee.
Because heat is nothing more than the microscopic kinetic energy of molecules. In the hot coffee, the water molecules are zipping around, crashing into each other furiously. They have immense trapped kinetic energy compared to the cold coffee.
And just like the clay clumps, that trapped kinetic energy literally adds mass to the cup.
Exactly. When the coffee cools down and radiates that heat away into the room, it physically loses a tiny, tiny fraction of its mass.
That is profound. It completely shifts how you view every physical object around you. And this realization that mass is just highly concentrated energy, it actually clarifies a massive historical myth that Feynman mentions in the text.
Oh, the atomic bomb myth.
Yeah, the idea that Einstein was the quote-unquote father of the atomic bomb.
Right. History often implies Einstein was in some laboratory tinkering with uranium to build a weapon. He didn't engineer the bomb. The chain reactions and the mechanics, that was the work of an entirely different team of physicists.
What Einstein provided was the master ledger, the famous equation E equals mc squared.
He gave them the cosmic exchange rate.
Think about what that implies for the scientists building the bomb.
Well, they measured the rest mass of a uranium atom. Then they measured the rest masses of the pieces it splits into, like barium and krypton. When they put those fragments on the scale, the pieces weighed slightly less than the original uranium atom. There was a tiny fraction of missing mass.
Books didn't balance.
But with Einstein's ledger, they realized the mass hadn't just vanished. It had transformed. By taking that microscopic amount of missing mass and multiplying it by the speed of light squared, which is an unfathomably huge number, they calculated exactly how much energy that missing mass would turn into.
A city-leveling amount of energy. He just showed them the terrifying potential locked inside the atom's ledger.
And as Feynman points out, even if Einstein hadn't handed them the formula, scientists measuring the explosion would have eventually figured out the conversion rate anyway just by analyzing the debris. But Einstein gave us the fundamental, elegant truth. Mass and energy are just two forms of the exact same thing.
Which leads to a really beautiful concluding idea in the text regarding subatomic particles. Feynman talks about the K-meson.
Ah, the K-meson. It is a fascinating headache for traditional physics because it can disintegrate into two smaller particles called pions, but, on a different day it might disintegrate into 3 pions.
Which completely ruins the idea of asking, well, what is a K-meson made of? If a Lego castle breaks into 2 blocks sometimes and 3 blocks other times, it's not made of consistent building blocks.
Exactly. And this is the ultimate paradigm shift of Chapter 16. We no longer need to worry about counting the pieces inside a particle. We don't have to separate an object into the mass of its parts plus the kinetic energy of its parts.
We just shift the origin of energy entirely.
Right. We stop treating mass as a separate category of existence.
We just accept that all mass is deeply concentrated energy.
The total energy of any object is simply its mass in motion multiplied by the speed of light squared. If the object is standing completely still, its total energy is just its rest mass times c squared. It provides this beautifully unified, simplified way to view the vast complexity of the universe.
It's a breathtaking way to see reality. Let's pull all of this together for everyone listening. We started by throwing out that cocktail party philosophy that everything is just a matter of perspective.
Because relativity isn't subjective. It is a highly precise, mathematically governed universe.
It's a universe where moving fast and feeling acceleration literally stretches time to keep you younger.
And it's a universe that enforces a strict cosmic tax bracket on speed, refusing to let anything break the speed of light, which in turn forces things moving sideways to appear sluggish to outside observers.
And ultimately, it's a universe where the sheer effort of trying to push something past that speed limit doesn't just disappear, it gets trapped. The kinetic energy of a violent crash literally turns into physical, weighable mass. Energy is mass.
Mass is energy.
And that leads to a final, pretty mind-bending thought I want to leave you with today. We just learned that pumping heat energy into a cup of coffee makes it heavier.
Huh.
We learned that energy literally possesses mass.
Right.
Well, your brain operates on electrical impulses, chemical reactions, and moving energy. So right now, as you are intensely concentrating, processing complex physics, and firing millions of neurons to understand relativity,
Oh, I see where you're going with this.
is your brain literally, physically getting heavier? Think about that next time you feel a particularly heavy thought coming on. Thank you so much for taking this deep dive with us. We'll see you next time.
You know, if you look at your watch and I look at mine and we both agree it's noon, there's this deep, comforting expectation of absolute certainty when it comes to time.
Oh, absolutely. I mean, we treat it like this background metronome that just ticks away.
Right. Exactly the same for everyone, everywhere in the universe. But in chapter 17 of his famous physics lectures, Richard Feynman just completely shatters this universal clock.
He really does. And he does it using nothing but geometry and logic, which is just, it's a brilliant piece of scientific communication.
Yeah, it's amazing.
He takes the Lorentz transformations, these mathematically dense equations that govern how space and time warp at high speeds, and he just strips away all the jargon.
He forces you to confront the reality that the universe simply does not share our intuitive biological sense of time.
Right. It's a tough pill to swallow.
And that is exactly our mission for you on this deep dive today. We're going to explore Feynman's mechanics of space-time without rushing to fundamentally rewire how you perceive reality.
Because once you grasp how physicists actually map the universe,
Yeah.
your intuitive understanding of past, present, and future is going to be completely dismantled.
Totally. Which, I mean, it's necessary, right? Because our intuition is basically a massive biological blind spot.
Exactly. I mean, think about how we evolved. We are these slow-moving creatures on the plains of Earth, dodging predators, navigating a basic 3D environment.
Right. Our brains are spectacularly good at calculating normal spatial relationships.
Yeah, but because humans have never, in our entire evolutionary history, traveled anywhere near the speed of light, we just lack the hardware to intuitively feel how velocity alters the fabric of reality.
We don't have the instinct for it.
No, not at all.
So Feynman introduces this with a deceptively simple analogy about just, well, looking at an object. If I'm looking at a physical object, say like a rectangular block, it has a certain apparent width and a certain depth from my perspective.
Right. And if you walk around it and look at it from a new angle, its apparent width and depth change.
Because my perspective shifted.
Exactly. What was entirely width a moment ago now has a little bit of depth mixed into it.
But you know, I don't freak out when that happens. I don't suddenly assume the block physically squished itself.
Right. Your brain knows width and depth aren't fundamental intrinsic properties of the block.
Yeah, they are just relationships based on my viewing angle.
Exactly.
Yeah.
Now, Feynman applies this exact logic to relativity. He argues that moving at high velocities does the exact same thing, but instead of mixing width and depth, it actually mixes your measurements of space and time.
Okay, wait, I always struggle with that leap.
It's a big leap.
Because with the block, the width and depth changing is just a trick of perspective. The block itself hasn't changed. But you're telling me that if I travel at a significant fraction of light speed, my focal space literally squishes and my time physically slows down?
Yes.
Are you saying time is just like a different viewing angle of space?
I am saying exactly that. And so is Feynman. We really have to abandon the idea that a 3D object just exists in the moment. Space and time are not independent theaters where events happen. They are a singular four-dimensional structure.
A single structure.
Yeah, an object occupies physical space, and it lasts for a certain duration. That makes it a 4D entity embedded in a space-time continuum.
So the universe is basically a giant four-dimensional blob.
Yes, a 4D block. And a single specific point in that block, like a specific spatial coordinate at a specific moment in time, is what physicists call an event.
Okay, an event.
Right. And when you change your velocity, you are literally changing your viewing angle through that 4D block. Just like shifting your viewing angle mixes width and depth, shifting your velocity mixes space and time.
Wow. Okay, but if our brains are so hardwired to fail at visualizing a 4D block, how are physicists actually doing the math? Like, they must use some sort of map to navigate this, right?
You do, yeah. And Feynman visualizes this beautifully by mapping it out on a two-dimensional plane. He plots space horizontally and time vertically.
Okay, so horizontal is space, vertical is time. So even if I'm sitting perfectly still in my chair right now, staring on the wall, I am tracing a path on this map.
You absolutely are. Your path is a straight vertical line.
Because I'm not moving through space.
Right. You aren't moving horizontally through space at all, but you are relentlessly moving vertically through time. Physicists call this continuous line your world line.
My world line. Okay, so what if I get up and start walking at a steady pace?
Then your vertical world line tilts. It becomes a slanted straight line because now you're covering horizontal distance space while still moving vertically through time.
And what if I sprint and then slide to a halt?
Then your world line curves.
Oh, because my speed is changing.
Exactly. It starts with the steep tilt because you're covering a lot of space quickly, and as you decelerate, the curve sweeps upward until it becomes perfectly vertical again the exact moment you stop.
But there's a hard physical limit to how far that line can tilt, isn't there? Because, well, there's a speed limit in the universe.
Precisely. Light. Light represents the absolute maximum tilt allowable on this space-time map. Nothing can lean further horizontally than a photon.
Okay, let's apply this map to something dynamic from the source material. Say we have a particle that suddenly disintegrates into two new particles that shoot off in opposite directions.
A classic example.
Right. So on this map, that looks like a single line moving upward that suddenly forks into two branching paths.
Yes.
And the fork itself is the event of the disintegration.
Exactly. And this is where we run into a major trap that catches, well, a lot of people off guard.
Oh!
Yeah. Let's say we want to figure out what that disintegration event looks like from the perspective of an observer flying past in a fast spaceship.
Okay, my instinct is to say, well, it's a geometric map, right? So if the observer has a different viewing angle, I'll just rotate the grid lines of the map like twisting a piece of paper.
And Feynman explicitly warns that doing so is entirely incorrect.
Yeah.
There's a figure 17.2a, that literally just says not correct over a rotated grid.
Wait, why not? If we just establish that a velocity is just a change in viewing angle, why doesn't a standard geometric rotation work?
Because of how the math of the universe enforces the speed of light. In normal geometry, if you rotate an x and y axis, the underlying math uses addition.
Like the Pythagorean theorem, a squared plus b squared.
Exactly. If you rotate the axis, the total distance from the center stays exactly the same. But the math of space-time, the Lorentz transformation, relies on subtraction.
A minus sign.
Yes. It's a hyperbolic geometry, not a Euclidean one. If you just rigidly rotated the grid, you would accidentally change the speed of light for that moving observer.
Which violates the core rule of relativity.
Exactly. The speed of light must be identical for everyone, no matter how fast they are moving. So to keep that diagonal light speed line exactly where it is, the moving observer's space and time axes don't rotate. They scissor together.
They scissor together, like closing a pair of scissors.
Yeah, imagine the vertical time axis and the horizontal space axis leaning in toward each other, squeezing toward that diagonal light speed line in the middle.
Oh, wow.
Space stretches and time squeezes inversely. That minus sign is the mathematical mechanism that forces space and time to compensate for one another so that the speed of light never, ever fluctuates.
That is deeply unsettling to think about.
That breaks your brain a little.
It does, because if time and space are constantly stretching and scissoring and morphing depending on how fast someone is moving, it implies there's no bedrock reality.
Yeah.
If you and I are moving at different speeds, we will completely disagree on how far apart two events are, and we'll disagree on how much time passed between them. Does anything stay the same?
There is an anchor, yes. But finding it requires us to stop measuring space and time as separate things. We actually have to calculate the space-time interval.
How does that work? If we disagree on the space and we disagree on the time, how do we possibly agree on the combination?
Think back to the width and depth of that physical block we talked about.
Okay.
If two people look at a block from different angles, they will argue about its apparent width and its apparent depth. But if they use those measurements to calculate the total volume of the block, they will arrive at the exact same number.
Right, the volume is intrinsic.
Exactly. The space-time interval is the cosmic equivalent of that total volume.
Okay, so what is the actual equation for this interval?
It's the time elapsed squared minus the spatial distance squared.
There's that crucial minus sign again.
Yeah, it's everywhere in relativity. But in classic physics notation, there's a frustratingly clunky element added in. The speed of light, represented by c, is multiplied against the time. So the raw formula is c squared t squared minus x squared minus y squared minus z squared.
Which brings up one of my absolute favorite critiques from Feynman in this chapter. He points out that the only reason c is muddying up this beautiful equation is because of human stubbornness.
Pretty much, yeah.
We insist on measuring distance in meters and time in seconds.
It's purely a historical accident. We developed rulers and clocks way before we understood relativity.
Feynman uses this absurd analogy to show how silly our units actually are. He says, imagine trying to measure the width of a box by the optical angle it takes up in your field of vision, but you measure the depth of the box by how much your eye muscles physically strain to focus on it.
Right. It's a nightmare. You'd end up with an absolute mess of conversion formulas. Every time you wanted to do a simple geometric calculation, you'd have to translate muscle strain units into optical angle units.
And he's saying that's exactly what we're doing when we use meters and seconds. We are measuring the exact same fabric space-time using completely incompatible tools.
So the mathematical revelation here is to force our units to match. We do this by setting the speed of light, c, equal to exactly 1.
Wait, you can't just declare the speed of light is 1. How does that translate to reality? Are we redefining the meter or redefining the second?
We are recognizing they are interchangeable. You can measure time in meters or space in seconds.
Space in seconds.
Yeah, for example, what is a second of distance? It is simply the distance light travels in 1 second, which is roughly 300 million meters.
Oh, I see. So instead of saying the moon is about 380,000 kilometers away, I could just say the moon is about 1.28 seconds away.
Exactly. And conversely, a meter of time is the duration it takes light to travel 1 meter, which is an incredibly tiny fraction of a second. By setting c equal to 1, the c just vanishes from our equations.
That's so clean.
It is. The space-time interval simplifies elegantly to just time squared minus distance squared. It mathematically proves that space and time are the exact same currency, merely exchanged at different rates by different observers.
This changes everything about how we interact with the universe. Because if light isn't just a thing flying through space, but the fundamental conversion rate between space and time, it creates strict, inescapable boundaries.
It really does.
Which brings us to figure 17-3, the structure known as the light cone. This is the concept that completely obliterates the idea of right now.
It does, and it forces us to look at causality, cause and effect, in a rigid mathematical way.
Okay, walk us through it.
Imagine you are standing at the exact origin point of our space-time map. You are in the dead center. The paths of light moving toward you from the past and away from you into the future form a sort of hourglass shape around you.
A cone opening upward into the future and a cone opening downward into the past.
Right. And these cones divide all of reality, the entire 4D block of the universe, into 3 distinct regions. Let's start with the bottom cone. Feynman calls this the effective past.
The effective past.
Because nothing can move faster than light, only events that occur physically inside this bottom cone could possibly send a signal fast enough to reach you at the origin.
So if a star goes supernova inside my bottom cone, the light of that explosion has had enough time to cross the distance. It can hit my telescope. It can affect my reality.
Exactly. Now look at the top cone, the effective future. These are all the locations and times in the universe that you could possibly reach or send a signal to, starting from where you are right now.
So if I shine a laser or launch a probe, it is permanently trapped inside that top cone.
Yep, it can never exit that cone.
Okay, so the bottom cone is what can impact me, and the top cone is what I can impact. But what about everything else? All the vast space outside the hourglass.
That is the region of space-like intervals. It is the unreachable elsewhere.
The unreachable elsewhere.
Yeah. Events happening in this region are so far away and happening so recently that light from them hasn't had time to reach you. And you couldn't possibly send a signal to them either.
Feynman uses Alpha Centauri to drive this home. It's a star system about 4 light years away. When we look up at it, we are seeing the light that left it 4 years ago. That event, the star shining 4 years ago, is safely inside our effective past cone.
But if you ask the seemingly normal question, what is Alpha Centauri doing right now? Relativity tells us that the question is physically meaningless.
Meaningless because the information literally does not exist in our universe yet. It's outside the cone.
Now is purely a psychological concept.
Yeah.
It has no physical definition across vast distances because we are strictly bound by the speed of light to confirm anything. Until the light from Alpha Centauri's current activities enters our future light cone 4 years from today, its present is entirely severed from our present.
There's a brilliant point in the text about fortune tellers that really highlights the absurdity of this.
Oh, I love that part.
Right. People always invent these sci-fi paradoxes about psychics knowing the future, but based on this geometry, a psychic couldn't even tell you what is happening in the present on another planet.
Exactly.
Because to know what is happening on Mars right now, they would need to access information that is traveling faster than the speed of light.
It completely destroys the illusion of simultaneity. Because observers moving at different speeds have space and time axes that scissor at different angles, their light cones actually tilt relative to one another.
So what I consider to be simultaneous events, someone else might not.
Exactly. Let's say you observe two supernovae exploding at the exact same moment on opposite sides of the galaxy. An alien flying past Earth in a high-speed ship will physically observe one star exploding years before the other.
And neither of us is wrong.
Neither of you is wrong. Your separate velocities mean you are slicing through the 4D space-time block at different angles. You physically disagree on what now actually is.
It's staggering to realize that a shared present is just well, a local hallucination. But we have to push this even further, because space and time aren't the only concepts that get fused together by these Lorentz equations.
Right. There's more.
If we upgrade the geometry of the universe to 4 dimensions, our basic laws of physics have to be upgraded to match.
This is a vital conceptual leap. In classical Newtonian physics, we have the law of conservation of momentum. Momentum operates in 3 spatial directions, x, y, and z. And completely separate from that, we have the law of conservation of energy.
Right, momentum is about mass and velocity in space, while energy is a scalar value. They're totally separate rules.
But in relativity, because space and time transform together, the things that occur in space and time must also transform together.
Makes sense.
Momentum, which relates to space, and energy, which relates to time, actually merge into a single mathematical object.
A 4-vector.
Yes, a 4-vector. You can visualize it as an arrow pointing tangentially off a particle's world line on our space-time map. The 3 spatial components of this arrow represent the particle's momentum, and the 4th, time-like component represents its total energy.
Wait, if these are fused together, does that mean the old 3D conservation of momentum is dead? Like, if 2 cars crash or 2 particles collide in an accelerator, I can't just add up their mass and velocity in 3D space to find the result anymore.
In high-speed physics, no, you cannot. Conserving 3D momentum alone is mathematically incomplete. In relativity, you must conserve all 4 components of the vector simultaneously.
Oh, wow.
You cannot separate the conservation of momentum from the conservation of energy. They are no longer 2 separate laws of nature. They are a single 4-dimensional law.
Okay, so just like the space-time interval gave us a bedrock constant, a distance all observers could agree on, does this 4-vector have an anchor? Does the length of this momentum-energy arrow stay the same for everyone?
It does. No matter how fast you are moving or how much the momentum and energy values appear to shift relative to your viewing angle, the squared length of that 4-vector is invariant.
And what is that length?
That length is equal to the particle's rest mass squared.
The rest mass. The mass the particle has when it is sitting perfectly still relative to you.
Exactly. It is an intrinsic property of the particle, hard-coded right into the geometry of its 4-vector.
Which brings us to the ultimate edge case that Feynman explores in figure 17-4, the photon, a single particle of light.
A very special particle.
Yeah. We know from, solar sails that light carries physical momentum, it can physically push objects, and we know it carries energy based on its frequency. That's why the Doppler effect shifts the color of fast-moving stars.
It clearly possesses both momentum and energy.
But the rest mass of a photon is exactly 0. The invariant length of its 4-vector is 0. So how can a particle with 0 mass possess momentum? And more importantly, what happens to it if it stops? Does a massless, stopped photon just vanish into nothingness?
The underlying truth of relativity provides the punchline here. It never stops.
It never stops.
A photon always, perpetually moves at the speed of light. It has no rest mass because it can never be at rest. Its energy and momentum are derived entirely from its perpetual motion.
It is a creature made purely of velocity.
Yes, if a photon were to somehow decelerate, it would literally cease to exist.
Yeah.
It perfectly embodies the geometry we've been discussing. Light is the fundamental conversion rate that bridges space and time, and the only way it can serve as that universal constant is by never, ever resting.
Let's pull all of this together. We started by stripping away the illusion that time is a universal metronome.
Right.
We learn that velocity literally scissors space and time together, keeping the speed of light perfectly intact. We abandon arbitrary human units to prove that space and time are the exact same currency.
Setting C to 1.
Exactly. We mapped the light cone, proving that the concept of a shared right now across the universe is physically impossible. And finally, we merged momentum and energy into a single four-dimensional law, powered by the tireless photon.
It's a profound shift in perspective. You are forced to stop viewing reality as a series of fleeting moments and start viewing it as a static, pre-existing whole.
Feynman captures this beautifully by quoting the mathematician Hermann Minkowski at the end of the chapter. He said, "Space of itself and time of itself will sink into mere shadows, and only a kind of union between them shall survive."
It's a hauntingly accurate description.
It really is. But I want to leave you, our listener, with one final, deeply unsettling implication of all this. An idea to mull over the next time you look at the stars. We've established that the universe is a singular, four-dimensional block.
Right, the 4D blob.
And your past, your present, and your future exist as a static, unchanging world line embedded in that block. And because simultaneity is an illusion, an alien moving at a high speed relative to Earth right now might have a present that intersects with what you consider to be your future.
Yeah, geometrically that is absolutely true.
If your future is already happening right now in someone else's reference frame,
Okay.
it means the future is already written. It is already sitting there in the 4D block, just waiting for your consciousness to slide upward along your time axis and experience it.
Wow.
So the ultimate question relativity leaves us with is this: in a universe where the past, present, and future all exist simultaneously in a frozen geometry, do you actually have any free will, or are you just playing out a script that the universe has already printed? Until next time, keep digging. I want you to picture something for a second. Imagine you have this really weird, complex object. Like, let's say it's made of a bunch of wooden blocks connected by these random spokes, maybe tied together with some string.
Right, just a total mess.
Exactly. It's
Yeah.
lopsided, it's ugly. Now take that chaotic contraption and just launch it into the air. If you watch it fly, it looks like pure chaos. It's
Right.
wobbling, the blocks are jiggling, the spokes are twisting in, every possible direction.
Yeah, it seems completely unpredictable. Just a mess of movement.
Totally unpredictable. But hidden entirely inside all of that tumbling chaos, there is actually a perfect mathematically definable path, like a smooth curve that completely ignores the madness happening all around it.
It really is a beautiful image to start with.
Yeah.
Because our instinct, when we look at the real world, is to focus on all of those flailing parts and think the whole system is messy. We like things to be clean and simple. We want to track a single point moving through space. But real things twist, they turn, they tumble. And, well, physics tells us that when a system looks like pure chaos, we usually just aren't looking at the right spot.
And today, we are going to find that exact spot. We are decoding the hidden architecture of how things spin, wobble, and turn. And to do that, we're using the legendary physicist Richard Feynman as our guide.
Specifically, Chapter 18 from Volume 1 of his famous lectures.
Yes, we are diving into his iconic text to translate the chaotic world of rotation into beautiful, predictable rules. I have to admit, when I first thought about tackling the physics of rotation, it sounded a bit intimidating.
Oh, absolutely. The math can look scary at first glance.
It really can. But I promise you, by the end of this deep dive, you are going to look at everything from a dancer leaping across a stage to the literal planets orbiting in our solar system in a completely different way.
And the reassuring thing here is that we aren't really learning an entirely new set of fundamental laws.
Yeah.
We're just going to take what we already instinctively understand about linear motion, things moving in a straight line from point A to point B.
Mm-hmm.
And we're going to translate that into a new rotational language. We're just shifting our perspective.
Okay, let's unpack this. Because before we can really understand how that wooden block contraption is spinning, we have to somehow separate the spinning part from the normal forward movement part.
Right, you need an anchor in the chaos.
Exactly. Where do we even start with that?
Well, to simplify matters, Feynman asks us to first imagine a rigid body.
Rigid body. Got it.
Yeah, this is a theoretical ideal object where the forces holding its atoms together are so strong that it never bends or flexes, it only turns. So no floppy strings in this version.
Ah, okay, so it's solid.
Exactly,
Yeah.
solid. Now remember that perfect mathematical path you mentioned, the one hidden inside the flying blocks?
Yeah.
That path is traced by something called the center of mass.
The center of mass. So is that the heaviest block in the contraption?
Actually, not necessarily. It might not even be a physical piece of the object at all.
Wait, really?
Yeah, it might just be empty space in the middle of the contraption. It is an imaginary, calculated point based on the average position of all the mass in that object.
Oh, wow.
And here's the magic of it. If you throw that object, that imaginary point moves in a perfectly smooth parabola. It behaves exactly as if the whole object were just one tiny particle.
So it just ignores the spinning entirely.
Completely oblivious to the chaotic spinning happening all around it.
Wait, so if I'm watching a dancer leap across a stage, their arms and legs might be flailing wildly, throwing their weight all over the place.
Right.
But their core, like their center of mass, is just following a smooth, predictable arc through the air, exactly like a thrown baseball.
You're hitting on the fundamental rule right there.
Yeah.
Once that dancer leaves the floor, gravity is the only external force acting on them overall. Their center of mass is locked into that parabolic trajectory. They can kick and twist all they want, but that center point is on a predetermined track.
That is wild.
It gets better. Feynman gives a brilliant mental exercise to prove this. Imagine a spaceship floating in deep, empty space.
Okay, picture a spaceship.
There are zero external forces acting on it. No gravity, no friction. Because there are no outside forces, the spaceship's overall center of mass must remain perfectly still.
But what if the people inside start running around? Like if the astronauts all sprint to the front of the ship, surely the ship moves.
The whole of the ship moves, yes.
Oh.
If the astronauts inside the ship all decide to walk to the front, they are shifting physical mass forward.
Right, because they weigh something.
Exactly. To compensate and to keep the overall calculated center of mass in the exact same location in space, the physical hull of the ship must move backward.
Wait, so rocket science essentially boils down to strictly defending this one imaginary dot in space.
That's one way to look at it, yeah.
To move the part of the rocket we care about forward, the astronauts and the payload, we are basically forced to spit a massive amount of uninteresting gas out the back.
Right.
We're just rearranging the pieces around a stationary center of mass.
That is a fantastic way to look at it. You are exploiting the fact that the center of mass refuses to move, and you use that to propel the piece you actually care about.
That just blew my mind a little bit.
It's elegant, isn't it?
Yeah.
So back to our rotation problem. The reason Feynman introduces this is to say, look, we understand the center of mass. We can isolate the forward motion.
Right, we've solved that part.
Now, let's essentially freeze the center of mass in place, ignore the forward movement, and focus entirely on the spinning itself.
And to do that, we need to build our new rotational dictionary, right? We need a new vocabulary because saying something is moving fast doesn't quite make sense when it's just turning in place.
Exactly. It's not going anywhere.
Yeah. So what are the new words?
We have to map our linear concepts to rotational ones. In a straight line, we talk about distance. How far did you walk? In rotation, distance is replaced by angle.
Angle, okay?
How many degrees or radians has the object turned? Next is velocity. How fast is your position changing? Linearly, that's distance over time, miles per hour.
Sure.
Rotationally, that becomes angular velocity. This measures how much the angle changes in a second.
Okay, got it.
And finally, linear acceleration speeding up or slowing down becomes angular acceleration.
Okay, so we swap distance for angle, speed for angular velocity, and acceleration for angular acceleration. It's a clean translation.
Very clean.
But how do the two worlds connect? Because, I mean, if I have a spinning disk, there's the angle it's turning, but the physical material of the disk is also moving through the air.
This is where we relate the two worlds, which Feynman lays out in Figure 18-1. Think about a single point on a spinning disk. The mathematical relationship Feynman shows is that your physical linear speed through space is simply your angular velocity multiplied by your distance from the center, your radius.
Let me try to visualize this. If I'm on a giant merry-go-round,
Perfect example.
the whole ride, like the entire disk, shares one single angular velocity.
Yes, exactly.
It all completes one full circle in the exact same amount of time. So the angular velocity is constant for the whole machine.
Correct. Every wooden horse is turning through the same angle every second.
But my actual physical speed, like the wind hitting my face, depends on my radius.
Right.
If I'm sitting on a horse right near the center, I'm barely moving. But if I move to the very outside edge, my radius is huge. So my physical speed is way faster, even though the angular velocity of the whole ride hasn't changed at all.
That's the core concept. The spin is constant, but your physical speed scales up the further you move away from the axis of rotation.
Okay, so we have the language, we know how to describe the spin, and we know how it relates to physical speed. But what actually causes a rigid body to start turning in the first place?
Right, the catalyst.
If I want to move a block in a straight line, I just push it. I apply force. What's the rotational version of force? I assume I just push the object really hard.
Well, it depends entirely on how and where you push it. The rotational analog to force is called torque.
Torque.
Torque is the twisting force. And Feynman defines it rigorously through the concept of work.
Okay, work, like energy expended.
Right. If you do work in a straight line, you multiply force by distance. To keep our dictionary perfectly consistent, rotational work is torque multiplied by the angle turned.
But getting back to the pushing part, why does it matter where I push? Force is force.
Let's test that assumption. This is illustrated in figure 18-2 in the text. Imagine a heavy door.
Okay.
If you walk up to that door, and instead of pushing it open, you push it radially, meaning you push the edge of the door directly toward the hinges. Does the door swing?
Oh. No, I guess I'm just crushing the door into the wall. Like I'm straining the hinges, but it's not rotating.
Right. Pushing directly at the center axis does absolutely nothing to make it spin. Mathematically, the only part of your push that matters is the part going completely perpendicular to the radius.
So pushing perfectly flat against it.
Yes. Any energy you spend pushing into the object or pulling straight away from it is completely wasted when it comes to rotation. You need a tangential force.
Oh. Which completely explains why door handles are always placed as far away from the hinges as possible.
Yes. You intuitively know this. And that brings us to the concept of the lever arm. You can calculate your torque by taking your force and multiplying it by the perpendicular distance from the axis.
So distance matters again.
Hugely. The longer that distance, the longer your lever arm, the more twist you get for the exact same amount of effort.
So if the handle was right next to the hinge, the lever arm is tiny, and I'd have to push incredibly hard to get enough torque to open the door. The text points out something really interesting about the word itself. Torque, or moment, comes from the Latin movementum.
Yes, the momentum of movement.
Right. It relates to the capability of a force to move an object using the leverage of a crowbar. It's literally all about leverage.
What's fascinating here is how this concept fundamentally redefines what it means for an object to be truly still.
How so?
We usually think of equilibrium as just, the forces cancel out. If you pull me left and I pull you right with the exact same strength, we don't go anywhere.
Net force is zero.
Right. But in the real world, for an extended object to be in true equilibrium, the net force must be zero. Indeed, the net torque must be zero.
Wait, how can the forces be zero but the torque isn't?
Imagine a steering wheel.
Okay.
If you push the left side up and pull the right side down with the exact same force, the total up and down force cancels out perfectly.
Oh, I see where this is going.
The steering wheel doesn't move up into the ceiling or down into the floor. But because those forces are applied at different points on opposite sides of the center...
You've created a massive twist.
Exactly. You've applied torque.
That makes perfect sense. Okay, so we've got torque as our twisting force. Now, torque is the rotational analog of force. There has to be a rotational analog of momentum.
Naturally.
In straight line physics, momentum is what makes a massive, fast-moving train so hard to stop. What is the measure of the unstoppable nature of a spinning object?
That is angular momentum. And following our symmetrical dictionary, it behaves just like linear momentum, but with a twist.
No pun intended.
Huh, right.
Yeah.
Just as a straight line force changes linear momentum, a torque is what changes angular momentum. This is the crucial theorem from the text. Torque is the rate of change of angular momentum.
So if I apply a twist, I change the amount of spin.
Yes. And more importantly, if there is no twist, if there is absolutely zero external torque, the angular momentum cannot change.
It just stays the same forever.
It is conserved. It is locked in.
And Feynman takes this abstract rule and applies it to the grandest scale possible planets orbiting the sun, which honestly broke my brain a little bit when I read it.
It's one of the most elegant applications of this physics. We're looking at figure 18-3 now. Think about the gravitational force the sun exerts on a planet. Gravity pulls the planet straight inward toward the sun.
Okay, pulling straight toward the center.
It's a radial pull.
A radial pull. And we just learned with the door hinge that radial force produces zero twist. So there is no tangential force pushing the planet along its orbital path.
None at all.
Wow.
The torque on the planet is exactly zero. And because the torque is zero, the angular momentum of the planet must remain perfectly, immutably constant.
But wait, orbits aren't perfect circles, they are ovals.
Yeah.
So the planet's distance from the sun, its radius, is constantly changing.
If we connect this to the bigger picture, think about what that means. The momentum is a combination of the planet's mass, its speed, and its distance from the sun.
Okay.
The mass isn't changing, but the distance is. As it travels in an elliptical orbit, sometimes it is closer to the sun. The radius is smaller.
Right.
But the universe demands that the total angular momentum stays exactly the same.
So if the radius shrinks, something else has to grow to balance the equation, the speed.
Yes.
The planet has to physically move faster along its path when it's closer to the sun, and it slows down when it swings further away.
That is exactly what happens. Mathematically, this balancing act means the planet sweeps out equal areas of space in equal amounts of time, regardless of where it is in its orbit.
Here's where it gets really interesting, because you just described Kepler's law of planetary motion.
I did.
Astronomers observed that centuries ago. They stared at the sky, tracked the math, and noticed this weird equal areas and equal times rule, but they didn't know why.
It was just empirical data. A strange quirk of the heavens.
And here Feynman is showing us that this grand celestial mystery is really just the universe obeying a basic rule of mechanics. Zero torque means constant angular momentum. The universe is just balancing a simple equation.
It's a perfect synthesis of observation and underlying physical law. The heavens aren't magic. They're just following the rules of leverage.
That is just so cool.
But while the vacuum of space provides a perfect, frictionless example of conservation, things get more complicated when we come back to Earth and look at objects we can actually touch.
Right, because we have friction and air resistance here.
Exactly. This raises an important question. If angular momentum is so strictly conserved, how do we see spinning things change their speed all the time?
Right. If angular momentum is conserved, how do things change? Feynman gives us the master equation for this. Angular momentum equals moment of inertia multiplied by angular velocity.
Moment of inertia is the crucial new concept here. It is the rotational equivalent of mass.
Okay,
It is an object's inertia for turning. Its built-in resistance to being twisted.
let me make sure I've got this. Mass is just how heavy something is. But moment of inertia is like where that heaviness lives.
Well put. With normal mass, it just depends on how much stuff you have. A 10-pound weight is 10 pounds.
Right.
But moment of inertia is calculated by looking at every little piece of mass in an object and multiplying it by its distance from the spin axis, squared.
That squared part is huge. It means the distance matters way, way more than the mass itself.
Yes. Let's visualize this with an experiment Feynman describes in figure 18-4. Imagine a vertical pole that can spin, and attached to it is a long horizontal rod.
Okay.
Now, hang a heavy weight on a string wrapped around the pole. As the weight falls, it pulls the string, creating a torque that spins the pole and the horizontal rod.
Okay, I picture it. A falling weight making a crossbar spin.
Now, take two heavy metal blocks and attach them to that horizontal rod. First, slide those heavy blocks all the way in, right next to the center pole.
So they're near the axis.
Right. When you drop the weight, the rod spins up very quickly. It has a low moment of inertia. But if you slide those exact same metal blocks all the way out to the extreme ends of the rod, further from the center,
The falling weight struggles.
it accelerates much, much slower.
Even though the actual weight of the machine hasn't changed by a single ounce, you still have the exact same amount of metal.
Exactly the same mass.
But because the mass is located further away, the inertia for turning, the resistance to the twist, has massively increased because that distance is squared.
Which leads to the dramatic difference between mass and moment of inertia.
Yeah.
Your physical mass never changes. If you weigh 150 pounds, you weigh 150 pounds whether your arms are tightly by your side or stretched all the way out.
Right.
But your moment of inertia can change. You can physically manipulate how hard you are to spin just by moving your own body.
And so what does this all mean? This is the secret behind the spinning figure skater.
It is.
It's the classic physics example. A skater starts spinning on the ice with their arms and maybe one leg outstretched. They have a large radius, so they have a large moment of inertia, and they are spinning at a certain relatively slow speed.
Now, consider the environment. We assume the ice is nearly frictionless. That means there is no external twist pushing or pulling on them. No torque.
Okay.
And as we established with the planet, zero torque means the total angular momentum is locked. It cannot change.
So the total momentum is locked. But then the skater suddenly pulls their arms and leg in, crossing them tightly over their chest. They are actively reducing their radius.
Exactly.
Because radius is squared in the moment of inertia formula, pulling their limbs in drastically drops their moment of inertia to a tiny fraction of what it was. but the universe demands that the total momentum stays exactly the same.
To balance the equation, the only thing that can change is the angular velocity, the speed of the spin. By drastically reducing their moment of inertia, they must drastically increase their spinning speed.
They aren't magically creating new energy. They aren't pushing off the ice to generate a new force. They are literally just manipulating their physical radius to hack the mathematical law of conservation.
That's beautifully said.
They're acting out an algebra equation in real time.
It really changes how you look at the physical world. Every time you open a heavy door, you aren't just pushing, you are intuitively calculating lever arms to maximize your torque. Every time you watch a dancer pull in their arms to spin faster, or watch the planets traverse the night sky, you are seeing the exact same beautiful hidden rules at work. It's the invisible architecture of motion.
You know, we've covered a tremendous amount of ground today.
We really have.
We started by looking at a chaotic, tumbling block of wood and realized we had to find the calm center of mass to anchor our perspective. Then we built a brand new dictionary, translating linear speeds and straight lines into angles and angular velocities.
A whole new way of speaking.
Exactly. We learned that to create a twist, you can't just push anywhere. You need torque, a tangential force acting on a lever arm. And finally, we discovered that spinning objects fiercely protect their momentum, and that by simply shifting mass around a center point, we can dictate the speed of a spin without ever adding a single drop of new force.
It's a powerful toolkit for seeing the invisible forces shaping our world.
But as we wrap up, I want to leave you with a thought to chew on. We just established, via Feynman and the unbreakable laws of physics, that angular momentum is conserved. Right, it doesn't just appear out of nowhere.
A spin cannot change. It cannot start, increase, or decrease without an external twisting force and external torque. So what does that mean for our entire galaxy?
Oh, that's a big question.
The Milky Way is a massive, incredibly complex structure slowly spinning through the vacuum of space. If angular momentum is always conserved and a twist absolutely requires a torque, where did the very first twist in the universe come from?
And perhaps more importantly, is there anything out there massive enough to ever make it stop?
So, if you push a wooden block across a table, right, it moves away from you.
Right, it just slides.
Yeah, and if you drop an apple, it falls straight down. The physics of our everyday world makes, intuitive, visible sense.
It's what we expect.
Exactly. But if you take a spinning gyroscope and you push straight down on its axle, it doesn't go down.
No, it does not.
It moves sideways.
Yeah, entirely sideways.
Which is wild. So today, we are opening up a stack of notes that, fundamentally breaks the rules of common sense. You, our listener, have handed us an incredibly dense, genuinely mind-bending collection of material based on Chapter 20 of Volume I of the legendary Feynman Lectures on Physics.
Oh, yes.
And the topic is rotation in three-dimensional space.
It's a topic that has historically confused some of the greatest scientific minds, honestly.
Yeah.
Yeah. Spinning objects like tops, wheels, gyroscopes, they seem to possess a sort of magic. They seem to, defy gravity.
Right, they just float there.
Yeah, and they react at right angles to the forces applied to them, which is highly counterintuitive because it completely defies our linear expectations of how the world works.
And the notes you gave us meticulously detail the mechanics of this, right? Like torques in 3 dimensions, cross products, precessing gyroscopes, and eventually, and I love this, the hidden physics of spinning potatoes.
The spinning potato is a highlight, for sure.
But our goal for this deep dive isn't just to, recite a list of equations back to you. We are on a mission to unpack the actual physical reality of three-dimensional rotation.
Absolutely.
We want to visualize exactly what is happening to the atoms inside these spinning metal wheels, decode the mysterious behaviors of tops, and clarify some massive misunderstandings about why they behave the way they do. So, okay, let's unpack this.
Let's do it.
Before we even get to the gravity-defying toys, we have to establish how we even describe a twisting motion in a 3D world, because it is wildly different from 2D.
Oh, very different. Let's think about a flat two-dimensional world for a moment, like a cartoon drawn on a piece of paper.
Okay, flat world.
In that 2D world, a twisting motion, what physicists call torque is incredibly simple to describe. It's just a number.
Like how fast it's spinning.
Yeah, and it's spinning either clockwise or counterclockwise. You don't need to specify a spatial direction for the twist itself because, well, the twist is permanently trapped flat on that single piece of paper.
Right. It has nowhere else to go. But the moment we pop up into our actual 3D universe, that simplicity just vanishes.
It completely vanishes because in 3 dimensions, we don't just have one flat plane. We have an infinite number of planes.
Yeah.
You have the flat ground, you have the vertical walls, and you have like every possible tilted angle in between.
It gets messy.
Exactly. So if you apply a twisting force to a wheel that is tilted at some bizarre 47-degree angle, how do you keep track of that twist mathematically?
Well, the source material calls it a, quote, miracle of good luck that our 3D space allows for a specific workaround here.
It really is lucky.
Because trying to draw curved, twisting arrows on tilted planes inside mathematical equations is just, it's a nightmare. So we represent that twist using a single, perfectly straight line.
Right, an axis.
Yeah, an axis that points perfectly perpendicular at right angles to the plane of the twist.
It is a profoundly clever geometric trick. Every single flat plane in 3D space can be uniquely identified by a single line that points straight out of it.
Like a flagpole on the ground.
Exactly. If the plane tilts, the perpendicular line tilts with it. So we represent the complex torque as a single straight arrow pointing along that perpendicular line.
Wait, I have to stop you there, because a flat plane has two sides. You can point a perpendicular line straight up from the table or straight down through the floor.
Ah, yes.
How do we know which way this arrow is supposed to point?
That is where we rely on the right-hand screw rule, which is entirely an arbitrary human convention.
Literally just a rule somebody made up.
Exactly. Somebody just decided on it. The convention asks you to imagine a standard right-handed screw. If the twisting motion on your plane would turn that screw so that it drives forward into the wood, the direction the screw advances is the direction we draw our vector arrow.
Oh, I see.
And if the twist would unscrew it, making it back out, the arrow points in that opposite direction.
I'm going to be honest here, and this is where I really push back on the math. Are we just inventing a completely fake arrow to make our equations easier to write?
It sounds like it, doesn't it?
I mean, if I have a record player spinning on a table, there isn't an actual physical force shooting straight up out of the spindle into the ceiling.
What's fascinating here is that physicists completely agree with your skepticism. Feynman explicitly makes this exact distinction in the material.
He does.
Yeah. We absolutely must separate honest vectors from these artificial ones. Honest vectors are called polar vectors.
Okay, polar vectors. I need a concrete example.
Yeah.
What does that look like?
Think about velocity or a pushing force. If I push a heavy box across the floor toward the north, the force vector points north. The box's velocity vector points north.
So the arrows match the actual movement.
Exactly. The arrows directly represent the physical reality of what is moving and where it's going. They are honest.
But the twisting arrow, the one shooting out of the record player, isn't honest.
No, it's what we call an axial vector or a pseudovector. It's an artificial construct created by mathematical rules.
That's pseudovector.
Yeah. Torque, angular momentum, angular velocity. These are all pseudovectors. The arrow doesn't point in the direction the object is actually moving.
Right, because the record player plotter is moving in a circle, but the arrow points straight up.
Exactly. It points perpendicular to the motion, purely to help us keep our mathematical ledgers balanced when calculating 3D space.
That distinction on honest polar vectors versus artificial pseudovectors feels so crucial for anyone trying to learn physics, because it suddenly explains why the math of rotation feels so alien.
Yeah.
We're basically tracking ghosts.
Tracking ghosts is a great way to put it.
So if we have these fake vectors representing twists, how do they interact? Like if I push a box north and someone else pushes it east, we just add the forces and it moves northeast. Simple. But I can't just add two twisting forces like regular numbers.
You can't. And this brings us to the mathematical engine designed specifically to handle these pseudovectors, which is the cross product.
Ugh, the dreaded cross product.
It sounds intimidating, I know, but it is just a geometric necessity for calculating how forces interact across multiple dimensions.
Okay, so how does it work?
Well, if you have two vectors, let's call them A and B, their cross product, written as A cross B, creates a brand new third vector, C.
Yeah.
And the defining magical feature of C is that it is perfectly perpendicular to both A and B.
Which means it's finding that perpendicular axis we just talked about.
Right.
But there is a really strange property here that stood out in the notes you brought us. With regular multiplication, 3 times 4 is exactly the same as 4 times 3. Order doesn't matter.
Yes, exactly.
But with a cross product, A cross B is fundamentally not the same as B cross A. If you reverse the order, the resulting arrow flips completely upside down. It becomes negative.
That is the right-hand rule in action again. Order determines direction.
I was trying to picture this and tell me if this analogy works. It's like the steering wheel of a car.
Okay, let's hear it.
If you are driving forward and you turn the wheel to the right, the car veers to the right. But if you put the car in reverse, essentially flipping the order of the operation, and you turn the steering wheel exactly the same way to the right, the front of the car sweeps left. Reversing the input flips the spatial output.
That is a brilliant way to conceptualize it. The input motion is the same, but the reverse context flips the output vector.
Yeah.
And this non-commutative math, where order matters, gives us the core rotational equations. First, torque is the radius crossed with the force.
Meaning how far out from the center you push, crossed with how hard you push.
Yes. Second, angular momentum is the radius crossed with the regular momentum. And third, the critical one, torque, is the rate of change of angular momentum.
So, if torque is what changes angular momentum, then if there is no torque, there is no change.
Precisely. That is the law of conservation of angular momentum. If there is zero external twisting force acting on a system, its total angular momentum absolutely cannot change. It is locked in.
Okay, let's step away from the equations and place you, the listener, right in the middle of a physical experiment to see how this conservation law plays out.
Oh, the first figure in the notes.
Yes, figure 24.1. Imagine you are sitting in a perfectly greased, frictionless swivel chair. You are holding a standard bicycle wheel by the pegs on its axle.
Okay, I'm picturing it.
You hold the axle perfectly horizontal, parallel to the floor. Now, a friend comes over and spins that bicycle wheel as fast as they possibly can.
At this specific moment, let's look at the pseudovectors. The wheel has a massive amount of angular momentum pointing horizontally along its axle. But importantly, around the vertical axis, the axis of your swivel chair, there is zero angular momentum. You aren't spinning. The chair isn't spinning.
So the vertical momentum ledger is at absolute zero.
Yes, exactly zero.
Now, using only your hands, you wrench that spinning wheel's axle so it points straight up at the ceiling. You turn it vertical.
This is the critical moment. By turning the axle vertical, the wheel is now spinning around the vertical axis. It suddenly has vertical angular momentum.
But wait, we just established a hard rule.
We did. The total angular momentum of the system, which is you, the chair, and the wheel combined, must remain zero around that vertical axis because no friend came over to push the chair. There's no external torque.
So the universe has to balance the books instantaneously.
It has to.
The wheel now has, let's say, a positive vertical spin. To keep the total sum at zero, you and the chair must instantly start spinning in the exact opposite direction, a negative vertical spin. And if you actually do this experiment, that is exactly what happens. You tilt the spinning wheel up, and the chair violently whips you around in circles the other way.
It feels like an invisible hand just grabbed you, but it's just the conservation of these pseudo-vectors perfectly playing out in reality. The universe refuses to let the vertical momentum change from zero.
That is just so cool. And that swivel chair trick scales up to what is arguably the most famous confounding object in all of physics, the gyroscope.
Oh, yes. Figures 20-2 and 20-3 in the source material.
Exactly. Imagine a heavy, solid metal wheel spinning incredibly fast on a short axle. You take one end of that axle and rest it on a little pivot stand. The other end is just hanging in midair.
Gravity's pulling down on the heavy wheel, desperately trying to make it fall.
But it doesn't fall. Instead, the wheel stays horizontal, and the entire axle slowly sweeps around in a horizontal circle, rotating around the pivot. This sweeping motion is called precession.
And if you try to intervene, like if you push straight down on the axle to force it to drop, it doesn't move down. It slips sideways at exact right angles to your push.
See, I refuse to just accept that. When you read the textbook explanations, they just point to the cross product.
Oh, I know.
They say, well, the downward torque from gravity crosses with the horizontal angular momentum, and the cross product creates a vector that points strictly sideways. So the math says it must move in a circle. That feels like a massive cop-out.
Feynman actually agrees with you. He makes a brilliant point about this in the notes.
Oh, he does?
Yes. He compares relying purely on the cross-product math to the Dirac equation in quantum mechanics.
Yes. Yeah.
Well, sometimes a mathematical formula works flawlessly to predict an outcome, but it completely obscures the intuitive physical reality. It tells you what happens, but it hides how it happens.
Here's where it gets really interesting for me. I want to look past the fake arrows. I want to know what the actual physical atoms of metal inside that solid metal wheel are doing to hold the thing up against gravity and make it walk sideways.
To do that, we have to look closely at the path of a single particle. Figure 20-4 really helps visualize this. Forget the abstract vectors. When the gyroscope is precessing sweeping sideways in that slow circle, the wheel is no longer just spinning in a stationary flat plane.
Right.
The whole plane is turning like a door on a hinge.
Because it's sweeping around the pivot.
Exactly. So imagine a single atom of metal on the rim of the wheel. As it travels from the bottom of the spinning wheel to the top, it isn't moving in a straight vertical circle anymore.
Oh, I see.
Because the whole wheel is sweeping sideways simultaneously, that atom traces a curved, sweeping path through 3D space.
So it's sort of like a roller coaster car entering a highly banked curve. And Newton's laws tell us that if an object with mass is moving in a curve, there must be a lateral force pushing it sideways to keep it in that curve. Otherwise, it would just fly straight off.
That is the perfect analogy. To force all those billions of metal atoms to travel in those curved paths, they require a constant lateral force.
Where does that force come from?
It originates from the pivot point. When gravity pulls down on the wheel, that downward pull levers against the pivot.
Okay.
The resulting force travels up the rigid metal of the axle, out through the solid spokes, and physically shoves those atoms into their sweeping curved paths.
Wait, but if the spokes are pushing the atoms on one side of the wheel as they go up, what about the atoms on the opposite side of the wheel that are coming down?
They are sweeping in the opposite direction, so they require a force pushing the opposite way.
Wow.
And the sheer beauty of the rigid metal wheel is that those structural forces exactly balance out. The wheel holds itself up against gravity not by magic, and not just because, quote, the cross product says so,
Right.
but because the wheel is the sum of countless physical particles constantly accelerating in curved paths. Those curved paths generate massive opposing forces within the metal structure, and the collective effort literally cancels out the downward fall.
That completely changes how I see a gyroscope. It's essentially a billion tiny roller coaster cars leaning into a curve, and their collective momentum generates the structural rigidity to hold the wheel floating in the air.
Exactly. It's profoundly physical.
But digging deeper into your notes, there is a dirty little secret about gyroscopes and spinning tops. This beautiful, steady precession we just described. It's a bit of a lie, or at least it's incomplete.
It is incomplete. The math of steady precession assumes the gyroscope is already moving sideways smoothly.
Right. But what happens if I am holding the spinning gyroscope perfectly still, keeping it horizontal, and then I just let go?
Right.
The common myth is that a spinning top is completely immune to gravity from the very first millisecond. You drop it, and it instantly glides sideways.
The truth is far messier, and figure 20-5 shows this perfectly. When you let go, the top absolutely does fall. Gravity immediately pulls it straight down.
So wait, how does it survive the fall to do the sideways sweep?
As the heavy end of the top begins to drop downward, that falling motion is technically a rotation around the pivot, but there is no balancing torque present for that specific downward turn yet.
Because it hasn't started moving sideways.
Exactly, hasn't built up the sideways curve. So as it falls, the math dictates it must start to twist sideways. It literally falls into the sideways precessional movement it needs to survive.
But because it's reacting to a fall, it goes too fast, right? It kind of panics.
Essentially, yes. It drops, twists sideways violently to compensate, and generates too much sideways motion.
An overcorrection.
Yep. That excess sideways momentum then causes it to curve back up, fighting against gravity, rising almost back to the exact level it started from.
So it's not a smooth horizontal circle at all. It traces a looping, scalloped path in the air. The notes refer to this path as a cycloid.
Yes.
I picture it like watching a bright white pebble stuck in the rubber tread of a rolling car tire. As the tire rolls, the pebble dips down to the road, loops up over the top, dips back down, loops up. This looping wobble has a specific name, doesn't it?
Yes, it's called nutation. It's the inherent wobble of a falling, spinning object trying to catch itself.
So why don't we see toy tops wobbling violently up and down like a roller coaster?
Well, because it usually happens incredibly fast. And because there are always tiny amounts of friction in the bearings or on the table surface, those looping, violent wobbles damp out almost instantly.
So it smooths out.
Yeah. Within a fraction of a second, it settles into that smooth, flat, horizontal precession we're used to seeing.
But here's the crucial takeaway, the detail that completely blew my mind. When the top finally settles out of its nutation and glides into its smooth, gravity-defying spin, its horizontal axis is actually resting a tiny bit lower than where your hand initially let it go.
It has to. It must yield to gravity just a tiny fraction of an inch to generate the vertical spin component it needs.
It is a wonderful, beautiful mechanism, but it is not magic.
Right.
It has to drop to survive. It obeys gravity, just like an apple does. It just uses its rotation to translate that downward drop into a horizontal escape route.
That's a perfect summary.
Okay, up until now, we've been dealing with ideal scenarios. Perfect symmetrical gyroscopes, perfectly balanced bicycle wheels, but the real world is messy.
Very messy.
What happens when the spinning object is irregular? Imagine a car wheel that is mounted onto its axle completely crookedly. It's horribly off-kilter.
Anyone who has ever driven a car with a badly aligned tire knows exactly what happens. It shakes violently. When you spin a lopsided, crooked wheel, centrifugal forces take over.
Like in figure 20-6.
Yes, the mass is trying to throw itself outward, away from the axis. The heavy, lopsided sections desperately want to flatten out and align perfectly perpendicular to the metal shaft.
But the rigid steel shaft won't let the wheel flatten out. So the bearings holding the shaft have to constantly exert a massive changing torque, a twisting pressure, just to force the lopsided wheel to stay in its crooked spin.
And exploring this reveals a truly startling truth in physics. In an irregular, lopsided rotating body, the angular momentum vector, our pseudo-vector pointing out the twist, and the angular velocity vector, the arrow, representing how fast and in what direction it's physically spinning, are not pointing in the same direction.
That is so wild to visualize. The object is physically spinning cleanly around the solid metal shaft, but its angular momentum arrow is pointing off at some weird diagonal angle, wobbling around in a circle as the wheel spins.
Yes. Because the physical mass is unevenly distributed, the momentum is skewed.
Right.
And because that momentum arrow is constantly sweeping around in a circle, constantly changing direction, the conservation laws demand there must be a continuous torque applied to the system to account for that change.
Which causes the shake.
Exactly. That required torque manifests as the violent, destructive shaking you feel in the bearings of the car.
So how does nature handle lumpy, asymmetrical, irregular objects? How do we find balance?
I love this analogy. Think of carrying a heavy extension ladder.
Okay, let's use that. If I hold a heavy ladder perfectly horizontally across my chest, like a tightrope walker holding a pole, and I try to spin around in a circle rapidly, it's incredibly hard. It requires massive force to start spinning, and it's almost impossible to stop.
Exactly. But what if you stand the ladder straight up vertically, hug it tight to your chest, and spin in a circle?
It's super easy. I can spin like an ice skater.
The mass of the ladder hasn't changed, but its distribution relative to your spin axis has. This resistance to rotational change is called the moment of inertia.
Okay.
The horizontal ladder has a maximum moment of inertia. The vertical ladder has a minimum moment of inertia.
Okay, so how does this help us with a lopsided, shaking object? The source material makes an incredible promise here about a potato.
If we connect this to the bigger picture, this is where the geometry of physics provides a truly elegant solution. Figure 27 illustrates this beautifully. Feynman points out that absolutely any rigid body in the universe, no matter how irregular, no matter if it is a completely lumpy, asymmetrical, ugly potato, has a hidden geometric perfection locked inside of it.
Principal axis.
Precisely. Passing through the exact center of mass of that lumpy potato, there exist three perfect, mutually perpendicular straight lines. Axes.
3 magic lines hidden in the lump.
They are magic. One of these axes represents the path of maximum moment of inertia, meaning if you skewer the potato on this line, it's the absolute hardest way to spin it.
Like the horizontal ladder.
Right. Another axis perfectly 90 degrees to that one represents the minimum moment of inertia, the absolute easiest way to spin it. And the third axis is exactly intermediate between the two.
And what makes them magic is that if you can perfectly skewer that potato along any one of these 3 specific axes and spin it, it will spin flawlessly smoothly. The violent shaking vanishes entirely.
It just disappears.
The angular momentum vector and the angular velocity vector will finally snap into perfect alignment.
Nature guarantees that no matter how chaotic, messy, or random an object's shape is, there are always 3 perfect orientations where it behaves exactly like a beautifully balanced, symmetrical toy top.
That is just phenomenal. You take this messy, real-world object, and math uncovers these 3 perfect, invisible lines of symmetry hidden inside.
It's quite poetic.
It really is. Okay, let's take a breath and recap the incredible journey you've sent us on today with these notes. We started by realizing that to handle twists in 3D space, we had to invent fake pseudovectors and use cross products just to keep track of the math.
Yeah.
We use those concepts to explain the swivel chair experiment, how forcing vertical spin suddenly makes the chair kick back in the opposite direction to keep the momentum ledger at zero.
Right.
We then pushed past the equations to peer inside the solid metal spokes of a precessing gyroscope, debunking the miracle by seeing it's just the sum of atoms moving in roller coaster curves.
Yeah.
We exposed the dirty secret of tops, that they actually fall, overshoot, and nutate in a looping path, dropping slightly to survive gravity. And finally, we discovered the principal axis, the hidden structural lines that let you spin a chaotic potato perfectly smoothly.
It is an incredible tour of physical mechanics, but there is one final, almost philosophical point tucked away in Feynman's notes on dimensions that I think we need to leave the listener with today.
Oh, I know what you're going to say.
We've talked so much about how lucky we are that 3D space works this way.
Right, the geometric miracle of good luck that lets us draw one perpendicular line to represent a twist.
Yes. All of these neat tricks, the pseudovectors, the right-hand screw rule, the very ability to assign a single perpendicular arrow to represent a spinning plane, they only work because we live in exactly 3 spatial dimensions.
Wait, what happens if we didn't?
Think about a 4-dimensional universe. Let's say we add time as a physical 4th spatial dimension. In a 4D universe, you don't just have 3 planes of rotation. You have the XY plane, the YZ plane, and the ZX plane. But you also have flat planes involving time. The TX plane, the TY plane, and the TZ plane. That is 6 independent planes of rotation.
Oh, wow.
You cannot uniquely represent 6 distinct twisting planes by drawing a single perpendicular vector. In 4 dimensions, the geometry literally runs out of room.
Wow.
The entire mathematical framework of cross products, pseudovectors, and the right-hand rule that makes a gyroscope understandable to us today would completely disintegrate.
That is a staggering thought. The math isn't a universal truth of all reality. It's a specific quirk of our 3D home. So as you go about your day, moving through our 3-dimensional world, maybe you see a kid spinning a top on a sidewalk, or maybe you're just turning the steering wheel of your car. Consider how uniquely lucky we are. The very specific restricted geometry of our universe is exactly what allows a spinning top to balance at all.
It's definitely something to think about.
Thank you so much to you, our listener, for bringing such an incredibly dense, fascinating set of sources to the table. This deep dive into the hidden rules of rotation was an absolute blast. Keep spinning and keep questioning.
You look at a toddler, right? And what is like the very first bit of math they ever actually learn? They hold up their little hands and they match physical objects to their fingers, 1, 2, 3, 4, 5. It is just the most tactile, intuitive, fundamentally human act imaginable.
Oh, absolutely. I mean, it is completely grounded in physical reality. You have, say, 3 wooden blocks, you add 2 more, and you can literally touch all 5 of them.
Exactly. But if you fast forward through a few centuries of human thought, that simple act of counting on your fingers somehow, and we're going to see how today leads us to what the legendary physicist Richard Feynman called the most remarkable, almost astounding formula in all of mathematics.
Yeah, it really is a massive leap. You go from those wooden blocks on a rug to these equations so bizarre that they literally bend space and geometry and, well, totally imaginary concepts together into a single line.
And tracing that exact journey is our mission for you today. Welcome to our deep dive into Chapter 22 of the Feynman Lectures on Physics. We are going to unpack the grand design of elementary algebra, translate all the complex terminology into plain English, and hopefully experience the sheer joy of mathematical discovery. Because, Feynman firmly believed that science is as much for intellectual enjoyment as it is for practical utility.
He really did. He just detested the artificial walls we build between subjects. Like, you know how we often put math and physics in completely different buildings on a university campus?
Oh, yeah, definitely.
We treat one as this abstract set of puzzles and the other as the gritty real world. But Feynman tears those walls down completely. He wants us to see this, what he calls the great map of how arithmetic naturally evolves into algebra, and how algebra inevitably discovers geometry.
So let's start mapping. To understand how we get to that astounding formula, we really have to look at how math grows. It starts with those direct operations we mentioned. Addition is simply successive counting. Multiplication is successive addition. And powers like 3 to the 4th power, well, that's just successive multiplication.
Right, and every one of those direct actions has an inverse operation. So subtraction undoes addition, division undoes multiplication, and powers actually have two inverses roots, like taking a square root and logarithms.
And this setup, this is where our first real crisis occurs. Because when you only have positive whole numbers, those counting fingers, you inevitably create an equation that just breaks reality, like something like 3 minus 5.
Yeah, you cannot take 5 apples away from 3 apples. It is physical nonsense.
Right. Under the strict rules of counting objects, it is totally impossible. But mathematicians employ a strategy here, and the sources call it abstraction and generalization. Instead of throwing their hands up, they ask this profound question: what if the rules of the operation are more fundamental than the numbers themselves?
That's the turning point.
But let me push back on that for a second, though, because if we are just like defining our way out of a problem, aren't we abandoning reality? I mean, if physics is about measuring the real physical universe, how does making up a rule to solve a puzzle help us measure an actual atom? It feels a bit like we're just coding more map in a video game because we don't want the game to end.
That's a totally valid skepticism, honestly. But think about it this way. The universe operates on consistent logic. The rules, like the fact that A plus B must equal B plus A, represent that underlying logic.
Okay, I track that.
So by demanding that the logic still holds, even when the physical analogies fail, we actually discover new dimensions of reality. We invent negative numbers to solve 3 minus 5. We basically say, let's assume a number exists that makes this true, and let's see if it breaks the rest of math.
And it doesn't break.
It doesn't. So the rules define the numbers. When division fails, like trying to divide 3 by 5 evenly, we invent fractions. The logic demands they exist.
And when roots fail, like trying to find the exact fraction for the square root of 2, we invent irrational numbers, right? Those unending decimals.
Precisely. The map keeps expanding, not because we are making up arbitrary fantasies, but because we refuse to abandon the logical structure.
But that expansion brings a pretty serious consequence. We've expanded our universe of numbers to include negatives and fractions and these unending irrational decimals, but now we face this massive computational nightmare. Like, how do you actually calculate something like 10 to the power of the square root of 2?
You really can't. You can't just multiply 10 by itself square root of 2 times. The physical analogy of successive multiplication is completely broken at that point.
Which means we need a new tool. And historically, this is where a man named Mr. Briggs of Halifax enters the picture, around the year 1620. And I gotta say, the sheer grit of this guy is unbelievable.
Oh, it's staggering.
To figure out how to calculate these fractional and irrational powers, he sat down and calculated successive square roots of 10, over and over by hand, to 14 decimal places.
Yeah, that kind of grunt work was necessary to build the very first tables of logarithms. And maybe we should define that term quickly, because logarithm often scares people off.
Please do. Yeah.
A logarithm is simply the inverse of an exponent. That's it. If 10 to the second power is 100, then the logarithm base 10 of 100 is 2. It's just asking, to what power must we raise our base to get this target number?
And Feynman insists logarithms are just as elementary as taking a simple square root. They aren't this alien math, but computing them required Briggs to do something extraordinary, which is laid out in table 22-1 of our sources.
Right, the successive roots.
Exactly. Briggs took the square root of 10, then the square root of that result, then the square root of that. Mathematically, he was raising 10 to the half power, then the quarter power, then the eighth power, literally cutting the exponent in half every single time.
And as you keep cutting that power in half, the resulting number gets closer and closer to 1. 10 to a very tiny fraction is just a little more than 1.
And Briggs noticed this beautiful, consistent pattern fall out of all this brute force work. If you raise 10 to a very, very small power, let's call that small power epsilon, the result is roughly 1 plus 2.3025 times epsilon.
Right.
So 10 to the power of epsilon is approximately 1 plus 2.3025 epsilon.
And that multiplier, that 2.3025,
Yeah.
is a constant that emerges specifically because we are using 10 as our base.
Yeah.
It is the scaling factor for base 10.
Which raises a crucial question, I think. Why 10? Like, is there a deep cosmic mathematical reason for base 10?
Not at all. It is entirely biological.
Because of the fingers.
Exactly. We have 10 fingers. If we had 8 fingers, Briggs would have been calculating the square roots of 8, and he would have found a completely different constant multiplier.
And that biological bias really annoyed mathematicians, didn't it? They wanted a base that was mathematically natural, something woven into the logic itself, not just based on our anatomy.
They did, and to find it, they looked at that constant, 2.3025. They asked what base would we have to use so that this constant multiplier is exactly 1.
Oh, I see.
They wanted the cleanest possible relationship, where a number raised to a tiny power epsilon is simply 1 plus epsilon.
So no messy human scaling factor.
Exactly. And to do that, you mathematically divide out the 2.3025, you shift the scale. And when you do, the base that gives you a perfect multiplier of 1 is an irrational number approximately equal to 2.718. We call it E.
E. So by stripping away our 10 fingers, we discover E, the natural base. Our map expands again. We have negatives, fractions, irrationals, and natural bases. But the sources point us to one final, seemingly insurmountable crisis. The equation x squared equals -1.
Yeah, that's the big wall. Because what number multiplied by itself gives you a -1? A positive times a positive is positive,
Right.
and a negative times a negative is also positive. Nothing works.
But following our strategy of abstraction and generalization, we know exactly what to do. We just invent a number that makes it work. We invent E, the unit imaginary number, defined simply as the square root of -1, so I squared equals -1.
And this creates what we call complex numbers. Let's clarify the structure here for everyone. A complex number is typically written as P plus IQ. The P is your regular real number. The IQ is the imaginary part. It is a hybrid number.
The sources also mention the complex conjugate, which honestly sounds really intimidating.
It does, but think of the complex conjugate as just a mathematical mirror. If you plot a complex number on a graph, say 2 units right and 3 units up, so 2 plus 3i, its conjugate is the exact same point mirrored below the axis.
So 2 minus 3i.
Exactly, 2 minus 3i. And this mirroring is incredibly useful because if you multiply a complex number by its conjugate, the imaginary parts perfectly cancel each other out, dropping you right back into the purely real world.
Okay, here is where my skepticism kicks in again, and I think a lot of you listening were probably going to wonder the same thing. If we invent I to solve squares what happens when we hit an equation like x to the 6th power plus 3x squared equals -2?
That's the logical next question.
Are we going to need super imaginary numbers? Will we eventually need a whole alphabet of invented concepts just to keep the math working every time we hit a snag?
It's the most logical assumption. You'd think the expanding map just never ends. But this is where we encounter what can only be described as a mathematical miracle. I is the last invention.
Wait, really? The map just stops?
The map is complete. This concept is tied to the fundamental theorem of algebra. With the creation of complex numbers, every single algebraic equation can be solved. The rules of addition, multiplication, and powers that we established for positive integers still hold up flawlessly. You never need to invent another class of numbers again.
Just by defining the square root of -1, the entire system is fully unlocked. That is absolutely astonishing. So let's mash these concepts together. We have our natural base E, we have our exponent rules, and we have our imaginary number I. What happens when you raise a number to an imaginary power? What is 10 to the power of I times s?
This is the territory where the magic really happens. We need to compute 10 to an imaginary power. And how do we do it? We rely on the exact same trick Mr. Briggs gave us. We assume the rules still hold.
Let's pause for the listener here, because the sources drop a lot of decimals, and I want to make sure we all clearly see the mechanism. We use the small power trick. We know that taking 10 to a tiny fraction, like over 1024, gave Briggs a tiny number plus 1.
Right.
If we make that tiny power imaginary, so I over 1024, our rule tells us the answer should be roughly 1 plus 0.000222486i.
And once you have that tiny foothold, you don't need any new tricks. You just start squaring it. You multiply it by itself to find the power of I over 512, square it again for I over 256, you systematically build table 22 to 4 in our sources.
And when you map out the results of those imaginary exponents, let's call the result x plus iy, an unbelievable pattern emerges. Think about normal exponents, like driving a car down a straight highway. 2 to the 2nd, 3rd, 4th power. The numbers just get larger and larger, accelerating toward infinity.
Yeah, but imaginary exponents fundamentally change the steering.
Right.
Actually, expand on that analogy for a second. Why does it change the steering?
Well, think about multiplication geometrically. If multiplying by 1 is driving forward, multiplying by -1 is an instant U-turn. You flip a full 180 degrees backward on the number line.
Yes, negative numbers represent opposite direction.
Exactly. And since I times I equals -1, multiplying by I must be exactly half of a U-turn. It is a 90-degree rotation.
A right turn.
Right. So when you raise a number to an imaginary power, you aren't driving straight anymore. You are continually turning the steering wheel 90 degrees. As the power increases, the values for x and y don't shoot off to infinity. The x value decreases, passes through 0, drops to -1, and swings back up. And the y value does the exact same thing, just offset.
They oscillate. They are periodic functions. Because you are constantly turning, you are essentially driving in a loop.
You are tracing a perfect circle. And this realization leads us directly to the grand finale of Chapter 22. What do those oscillating x and y curves actually look like? The sources spell it out. They are exactly the sine and cosine waves from trigonometry.
The very same sine and cosine you use to measure the angles of triangles and the geometry of circles. By merely pushing the algebraic rules of counting and fractions to their logical limits, we accidentally generated the fundamental curves of physical geometry.
It is wild. And to make the timing of those geometric waves line up perfectly, we drop our human base 10 and switch back to our natural base e. When you do that, the formula solidifies. The real part, x, becomes the cosine of the angle. The imaginary part, y, becomes the sine of the angle.
And we arrive at Euler's formula. E to the power of I theta equals cosine theta plus I sine theta.
Visualize figure 22-2 from the text for a second. Imagine a flat piece of graph paper. The horizontal line is our real numbers. The vertical line is our imaginary numbers. Any complex number is just a dot somewhere on this paper.
Right, and if you draw a straight line from the center out to that dot, the length of your line is r. The angle that line makes with the horizontal axis is theta.
So using algebra, the exact location of that dot is r times e to the power of I theta. You've taken an abstract algebraic equation and mapped it perfectly onto physical geometric space. Algebra and geometry, distinct subjects taught in entirely separate classrooms, are entirely unified.
It is the ultimate synthesis. We started with toddlers counting fingers. We refused to let our logic break when faced with 3 minus 5. We endured the grueling century of calculating log tables by hand. We took the huge leap of faith to invent the square root of -1. And it culminated in the realization that raising a natural number to an imaginary power traces a perfect circle.
Which brings us to the true jewel. Feynman promised us the most remarkable formula in mathematics. Euler's formula is the engine, but the actual payoff Euler's identity happens when we apply it to a specific point on that circle.
Let's walk the listener through it. Our formula is e to the I theta equals cosine theta plus I sine theta. Theta is our angle. What happens if we plug in pi for theta?
Pi represents exactly half a circle, a 180-degree rotation. If you look at the geometric waves at half a circle, the horizontal x value, the cosine of pi, is exactly -1.
And the vertical y value, the sine of pi, is exactly 0. The imaginary part completely vanishes.
So the equation simplifies radically. E to the power of I pi equals -1. If you just move the -1 to the other side of the equal sign, you get it. E to the power of I pi plus 1 equals 0.
There it is, Euler's identity. Just look at what is in that single, elegant line. The 5 most important constants in all of mathematics finally united.
You have 0, the concept of nothingness. You have 1, the foundation of counting. You have pi, the geometry of space. You have I, the imaginary bridge of algebra. And you have E, the natural base of continuous growth. All of them, perfectly balanced.
It is profoundly beautiful, and it leaves us with an inescapable philosophical question.
Yeah, because we started this deep dive talking about inventing math. We defined negatives, we invented fractions, we formulated I just to make our puzzles work. We thought we were just making up the rules to a game.
But if our arbitrary game of algebraic logic flawlessly generates the exact geometry of circles in physical space, if it miraculously ties together E, pi, I, 1, and 0 without us ever actively planning it.
Did we actually invent any of this? Or did we just uncover a fundamental code that was already written into the fabric of the universe? It really makes you wonder what else is hiding in the simple act of counting on your fingers.
You know, when you sit down at a solid oak table, or even just tap the screen of the device you're listening to right now, there's this fundamental expectation of, well, solid reality.
Right. Yeah. It feels fixed.
Exactly. It feels sturdy.
It's comforting, honestly. I mean, human beings are basically wired to perceive the physical world as this collection of static, unmoving building blocks.
But then you peel back the layers of how the universe actually works, and suddenly that solid reality isn't really solid at all.
No, not even a little bit.
We're looking at a landscape of just constant invisible motion. And today, we're cracking open a really fascinating stack of physics lectures for our deep dive to uncover, like the single mathematical blueprint holding all that motion together.
Which is resonance.
Resonance, yes.
Yeah.
We're going to decode this bizarre mathematical trick that physicists use to understand vibrations. And then we're going to trace how this exact same blueprint dictates everything from the sloshing of Earth's atmosphere to the discovery of subatomic particles.
Yeah, and the true beauty of the physics we're exploring today, it isn't just in isolating a single event. It's in recognizing the universal patterns. Because the sources show us that whether you're studying the microscopic structure of a salt crystal, or tuning a radio circuit, or even observing a violent nuclear reaction, nature is secretly relying on the exact same equation.
Which is mind-blowing.
Yeah.
But before we can take that grand tour of the universe, we have to unpack the math. And if you're listening to this, you probably remember the classic everyday example of resonance from grade school.
Pushing a kid on a swing.
Exactly. You time your pushes to match the natural rhythm of the swing, and the child goes higher. It seems simple enough.
It does seem simple, but calculating the exact movement of that swing, or really any driven oscillator, it gets incredibly complicated very, very quickly.
So why is it so messy?
Well, to understand the solution physicists came up with, we first have to understand the problem. So imagine a mass attached to a spring. You are applying a driving force, right? Pushing and pulling it.
Okay, I'm picturing it.
Trying to calculate that movement involves these nasty differential equations filled with sines and cosines.
Which, if you remember your calculus, can turn into a massive headache.
A huge headache. And it comes from the feedback loop. As the mass moves, its position changes.
Right.
And that changes the tension in the spring, which alters the force. Then a changed force updates the acceleration, which constantly updates the velocity, which then changes the position all over again.
It's just an endless cycle.
Exactly. Trying to track that constant feedback loop using sine and cosine waves is mathematically tedious. Every time you take a derivative to find the velocity or acceleration, a sine becomes a cosine, and a cosine becomes a negative sine. You are basically constantly chasing your tail through trig functions.
Okay, so here's a way to visualize the problem for you listening. Imagine you're trying to navigate across a major congested city during rush hour.
Oh, sounds awful.
Right. Driving through it using sines and cosines is like taking the surface streets.
Yeah.
You hit stoplights, you deal with unpredictable pedestrians, you're constantly stopping and starting. It takes forever.
Right.
So instead of dealing with the surface traffic, the physicist essentially invents a secret underground tunnel to bypass the traffic entirely.
And that tunnel is the concept of complex numbers. By moving the problem off the surface streets and into the complex plane, we can completely avoid sines and cosines.
Okay, but let me play devil's advocate here. To solve a problem about a real physical mass on a real physical spring, you're saying we have to pretend the physical forces have an imaginary component.
Yeah.
Like using the square root of -1. How does that not just completely break physics?
I know, it sounds totally counterintuitive, but it is a brilliant workaround. By pretending the real physical force has an imaginary part attached to it, we can represent our oscillating wave not as a sine or cosine, but as an exponential function.
Okay.
And the beauty of an exponential function is its behavior when you take a derivative.
Because the derivative is just the rate of change, right? We're trying to find out how fast the spring is actually moving.
Exactly. When you take the derivative of this complex exponential function to find the velocity or the acceleration, you don't have to go through a convoluted transformation. The function stays exactly the same. You simply multiply it by a factor of the imaginary unit. It's times the frequency.
Wait, I really want to make sure the gravity of that shortcut lands for you.
Yeah.
Differentiation, which is normally this complex, multi-step calculus operation, literally just becomes basic grade school multiplication.
Yes. The calculus traffic jam just disappears. The lectures emphasize this point heavily. This trick allows you to look at a terrifying differential equation and literally just by sight turn it into a mere algebraic equation.
Wow.
It condenses pages of tedious calculus into a single line of algebra.
Okay, but there has to be a catch. Because I can't go to the hardware store and buy an imaginary spring. Nature is real.
Nature is real, yes, and actual physical forces do not have an imaginary part. That's the catch.
So what do you do?
Well, After you take your mathematical tunnel, after you do all this incredibly fast, easy math using multiplication in the complex plane, you get a complex number as your final answer. To get back to reality, you simply take the real part of that final number.
You just throw the rest away.
You deliberately ignore the imaginary part that you use to make the math easy, yeah. And what remains perfectly describes your physical reality.
That feels like cheating.
It does. Now, it only works for linear equations where variables don't multiply each other in complex ways, but for solving these vibration problems, it is a flawless shortcut.
Okay, so we take our tunnel, we bypass the calculus, and the map spits out a formula for our vibrating spring. But looking at the resulting equation from the source, there's a very dangerous implication hidden in the denominator.
Oh, yes, the division by zero problem.
Right, if you have a perfect oscillator, and you drive it, you push the swing at exactly its natural frequency. The denominator of the equation mathematically drops to zero.
And dividing by zero in this context means the mathematical response shoots up to infinity.
Which means the system would literally tear itself apart. Like, if I push a child on a swing with perfectly timed pushes, the math suggests they should eventually swing into orbit.
Right, because every single time you push, energy is added and the amplitude just grows forever.
But in the real world, things don't infinitely explode. Bridges don't instantly vaporize when the wind blows at their exact natural frequency.
Thankfully, no. And this raises a really fundamental question about the mechanics of the universe. Why doesn't nature shatter into a million pieces every time something vibrates perfectly?
Because the universe protects itself, basically,
Yep.
with damping. Or, in everyday terms, friction.
Right. The universe is a messy, sticky place. There's air resistance, there's heat loss. The source text introduces a damping term, represented by the Greek letter gamma.
Gamma. Okay.
But this friction is not just a constant, unchanging force. It is actually proportional to velocity. Imagine you're trying to move your hand through a pool of thick oil.
Okay, I can picture that.
If you move your hand very slowly, the resistance is mild. You barely feel it. But if you try to violently slash your hand through that same oil, the fluid pushes back with immense force.
Oh, so the faster the spring tries to bounce, the more violently the friction works to slow it down. It fights back harder.
Exactly. So when we feed this new velocity-dependent friction term back into our complex number equation, it prevents that denominator from ever hitting zero. And this generates a really fascinating shape.
The bell-shaped resonance curve.
Yes. If you were to look at a graph of this curve, the vertical axis represents the square of the amplitude, basically the total energy developed in the system. And the horizontal axis is the frequency of your pushes.
Okay, so as you approach the natural frequency of the object, that sweet spot, the energy on the curve spikes dramatically.
But thanks to that friction term, gamma, the peak never reaches infinity. The friction literally rounds off the top of the bell curve.
It acts as nature's safety valve. I mean, without it, the universe wouldn't be stable enough to exist.
It really wouldn't. And the math also exposes another deeply counterintuitive detail about how things move. The displacement of the spring actually lags behind the driving force. There's a phase shift.
Wait, what does that actually look like in practice?
It means you push the system, but the system hesitates for just a fraction of a second before reaching its maximum swing. The force and the movement are completely out of sync.
Oh, that makes intuitive sense if you picture fighting through that thick oil we mentioned earlier.
Yeah.
You apply the force immediately, but it takes a moment for the object to plow through the resistance and actually reach its destination.
Precisely. And this friction concept leads directly into a term physicists use all the time, the Q factor, or quality factor.
And the math for this is delightfully simple, right?
Yeah, it's just the natural frequency of the object divided by gamma, or friction. Q is fundamentally a measure of how narrow and sharp that resonance peak is.
So if gamma is the friction, a tiny gamma means almost zero friction. And dividing by a tiny fraction gives you a massive number, a massive Q factor.
Right.
Think of a flawless, high-quality tuning fork. You strike it once, and it rings pure and clear for a very long time because there is almost no friction to steal the energy. It has a massive, sharp response at one specific frequency.
Exactly.
But a low Q factor. That's like taking a baseball bat and thumping a feather pillow. The friction of the feathers absorbs the energy immediately. There's no sustained ringing, just a dull thud.
That's a great analogy. The width of the peak on the resonance curve, if you measure it at exactly half of its maximum height, is precisely equal to gamma. The friction dictates the entire physical profile of the vibration.
Wow. And this is where the story takes a massive leap, I think. Physicists spend all this time perfecting the math for a mechanical mass bouncing on a spring, fighting through friction. And then they look over at an entirely different field of science and realize they didn't just solve a mechanical problem.
They accidentally solved electrical engineering, too.
Which is just crazy to me. The translation between these two worlds in the source text is astonishing. In a basic electrical circuit, you have three passive elements. And mathematically, they mimic the physical parts of our spring with perfect precision.
It's almost too perfect.
Let's map this out for everyone because it feels like a glitch in the matrix. First, you have a capacitor. This is a component that stores electrical charge and voltage.
Right, and in the equations, the capacitor acts just like the physical stiffness of a mechanical spring. It stores potential energy and pushes back.
Okay, then you have a resistor, which restricts the flow of electricity.
That maps perfectly to our gamma. It is the friction. It's the thick oil dragging on the electrical current, bleeding off energy as heat.
So that leaves the third piece, the inductor. Now, I can visualize a spring, but how does an electrical coil act like a mechanical weight?
Well, it comes down to inertia. If you try to push a heavy boulder, its mass resists moving, right? And once you finally get it rolling, it stubbornly resists stopping. An inductor is just a coil of wire. When you push electricity through it, it doesn't just flow, it creates a magnetic field.
Oh, I see.
That magnetic field acts identically to the boulder's inertia. It fights any sudden change in the current. It takes effort to build the field and get the current going, and once it is flowing, the collapsing magnetic field keeps pushing the current forward, even if you try to shut it off.
So the math truly does not care whether you're talking about chunks of metal bouncing around or invisible electric fields flowing through copper wire.
Not at all. The differential equation for an LCR circuit that's inductor, capacitor, resistor is identically the same as the mechanical mass on a spring.
Identically.
Yes.
Yeah.
You just swap physical displacement for electric charge and physical velocity for electrical current. And out pops the exact same bell-shaped resonance curve.
So tuning your car radio to capture a specific station's frequency is mathematically indistinguishable from a swing going high when you push it at the perfect time.
It is the same underlying reality, just wearing different clothes.
Though it is worth noting a slightly petty detail about human nature hidden in all this elegant math that the text points out.
Oh, the letters. Yes.
Right. Physicists love using the letter I for their imaginary numbers in that shortcut tunnel we talked about earlier. But electrical engineers completely refuse to use I.
Well, the engineers already used I to stand for electrical current. Using it for imaginary numbers would have created total chaos in their formulas.
So they stubbornly insisted on using the letter J instead. And then they went even further. They invented an entirely new term called complex impedance, designated by the letter Z.
Yep.
And they did this purely so their alternating current equations could look exactly like the classic Ohm's law, voltage equals current times resistance that they learned when they were kids. It's hilarious.
It really is.
You realize how much of the perceived difficulty of science isn't the universe being complicated, it's just different departments of humans arguing over which letters to use to describe it.
It's a humbling reminder that our equations are just human languages trying to describe non-human phenomena. But semantic arguments aside, this resonance blueprint really is everywhere. The material takes us on a tour of the universe to prove it.
Let's do that. Let's leave the radios and springs behind and look at the macro scale. Because this resonance curve is hiding in plain sight. The first example the lectures provide is the Earth's atmosphere.
Yeah, the atmosphere that blankets our planet is actually an enormous oscillator. It is constantly being driven, squashed, and pulled by the gravitational tidal forces of the moon.
So the moon is essentially the person pushing the atmospheric swing.
Exactly. Because it's a driven oscillator, physicists knew they could calculate its natural frequency, its giant resonance curve, just based on the lunar tides. But for a long time, it was purely theoretical because, how do you practically test the natural ringing frequency of the entire sky?
You wait for a hammer big enough to ring the bell? The lectures point to the historic explosion of the Krakatoa volcano in 1883. It blew an island apart with so much force that the shockwave hit the atmosphere like a giant mallet. The atmosphere literally sloshed back and forth around the entire globe.
And when they measured the ringing, the actual natural frequency of the sky, it was exactly 10.5 hours.
Which perfectly matched the resonance curve calculated from the lunar tides. It's just wild.
From the macro scale of the entire planet, we can actually zoom all the way down to the micro scale. The lectures examine a simple sodium chloride crystal, table salt.
Okay, so we're looking at salt now.
Yeah, it's a lattice made of alternating positive sodium ions and negative chlorine ions.
But how do you ring a tiny salt crystal like a bell?
You hit it with high-frequency infrared light.
Ah, light.
The electric field of the incoming light pushes the positive charges one way and the negative charges the opposite way. It drives them to oscillate. And when you measure how much of that infrared light the crystal absorbs at different frequencies, you get our familiar bell-shaped resonance curve.
Okay, but the data reveals a crucial nuance about the width of that curve.
Right.
Our gamma, our friction. Sometimes the curve on the readout looks wider or blurrier than the pure math says it should be.
Yes. And understanding why requires looking past the raw data. Is the curve wide because of the natural friction inherent in the crystal lattice?
Right.
Or is the physical crystal strained and cracked, meaning different sections are vibrating at slightly different frequencies, blurring the total curve? Or, and this is often the case, is it simply human error? Is the physical slit on the spectrometer the scientist is using just too wide to measure the light accurately?
The human element, once again, mudding up the perfect mathematical blueprint.
Always.
But the ultimate test of any physics concept is whether it holds up when the classical rules break down entirely. We have to go to the quantum realm.
Oh, absolutely. The material shows a graph of lithium atoms being bombarded with protons, emitting gamma rays as a result. You get the exact same resonance curve, but the horizontal axis is no longer frequency.
It's energy.
Yes, energy.
Because at the everyday scale, we think of frequency as how fast the swing goes back and forth. But at the quantum level, frequency and energy are intrinsically linked. They're practically synonyms.
Correct. So the resonance peak doesn't just show a favored vibration speed, it shows a favored energy state.
Which brings us to the Musbauer effect, which might be my favorite part of the source text.
It's incredible.
Dr. Musbauer won a Nobel Prize for measuring a nuclear energy resonance of staggering precision. If you recall our Q factor from earlier, the sharpness of the tuning fork, his nuclear resonance had a Q factor of 10 billion.
10 billion.
10 billion. The peak was so unbelievably narrow, meaning the friction was practically non-existent.
Yeah, and the methodology for how they even found a peak that narrow is mind-blowing. If their frequency was off by even a microscopic fraction, they would miss the peak entirely.
That would just look flat.
Exactly. The equipment couldn't be tuned finely enough to hit it, so to scan for it, they had to use the Doppler effect.
Okay, so the Doppler effect is what makes a passing ambulance siren sound higher in pitch as it approaches you and lower as it speeds away, right? The motion compresses or stretches the waves.
Yes. To change the frequency of the gamma rays hitting the target, they physically put the radiation source on a track and moved it. And the resonance was so delicate, they only had to move it at a walking speed.
Wait, really? A walking speed?
Just a few centimeters per second. That was enough to stretch the waves, shift the frequency, and find this incredibly sharp peak.
It's just a triumph of experimental physics. But if we follow this blueprint to the absolute deepest level of reality, we reach the final concept in the material: high-energy particle physics.
Right.
Imagine a K- meson, which is a specific type of subatomic projectile being fired into a proton to produce new, strange particles.
When you look at the graph of that violent subatomic collision, plotted against the energy of the impact, what do you see? You see a massive bump. You see our exact same bell-shaped resonance curve.
The identical mathematical curve is the mass on a spring and the sloshing atmosphere.
But here's where it gets weird. In the world of quantum mechanics, a really sharp resonance peak on an energy graph literally is a particle.
I need you to clarify that. A peak on a graph is a physical particle.
Well, when a resonance is that incredibly sharp, it corresponds to a very specific, definite energy state. And it acts exactly as though there is a distinct physical particle present for that fleeting moment. The physics community faces a profound semantic question here.
What's the question?
At a certain point, when observing these quantum collisions, we honestly do not actually know whether it is more accurate to call it a newly created short-lived particle or simply a resonance in the reaction probability.
Let me make sure I am fully grasping the scale of what we've uncovered today. We started with the mathematical trick, a way to avoid doing messy calculus by pretending numbers are imaginary.
Right.
That trick gives us a bell curve. We apply that curve to a physical spring. Then we realize it perfectly governs electrical circuits. We find it in the sloshing of the Earth's sky after a volcano erupts. We find it in table salt and nuclear radiation. And now, at the very bottom of reality, The fundamental building blocks making up our universe might just be sharp little resonance peaks on a probability graph.
The distinction between a solid thing and a temporary vibration begins to dissolve entirely. The math does not distinguish between the two.
That is staggering.
Yeah.
We have gone from a kid swinging on a playground to the very fabric of existence, all tied together by one elegant mathematical shape.
It really leaves us with a lingering concept to ponder, doesn't it? If what we call solid matter and subatomic particles are mathematically indistinguishable from mere resonances, temporary vibrations in energy, then what does that mean for the solid reality you interact with every day?
Yeah.
Are you, the chair you're sitting on, and the ground beneath your feet, ultimately just an incredibly complex, stabilized symphony of interacting vibrations?
The solid world isn't solid at all. It's just ringing. Thank you for joining us on this deep dive into the source material. Keep looking for the invisible curves and vibrations that shape the world around you. They really are everywhere once you know how to look.
I want you to imagine a giant, beautiful grandfather clock, the kind with a massive brass pendulum swinging back and forth.
Yeah, the really heavy ones.
Right, exactly. So you pull that pendulum back, you let it go, and it just ticks steadily for days. But now I want you to imagine trying to build that exact same clock, but making the pendulum entirely out of a fluffy down pillow.
Well, I mean, one of those systems is going to tick for a week with almost no effort, right? The other, the pillow, won't even make it past a single second before it just stops completely dead.
Yeah, and the difference between them comes down to this really fascinating hidden phase of physics. It's a specific window of time that happens the exact moment a system stops being pushed and is just, left to its own devices.
Right, the winding down phase, or as physicists call it, the transient.
The transient. Today, we are cracking open Chapter 24 of the legendary Feynman Lectures on Physics. This is our deep dive into the hidden machinery of systems that are left to wind down on their own.
Yeah, from mechanical springs to, like, complex electrical circuits. It's really about the transition from a state of being actively driven by an outside force to just returning to a natural resting state.
Which we see all the time, right? Like every time a kid hops off a playground swing and the swing slowly dies down.
Exactly. But the underlying mechanics of that transition, how the universe manages that drain of energy, are incredibly profound. Feynman doesn't want you to just memorize the fact that a swing slows down.
No, of course not.
He wants you to understand the intricate interplay of forces dictating the exact shape of that slowdown. And how the math we invent to track it sometimes has to play clever little tricks on us just to reflect reality.
Okay, let's unpack this, because before we can really grasp the transient, the dying down of a system, we first need to understand the healthy patient.
Right, the steady state.
Yeah, we need to look at what the system looks like when it is running perfectly.
So when a system is being continuously driven, like you constantly giving that grandfather clock pendulum a tiny tap at just the right moment, there is this steady interplay of energy.
Right.
But physicists need to calculate that energy, and Feynman highlights a very common math trap that people fall into here. It has to do with the mathematical shortcuts we take.
Because to make the brutal calculus of tracking a swinging object easier, we don't write down the velocity as a standard physical number, do we?
No, we don't. We represent physical quantities like velocity or position using complex numbers.
And those are the numbers that include an imaginary component, right? Like
Right.
incorporating the square root of -1.
Exactly. And we do this for a very pragmatic reason. Doing calculus on exponential functions that use complex numbers is honestly a breeze. It's basically basic algebra.
Oh, wow.
Yeah, whereas doing calculus on complex sine and cosine waves is just a nightmare of endless pages of math.
Wait, okay, I see the trap, though. Because if velocity is represented as complex number, and calculating kinetic energy requires you to square the velocity.
You square an imaginary number.
Right, and squaring an imaginary number gives you a negative, so you end up calculating a negative kinetic energy.
Exactly.
Which is physically impossible for a swinging pendulum on a real physical clock.
Right. I mean, you can't have less than zero movement. So to avoid that impossible negative, you have to recognize the limits of the shortcut. The physical world, the actual brass pendulum moving through the air, only corresponds to the real part of that complex mathematical setup.
Okay, so how do you fix it?
To get the true energy, you must step away from the complex notation entirely. You extract the real physical quantity, which is modeled as a cosine wave, and you square that.
Ah, and when you square a cosine wave, it behaves exactly the way physical reality behaves.
Precisely. A standard cosine wave fluctuates between +1 and -1. Square it, and suddenly it fluctuates perfectly between +1 and 0.
No negative values.
No negative values. It perfectly matches the reality that kinetic energy can drop to 0 but never go below it. And because it bounces evenly and symmetrically between 1 and 0, its average value over time is exactly 1/2.
Meaning that when we track the steady swinging of the clock, the stored energy, the energy trading back and forth between gravity pulling it down and the physical motion of the weight averages out to a constant amount.
Right. The power being pumped in perfectly matches the energy being lost to friction,
Mhm.
or joule heating in a circuit.
Right, air resistance for the clock.
Exactly. That tiny tap you give the pendulum is only there to fight the air resistance. The vast majority of the energy is already stored in the pendulum itself, safely retained cycle after cycle.
So it's like initially you do a lot of work to get the pendulum going, but to keep it steady, you just give it a little nudge.
Yeah, tiny nudge. And this brings us to how we measure a system's ability to hold on to that stored energy, the Q factor or quality factor.
Right, the Q factor.
The Q factor is really the ultimate measure of an oscillator's efficiency. Conceptually, it's just 2 pi times the massive amount of stored energy divided by the tiny amount of work you have to put in each cycle to keep it going.
So our grandfather clock pendulum has a massive amount of stored energy and requires only a tiny tap. So it has a very high Q factor.
Exactly. Or think of a tuning fork. You strike it once, and it rings for a remarkably long time because it loses very little energy to the air per vibration. It has a high Q.
But our hypothetical pillow clock?
The pillow has a remarkably low Q. I mean, you hit a pillow, it absorbs the energy, dissipates it instantly as microscopic heat, and just sits there. It holds on to nothing.
Right. Okay, so we have our highly efficient high Q grandfather clock ticking away perfectly. Now, we abruptly stop tapping it. We just walk away.
Enter the transient.
The transient begins. So what actually happens?
Well, because there is no more power being pumped in, the loss is the air resistance, the internal friction of the gears. Now have nothing to eat but the system's stored energy.
They start draining the battery, basically.
Exactly. And Feynman points out that in a high Q system, this energy doesn't just drop off a cliff, nor does it tick down linearly like a stopwatch. It decays exponentially.
Okay, exponentially.
Right. It loses a specific fraction of its total energy. A fraction defined as 1 over the Q factor every single radian of the cycle.
Okay, just to ground that mathematical term physically for you listening,
Yeah.
a radian is just a specific chunk of the pendulum's circular arc, right? Like a bit less than a third of a half circle.
Yeah, that's a good way to picture it. With every single chunk of distance the pendulum travels, it pays a fixed percentage tax on whatever total energy it has left at that moment.
Okay, so what does this all mean? If I'm watching the physical clock and the energy is being taxed and drained at that specific exponential rate, does the actual physical distance of the swing, the amplitude, shrink at that exact same rate?
See, it is deeply intuitive to assume the physical swing shrinks at the same rate the energy drains, but it doesn't.
It doesn't.
No, there is a fundamental disconnect between the decay of the invisible energy and the decay of the visible amplitude. If you recall the basic physics of a spring or a pendulum, the total energy is proportional to the square of the physical displacement.
Oh, wait. Because the mathematical formula links energy to the square of the amplitude, the physical distance of the bounce actually has to shrink much slower.
Exactly. It
Yeah.
shrinks exactly half as fast as the energy drains.
Wow, half as fast.
The mathematical formula for this decay visually reflects that. It dictates a beautiful damped sine wave where the amplitude diminishes as e to the power of negative gamma t over 2. That over 2 is the half as fast rule.
Okay, Feynman provides a phenomenal visual for this in figure 24-1 of the source material. Imagine a classic wavy line, bouncing up and down across the center axis, representing your pendulum swinging back and forth over time. Now, draw an invisible funnel around that wavy line, a funnel that gets narrower and narrower the further right you look. The wavy line has to squeeze itself inside that shrinking funnel. The waves still happen at the exact same rhythm, they just get squished tighter and tighter to the zero line.
That invisible funnel is the physical manifestation of the exponential decay envelope. It perfectly bounds the oscillation, guiding it gently and inevitably down to absolute zero.
But to get to that elegant, perfect description, physicists have to actually solve the differential equations of motion, don't they?
They do, and when they do, the math throws a massive curveball.
Of course it does.
So physicists try solving these equations by plugging in an exponential curve a to the power of I alpha t again, because differentiating exponentials is the easiest path forward. But when you process that guess, the math spits out a quadratic equation.
And a quadratic equation generally forces you to reckon with two distinct solutions.
Right, two solutions for alpha.
Okay, wait, I have to push back here. If we are looking at one single physical pendulum in one real room doing one specific physical movement, why use mathematical tools that create multiple contradictory realities?
It sounds messy, I know.
Yeah, I mean, if using complex numbers forces us into a situation where we have two solutions and we have to invent workarounds just to clean up a mess we created, why use imaginary numbers at all? It sounds like physicists are just making the math arbitrarily harder and more abstracted from reality.
What's fascinating here is that the math isn't arbitrarily harder. It's actually the only practical way through the woods. Attempting to solve complex differential equations with real-world sines and cosines is brutally, almost impossibly complicated.
So it really is just a necessary shortcut.
Absolutely.
Thanks.
By introducing that complex exponential, we take a shortcut through a multidimensional mathematical space. The mathematical equation blindly follows the rigorous logic of that complex space. It gives us a first solution that contains both a real part representing the decay and an imaginary part representing the oscillation.
But a physical pendulum cannot swing into an imaginary dimension. It can only exist in the physical room.
Right, and to pull us back into the physical room, the math organically generates the second solution, the complex conjugate.
The complex conjugate.
Yeah, it is the shadow solution. It looks almost identical to the first, but the sign of the imaginary part is perfectly flipped to the opposite direction.
Oh, I see. Think of it like two mirror image spiral staircases. One staircase spirals up and to the right, deep into the imaginary dimension. The other staircase spirals up and to the left.
That's a great analogy.
If you stand right between them and mathematically combine them, the left and right twisting forces cancel each other out completely. You are left with just a straight elevator ride, up or down physical reality.
Exactly. When you add the primary solution and its shadow together, the positive imaginary parts and the negative imaginary parts annihilate each other. They just vanish.
Yeah.
You are left with a purely real equation, a pure real oscillation with a phase shift and an exponential damping that perfectly matches the physical movement of the clock. Yeah. The math took a highly efficient detour into an imaginary dimension to bypass the hard calculus, found the answer, and then used the second solution to erase its own tracks, dropping us safely back in the real world.
That is just brilliant. But, it's still just chalkboard wizardry. How do we actually observe and verify this in a lab without just staring at a mechanical spring for hours trying to eyeball the decay rate?
Well, Feynman takes us into the lab for this, but he doesn't build a physical clock. He builds the pendulum's electronic twin.
Because mechanical systems are incredibly clunky to measure with absolute precision, right? Air pressure changes, mechanical friction wears down the pivot.
Exactly. Yeah. But an electrical circuit governed by the exact same differential equations, that we can measure down to the microsecond.
Right. So in figure 24-2, we see this setup. We build a circuit that behaves exactly like our mechanical oscillator. The physical mass of our pendulum is replaced by an electrical component called an inductor, right?
Yep, an inductor represented by L, which fundamentally resists changes in electrical current, giving the circuit its momentum.
And the physical tension of the spring or gravity is replaced by a capacitor, C, which stores electrical charge.
Right again.
And finally, the mechanical friction, the air resistance, is replaced by a simple electrical resistor, R.
The mathematics governing the flow of voltage and current in that circuit are completely indistinguishable from the mathematics governing the physical position and velocity of the swinging pendulum. They are perfect twins.
The genius is in how we observe it. I mean, a mechanical swing takes minutes to wind down. You have to measure it manually, push it again, measure it again. But in the electrical circuit, Feynman hooks the whole thing up to an oscilloscope screen and flips a switch 60 times a second.
Turn the electrical force on, let the circuit ring out and decay, turn it on, let it ring out.
And because it happens 60 times a second, the persistence of our vision makes it look like a single, solid, glowing green curve on the screen that we can study perfectly.
And what we study is the effect of directly manipulating the Q factor. Because we are in a circuit, we can artificially lower the Q just by turning a dial on the resistor. We are instantly dialing up the friction.
As you turn that dial, figures 24-3 through 24-5 show exactly what happens on the screen. The electrical bouncing dies out faster and faster. The waves get fewer, they get flatter, and that invisible decay funnel gets aggressively steeper.
Yeah.
It's like taking our physical grandfather clock and instead of letting it swing in the air, we submerge the entire clock in water. The resistance of the water eats the kinetic energy almost instantly. You might get 1 or 2 sluggish ticks before it stops.
And if you keep turning the resistor dial, taking the friction even higher, you hit what we call overdamping. The visual on the oscilloscope in figure 24-6 is striking.
The oscillation completely entirely vanishes, right?
Yes. There are no sluggish waves at all. The glowing line just drops down and flattens out smoothly to zero.
It's as if we took that same physical clock and tried to swing it in a pool of thick, heavy molasses. You pull the pendulum back, you let it go, and it doesn't swing past the center point. It just slowly oozes back to the resting position and permanently starts.
Exactly. It just dies.
But why? I mean, what physically and mathematically triggers the complete deletion of the bouncing?
The climax of this entire phenomenon lies hidden inside the quadratic equation we use to solve the system. Inside that solution is a square root. The math pits two forces against each other inside that square root.
Okay.
You have the natural physical balance of the system on one side, represented by omega naught squared, and the drag of the friction on the other, represented by gamma squared over 4.
Here's where it gets really interesting. When the friction is low, the bounce term wins. The number inside the square root remains positive. A positive square root yields a real number, which drives the cosine wave and forces the system to oscillate.
Right.
But if we crank that resistor dial so high that the friction term completely overpowers the natural bounce,
The number under the square root becomes a negative number.
and taking the square root of a negative number forces the creation of a new imaginary number, an I. But wait, we already had an imaginary number built into our initial mathematical guess.
We did. So this new I generated by the heavy friction multiplies by the I already sitting in our wave equation.
Yeah.
And NA times I equals -1.
-1.
The newly generated imaginary component multiplies with the existing imaginary component and destroys them both. By turning into -1, it literally deletes the mathematical term responsible for the oscillating sine and cosine waves. It transforms an oscillating wave function into a pure, steep downward slope.
So the thick molasses friction physically overpowers the pendulum's ability to pull itself back to the center before all its kinetic energy is eaten as heat.
Yes.
And the math completely enforces this reality. The equation dynamically adapts. It shifts its entire nature from a wave to a pure decay, the exact millisecond that critical threshold of friction is crossed.
If we connect this to the bigger picture, it shows us that the superficial details of the system, like, how far back you pulled the swing or how hard you pushed it at the start, they only finalize the cosmetic shape of the curve. They dictate how tall the first wave is.
Right, the initial conditions.
Exactly. But the underlying truth of the universe is governed by a single mathematical tipping point. The fragile boundary between positive and negative numbers inside a square root dictates whether a physical object in our world swings or stops dead.
We started with a simple playground swing, and we ended up at the mathematical boundary governing physical reality itself. Feynman highlights this profound takeaway. The intimate, hidden mathematical relationship between bouncing sinusoidal waves and fading exponential functions isn't just a chalkboard trick.
No, it's very real.
It manifests physically right in front of us on an oscilloscope screen as a sudden, violent change from rhythmic bouncing to pure decay, simply because friction crossed a critical threshold.
It's beautiful, really.
It really is. So where else in your life, or in nature, does adding just a tiny bit more resistance completely change a cycle of bouncing back and forth into a single permanent stop? The math tells us that tipping point is always there, waiting silently in the square root, ready to change the rules of the game. Keep an eye out for those critical thresholds. Until next time, keep digging deeper. If you break your arm, an X-ray gives you absolute binary precision, right? Just a jagged white line on a black background. Broken or not broken.
Right. It's very definitive.
Exactly. But the moment you put on a pair of glasses or, look through your phone's camera, you're interacting with a branch of physics that is, it's built on a massive fundamental lie.
Or at the very least, a very, very murky approximation.
Yeah, totally. Welcome to the deep dive. Today we're looking at Chapter 27 of the Feynman Lectures on Physics, and the mission for you listening today is to explore this fascinating, somewhat frustrating world of geometrical optics. We expect optics to be an exact science, but its whole mathematical foundation depends on, well, ignoring the actual physical reality of light.
Yeah, and that approximation is really the only reason we've been able to engineer optical instruments for the last few centuries. It's wild to think about.
It is. So we're going to unpack why perfect lenses are basically impossible to make, how a negative number in an equation explains your bathroom mirror, and why you can't just keep adding magnifying glasses together to see an atom.
Right. And to understand why we have to cheat the physics, we first have to look at the strict, unyielding rule that light actually follows. We're talking about Fermat's principle of least time.
Okay, the principle of least time. Break that down for us.
So light traveling from point A to point B will always take the path that requires the shortest amount of time, period. In a vacuum, or just uniformly through the air, that path is a straight line.
Makes sense. Shortest distance is a straight line, so shortest time is a straight line.
Exactly. But the moment you introduce a denser medium, like a piece of glass light, slows down.
And that slowdown is what we call the index of refraction, right? The n value.
You got it. The index of refraction is literally just a measure of that slowdown.
Yeah.
So imagine light is moving from a single point, like a glowing filament, and it's spreading out through the air.
Okay, I'm picturing it.
And say, we want to capture all those diverging rays and bend them so they perfectly converge onto a single point on the other side of a piece of glass. Well, we're fighting against time.
Because the rays are taking different paths? The ray that shoots straight down the middle, along the central axis, has the shortest physical distance to travel, right?
Right. But the rays that shoot out at an angle, hitting the outer edges of the glass, they have to travel a much longer physical distance through the air to reach that exact same destination.
So if they travel different physical distances at the same speed, they're going to arrive at different times.
And if they arrive at different times, they do not form a perfect, sharp point of focus. It's just a blur.
Wow, okay.
So to get a perfect image, every single ray of light leaving the source has to take the exact same amount of time to reach the focal point.
But wait, we can't speed up the outer rays, right? Because light is already at the universal speed limit.
Right, you can't go faster than light in a vacuum. So if we can't speed the outer ones up, we have to deliberately slow down the central ray.
Ah, I see. We force it to spend more time in the denser medium. We make the glass thicker in the middle.
Exactly. The central ray takes the shortest physical path, but it gets bogged down in the thickest part of the glass.
Which delays it just enough for the outer rays to catch up because they hit the thinner edges and travel mostly through the faster air.
You've got it. We're equalizing the optical path lengths.
That sounds incredibly complicated, though. Figuring out the exact surface shape of that glass so every conceivable ray arrives simultaneously, I mean, that sounds like a mathematical nightmare.
Oh, it is. The geometry required to perfectly equalize the travel time for all those rays dictates that the surface of the glass has to be this highly complex fourth-degree curve.
A fourth-degree curve?
Yeah, a quartic surface. It is a very specific, intricate mathematical shape. It is not a simple sphere, and it's not a parabola.
But wait, grinding a perfect fourth-degree curve out of a block of glass, especially back in the 17th or 18th century, that would have been practically impossible.
Utterly impossible. You couldn't just put that on a standard lathe.
Right. So human practicality steps in. Engineers must have realized that a simple sphere, which is, incredibly easy to grind just by rubbing two pieces of glass together.
Yeah, with an abrasive in random directions.
That a sphere has a curve that closely mimics the very tip of that perfect fourth-degree curve.
They match up almost perfectly right at the central axis. And that realization right there gave birth to the foundational cheat of geometrical optics.
The paraxial approximation.
Exactly. Paraxial meaning near the axis. Lens makers basically decided to just use spheres and mathematically ignore any light rays that hit the outer edges of the lens.
So if you only allow rays that are very close to the center and very shallow in their angle, the spherical surface is basically a flawless substitute.
Right. For those paraxial rays, it works perfectly.
It's essentially truncating a mathematical series, right? Like if you describe the angle of the light ray using a Taylor series expansion.
Yeah, you have the first-degree term, a third-degree term, fifth-degree, and so on.
Geometrical optics just lops off everything after the first term. We just declare that the sine of the angle is equal to the angle itself.
Which is only true if the angle is minuscule. But once you accept that paraxial limit, the math becomes incredibly elegant.
That's where we get the fundamental lens equation.
Right. It defines the relationship between the distance of the object from the lens, the distance of the focused image on the other side, and the focal length of the lens itself.
And just to clarify for everyone listening, the focal length is the intrinsic property of the lens, right? It's the specific distance where parallel rays of light will naturally converge to a point.
Correct, like light arriving from a star, effectively at infinity.
So the equation is what 1 over the object distance plus 1 over the image distance equals 1 over the focal length.
Exactly. And since the focal length is a fixed property of that specific piece of curved glass, it dictates exactly where the image will form.
But this equation implies a pretty hard physical threshold. If the focal length is fixed and you move the object closer and closer to the lens, the image distance has to increase to keep the equation balanced.
The focal point pushes further and further away on the other side.
So what happens when you push the object so close to the glass that its distance is less than the focal length?
Well, the math breaks.
Yeah.
Or rather, it spits out a negative number for the image distance.
Which is so weird to think about. What does a negative physical distance even mean in the real world? Did the light hit the glass and turn around?
No, it doesn't turn around. The physics of what's happening is all about angular divergence. See, the glass has a finite, fixed bending power.
Based on its curve and the index of refraction.
Right. When an object is placed extremely close to the lens, the rays of light radiating from it are hitting the glass at a very steep, highly divergent outward angle.
Okay, so the lens applies its maximum bending power, trying to pull those rays inward.
But that fixed power just isn't enough to overcome the extreme initial spread. The rays come out the other side of the glass, still spreading apart.
Oh, wow. So they're diverging less than before, but they're still diverging.
Exactly. They will never converge to form a real focal point in space. There is no real image.
But if there's no real image, how do we see anything?
Well, human visual perception relies on a hardwired assumption. Our brains assume that light always travels in straight lines.
Right.
So when those diverging rays exiting the lens hit your eye, your optical cortex traces them backward. It mathematically extends straight lines backwards through the glass until those lines intersect at a fictitious point behind the lens.
Your brain literally hallucinates a point of origin.
Yes, that intersection is the virtual image. The negative image distance in the equation is simply telling us that this fictitious focal point lies on the same side of the lens as the original object.
This is the bathroom mirror. That's the classic manifestation of this. The mirror reflects the diverging light rays from your face, and your brain traces those reflected lines backward, perceiving this virtual avatar of yourself standing 2 feet behind the drywall.
Exactly. And Feynman illustrates this beautifully in figure 27-3, showing this geometric traceback. And it scales to other shapes, too.
Right, like a perfectly flat boundary between 2 mediums.
Like the surface of a swimming pool.
Yeah.
Mathematically, a flat plane is just a spherical surface with a radius of infinity.
Which is wild to think about. The bending power of a flat surface isn't coming from a curve. It's coming entirely from the drastic change in the index of refraction between the water and the air.
Because the index of water is roughly 4/3, meaning light travels significantly slower in the pool than in the atmosphere above it.
So if you're standing at the edge and you drop a coin to the bottom of an 8-foot deep pool and you look straight down at it, the light rays bouncing off the coin travel up through the water, hit the boundary, and speed up as they enter the air.
And when they speed up, they bend. They refract outward, away from the normal line.
So the tight bundle of rays traveling up from the coin suddenly spreads out wider when it hits the air.
Right. And once again, your brain traces that wider spread of diverging rays straight backward.
Because they're spreading at a wider angle, those traced lines intersect much higher up than the actual bottom of the pool.
Exactly. The mathematics dictated by that 4/3 index of refraction are absolute. The reciprocal is 3/4.
So the virtual image of the pool floor forms at exactly 3/4 of the actual depth.
Right. Your brain tells you the 8-foot pool is only 6 feet deep.
It's just a biological calculation error based on an optical illusion?
Pretty much.
Yeah.
Now take that illusion and compound it. A single lens or a single flat surface creates a clear mathematical relationship. But think about modern optical instruments.
Oh, like microscopes or high-end telephoto camera lenses.
Yeah, satellite optics. They never rely on a single piece of glass. They're these complex optical trains containing 5, 10, sometimes 20 individual lenses stacked in a metal tube.
Which begs the question, how do scientists even deal with that? Calculating the trajectory of a ray as it refracts through 40 different curved surfaces? I mean, that seems like it would require a supercomputer just to find the final focal point.
It sounds like it, right?
Yeah.
But the methodology is surprisingly modular. You don't try to solve a 20-lens system simultaneously. The technique is called matrix optics, or more simply just chasing the light.
Raising the light. I love that.
Yeah, so you take the original physical object and run it through the basic lens equation for the very first piece of glass. That gives you an image, either real or virtual.
Okay, and then what?
Then you discard the physical object from your calculations entirely. That first image becomes the new object for the second lens.
Oh, wow.
You run the equation again, find the second image, and that becomes the object for the third lens. You just cascade the math down the optical axis.
But even with cascading math, analyzing a 20-lens system manually would be tedious.
Very. But there's a phenomenal mathematical shortcut that emerges when you treat a complex optical train as a single system. Any sequence of lenses, no matter how convoluted, can be simplified down to two theoretical planes perpendicular to the optical axis.
The principal planes.
Yes. Feynman illustrates this in Figure 27-8. They are planes of unit magnification. They allow you to treat an entire opaque, foot-long camera lens as a black box.
So you don't even need to know the curvature or index of refraction of a single piece of glass inside the tube?
Nope. If you can locate the first principal plane and the second principal plane, you just assume that a light ray entering the first plane is mathematically translated instantly to the exact same height on the second plane.
And then it's bent toward the final focal point. You basically collapse a multi-lens behemoth into a single theoretical thin lens located exactly between those two planes.
It's a brilliant reduction.
It really is. But I think this is exactly where we have to confess something to everyone listening. This is where the bill comes due for the approximation we made at the very beginning.
Ah, yes, the paraxial approximation.
Right. We built this elegant system of cascading math and principal planes on the assumption that we are only using the very center of the lens.
But physical lenses have real diameters. They have apertures. Light inevitably hits the edges.
And when we use the edges of a spherical lens, that truncation of the Taylor series we talked about earlier really rears its ugly head.
It does. The higher order terms we ignored suddenly matter. Remember, we swapped the perfect quartic curve for a sphere. Near the center, they match. But as you move outward toward the edge of the lens, the curvature of the sphere curves inward too sharply compared to the ideal quartic shape.
So the rays hitting the margins of the lens are bent far too severely.
Exactly. They don't have the correct optical path length. They fall short, intersecting the central axis well in front of the true focal point where the central paraxial rays are converging.
And this is called spherical aberration, right?
Yes, spherical aberration. Because the marginal rays focus too early, by the time they reach the sensor, or your retina, where the paraxial rays are perfectly focused, those edge rays have already crossed the axis and are spreading out again.
So you don't get a crisp, small point of light. You get a solid central dot surrounded by this hazy, diffuse halo.
It completely destroys the image contrast.
And spherical aberration is purely a geometric flaw based on the physical shape of the glass. But even if we went back to the drawing board, abandoned the paraxial cheat, and successfully manufactured that perfect, flawless fourth-degree quartic surface, the image would still be flawed.
Because the medium itself reacts differently depending on the nature of the light. Now we have to confront chromatic aberration, which is driven by dispersion.
Right, color. Because the index of refraction is not actually a constant number for a given material, is it?
Not at all. The N actually varies depending on the frequency of the light wave traveling through it. White light from a star or a light bulb is a composite of a vast spectrum of frequencies.
And when those electromagnetic waves enter the glass, they interact with the electrons in the material. Higher frequency light, like blue or violet, oscillates faster and interacts more strongly with the glass lattice.
Exactly. That increased interaction drags on the wave. It slows it down more than lower frequency light, like red.
And since the blue light slows down more, it essentially experiences a higher index of refraction.
And a higher index means the lens exerts a stronger bending power on it. The lens literally rips the image apart by frequency.
Oh, wow. So imagine trying to focus a projector, but the blue light is bent sharply and focuses closer to the lens, while the red light pushes through faster, bends less, and focuses further away.
Exactly. The focal length is different for every single frequency in the spectrum. If you adjust your microscope to bring the blue wavelengths into sharp focus on your sensor, the red wavelengths are still converging, creating a blurry red halo.
And if you adjust the focus to capture the red light perfectly, the blue light has already crossed the axis and is spreading out, creating a blue halo. You literally cannot focus an uncorrected lens because there is no single focal plane.
So to fix this chromatic aberration, optical designers spend their entire careers doing this. They have to introduce a second lens, made of an entirely different material with a different dispersion profile.
A different Abbey number, I think it's called?
Right. You typically pair a convex lens made of crown glass, which has a low dispersion, with a concave lens made of flint glass, which has a high dispersion.
So the first lens bends the light and separates the frequencies, and then the second lens bends the light in the opposite direction, just enough to violently force the different frequencies back together to intersect at the same focal point.
Without completely undoing the converging power of the first lens.
Yeah.
It's called an achromatic doublet. You are intentionally introducing a second controlled error to cancel out the first error.
That is just incredible. Okay, so we combined different glasses to cancel chromatic aberration. We use complex elements to fight spherical aberration. We coat the lenses to prevent reflections.
We do it all.
So let's imagine the absolute peak of human engineering. Unlimited budget. A supercomputer calculates an optical train of 50 perfectly crafted lenses that cancel out every single aberration flawlessly. A perfect geometric optical system.
Okay, I'm with you.
Can we just use that system to magnify an object infinitely? Like, could we look through this flawless microscope and resolve the internal structure of a single atom?
No.
Just a hard no.
A hard stop. No. Even if you eliminate every geometric and material flaw, you eventually hit an absolute physical hard stop known as the resolving power limit. Figure 27-9 in the source text addresses this directly.
Okay, why? What is stopping us?
This is the moment where the foundational premise of geometrical optics treating light as a perfectly straight ray completely collapses.
Because light isn't a geometric line, it's an oscillating electromagnetic wave.
Exactly. It has crests, troughs, and a specific physical wavelength. Geometrical optics works totally fine when the objects we're looking at are millions of times larger than the wavelength of light. But when you try to resolve microscopic details, wave optics takes over.
Whoa, I see.
The transition from geometrical optics to wave optics really centers on the concept of phase. Earlier, we defined a perfect image as a result of all light paths taking the exact same amount of time to reach the focal point.
Right, to prevent a blurry image.
But in wave terms, because they take the same time, the peaks and troughs of the light waves arrive perfectly in sync. They interfere constructively, building a bright, sharp point.
Okay, but suppose you're looking at two minuscule separate dots that are incredibly close to each other, like two parts of a bacterium. For your optical system to resolve them as two distinct objects, it must map them to two distinct focal points on your sensor.
Right. And if the 2 points are too close together, the light waves emanating from point A will inevitably bleed into the focal destination meant for point B.
And this is where the physical limit of the wave asserts itself.
Exactly. For the system to recognize that point A and point B are separate, the light arriving at the wrong focal point must be visibly distinct from the light arriving at the correct focal point.
Visibly distinct, meaning out of phase.
Yes. If the light from point A travels to point B's focal spot and arrives at the exact same time as point B's own light, they will constructively interfere. The sensor will just see one massive combined wave, a single blurry blob.
So to distinguish them, the light from point A reaching point B's focus must arrive at a different time so that its wave is out of sync.
Specifically, the difference in the travel time of the extreme upper and extreme lower rays reaching that wrong focus must be greater than the duration of one full period of oscillation of the light wave.
Oh, wow.
If the time difference is less than one wave's period, the phase shift isn't significant enough to cause destructive interference. The waves merge. You cannot resolve the separation.
So geometrical optics has a built-in resolution limit based on the actual physical size of a light wave. It's like the wavelength of the light is effectively the physical brush size of the universe for your instrument. If you try to paint two distinct dots closer together than the width of the bristles on your brush, you just get one giant smear of ink.
That is a perfect analogy. The smallest distinct feature you can possibly resolve with a traditional optical microscope is strictly limited by the wavelength of the light illuminating the object.
And visible light has a wavelength of, what, roughly 400 to 700 nanometers.
Right around there, yeah.
So you simply cannot see anything smaller than the tool you are using to observe it. Pushing the magnification higher doesn't reveal more detail, it merely enlarges the unresolved, diffraction-blurred blob.
Geometrical optics breaks down because you cannot mathematically slice a wave thinner than its own crest-to-crest physical dimension.
That is profound. So just to recap the journey we've been on today, we started with the mathematical compromise of spherical lenses and the paraxial cheat. We learned how chasing light creates virtual images and swimming pool illusions. We confronted the reality of lens aberrations and finally hit the absolute physical wall of resolving power.
It's quite a journey. And, the irony here is that while the strict geometrical interpretation of light as a straight ray fails at the microscopic limit of optics, the mathematics developed to describe those rays proved to be foundational for an entirely different branch of physics.
Really? How so?
Well, William Rowan Hamilton took Fermat's principle of least time, the idea that light rays minimize their travel time through different media, and he formalized it mathematically. But the ultimate twist, something really fascinating found in the introduction to the source material, is that Hamilton's optical framework turned out to be the exact mathematical scaffolding needed for advanced analytical mechanics.
Yeah, mechanics, like physical objects moving.
Yes. The equations Hamilton wrote to trace a theoretical ray of light bending through a piece of glass are mathematically identical to the principle of least action, which governs the physical movement of mass in the universe.
That is mind-blowing. So the murky, compromised approximation we used to build reading glasses and camera lenses ended up being the exact mathematical key required to calculate the precise orbits of planets and the trajectory of physical objects through space-time.
Exactly. It's a pretty incredible historical twist for you to ponder.
What an amazing place to leave it. Thank you so much for joining us on this deep dive.
My pleasure. Thanks for having me.
Imagine standing outside on a really clear, really dark night. You look up and you lock your eyes on a single faint star.
Just a tiny speck in the sky.
Right, just a speck. But the light hitting your eye from that star, I mean, it might have been traveling for 5 billion years.
Yeah, it left that star before our solar system even existed.
Which is wild. And we accept that as this, fun trivia fact. But we rarely stop to think about the actual physical mechanics of it. Like, how is it physically possible that something 5 billion light years away can reach out, physically touch your eye, and register in your brain as light?
Well, we tend to treat light as this abstract concept, just a glow that magically appears. But it's actually a strictly mechanical process. It's governed by really rigid physical laws.
Right.
There's a mathematical structural connection across that unimaginable distance. An electron over there, billions of years ago, had to move. And that created a physical ripple in an invisible field.
A physical ripple?
Exactly.
Yeah.
And that ripple traveled across the universe until it crashed into the electrons in your own retina.
Unraveling the mechanics of that ripple is basically our mission for this deep dive. We are exploring the foundational rules of electromagnetic radiation.
Yeah, getting into the real nuts and bolts of it.
Right, and we're using Richard Feynman's famous lectures on physics for this. Specifically, Volume I, Chapter 28. Our goal today is to move past the intimidating chalkboard math and really understand the actual physical wiggle, as Feynman calls it, that connects every point in the universe to every other point.
And to set the stage for how physicists even discovered that wiggle, we kind of have to go back to the 1860s.
The era of James Clerk Maxwell.
Right. Because before Maxwell, science had these distinct separate buckets for these phenomena. You had electricity, which, gave you static shocks.
Yeah.
You had magnetism, which moved compass needles. And then you had light. Completely separate things in the minds of scientists.
But Maxwell realized electricity and magnetism were actually two sides of the same coin.
Yeah.
It did. But the problem was, when he tried to unify them mathematically, the existing laws they broke down. They completely contradicted each other.
Let's get into the mechanics of that breakdown, because it wasn't just a mathematical error on a piece of paper, right? It was a missing piece of physical reality.
Exactly. The problem was with Ampere's law. Basically, that law said that electrical currents produce magnetic fields, which, worked totally fine for a wire.
Okay.
But imagine a circuit with a capacitor. So essentially, two metal plates with a gap of just empty space between them.
Right, a literal physical gap.
Yeah. And when current flows, charge builds up on one plate and drains from the other. So the electric field in that gap gets stronger and stronger. But because there's no physical wire connecting the plates, Ampere's law suggested the magnetic field should just poof, vanish in the gap.
Which would completely break the continuity of the universe. I mean, you can't just have physical laws stop functioning because of a little gap in a wire.
Right. So Maxwell realized the changing electric field inside that gap had to act exactly like a physical current. He called it a displacement current.
A displacement current.
Yeah, and he added a new term to the equations to account for it. He basically stated that a changing electric field generates a magnetic field.
And vice versa. Right.
Exactly. A changing magnetic field generates an electric field. They feed off each other in this endless loop. And when he calculated the speed at which this self-sustaining chain reaction would travel through empty space,
The math spit out a very specific number.
it matched the known speed of light perfectly. It was this massive aha moment. Light wasn't a separate bucket anymore. It was just a propagating electromagnetic wave.
I always think of it like finding out your three completely different friends are actually just the same person wearing different disguises.
That's a great way to look at it.
But this grand synthesis, it creates an immediate logical problem. If light is just an electrical and magnetic force, why does it survive a 5 billion light-year journey?
Right, because normally those forces fade fast.
Exactly. Think about static cling from a charged balloon. It pulls on your hair if it's like an inch away, but you move it a foot away, and the force is effectively zero. It's gone.
Well, the secret to light's survival lies in how different parts of an electromagnetic field fall off over distance. The stationary charge on that balloon, it follows Coulomb's law. That means the electrical force falls off as the inverse square of the distance.
The inverse square, so it drops off exponentially.
It disperses incredibly fast. I mean, if the light from that distant star behaved like a stationary charge, its signal would be so unimaginably diluted by the time it reached Earth.
It could never move an electron in your eye.
Never. The night sky would be completely pitch dark to us.
It's basically the difference between a campfire and a laser pointer, right? Like a campfire's heat disperses in all directions so fast that walking 20 feet away leaves you freezing. That inverse square drop-off is brutal.
It really is.
But a laser maintains its intensity because its energy isn't diluting in the same way. It can reach a target miles away.
That laser beam effect is essentially what Maxwell's new term unlocked. The math showed that when a charge moves, it generates a radiation field that doesn't fall off as the inverse square. It falls off inversely as the first power of the distance.
Just 1 over r instead of 1 over r squared.
Exactly. It still fades, sure, but at a vastly, vastly slower rate.
But why? I mean, what is physically happening to the electric field that makes it act like a far-reaching laser instead of a local campfire?
Feynman gives us a really beautiful way to visualize this. So imagine an electron sitting perfectly still. Its electric field lines are radiating outward in all directions, straight out like tight strings.
Okay, got the visual. Tight strings in every direction.
Now imagine you suddenly grab that electron and violently jerk it upward. The part of the field line directly attached to the electron that moves immediately.
Right.
But the rest of the field line, the part stretching way out into space, it hasn't gotten the memo yet.
Because the information can't travel infinitely fast. It has a speed limit.
The speed of light.
Exactly.
So you have a moving section of the field near the electron and a stationary section of the field further out. And connecting those two sections is a sharp, distinct kink in the field line.
A literal kink, like a whip.
Like a whip. That kink travels outward along the field line at the speed of light, constantly updating the universe on the electron's new position. That traveling kink that is the radiation field. And because of the geometry of how that kink propagates, its strength only drops off inversely with distance.
Wow. But wait, if that kink travels at the speed of light, it fundamentally changes how we interact with the universe. It means every single interaction is on a delay.
Yep. Physicists call it retarded time. It's a foundational cornerstone of electromagnetic theory.
Retarded time.
Yeah. Basically, to calculate the electric field you are feeling right now, you don't look at what a distant electron is doing in the present moment. You can't.
Because the kink hasn't reached you yet.
Right. You take the current time, and you subtract the distance to the object divided by the speed of light.
Okay, so wait. So the entire universe is essentially operating like an online video game with a terrible ping issue.
That is exactly what it is. You are constantly experiencing a delayed server response from the cosmos. The feel hitting your eye right now was generated by an event in the past.
Taking that video game analogy a step further, though, a bad ping doesn't just mess up when an event registers. It messes up where you perceive the other players to be. So if I look at the night sky, I'm not just seeing a star's past timeline. Am I seeing its past location, too?
You absolutely are. Because the star is moving while that kink in the field is traveling towards you. The equations prove that we perceive the apparent retarded direction of the object.
That is mind-bending.
It is. The sky above you isn't a real-time map. It's this incredibly complex, overlapping projection of past events and old coordinates.
Okay, let's connect this back to that physical kink in the field line. You mentioned the kink forms when you jerk the electron upward. Does it only form during that sudden movement?
Yes. And this is crucial. The absolute rigid rule of radiation is that it is only produced by acceleration.
Just acceleration.
Only acceleration. If an electrical charge is sitting perfectly still, you get the campfire effect, the inverse square field. Even if a charge is moving at a perfectly steady speed in a straight line, it still produces no radiation.
Yes, there's no jerk.
Right. The only way to snap that field line and create the far-reaching kink is to make the charge speed up, slow down, or change direction. It has to wiggle.
But Feynman introduces a really interesting nuance to this wiggle. He calls it the projection rule, because we don't just see every wiggle equally, do we?
We don't. We only detect the wiggle that is perpendicular to our line of sight. Feynman uses the analogy of a painter.
Oh, right, the canvas.
Yeah, imagine a painter projecting a three-dimensional scene onto a flat, two-dimensional canvas. We only receive radiation proportional to the charge's acceleration projected onto our flat field of vision.
The painter analogy makes sense for the geometry, but let's think about the actual physical mechanism. Like, imagine holding one end of a really long, taut rope, and you have a friend holding the other end 50 feet away.
Okay.
If you whip your hand violently up and down, so a perpendicular wiggle, a massive transverse wave travels all the way down the rope and knocks the handle out of your friend's hand.
Right, and that transverse wave is your radiation field.
Exactly. But if you take that same rope and you just push and pull it straight forward and backward, directly at your friend, nothing happens.
Nothing at all.
I mean, the rope might get a little slack, then a little tight, but no wave travels down it. Your friend doesn't feel a sudden snap.
Because that push and pull is acceleration along the line of sight. From the perspective of the receiver, your friend, there is no sideways projection. There is no transverse kink in the field line.
Which means you have a fundamental blind spot.
A massive one. A star could be violently accelerating electrons, blasting out huge amounts of energy. But if those electrons are moving on an axis pointed directly at your eye, you detect absolutely zero radiation from them.
That is just wild to think about. Okay, so we have this profound mathematical framework now. An inverse drop-off caused by a propagating kink, locked into a cosmic lag, restricted by a perpendicular projection rule. But physicists aren't content just leaving that on a chalkboard.
No, they have to test it.
Right. How do we physically prove all these invisible mechanics are real?
Well, you build a trap for the invisible wiggle. In Chapter 28, Feynman walks through this classic laboratory setup for what's called a dipole radiator.
Figure 28:1 in the source text.
That's the one. So you take two straight pieces of wire, line them up end to end, and leave a tiny gap in the middle. Then you connect a high-frequency generator to that gap. And that generator is just an incredibly fast electron pump,
It forcefully yanks electrons out of the bottom wire and shoves them into the top wire.
creating rapid upward acceleration. And then the generator reverses instantly, slamming the electrons back down into the bottom wire. Up and down, millions of times a second.
So you have manufactured a perfectly synchronized artificial wiggle of charges.
Exactly. You've created the sender. Now, to catch the signal, you build a mirror image of that setup across the room. A second pair of wires with a gap.
But instead of a generator pumping the electrons, you hook the gap up to an amplifier and a loudspeaker, right?
Right. So the electric field from the sender, that continuous stream of outward traveling kinks, washes over the receiving wires. The field violently grabs the free electrons in those receiving wires and forces them to accelerate up and down in exact rhythm with the sender.
And that moving charge creates a current in the receiver, the amplifier catches it, and the loudspeaker buzzes.
You hear the wiggle. And we can use this exact room setup to prove your rope metaphor, the projection rule.
Oh.
If you, the listener, were standing in this lab right now, holding the receiving antenna parallel to the sending antenna, the speaker would be buzzing really loudly because you are catching the full perpendicular waves.
But what if we move? Imagine taking that receiver and walking over to the sending antenna. You hold your receiver directly above it, looking straight down the axis of the wiggling wires.
Figure 28:2. Looking straight down means the electrons in the sender are just rushing directly at your receiver and then directly away,
The rope is just being pushed and pulled straight at me.
which means the sideways projection is mathematically zero. And what you hear from the loudspeaker in your hands is Absolute silence.
Total silence. Even though the generator is running at full power, electrons are violently accelerating, but you are standing in the physical blind spot dictated by the geometry of the field.
It's a perfect physical proof.
It really is. But the universe isn't just one wiggling wire. I mean, think about the Wi-Fi router sitting in your living room right now. It's competing with a landscape full of other signals. What happens when we introduce a second sending antenna to our laboratory?
Now we enter the realm of interference.
Yeah.
This is figure 28-3. Imagine placing two sending antennas side by side, hooked up to the same generator. If they wiggle perfectly in sync so they're pumping electrons up at the exact same instant, their propagating kinks merge.
The electric fields combine.
Right, and the receiver across the room picks up a signal that is double the strength.
So two speakers playing the exact same note amplify each other. But if we can control the generator, we can mess with the timing. What if we delay the signal going to the second antenna by exactly half a cycle?
A 180-degree phase shift.
Yeah.
Well, now, when antenna 1 forcefully pumps electrons upward, antenna 2 is simultaneously pumping electrons downward. Both are generating massive radiation fields. But at the location of your receiver across the room, the field from antenna 1 is screaming, pull the electrons up, while the field from antenna 2 is screaming, pull the electrons down, with the exact same intensity.
Wait, if both antennas are plugged into the wall, drawing maximum power and blasting out energy, how can the result be nothing? You can't just destroy the energy from two powerful sources. Where does the energy go?
That's the beauty of it. You haven't destroyed the energy, you've just dictated how the fields interact at that specific point in space. At the location of your receiver, the opposing forces cancel out perfectly.
The push and the pull equalize.
Exactly. The electrons in your receiving wire experience a net force of 0, so they don't move. Because they don't move, no energy is absorbed from the field at that location. The loudspeaker is dead silent.
Even though the room is flooded with radiation?
Yes. The energy from the senders is essentially redistributed into other areas of the room where the fields do constructively add up.
It's the exact same principle as noise-canceling headphones, just scaled up to the fundamental electromagnetic forces of the universe.
Perfectly said.
And we can manipulate these fields even further using vector addition, which Feynman shows in figure 28 before. What if we remove the time delay, keep them perfectly in sync, but physically turn the second antenna 90 degrees? So one is vertical, pumping up and down. The other is horizontal, pumping left and right.
Well, electric fields are vectors, meaning they have both magnitude and direction. So your receiver across the room is hit simultaneously by an invisible force pulling its electrons straight up and an invisible force pulling them straight to the right.
The electrons can't do both, obviously, so they take the compromise path. They are pulled diagonally at exactly a 45-degree angle.
Right. And the only way your receiving antenna can catch that combined signal is if you actually tilt it to 45 degrees.
You are literally witnessing mathematical vector addition happening invisibly in the empty space of the room.
It makes the math so tangible.
It really does. So we've used this lab to prove the projection rule with the blind spot and vector addition with the tilted antenna. But what about the lag? Can we prove the concept of retarded time, that cosmic lag, without needing a telescope pointed at a star 5 billion light years away?
Oh, absolutely. The proof of retarded time on Earth is remarkably simple. We just returned to our two vertical antennas, perfectly in sync side by side. No delay, no tilting.
So the receiver is picking up that really loud double-strength signal.
Exactly. Now, without touching the generator or the senders, simply pick up the receiver and walk through the room.
Okay, so if I walk so that I am standing physically closer to antenna 2 and further away from antenna 1, I'm changing the travel distance of the fields.
And because the speed of light is rigid and finite, changing the distance changes the travel time. The kink from antenna 2 has a shorter distance to cover, so it arrives sooner. The kink from antenna 1 has a longer path, so it arrives later.
I'm basically forcing the signals to be out of sync purely based on my location.
Precisely. If you find the exact spot in the room where the distance difference equals exactly half a wavelength, the signal from antenna 1 lags just enough to arrive 180 degrees out of phase with antenna 2.
Even though the antennas are wiggling perfectly together at the source, the travel time delay forces them to cancel each other out from my perspective. I find a dead zone of total silence just by standing in a different spot.
You are physically measuring the finite speed of electromagnetic radiation by using your own body to change the ping rate.
That is incredible.
The distance creates the delay creates the phase shift, and the phase shift creates the cancellation. The equation for retarded time governs your living room just as strictly as it governs the deep cosmos.
Looking back at this sequence, the elegance of the physical laws is just striking. We moved from Maxwell realizing a changing electric field in a gap must act like a current, which led to a self-propagating wave.
Right.
And then we saw how jerking an electron creates a kink in its field line that drops off slowly enough to cross billions of light years.
And we established that this kink only propagates perpendicular to the acceleration, creating those weird blind spots for any motion along our line of sight.
And finally, we brought all of it down to Earth, proving that the delayed, overlapping projection of these kinks creates zones of intense noise and total silence right in front of us, dictated purely by geometry and the rigid speed limit of light.
Understanding these mechanics, I think, it strips away the abstract magic of light and replaces it with this intricate mechanical choreography. The empty space around you isn't actually empty. It is a dense intersection of traveling field lines, constantly updating the universe with new information.
It totally recontextualizes everyday actions. Like when you pull out your phone and connect to a cell tower, you are forcing a tiny generator to yank electrons back and forth, broadcasting physical kinks into the electromagnetic field that wash over antennas miles away.
You are participating in the exact same mechanical process as a distant galaxy. The scale is different, but the rules are identical.
That universality leaves us with a lingering thought about our place in the cosmos. We know that every time an electron is accelerated, it creates a 1/over ripple that travels outward forever. It fades, yeah, but mathematically it never truly hits zero.
It keeps going.
So look at our modern planet. Trillions of microchips, power lines, radio towers, and satellites, all relentlessly jerking electrons back and forth billions of times a second.
We are just a sphere of frantic, unending acceleration.
What is the collective, chaotic, electromagnetic noise that Earth is constantly broadcasting outward? We are pushing an expanding bubble of our own making into the deep lag of the universe, traveling infinitely at the speed of light. So if a consciousness out there 5 billion light years away is standing outside on a really clear, really dark night, they are surrounded by an electric field waiting to deliver our wiggle.
Imagine for a second that you're standing on the edge of a lake on a really bright, sunny afternoon.
Oh, yeah. The glare coming off the water is just, it's so intense. You have to squint just to look at it.
Right. Then, you slide on a pair of polarized sunglasses and the glare simply vanishes.
It's like magic.
It really is. You can suddenly see straight through the surface, down to the rocks and like the fish below.
Yeah.
Or think about picking up a clear plastic ruler, holding it up to an LCD computer monitor, and rotating it. Suddenly, that completely transparent plastic reveals this vibrant, glowing rainbow of stress lines hidden inside.
It looks like an optical illusion, a total trick of the eye. But what you are doing in both of those situations is actually filtering reality based on a hidden physical geometry that light just inherently possesses.
And that hidden geometry is exactly what we are unpacking today. So welcome to this deep dive into Richard Feynman's legendary lecture, specifically focusing on his insights into polarization.
Yeah, chapter 33.
Exactly. Our mission today is to really break down his core ideas, his terminology, and the fascinating mental models he uses to explain what he calls the electric vector of light.
We are definitely moving past the short, watered down textbook definitions today.
Oh, absolutely. We are going to explore the full reality of how light vibrates, how it bends, and how it can literally twist physical matter.
But to do that, well, we first have to understand the physical mechanism of light itself.
Right, because we casually think of a beam of light as a straight ray shooting through space, like a laser pointer.
Exactly. And while the beam travels in a straight line, light is actually an electromagnetic wave.
Okay.
So for our conversation today, we are going to focus entirely on just the electric field portion of that wave. As a beam of light travels toward you, its electric field is constantly oscillating.
Oscillating back and forth.
Right. But the vital piece of the puzzle here is that it vibrates in a specific direction that is perpendicular to the way the beam is moving.
Okay, let's unpack this a bit for the listener. If a light beam is coming straight at your face, the electric field might be vibrating up and down.
Yeah.
Or it might be vibrating, left and right.
Yes.
That specific direction of vibration is the polarization.
Mm-hmm.
And Feynman gives us this fantastic way to visualize this by breaking down that vibration into two components, horizontal and vertical.
Yeah, think of the field's movement as a combination of how much it swings horizontally and how much it swings vertically. Feynman asks us to picture a pendulum, like a heavy weight hanging from a string from the ceiling.
Okay, I'm picturing it.
If you push that pendulum straight forward, it swings back and forth in a simple straight line.
Right.
The horizontal motion and the vertical motion are perfectly synchronized. They hit their extreme points at the exact same time. And physicists call that being in phase.
In phase, okay. And as long as those two motions stay perfectly in sync, no matter how hard you push it, the resulting motion is always going to be a straight line.
Correct.
It could be a tilted diagonal line, but it remains strictly linear, so that is linear polarization. But the truly weird stuff happens when you mess with that synchronization, right?
Oh, totally.
Like, what if the horizontal vibration and the vertical vibration get out of sync?
Well, that changes the geometry completely. If those two motions are out of phase by exactly 90 degrees...
Meaning what, exactly?
Meaning the horizontal swing is at its absolute maximum speed right when the vertical swing is completely stopped.
Oh, okay.
When that happens, the pendulum doesn't swing in a line anymore. It actually traces a perfect circle.
Wow.
Yeah. In optics, we call this circular polarization. Depending on the timing, the electric field is literally spiraling through space like a right-handed or left-handed corkscrew.
That's so cool. And if the timing is anywhere in between those two extremes, or if the pushes are uneven, the field just traces an oval, which we call elliptical polarization.
Exactly right.
But before we get into how we actually manipulate those shapes, I want to address a massive misunderstanding that Feynman clears up in this chapter, which completely shifted my perspective.
I think I know what you're going to say.
It's about the concept of unpolarized light.
Yes. It is such a terrible name for the phenomenon.
It really is. When you hear that the light from the sun or a standard desk lamp is unpolarized, the natural assumption is that the light just lacks polarization altogether.
Right, like it's just a generic, structureless blob of energy.
But logically, that's impossible. We just established that an electric field absolutely must vibrate in some physical shape, a line, a circle, or an ellipse.
Right.
It can't vibrate in no shape. So what actually is the light coming out of a desk lamp?
To really understand it, we have to zoom way down to the atomic level.
Yeah.
Inside that light bulb filament, a single atom gets excited and emits a microscopic burst of light.
Just a tiny flash.
Yeah, and that tiny burst lasts for roughly 100 millionth of a second, 10 to the negative 8th second.
That is unimaginably fast.
It really is. But during that brief window, that single burst of light is perfectly polarized. It has a definitive geometry.
So it's not a messy blob, it's a perfectly structured wave.
Exactly. But here's the catch. A fraction of a nanosecond later, a different atom in the filament fires off its own burst of light, and that burst has a completely different random polarization.
Oh, I see.
Then a third atom fires with yet another random polarization direction. And this is happening constantly, billions of times a second, with all these overlapping bursts.
So the polarization is actually just changing way too fast for our eyes, or even our best standard instruments, to track it.
Precisely. We call it unpolarized just because all those rapid-fire chaotic changes basically average out to zero from our slow macroscopic perspective.
It's a limitation of human perception, basically, not a physical property of the light itself.
That is a crucial distinction to make. The underlying structure is always there.
Yeah.
Now, for anyone who decides to read Feynman's original text, I should mention he uses complex numbers and imaginary components to calculate these rapid phase changes.
Right, the math gets pretty intense.
It does. But he issues a very stern warning that we should probably repeat here. Do not confuse the imaginary components of the math with some kind of hidden physical dimension.
Oh, yeah, that's a great point.
The mathematical notation is literally just a highly efficient bookkeeping trick for calculating timing differences. The electric fields themselves are absolutely real physical forces operating in our normal three-dimensional space.
So keep the mathematical shortcuts in the math box and the physical reality in the physics box.
Well said.
So knowing that light is this intricate, high-speed dance of electric vectors, how do we actually filter it? Because this leads us to polarizers, and honestly, one of the most counterintuitive paradoxes in physics.
Oh, the three Polaroid paradox.
Yes. But first, let's talk about the filters themselves.
Right. So the most common way to filter light is using a material like Polaroid film, which contains a thin layer of carefully aligned crystals. Traditionally, it's a synthetic compound called herapethite.
Herapatite, okay.
Because of how these microscopic crystals are lined up, they treat different vibration directions differently.
They act kind of like a microscopic gate. Like,
Hmm.
if the light's electric field is vibrating parallel to the alignment of those crystals, it slips right through.
Yeah.
But if the light is vibrating perpendicular to the crystals, the material just absorbs the energy. The light stops.
And the math for exactly how much light gets through is surprisingly elegant.
Oh.
Yeah, the intensity drops by the square of the cosine of the angle between the light's vibration and the film's axis.
Okay, so if they perfectly match, the angle is 0, the cosine is 1, and all the light passes.
Exactly. And if they are completely crossed at 90 degrees, the cosine is 0, and the light is completely blocked.
Which brings up the famous three-Polaroid paradox.
Let's hear it.
Okay, let's paint the picture for the listener.
Mm-hmm.
You take 2 sheets of this Polaroid film, you hold the first one up, and it lets through, say, only vertically vibrating light. Then you hold up the second sheet right behind it, but you turn it 90 degrees so it only lets through horizontally vibrating light. What happens?
Pitch black.
Pitch black. The vertical light hits the horizontal filter and gets entirely absorbed. 0 light gets to your eye.
That perfectly aligns with the mechanics we just outlined. Vertical wave meets horizontal gate. The wave is absorbed.
Right. But then you do something that just seems impossible. You take a third sheet of Polaroid film, you sandwich it right between the 2 crossed sheets, and you tilt this middle sheet to a 45-degree angle.
Uh-huh.
And suddenly, light shines right through the final sheet. I have to play the skeptic here. You have a system that is completely blocking all light. You add more dark light-absorbing material into the middle of the stack, and somehow that creates light.
It sounds totally crazy.
It feels like it breaks the laws of thermodynamics.
It really does feel like a magic trick, but it is actually this beautiful demonstration of vector mathematics. The middle sheet isn't generating new light energy.
Okay.
It is physically forcing the electric vector to realign itself.
Walk us through the step-by-step mechanics of that realignment, because honestly, it's a tough concept to visualize.
Sure. Let's trace the journey of just a single burst of light. It passes through the first sheet and emerges vibrating perfectly vertically.
Got it.
It travels forward and smacks into the middle sheet, which is angled at 45 degrees. This middle sheet effectively says, I will only transmit energy that vibrates along my 45-degree diagonal axis.
But the light is vertical. It doesn't have a diagonal axis.
Well, it doesn't exclusively, but think back to our pendulum. A vertical vibration can be thought of as containing a diagonal component.
Oh, yeah.
When that purely vertical light hits the diagonal crystals, the material absorbs the portion of the energy that is fighting the crystals, but it allows the diagonal component of that vertical wave to actually pass.
So the light that emerges from the middle sheet is now physically vibrating at a 45-degree angle.
Yes.
It's almost like, okay, it's like a sailboat sailing into the wind.
Oh, I like that.
Right. Because a boat can't sail directly into a headwind. But if you angle the sail, the physics of the sail redirects a component of that wind force to push the boat forward diagonally. The sail basically takes the original vector of the wind and projects it into a new direction.
That is an excellent analogy. The middle polarizer acts exactly like the angled sail. It takes the vertical energy and forces it to project onto a new diagonal vector.
Okay, this is clicking for me now.
And now that newly diagonal light hits the final sheet. The final sheet only allows horizontal vibrations to pass.
Which would normally block vertical light.
Right. If the light had remained perfectly vertical, it would have been stopped cold. But because our sail tilted the vibration diagonally, that light wave now inherently possesses a horizontal component.
Wow. And the final sheet grabs that horizontal piece and just lets it right through. You aren't creating light. You are progressively bending the geometry of the wave so it can basically pick the lock of the next filter.
Exactly. You are reshaping the wave in midair. And, we don't just rely on synthetic film to do this. Nature does it constantly.
Right, which brings us back to the opening example of the glaring lake and something called Brewster's angle.
Yes.
Because when unpolarized sunlight hits a flat surface like a lake or a pane of glass, the beam basically splits. Some of the light refracts, bending down into the water, and some of it reflects off the surface into your eyes as glare.
And David Brewster discovered that if the light hits the water at one highly specific angle, the glare that bounces off is 100% linearly polarized.
And Feynman highlights the geometric elegance of this. Complete polarization occurs precisely when the reflected beam bouncing up at you and the refracted beam bending down into the water form a perfect 90-degree angle to each other.
Yeah.
But I need to push on the why here. Why does a 90-degree angle somehow magically organize chaotic sunlight into a perfectly flat, polarized beam?
Well, to understand the why, we have to remember what a reflection actually is. Light doesn't just bounce off the surface of a lake like a tennis ball hitting concrete.
Right, it's an electromagnetic interaction.
Exactly. The incoming sunlight plunges into the water, and its oscillating electric field violently shakes the electrons inside the water molecules.
It basically forces the charges in the water to dance to its rhythm.
Precisely. And in physics, whenever you shake an electrical charge, that charge radiates its own brand new electromagnetic wave.
Okay.
That new outgoing wave is what you actually perceive as the reflected glare.
Oh, wow.
But here is the critical rule. An oscillating charge radiates energy out to its sides, but it physically cannot radiate energy straight ahead along the exact line of its own movement.
Oh, I see. It's like an antenna. If I have a tall radio antenna, the signal blasts out horizontally in all directions, but it doesn't shoot straight up into the sky out the tip of the metal.
Yes, perfect example. Now apply that rule to our 90-degree geometry. At Brewster's angle, the electrons in the water are being shaken in a direction that points exactly along your line of sight for the reflected beam. Because they are moving straight along that line, they cannot radiate any energy toward you in that specific polarization plane.
So that entire portion of the light just dives deeper into the water.
Exactly, leaving only the light that is vibrating horizontally, perpendicular to that motion, to radiate back out at you. The surface of the water literally acts as a natural sorting mechanism, stripping away the vertical components.
Which is exactly why your polarized sunglasses have their crystals aligned vertically.
Yeah.
They are designed to act as a brick wall against that horizontally vibrating glare, wiping it out completely.
That's brilliant.
It really is. But, Feynman being Feynman, he isn't satisfied with just knowing that light reflects. He demands to know exactly how much light reflects.
Oh, of course.
And this leads to his derivation of the Fresnel formulas. And I have to admit, his approach here is just mind-bending.
It is a masterclass in theoretical physics. Normally, calculating the exact percentage of light that reflects off a surface requires slogging through some notoriously brutal mathematics.
Like serious boundary conditions stuff.
Oh, yeah. Dealing with the boundary conditions between two different mediums like air and glass.
It's the kind of math that makes graduate students cry.
Honestly, yes. But Feynman completely sidesteps it. He uses this conceptual trick based on the principle of superposition.
Okay, lay it on us.
He asks us to imagine the incoming sunlight as having an amplitude of 1. If the glass wasn't there, that wave of 1 would just keep traveling straight forward into infinity.
Uninterrupted.
But the glass is there, and we know from observation that the wave slows down and changes when it enters the glass.
So Feynman reasons, well, the original incoming waves didn't just cease to exist. If the final wave inside the glass is different from the original wave of 1, something must have actively canceled the original wave out.
That is the stroke of genius. He hypothesizes that the shaking electrons inside the glass are radiating a brand new invisible wave exactly backward along the original path with an amplitude of exactly -1.
Okay, hold on. You can't just invent a theoretical -1 cancellation wave out of thin air just because the boundary math is too hard. Like, how is that physically justified?
I know it sounds like cheating, but it's justified by the rule that all electromagnetic fields in the universe must add together perfectly.
Yeah.
The original wave of 1 is still technically moving forward, but the atoms in the glass generate a new wave of -1. When you add 1 and -1, they perfectly cancel out. And that explains why the original wave seemingly disappears, allowing the new, slower refracted wave to take its place. By framing the problem around this necessary cancellation wave, Feynman can actually calculate the reflection ratios using basic algebra instead of calculus.
It's incredible. He bypasses the complex boundary conditions entirely and just says, what must the atoms be doing to make the math balance?
Exactly.
And the real-world application of this is fascinating. He simplifies the formula for what happens when you look straight down at a surface, which is called normal incidence. For water, the math dictates that only about 2% of the light reflects back at you.
So if you are standing on a pier looking straight down into the water, 98% of the light is penetrating the surface, allowing you to see the fish.
Yeah.
But as you lift your gaze and look further out toward the horizon, the angle changes, the math of the Fresnel equations shifts, and the reflection grows exponentially stronger until the surface just becomes a mirror of blinding glare.
Okay, so we know how light reflects off a boundary. But what happens when it actually penetrates a complex, highly structured material. This brings us to birefringence, or double refraction.
Yeah, birefringence. This occurs in materials where the speed of light is not constant.
Wait, really?
Yeah, the speed actually changes depending on the light's direction of polarization. We see this in materials composed of long, asymmetrical molecules that align in a specific direction, creating what we call an optic axis.
I like to visualize this like the grain in a piece of wood. If you take an axe to a log, swinging parallel to the grain splits the wood easily.
Right.
But if you try to chop perpendicular against the grain, it takes significantly more force. The wood structurally resists you.
That's exactly it. The electric field of the light wave experiences a very similar structural grain inside birefringent crystals. If the light is vibrating parallel to the molecular grain, it interacts with the material differently than if it vibrates across the grain. Because the resistance is different, the wave literally travels at two different velocities inside the same material, depending purely on its polarization.
See, this is where things get wild. Because if you have two different speeds, you can start manipulating the phase.
Exactly.
Imagine taking linearly polarized light and aiming it at a 45-degree angle to the grain. As we know, that diagonal line is made of equal parts horizontal and vertical vibration.
Right. And as that light enters the crystal, the component moving along the grain zips ahead, while the component moving against the grain drags behind. They lose their synchronization.
It's kind of like a marching band where
Yeah.
half the band is walking on smooth pavement and the other half is walking through thick mud. Even if they try to take steps at the exact same time, the mud side is going to fall behind and get out of phase.
Great analogy. And as we established with the pendulum earlier, when the vertical and horizontal components fall out of phase, the wave stops being a straight line.
Right.
The material physically converts the linear polarization into an ellipse, or even a circle. If you manufacture a crystal to the precise thickness where one component falls exactly a quarter of a wave behind the other, you've created a quarter wave plate.
So it literally turns a straight line into a spinning circle.
It does.
And Feynman points out you can observe this phase-shifting magic at home with a piece of standard commercial cellophane.
Oh, yeah, the cellophane experiment.
Because the manufacturing process of cellophane actually stretches the plastic molecules out, creating a synthetic grain. And it just so happens that a typical sheet of cellophane is the exact right thickness to act as a phase shifter for certain colors of light.
So, if you place that crinkly piece of cellophane between two cross-Polaroid sheets, which normally block all light, as we know, the cellophane actually twists the polarization of specific wavelengths, allowing them to escape the final filter.
That is so cool.
By tilting the cellophane and changing the distance the light travels through the grain, you change which colors get twisted, essentially turning clear plastic into a vibrant, shifting color filter.
Which is exactly what causes the glowing rainbow stress lines on the plastic ruler I mentioned at the start of the deep dive.
Exactly.
When you physically bend a piece of plastic, the mechanical stress forces the molecules to temporarily align, creating instant birefringence. Engineers use this property constantly.
Oh, all the time.
They build clear plastic models of bridges or machine parts, put them in a vise, and look at them through polarized lenses. And the invisible mechanical forces basically light up in bright colored bands, showing exactly where the part is most likely to snap.
It allows us to literally see physical stress.
Yeah.
And nature produces extreme versions of this too, like the crystal Iceland spar. Its birefringence is so intense that when a single beam of unpolarized light enters it, the two different speeds cause the beam to drastically split into two entirely separate rays that bend at different angles.
So if you laid the crystal over a piece of text, you literally see double. The letters appear twice, overlapping.
Yep.
And if you test those two images with polarized sunglasses, you'll find that one image is horizontally polarized and the other is vertically polarized.
It's wild. We can even artificially induce this effect in liquids using a device called a Kerr cell.
Oh, right.
You take a liquid full of asymmetrical molecules that are normally sloshing around randomly, but the moment you apply a massive electric field to the liquid, all the molecules violently snap into alignment.
You instantly create a grain out of nothing.
Exactly. It goes from behaving like water to behaving like a crystal in a fraction of a second, acting as an optical switch with zero moving parts.
That is incredible. But I want to move to the final and arguably most profound revelation in Feynman's chapter Optical Activity and the physical mechanical punch that light actually packs.
Yes. Thus far, we have discussed molecules that look like long, straight sticks. But the natural world is full of chiral molecules, meaning They lack mirror symmetry. They are physically shaped like corkscrews or spiral staircases. A perfect everyday example is the sugar molecules in corn syrup.
Okay, so when a linearly polarized wave of light enters a jar of corn syrup, the electric field pushes the electrons up and down.
Right?
But because the molecule is shaped like a twisted spiral staircase, the electrons can't just move straight up and down. The physical shape of the molecule literally forces them to travel slightly sideways as they move vertically.
The physical curve of the track dictates the motion, and because those electrons are now moving sideways, they generate a tiny secondary electric field that's perpendicular to the original wave.
Oh, I see.
When you add that new sideways push to the original vertical push, the entire axis of polarization rotates. As the light travels deeper into the syrup, the angle of the light physically twists.
It is such a mechanical, tactile interaction between light and matter.
Hmm.
But Feynman takes us one step deeper. He proposes a conceptual leap that really made me pause.
The circular superposition.
Yes. He demonstrates that a simple, linearly polarized wave, a straight vertical line, can mathematically and physically be constructed by adding together equal amounts of right-handed circular polarization and left-handed circular polarization.
It's a beautiful concept.
I really had to wrestle with this, though. You are telling me that a straight line oscillating up and down is actually two circles spinning in opposite directions.
Huh?
That sounds completely counterintuitive.
I know it does until you map out the vectors. Imagine a dot spinning clockwise in a circle and another dot spinning counterclockwise at the exact same speed.
Okay, tracking.
When they are at the top and bottom of their circles, their vertical motions perfectly align and add together. But when they are on the sides of their circles, one is moving hard left and the other is moving hard right.
Ah, so the horizontal sideways motions perfectly cancel each other out.
Precisely. The sideways movements destroy each other, leaving nothing but a pure amplified vertical oscillation. A straight line really is just a superposition of two opposing spirals.
Which sets up the ultimate so what of this entire deep dive. We know light carries energy, and we know it carries linear momentum, like it can push a solar sail forward through space.
Yep.
But because light can exist as a spiraling circular wave, Feynman proves that light carries actual angular momentum.
It's true. If you hit an atom with a beam of circularly polarized light, that spiraling electric field grabs the electron and forces it to physically sweep out a circle in space.
Wow.
The wave is exerting a force across a distance, doing continuous work over time. In physics terms, it is applying torque.
It is delivering true angular momentum to physical matter. Light, an entity with absolutely zero mass, can act like a microscopic socket wrench, locking onto an atom and physically twisting it.
It is a staggering realization, honestly. You can calculate the exact amount of angular momentum delivered simply by taking the energy of the light and dividing it by its angular frequency.
That is just... Well,
Left-handed light twists the atom one way, and right-handed light twists it the exact opposite way.
it fundamentally changes how you view a beam of light. So let's bring this all together. We started by looking at light as a vibrating arrow. We explored how the atomic structure of herapatite crystals can cleanly slice and block that vibration.
Yeah.
We discussed how water acts as a natural filter, bouncing perfectly flat light into your eyes at Brewster's angle, and how Feynman used a ghost-like -1 cancellation wave to avoid the nightmare boundary math of reflection.
We also examine how light interacts with the grain of birefringent materials like cellophane and stressed plastic, changing its speed and slipping its phase.
And finally, we saw it navigate the spiral staircases of corn syrup molecules, revealing that light isn't just a passive beam of illumination. It is a spinning mechanical force capable of physically torquing the atomic structure of the universe.
It proves that to truly understand optics, you have to stop thinking of light as just a straight line and start thinking of it as an intricate geometry interacting with matter.
Which leaves me with one final provocative thought for you to mull over. If a continuous beam of circularly polarized light is absorbed by an object, and we know absolutely that it delivers real physical torque, could you theoretically place a macroscopic physical object in complete vacuum, hit it with an intensely powerful beam of circularly polarized light, and watch it start to spin? Like, could you build a physical motor driven entirely by the angular momentum of light?
The underlying physics absolutely says yes.
Something to chew on. Next time you slide on a pair of polarized sunglasses and look out at the glare on the water, remember, you aren't just darkening the world, you are actively filtering the hidden, spinning geometry of reality. Thanks for taking this deep dive with us. So stand up for a second. Like, seriously, if you are somewhere right now where you can actually stand up, just do it.
Okay. I feel like you're setting up a magic trick here.
Well, I mean, I kind of am. I want you to think about this. Why aren't your shoes falling straight through the floorboards right now?
I mean, it sounds like a question a toddler would ask, doesn't it? Like, why doesn't my hand go through the table?
It really does.
Yeah.
Because we just, we take the solidity of the world entirely for granted. But if you look at this through the lens of classical physics, it makes absolutely zero sense.
Right, because of empty space.
Exactly. We know that atoms are overwhelmingly composed of empty space. I mean, the atoms making up the rubber in your shoes and the atoms in the wood or the concrete of your floor, they are basically 99.9% void.
Yeah, which means by the old classical rules that empty space should just compress. Matter should theoretically be able to infinitely squish together.
So the real reason you don't just fall straight through the floor, the answer actually forces us to throw out the entire classical rule book of physics.
You really have to step into this completely bizarre reality where particles absolutely refuse to act like solid little billiard balls. And instead, they behave like waves.
Yeah, and to truly understand why the floor actually holds your weight, you have to understand the sheer impossibility of pinning a single one of those particles down.
Which is quite the leap from just standing on a floor.
It is, and that is exactly what we are doing today. We're exploring the ideas that totally broke classical physics. We're doing a deep dive into the brilliant insights from Richard Feynman's legendary lectures.
Specifically, chapter 38, right, where he tackles this whole wave-particle relationship.
Yep, chapter 38. We're going to decode what this built-in blurriness of the universe actually means for the physical world around us and do it without drowning in all the heavy math.
I think the best place to start is really with the historical debate. Because for a long time, physicists were just fighting over a really basic question.
Was it a wave or a particle?
Exactly. Is light a wave or is it a particle? Are electrons tiny spheres of matter or are they continuous waves? And, well, Feynman's genius is in how he explains that neither the pure wave viewpoint nor the pure particle viewpoint is actually correct.
Right, they had to come up with something else entirely.
Yeah, we have to use this hybrid concept called a probability wave amplitude.
Okay, let's unpack this. Because if it's not a hard little sphere, and it's not a physical wave, like a ripple on a pond, what exactly is a probability wave?
Well, think of it as a mathematical wave flowing through space.
Yeah.
And the height, or I guess the intensity of the wave at any given spot, represents the literal probability of finding the particle there.
So the taller the wave at point A, the more likely the particle is to actually be at point A.
Exactly. Which creates a really bizarre trade-off when we actually try to measure things.
Let's try to visualize this for everyone. Imagine a perfect, endlessly repeating sine wave, like perfect ripples on an infinite ocean.
Right, they just go on forever in both directions.
Yeah. Now, in quantum mechanics, the distance between the peaks of that wave, so its wavelength, corresponds directly to the particle's momentum, which tells us its speed and its mass in a specific direction.
So if you have a perfect infinite wave, you can measure the distance between those peaks perfectly. You know the particle's momentum with absolute certainty.
But there's a catch, right?
A huge catch. Because that wave stretches across the entire infinite ocean, you have absolutely zero idea where the particle actually is.
Oh, wow.
Yeah, the probability is spread out everywhere. Its position is completely unknown.
But, I mean, obviously, things in our universe exist in specific places.
Hmm.
So to know where the particle is, we have to sort of squish that endless wave down, right?
We do. We confine it to a short little burst, what physicists actually call a wave packet.
A wave packet. So it basically looks like a concentrated little jumble of ripples that just quickly fades out to flat water on either side.
Exactly. And the moment you do that, you've narrowed down the position. You know the particle is somewhere inside that little jumbled burst.
But look at what happens to the wave itself when you do that.
Right, because you squeezed it, it's no longer a perfect repeating sine wave. The distance between the peaks gets all messy and irregular.
So it doesn't have a single definite wavelength anymore. And because wavelength equals momentum, the momentum is now totally uncertain. You literally cannot know both at the same time.
You really can't.
I was thinking about how to visualize this trade-off, and it reminds me of cropping a photograph of a runner, like sprinting down a track.
Oh, I like that. How so?
Well, if you take that photo and you crop it really, really tight, right onto the runner's face, you know exactly where they are in that frame.
Yeah.
Their position is completely locked.
Right.
But because you've cropped out the blurry background and you've cropped out the motion of their swinging arms and legs, you completely lose the context of how fast they are moving.
That is a phenomenal analogy. By forcing certainty onto their position, you completely destroy your knowledge of their momentum. And, you know, we can actually see this play out in a physical experiment. Imagine we set up a massive concrete wall and we cut a tiny microscopic vertical slit right down the middle of it.
Okay, I'm picturing it.
Then from a mile away, we start firing a particle cannon at that wall, shooting electrons perfectly horizontally.
Okay, so since they are flying perfectly horizontally toward the wall, their vertical momentum is zero. I mean, they aren't drifting up or down at all. We know their momentum.
Right up until they hit the wall. A few of those electrons will happen to fly straight through that tiny vertical slit.
And the moment they pass through, we suddenly know their vertical position with incredible accuracy because they have to be somewhere within the width of that tiny microscopic gap.
We've cropped the photograph.
Right, but because we just squeeze their position, their momentum has to break. And it totally does. Because these particles behave like waves, they diffract.
Exactly. As the wave squeezes through the tiny gap, it bends and fans out widely on the other side.
Which means the electron could now fly off and hit the detector screen at a steep upward angle or, a sharp downward angle.
The vertical momentum is no longer zero. It's totally, wildly uncertain.
Wait, let me play devil's advocate here for a second because I feel like this is a trap a lot of people fall into.
Go for it.
If I knew the electron was flying perfectly horizontally a second ago, and I know it's passing through the slit right now, haven't I just beaten the system? Like, don't I know its past momentum in its current position?
Well, you do, but that is a major historical fallacy. Feynman is very quick to point out that the uncertainty principle is not a statement about historical knowledge.
So it doesn't care about what just happened.
Right. It's not about what you knew a second ago. It is entirely about the predictability of the future.
Yeah.
The theory of quantum mechanics is a predictive framework.
Oh, I see.
It does you absolutely no good to say, well, I knew what its momentum was before it hit the slit, because that momentum is physically erased the second it squeezes through.
Wow. So once you force the universe to reveal a precise position, you can no longer predict where that particle is going to go next.
Exactly. And if we want to measure momentum perfectly, we have to do the exact opposite. We use something called a diffraction grating.
Which is essentially a barrier with thousands of tiny parallel slits, right?
Yep. To measure the momentum based on how the wave bounces off all those slits, the wave hitting it has to be really, really long and spread out across the entire grating.
So you have to completely sacrifice your knowledge of the particle's position just to let the wave interact with enough slits to get a clean momentum reading.
What's fascinating here is that this trade-off isn't some mystical, spooky quantum magic.
It's not.
No. This relationship between the length of a wave burst and the definiteness of its wavelength is a mathematical property of all waves. Anyone who studies acoustics or ocean dynamics knows this.
Wait, really?
Yeah.
Even just regular sound waves?
Absolutely. You literally cannot define a precise musical pitch for a sound that only lasts a millionth of a second. The wave simply hasn't oscillated enough times to even have a pitch.
Oh, that makes so much sense. So the huge quantum leap in the 1920s was simply applying this everyday wave math to the actual physical matter of particles.
Precisely.
Okay, so we've established that a single particle is this blurry, unpredictable wave packet. But I mean, the world isn't made of single particles floating in a void. What happens when you slam a billion of these blurry waves together into a solid chunk of matter?
Like a diamond or a block of graphite.
Yeah, exactly.
This is where we have to look at the structure of crystals. At the atomic level, a crystal is just a heavily organized, three-dimensional grid of atoms.
Feynman talks about this, right? Think of a repeating pattern, like three-dimensional wallpaper stacked layer upon layer.
That's a great way to picture it. And when a wave hits that 3D wallpaper, it bounces off. But it's not like a single mirror. It's bouncing off the first layer of atoms, the second layer deep inside, the third layer.
And for that wave to successfully reflect back out to our eyes or our instruments, all those separate little bounces have to sync up perfectly.
Yes. The peaks of the wave bouncing off the top layer have to align precisely with the peaks bouncing off the deeper layers. They have to be perfectly in phase.
Because if they don't line up, like if the peak of one wave hits the valley of another wave, they just cancel each other out to zero.
Exactly. The wave destroys itself. It's a process called destructive interference.
Right. So the waves only survive if they hit the crystal at very specific angles where the geometry of their wavelength perfectly matches the spacing of the atoms.
It's a highly selective process, and this leads Feynman to introduce one of the most mind-bending anomalies in all of physics. It involves graphite and nuclear reactors.
Oh, the nuclear pile example. Let's walk through this.
Imagine a nuclear pile shooting a massive beam of neutrons into a very long, solid block of graphite. The graphite acts like a giant, selective sieve.
Hold on, I need to stop you there for a second. Because Feynman explicitly says neutrons are solid particles for anybody's money.
They definitely are.
They are heavy. They are the literal chunky building blocks inside an atomic nucleus. How on earth does a solid block of dense graphite sort out heavy physical particles based on wave mechanics?
I know, it feels deeply counterintuitive, but it perfectly proves the wave nature of matter. Remember how we said the waves have to bounce off the layered planes of atoms in the crystal?
Yeah, and they have to fold into the gaps between those layers to sync up.
Right. The peaks have to align with the geometric spacing of the atoms. Well, what if the physical wavelength of the neutron is simply too long?
What do you mean?
The math of crystal reflection dictates that if a neutron's wavelength is longer than twice the distance between the crystal planes of the graphite atoms, it is mathematically impossible for it to diffract.
Oh, wow. So it's like trying to catch a massive rolling ocean swell with a tiny handheld fishing net.
That is exactly it. The wave just completely ignores the structure.
So it doesn't bounce. What does it actually do?
It ghosts right through the dense structure as if the graphite block were completely transparent, like sunlight passing through a pane of clear glass.
Are you serious?
Yeah. So as this beam of chaotic neutrons crashes into this long block of graphite, all the fast neutrons, the ones with short, tight wavelengths, bounce around, scatter off the atomic layers, and get lost out the sides.
Not the slowest one.
The slowest, waviest neutrons, the ones with wavelengths too long to interact with the crystal lattice, they survive the trip. They just phase straight through the solid material and come out the far end in a pure, filtered beam.
That is just wild. The idea of a heavy piece of a nucleus just ghosting through a solid wall because it's too wavy to bounce.
It really challenges your perception of solid matter, doesn't it?
It does, which actually brings us perfectly back to our opening question. We've looked at massive arrays of atoms in a crystal, but let's zoom all the way back into a single atom. Let's talk about the quantum floor.
Ah, yes, let's do it. Picture a single hydrogen atom. You have a positive proton in the middle and a negative electron buzzing around it.
Okay, I've got it.
Under the laws of classical physics, the positive proton is magnetically pulling on the negative electron. The electron should instantly radiate away its energy, spiral inward, and crash right on top of the nucleus.
Basically, the atom should collapse into an infinitely dense dot.
Exactly. But it doesn't.
And here's where it gets really interesting. The reason it doesn't crash is the exact same wave uncertainty we've been talking about this whole time.
Think about the tug of war happening here. The electrical force wants to pull the electron into a tiny, tiny space right against the proton.
But if the electron is perfectly confined to that tiny space, we would know its position with extreme accuracy. We've basically cropped the photograph incredibly tight again.
And we know what happens when you squeeze a particle's position. Its momentum has to become wildly uncertain. It shoots up to infinity.
So the tighter the nucleus squeezes it, the faster and more violently the electron jiggles.
Place. If it's pulled too close, the quantum push of the uncertainty principle demands that its kinetic energy skyrockets. It's a literal quantum resistance to being pinned down.
So the atom has to strike a compromise. The electrical pull wants it in, but the quantum uncertainty pushes it out.
And they settle at a truce. The math balances perfectly so that they compromise at a specific distance, about 0.529 angstroms from the center. It's called the Bohr radius.
And that specific compromise requires an energy of negative 13.6 electron volts, which is known as a Rydberg of energy.
Right. Because of this balance, the electron is securely bound to the nucleus, but it maintains a definitive stable size. This fundamental quantum limit is literally the only reason atoms have volume.
Which brings us all the way back to your shoes and the floorboards.
Finally.
When you stand up, gravity is trying to pull you down. The atoms in the rubber bottom of your shoes are pressing physically against the atoms of the wood in the floor.
Right, but for your shoe to pass through the floor, for the materials to compress, their atoms would have to squish together. The electrons would be forced into a smaller, shared space.
And if they are confined to a smaller space, their position becomes more certain, which means
their momentum must spike. The electrons start moving with massive, violent kinetic energy, violently resisting being compressed any further.
the solid strength of the wood under your feet, the steel beams holding up a skyscraper, the chair you're sitting in, None of it is because matter is made of tiny, hard billiard balls.
No, it is purely a quantum mechanical resistance to compression. The universe mathematically refuses to let you know exactly where its particles are, and that refusal is the structural foundation of solid matter.
The floor holds you up because of the uncertainty principle.
It's mind-blowing when you really think about it. The blurriness isn't a glitch in the universe, it's the load-bearing feature of matter.
It really is. And this electron doesn't just sit at that one baseline compromise level forever. Like, if you pump energy into it, it can jump up into higher, wider orbits, right? Excited states?
Yes, but it can't stay there. Eventually, it drops from that higher excited state back down to a lower, more comfortable one. And when it drops, it has to get rid of that extra energy somehow.
It emits it as a photon of light at a very specific frequency.
Exactly. And because those jump distances are mathematically fixed, the color of the light is fixed.
Is this why neon signs glow specific colors, or why fireworks burn green or red depending on the chemicals?
Absolutely. Feynman points out something called the Ritz combination principle, which maps out these jumps. It shows that the frequencies of light emitted by these quantum drops are perfectly mathematical.
How so?
Well, if you know the frequency emitted when an electron drops from level 3 to level 1, and the frequency from level 1 to level 0, you just add them together to find the frequency of a massive drop from level 3 all the way down to 0.
Oh, that's so elegant. Feynman uses a wonderful analogy of an organ pipe for this, doesn't he?
Yes, an organ pipe traps sound waves inside a physical tube. Because the space is confined, the sound can only vibrate at specific resonance frequencies. It can only sing certain specific notes.
I love this part.
In the exact same way, the confined space around a nucleus limits the electron's wave to definite, distinct energy levels.
So if we connect this to the bigger picture, this is exactly how astronomers know what stars are made of, right?
Exactly.
Even if a star is a billion light years away, the hydrogen or helium atoms in that star are acting like tiny quantum organ pipes, singing the exact same specific light frequencies as hydrogen here on Earth.
Precisely. The quantum constraints are universal.
So we've built this reality where the structural integrity of everything we touch, and even the light from the stars, depends on the universe refusing to be perfectly measured.
It's a profound thought.
It really is. What does this mean for science and for us philosophically? Because that's a heavy concept.
It leads to a lot of big questions. Feynman briefly touches on the observer effect. That's the idea that making an observation inextricably affects the phenomenon.
Right, because to see an electron, you have to bounce a photon of light off of it.
But bouncing a photon off of it inherently disturbs its momentum. You physically cannot observe the universe without interacting with it.
Which leads some people to just throw their hands up. People say, well, if we can't accurately measure a particle's exact position and momentum simultaneously, we shouldn't even talk about them as real concepts.
Yeah, that science should only deal with what is perfectly measurable.
Exactly.
Feynman strongly warns against that mindset. He calls it a false position. Just because we can't measure something directly doesn't mean we can't use it as a conceptual tool.
Science is about making models to predict the future.
Right. We have to use constructs like these invisible wave function amplitudes to make sense of the world. As Feynman puts it, we have to stick our neck out.
We build a model assuming things exist independently of our clumsy experiments, and we just see if our predictions hold true.
If science only ever talked about what could be perfectly concurrently measured, discovery would just stall completely.
That makes total sense.
Oui.
Now, the other massive philosophical leap people make is about determinism and free will.
Oh yeah, this comes up a lot.
People look at quantum uncertainty, the fact that we can only calculate the probability of an electron jumping, and we can never predict exactly when an atom will emit a photon, and they say, aha, the universe isn't a strict clockwork machine, therefore human free will exists.
It is a very tempting thought. We all want to feel like we aren't just cogs in a deterministic machine. But Feynman actually shuts this down with a truly beautiful analogy of water falling over a dam.
Oh, let's dive into that because it totally reframes the whole debate.
So classical physics claims to be perfectly deterministic. In theory, if you knew the exact position and velocity of every single atom in the universe, you could calculate the future perfectly.
The ultimate clockwork universe.
Right. But imagine you are standing at the bottom of the Hoover Dam and you are trying to predict the exact millisecond a single specific drop of splashing water will land on the tip of your nose.
You can't. It feels totally chaotic and random.
Even under classical, perfectly rigid physics, you can't predict it. Because a tiny microscopic error in measuring the wiggling water at the top of the dam, say an error of 1 part in a billion, magnifies logarithmically as the water falls and crashes into other drops.
So it cascades.
Exactly. Within a fraction of a second, that tiny initial measurement error has grown so massively large that your mathematical prediction is entirely useless.
So what does this all actually mean? If classical physics is totally unpredictable in practice because of this cascading chaos, and quantum physics is unpredictable at its absolute core, does the difference actually matter to our human experience of free will?
This raises an important question, and Feynman's takeaway is incredibly profound. He argues we shouldn't welcome quantum mechanics merely as a psychological release from a mechanistic universe.
Because practically speaking, the universe was already completely unpredictable.
Yes. Even if classical mechanics were 100% true, the sheer complexity of nature and the logarithmic growth of tiny errors mean we could never predict the actions of the human mind or the future of society anyway.
The deep mystery of human free will isn't suddenly solved just because electrons happen to be blurry.
Exactly.
Wow. Okay, let's take a breath and recap the incredible journey we've been on today.
It's been a lot of ground to cover.
It really has. We started by trying to squish endless probability waves into tiny packets, realizing that cropping the photograph to pin down an electron's location completely ruins our knowledge of its momentum.
Then we watched solid, heavy blocks of graphite act like selective, transparent glass windows, allowing the waviest neutrons to simply ghost straight through because their wavelength was too large to interact with the crystal math.
And we finally discovered that the atoms in our shoes push back against the floorboards, purely because confining their electrons triggers a massive, violent spike in quantum kinetic energy.
The structural integrity of your own body and the chair you're sitting in is entirely dependent on the universe's mathematical refusal to be pinned down.
The blurriness isn't a bug. It's literally the only thing keeping the world from collapsing.
It is so humbling when you put it like that.
It really is. Which leaves me with a final thought I want you, the listener, to mull over as you go about your day. We've seen today that our solid physical reality is built entirely on a foundation of compromise.
Right, the tug of war.
Exactly. The electron needs just a little bit of uncertainty, a little bit of wiggle room to strike a balance and keep the atom from collapsing in on itself.
Yeah.
So if the universe requires a fundamental lack of strict rigidity just to exist physically, what other complex systems in our lives actually rely on a built-in lack of strict rigidity to survive?
It's a fascinating way to look at it.
Think about our societies, our relationships, our economies. Maybe an obsession with total predictability and rigidity is actually a recipe for collapse. Maybe a little uncertainty is the only thing keeping our human world standing too.
It certainly makes you view the unknown in a completely different light.
It really does. Thanks for joining us on this deep dive. Keep questioning the solid ground beneath your feet.
Usually when we talk about discovering some grand universal law of physics, there is this inherent expectation of really high-tech lab equipment.
Right, yeah. You picture like a massive underground particle accelerator.
Exactly. Or vacuum chambers, or at least some kind of supercomputer just humming away in the background.
It definitely creates this illusion that the fundamental rules of reality are, hidden away. Like you need billions of dollars and completely isolated environments just to catch a glimpse of them.
But then you look at the origins of thermodynamics, and instead of a particle accelerator, the only scientific instrument you actually need is a rubber band.
A literal rubber band.
Seriously, if you take an ordinary, everyday rubber band, stretch it out really tight, and immediately press it against your lips, which, by the way, happen to be incredibly sensitive to tiny temperature changes, you will feel a distinct, surprising warmth.
It is remarkably noticeable.
Right.
And the really fascinating part is the immediate reversibility of that action.
Yes.
Because if you keep the rubber band against your lips and quickly let it just snap back to its relaxed state, you will feel a sudden, very distinct chill.
Which is just wild. Welcome to the deep dive. Today, we have a really fascinating mission for you, the listener. We are unpacking a legendary physics lecture, Chapter 44 of the Feynman Lectures on Physics.
Yeah.
Our goal here is to explore how a simple rubber band holds the secret to the ultimate limits of the universe. We're going to decode the grand, unbreakable rules governing heat, energy, and work. And we are going to do it, hopefully, entirely without getting bogged down in complex algebra or dense equations.
Which is actually an incredibly fitting approach, I think.
Oh, yeah.
Yeah, considering the pioneers of this field had to deduce the absolute limits of reality long before they even had a working model of the atom.
That's right.
They relied entirely on macroscopic observation, logic, and just a relentless curiosity about how things actually move and work in the real world.
Okay, well, let's unpack this, because the sheer deductive power of these early scientists just blows my mind. And it really does all start with that weird, totally counterintuitive behavior of rubber that we just mentioned.
So true.
Let's look at figure 44:1 from the source material. We set up this little experiment. We take a rubber band, hang it vertically, and attach a small weight to the bottom so it's fully stretched out.
Okay, got the visual.
Now, we take a heat source, like a gas flame or a really strong lamp, and apply it directly to the stretched band. Based on everything we intuitively know about the physical world, what should happen?
Well, our intuition is heavily biased by materials like metal, right?
Sure.
If you heat a steel beam or a copper wire, it expands. The atoms in a metal are arranged in this rigid crystalline grid.
Right.
So when you add heat, you're adding kinetic energy. Those atoms vibrate more violently in place, pushing their neighbors further away, which physically causes the entire piece of metal to lengthen and expand.
Makes total sense.
So following that exact logic, heating our stretched rubber band should make it expand, causing the weight to drop down toward the floor.
But the rubber band defies that expectation completely.
Totally does.
When you apply heat, the rubber band abruptly contracts. It shrinks, physically pulling the weight upward against gravity. I mean, heat doesn't make it expand, heat makes it pull.
And to understand the why behind this, the source provides this brilliant, highly visual analogy: molecular spaghetti.
I love that phrase, molecular spaghetti.
It's so accurate. Rubber is fundamentally different from the rigid crystal grid of a metal. It is a polymer. If you zoomed into a microscopic level, you wouldn't see a neat grid. You would see an enormous chaotic tangle of long molecule chains, just loosely bound together by occasional crosslinks.
So when I pull on that rubber band and stretch it out, I'm forcing that messy bowl of molecular spaghetti to straighten out. I am physically dragging those chaotic wandering chains into a highly ordered parallel alignment along the direction I'm pulling.
Precisely. But those molecular chains are never perfectly still. They possess internal thermal energy. They're constantly wriggling and vibrating.
Right.
So when you take a flame and heat that stretched rubber band, you are injecting a massive amount of new kinetic energy directly into those chains.
So they start violently thrashing side to side.
Yes, and because they are trapped in that stretched parallel alignment, all that lateral thrashing causes them to bump into their neighbors. They just can't stay straight anymore.
Oh, I see.
The intense vibration forces the chains to kink up and curl. And as they kink, the overall length of the chain shortens. That microscopic thrashing literally pulls the ends of the rubber band closer together, lifting the weight in the macroscopic world.
Wow. And that perfectly explains the cooling effect you felt on your lips when you let the band relax.
It does, yeah.
Because as it snaps back, the chains lose that tense alignment and soften up into a tangle again. The molecules pounding into them actually transfer energy away during those collisions, losing kinetic energy in the process.
And that loss of kinetic energy registers to your nerves as a drop in temperature.
Okay, so that molecular explanation makes perfect sense to us now, but here is the really critical historical context for you. Early scientists didn't know about polymer chains or molecular spaghetti.
No, they didn't have microscopes that powerful.
Right. They couldn't see the microscopic thrashing. All they saw was the macroscopic result. Adding heat to this material caused it to contract and lift a physical weight. Heat was performing mechanical work.
And the moment humanity realized heat could consistently perform mechanical work, the immediate, just inevitable question became,
how do we build an engine out of this?
exactly, how can we harness this to build an engine?
Which brings us to figure 44.2 in the lecture, and quite possibly the most delightfully absurd engine ever put to paper, the rubber band engine.
It's so good.
It is. Imagine a standard bicycle wheel mounted on an axle, but you remove all the metal wire spokes. Instead, you connect the center hub to the outer rim using a series of stretched rubber bands.
It's just a phenomenal proof of concept. To make it run, you simply place a pair of strong, heat-emitting lamps on one side of the wheel, shining onto the rubber bands currently positioned on, say, the right side.
Right, so the lamps heat up the rubber bands on the right, and thanks to the spaghetti effect we just talked about, Those heated bands contract and pull tighter than the cool bands on the left side.
Yeah.
And this uneven tension physically pulls the heavy center hub off-center, shifting the entire wheel's center of gravity toward the lamps.
And that gravitational imbalance forces the wheel to rotate. As it turns, the heated, contracted rubber bands rotate away from the lamps into the ambient air, where they naturally cool down and relax.
Meanwhile, fresh, cool bands rotate into the light, heat up, contract, and pull the hub again.
Exactly. As long as you supply heat from the lamps, the wheel continues to spin, driven entirely by the contraction and relaxation of rubber.
Now look, the lecture points out this is a spectacularly terrible engine in practical.
Horribly inefficient.
Right, you have to pump roughly 400 watts of raw power from the heat lamps into it, and the resulting rotational work is barely strong enough to lift a single tiny fly.
Yeah, but the efficiency isn't the point at all. It proves unequivocally that a continuous cycle of heating and cooling can produce continuous mechanical motion.
Right, it proves the concept.
And this relentless drive to understand and improve engines is the very crucible that forged thermodynamics. In the early 19th century, the Industrial Revolution was just raging.
Trains, factories, all of it.
Exactly. Engineers were building massive steam engines, boiling water to push pistons, and condensing the steam to repeat the cycle. But they were doing it mostly through trial and error.
Right, just tinkering until it worked better.
Yeah, until a brilliant French engineer named Sadi Carnot stepped back and asked the really fundamental questions. What actually governs this process? Is water the absolute best fluid to use? Or would boiling alcohol or expanding air produce more power? What is the theoretical limit of an engine?
But before Carnot could build the ultimate engine, he needed to establish the foundational rules of the universe's accounting system. We need to talk about the first law of thermodynamics.
Yes. The first law is the principle of the conservation of energy.
Right.
It dictates that energy cannot be magically created out of nowhere, nor can it be permanently destroyed. It can only change forms.
So in the context of our engines, what does that mean?
It means the change in the internal energy of a system is always perfectly equal to the heat you put into it, plus any work done on it. The cosmic ledger must always balance.
Wait, okay, if the only rule is that the ledger must balance, I have a pitch for you.
Uh-oh. Okay, let's hear it.
I have designed the ultimate cargo ship for you and the listener. It requires 0 fuel tanks. It just glides through the ocean, sucking in the ambient heat from the seawater around it.
Okay.
It converts that ocean heat perfectly into mechanical work to spin the propellers. And the only byproduct we leave behind in our wake is a trail of slightly cooler seawater, maybe a few ice cubes.
Let's see where this is going.
Energy is conserved because I'm just taking it from the ocean and putting it into the propellers. We have unlimited, free energy.
It is a beautiful dream. A hypothetical device often called a perpetual motion machine of the second kind. And unfortunately, the second law of thermodynamics dictates that your ocean engine is a physical impossibility.
But I'm not breaking the first law. I'm not creating energy. I'm just moving it. Why can't I do it?
Because Sadi Carnot deduced a profound constraint on how heat actually moves. He realized that it is fundamentally impossible to extract heat from a single thermal reservoir like your ocean and convert it entirely into work with no other changes happening in the system or the surrounding environment.
Wait, so nature demands a tax. I can't just harvest heat from one place. I have to have a second place to dump the exhaust.
That is the perfect way to phrase it. Nature demands a temperature gradient. Our everyday experience confirms this, right? Heat naturally flows from a hot object to a cold object.
Yeah, like a hot cup of coffee.
Exactly. If you place a hot cup of coffee next to an ice cube, the coffee doesn't spontaneously get hotter while freezing the ice cube harder. Heat only moves downhill, thermally speaking.
Right.
To extract mechanical work from heat, you're essentially putting a water wheel in the middle of a flowing river of energy. You must have a high temperature source to draw the heat from, and you absolutely must have a low temperature condenser to dump the leftover unutilized heat into. Without the cold dump, the river stops flowing. No flow, no work.
Oh, I see. My ship failed because it was trying to operate at a single temperature. It just had the ocean.
Exactly.
So to build the best possible engine, we genuinely need 2 distinct temperatures, a hot boiler and a cold dump. But that brings us right back to Carnot's puzzle. If we have those 2 temperatures, what does the absolute most efficient engine running between them look like?
Well, to find the maximum theoretical efficiency, we have to strip away all the messy realities of engineering. Real engines leak heat. They suffer from the friction of metal pistons scraping against cylinders.
Sure, they're noisy and hot.
They experience violent thermal shocks when hot steam is suddenly dumped into a cold chamber. So to find the true limit, Carnot had to conceptualize a perfectly reversible engine.
Well, let's define reversible, actually, because my mind immediately jumps to mechanical friction.
Okay, yeah.
Like if I push a heavy wooden crate across a rough concrete floor, that is irreversible. The friction generates heat, the energy dissipates into the floorboards, and I can't just, blow gently on the crate to get that lost energy back.
No, you definitely can't.
But if I imagine an idealized scenario, like a perfectly smooth, utterly frictionless block hovering over a sheet of perfect ice, a tiny puff of air slides it forward. A tiny puff of air slides it back. No energy is lost to friction. It's a pure, idealized mental model.
That captures mechanical reversibility perfectly. And the genius of Carnot was applying that exact same frictionless concept to the flow of heat itself.
How do you have frictionless heat?
Think about it this way. If you take a glowing hot brick and plunge it into an ice bath, heat violently rushes across that massive temperature gap. That is an irreversible thermal shock. You cannot raise the temperature of the ice bath by a tiny fraction of a degree and force the heat to flow back into the brick. The energy has permanently cascaded down the temperature hill.
Ah, so a reversible heat transfer would mean moving heat without ever dropping it down a hill. The heat can only flow between two things that are already at the exact same temperature.
Exactly. The temperature difference between the engine and the heat source must be infinitesimal. Just the tiniest microscopic fraction of a degree. It's the thermal equivalent of your frictionless ice block. The gentlest possible nudge pushes the heat in, and the gentlest possible nudge can pull it back out. No sudden shocks.
Okay, which brings us to the famous Carnot cycle. This is the ultimate blueprint for moving heat around without ever dropping it off a cliff. The source lecture breaks this down using figures 44-5 and 44-6. Imagine a simple cylinder filled with a perfect gas capped with a frictionless piston. We have a hot heat pad and a cold heat pad. The puzzle is, how do we extract work from the hot pad and dump the remainder to the cold pad without any sudden temperature shocks?
We have to do it in 4 very careful phases. Phase 1 is an isothermal expansion. Iso, meaning same. Thermal, meaning temperature.
Okay, same temperature.
We place our gas cylinder directly onto the hot pad. The pad transfers heat into the gas, causing it to expand and push the piston out, doing work. But we let it expand incredibly slowly.
Why so slowly?
So slowly that the gas never actually heats up. It maintains the exact same temperature as a hot pad the entire time. It absorbs energy, turns it immediately into work, and the temperature stays flat.
That's wild. But eventually we have to visit the cold pad to dump our exhaust. If we just move the cylinder directly from the hot pad to the cold pad, the gas would experience a massive thermal shock.
Right, which is irreversible.
So how do we cool the gas down safely?
We use phase 2. Adiabatic expansion. We remove the cylinder from the hot pad and completely isolate it. No heat is allowed to enter or leave the cylinder. We then allow the gas to continue expanding and pushing the piston just a little bit further.
Wait, if it's isolated, where does it get the energy to push?
Because it is completely isolated, the only way it can do that work is by burning its own internal energy. As it burns that internal energy, the gas naturally cools down. We let it expand just enough so its internal temperature glides perfectly down to match the temperature of our cold pad.
Brilliant. We lowered the temperature using internal work, not a thermal shock.
Exactly.
Phase 3 is isothermal compression. We set the now cool cylinder onto the cold pad. We slowly compress the piston. This generates heat, but because we are touching the cold pad, that heat gently flows out of the gas and into the pad.
And we do this infinitely slowly, so the gas stays at the exact constant temperature of the cold pad.
And finally, phase 4, adiabatic compression. We isolate the cylinder one last time. We compress the piston the rest of the way. The gas is isolated, so the heat of compression can't escape.
Right.
The internal temperature of the gas glides perfectly back up until it matches our starting hot pad. We have completed one flawless, reversible cycle.
It's beautiful, really.
Yeah.
We took heat from the hot source, extracted work, dumped the tax to the cold source, and returned to our exact starting point without a single irreversible shock. It is the absolute pinnacle of theoretical efficiency.
But here is the massive question Carnot faced. You asked earlier if water was the best fluid. What if tomorrow an engineer invents a miraculous new material, like a supersynthetic polymer or a highly volatile chemical gas? Couldn't they use that to build a real engine that beats our perfectly reversible gas cycle?
This is where Carnot unleashes a logical trap that fundamentally changed physics. He proved, beyond a shadow of a doubt, that no engine, regardless of its design or its mysterious supermaterials, can ever be more efficient than a reversible engine. Let's walk through his logical duel. It's illustrated in figure 44-7.
Okay, let's set up the ultimate heavyweight bout. In the champion's corner, we have Engine A, our perfectly reversible gas engine.
Okay.
In the challenger's corner, Engine B, constructed from our hypothetical supermaterial. We hook both of them up to the exact same hot boiler and the exact same cold ocean dump. Let's give them a strict energy budget. Both engines pull exactly 100 units of heat from the hot boiler.
Right. Now, we are assuming the Challenger Engine B is more efficient. So from that 100-unit budget, our reversible Engine A produces, say, 30 units of useful mechanical work. But the supermaterial Engine B produces 40 units of work. It squeezed more power out of the same heat.
The Challenger wins. But wait, you said Engine A is perfectly reversible?
It is.
That means if we force it to run backward, it stops being an engine and becomes a refrigerator. If we feed mechanical work into Engine A, it will pull heat out of the cold dump and push it uphill back into the hot boiler.
And this is exactly where the trap springs. Let's physically connect the two machines. We use the 40 units of work produced by Engine B to drive Engine A completely in reverse.
Oh, wow.
Engine A requires 30 units of work to run backward. So we feed it 30 units, and we still have 10 units of pure leftover work sitting in our pocket.
Okay, let's check the ledger. Engine A, running backward, takes that work and pumps exactly 100 units of heat back into the hot boiler.
Now look at the hot boiler's net balance. Engine B withdrew 100 units, Engine A deposited 100 units. The boiler experiences absolute zero net change. The energy is completely refunded.
But hold on, the boiler is fully refunded, yet I still have 10 units of pure usable work in my pocket from Engine B. Where did the energy for that 10 units of work come from?
The only place left, the cold dump. Because Engine A was running backward as a refrigerator, it extracted more heat from the cold dump than Engine B deposited into it. The net result of this entire coupled system is that we have extracted heat from a single cold reservoir and turned it into pure mechanical work, leaving no other trace in the universe.
Wait, that's my ocean engine? That's the perpetual motion machine of the second kind? We already established the second law makes that physically impossible. Nature demands the tax.
Exactly. It is a logical impossibility. Because the ocean engine cannot exist, our initial assumption must be fatally flawed. Engine B cannot be more efficient than the reversible Engine A.
So the supermaterial doesn't matter.
Not at all. No engine in the universe can beat a reversible engine.
That is an incredibly elegant deduction, and the implications are just staggering, because Carnot proved the material inside the cylinder, steam, rubber, alcohol, perfect gas, is completely irrelevant to the maximum efficiency. It means the efficiency is dictated by something else entirely.
It is dictated solely by the two temperatures, the specific gap between the hot source and the cold dump. That is the only variable that matters.
Which fundamentally changed how humanity defines temperature. Because before this, measuring temperature was totally arbitrary.
Very much so.
You'd trap some mercury in a glass tube, watch it expand when heated, and etch some random lines on the glass. But mercury expands differently at different heat levels. The lines aren't a true reflection of the universe.
But Carnot gave scientists a universal ruler. Because the efficiency of a reversible engine relies entirely on temperature, completely independent of any physical substance, scientists could use the idealized engine itself as the ultimate thermometer.
The absolute scale.
Exactly. They define the absolute thermodynamic temperature scale. It is based purely on the ratio of heat flowing through a perfect engine. It is a fundamental truth of reality, completely free from the quirky behaviors of water or mercury.
And exploring that ratio of heat flow led them to perhaps the most profound concept in all of physics. If we look at the relationship of the energy in our perfect Carnot cycle, the amount of heat absorbed from the hot pad relative to its high temperature perfectly balances the amount of heat delivered to the cold pad relative to its lower temperature.
Because that ratio balances perfectly in a reversible cycle, the net change across the whole loop is zero. The ledger is perfectly balanced. Scientists realize this ratio heat transferred relative to the temperature at which it transfers is a fundamental property of matter, much like mass, volume, or pressure.
It's a conserved state.
Yes, and they named this property entropy.
Entropy. It is a term thrown around in pop culture constantly, usually just meaning, like, messiness.
Yeah, that's the common usage.
But here it is, defined conceptually as a universal ledger. The lecture stresses that entropy is a state function. To use an analogy, think of your physical altitude on a mountain. If you stand at base camp, your altitude is 5,000 feet. If you stand on the summit, your altitude is 10,000 feet. It absolutely does not matter if you took the steep direct trail or the long winding scenic trail. The total change in your altitude between those two states is identical. Entropy acts the exact same way. Regardless of the path a system takes between state A and state B, the total change in entropy is fixed.
It is a permanent record of the system's condition. And just to complete the picture, the third law of thermodynamics establishes the absolute bottom floor of this record. At absolute zero temperature, where all thermal motion stops, the entropy of a perfect substance is exactly zero.
Okay, I follow the perfect ledger of the Carnot cycle, but I have to push back here.
Okay, push back.
We do not live in Carnot's idealized, frictionless universe. Our world is messy. We have real friction, we have sudden thermal shocks. What happens to this perfect entropy ledger in reality? For example, what happens if I take a glowing hot stone out of a campfire and drop it into a bucket of freezing cold water?
That scenario is the key to understanding the true nature of our universe. When you drop the hot stone into the cold water, heat violently rushes from the stone to the water. That is an irreversible thermal shock.
Right.
To understand the mechanism, imagine the heat energy inside the hot stone as a handful of perfectly stacked, highly organized coins. When the stone hits the water, it's like dropping those coins onto a crowded, bustling dance floor. The kinetic energy violently scatters, dispersing chaotically into the vast, sluggish ocean of cold water molecules.
And you can't just gather those scattered coins back up into a neat stack. You can't gather that scattered kinetic energy back into the stone. It's irreversibly disorganized.
Precisely. And the concept of entropy mathematically captures that disorganization. The stone loses a specific amount of heat. But because the stone was at a high temperature, that loss represents a relatively small change to its overall entropy ratio. However, the cold water absorbs that exact same amount of heat. Because the water is at a low temperature, adding that heat causes a massive disruption. The ratio of the heat added relative to the small temperature results in a large number.
Oh, I get it. So the entropy gained by the chaotic scattering water is significantly larger than the entropy lost by the highly organized stone.
Exactly. When you add the two sides of the ledger together, the net result is always positive. The total entropy of the world goes up, the math guarantees it, and the physical scattering of energy drives it. Every single time heat flows irreversibly from hot to cold, every time friction grinds energy away, the total cumulative entropy of the universe increases.
Wow. Let's pull all of this together for you. We started by looking at a simple rubber band, trying to deduce universal rules without needing to understand atoms, and we uncovered two absolute pillars of reality.
That we did.
The first law. The total energy of the universe is a locked, constant ledger. You cannot create a single drop of new energy, and you cannot destroy it. It just moves around.
And the second law. Because our reality is not a perfect, frictionless Carnot engine, every action involves irreversible processes. Therefore, the entropy, the disorganization of that energy ledger, is always relentlessly increasing.
It is a staggering reality. The amount of energy never changes, but the quality of that energy is constantly degrading. It's always scattering.
And that relentless scattering is actually what gives us the arrow of time.
Oh, so.
Because entropy must continually increase in our universe, the future must look fundamentally different, fundamentally more disorganized than the past. Every fire humanity burns, every hot stone that cools in a river, every single breath you take, irreversibly increases the total entropy of the cosmos.
From the chaotic molecular spaghetti of a rubber band violently thrashing against its constraints to the absolute laws governing the engines that built the modern world. Thank you for joining us on this deep dive. Keep stretching those rubber bands, keep wondering about the unseen mechanisms around you, and we'll catch you next time.
But before you go, I want to leave you with one final unresolved thought.
Oh, late on us.
If the entropy of the universe is constantly, unavoidably increasing, inevitably spreading out and destroying temperature differences, what happens in the unfathomably distant future when the universe reaches maximum entropy?
Oh, boy.
When all the hot stars have cooled, all the cold voids have warmed, and the entire cosmos settles into one uniform, lukewarm temperature where no more thermodynamic work can ever be done. That is the heat death of the universe. Something to think about.